All right, let's take a look at the practice test. For the instructions, we're asked to determine if the function is one-to-one. All right, for problem 1, we're given f of x is equal to 1/3 x minus 1. So the idea here is that we're going to use the graphical approach to determine if our function here is a one-to-one function. So basically, remember that a one-to-one function says that for each x, there's one y, and for each y, there's one x. So basically, what you're going to do is sketch the graph of this function. You can do it with a piece of graph paper if you want, or you can use an online graphing calculator like Desmos. Once you have the graph, you're going to look to see if any horizontal line, so a horizontal line is of the form, let's say y equals k, so if that impacts the graph in more than one location, well, that's not the graph of a one-to-one function. For each y value, there's going to be more than one x value that's associated with it, because on a horizontal line y equals k, the y value is always the same. Then when you think about the other scenario where no horizontal line impacts the graph in more than one location for your function, well, that is the graph of a one-to-one function. So let me copy this down. We have f of x is equal to 1/3 x minus 1. I went ahead and sketched the graph of everything already, so we can just speed up the process here. So basically, once you have your graph, again, you can either manually draw it or key it into Desmos. You're just going to look and see if any horizontal line would impact the graph in more than one location. And the answer here is that it wouldn't. So this is a one-to-one function. Let me write here that this is one-to-one. And I'll make a few horizontal lines just for the sake of the tutorial. But if you're doing this on your own, then you can just easily see that no horizontal line would impact the graph in more than one location. Just write one-to-one and then move on. Okay, so I'll just put in 2 there. Let me go ahead and put some arrows in there. So this one right here is the line y equals 1. And again, you'll see that it only impacts the graph in one place. So that's going to be right there. And if you looked at that as an ordered pair, it's going to be 6, 1. But again, this horizontal line here, y equals 1, only impacts the graph in one spot. Then if we look at this one right here, looks like we're only going to hit right there. This is the y is equal to -2. And this point right here, let me label this in case you want to follow along. So this is 6, 1. This point right here, this would be -3, -2. So again, each horizontal line, it doesn't matter how many you draw, is only going to impact the graph in one location. So for each x, there's one y, and then also for each y, there's one x. All right, let's take a look at problem 2 now. So we have f of x is equal to the quantity x plus 1 cubed, then plus 1. Let me just copy this down real quick. So again, f of x equals the quantity x plus 1 cubed, plus 1. Okay, so coming down here and looking at our graph, again, we can see clearly that this is going to be a one-to-one function. The only part about this graph that is a little bit tricky is this part right here. So if you're on Desmos or something like that and you zoom in, you have to be really, really careful because they are approximating the values. So if you look at this part of the graph right here, you might see a y value of 1 more than once, but again, that's because they're approximating things. So what I'm going to do, I'll just draw a little horizontal line here. So this is the line y equals 1. And we're going to see that this actually impacts the graph in only one location. So right there. And the ordered pair is going to be -1, 1. Now there's different ways you could prove this. You could, of course, plug in a 1 for your f of x or your y. So you can say that this is 1, and this equals the quantity x plus 1 cubed, and then plus 1. So of course, what you can do is subtract 1 away from each side. This cancels and cancels over there. So this is a 0. Let me actually rewrite this as this being equal to 0. So basically you would take the cube root of each side. So the cube root of this quantity x plus 1 cubed is equal to the cube root of 0. So of course this will undo this and you get x plus 1 is equal to the cube root of 0 is just 0. Let me get rid of this. And of course when we solve this, we're going to subtract 1 away from each side, and you get x is equal to -1. So basically what we just showed there was that a y value, or the function's value of 1, is going to correspond only to an x value of -1. So you can say conclusively here that for each x there's one y, and then also for each y there's one x. So I'm going to go ahead and write that this is a one-to-one function. All right, let's take a look at problem 3. So here we have f of x is equal to the absolute value of x minus 1, and then -1. So you should know already this is not going to be a one-to-one function. When you think about an absolute value function, it's a V shape. So coming down here, let me paste this in. You can immediately tell that this is not going to be the graph of a one-to-one function. If I draw a horizontal line, let me just draw one at y equals 3, for example. So this guy right here, this is y is equal to 3. I want you to notice that this horizontal line impacts the graph in more than one location. So right here and then right here. So basically this guy right here, this is going to be 5 units to the right and then 3 units up. So this is 5, 3. And this one is 3 units to the left and then 3 units up. So this one right here is going to be negative 3, 3. So what's causing that? Let's think about this for a moment. So let's say we write this as y is equal to the absolute value of x minus 1 and then minus 1, like this. And we want to see, well, what would produce a y value of 3? So I'm just going to plug in a 3 and solve for that. So basically, I would add 1 to both sides. So this would cancel. And so you get 3 plus 1, that's going to be 4. So you're going to get that the absolute value of x minus 1 is equal to 4. Let me get rid of this. Now, we've solved absolute value equations in this course. And we know that basically you set up a compound equation with OR. So this right here could end up being positive 4, and the absolute value of positive 4 would be 4. So I could say that x minus 1 could be equal to 4. Or, because of the absolute value operation, changing a negative into a positive, this guy right here could be equal to negative 4, because the absolute value of negative 4 is also 4. So x minus 1 could be equal to negative 4. Let me get rid of this. And basically, if I add 1 to both sides, I get x is equal to 5. So that's where this is coming from, this 0.5, 3. You plug in a 5 here. 5 minus 1 is 4. The absolute value of 4 is 4. 4 minus 1 is 3. Then the other side is I add 1 to both sides, and then I get x is equal to negative 3. So x equals 5, or x equals negative 3. And so that gives me this guy right here. If x is negative 3, y is 3. So if I plug in a negative 3 there, negative 3 minus 1 is negative 4. Again, the absolute value of negative 4 is positive 4. So positive 4 minus 1 would give me 3. So you can see that this function is not a one-to-one function. You have an x value of 5 that's corresponding to a y value of 3. And then you also have another x value of negative 3 that's corresponding to the same y value of 3. So this is not a one-to-one function. So let me just put not a one-to-one. All right, let's take a look at problem 4. So here we have f of x equals the quantity x minus 2 squared. So again, you immediately can tell that this is not going to be one-to-one because this right here is going to be a parabola. So let's go ahead and say that this is f of x is equal to the quantity x minus 2 squared. Let's come down here and paste this in. So again, we see our parabola, and obviously you can create a horizontal line that would impact the graph in more than one location. Let's just make one of them. So this right here would be the line y is equal to 4. Again, you can see that this y value is associated with more than one x value. So right here, this is the point. We're going 4 units to the right and 4 units up. So this right here would be 4, 4. And then this point right here, you're on the y-axis. So basically the x value is 0 and the y value is positive 4. So this right here is 0, 4. Again, if you want to plug this in for completeness, you can. You can just replace f of x with 4. So basically 4 is equal to the quantity x minus 2 squared. So basically by the square root property, you would say x minus 2 is equal to plus or minus the square root of 4. And so the square root of 4 is 2, so this becomes plus or minus 2. And so you get x minus 2 is equal to 2, or x minus 2 is equal to negative 2. So this one, if you add 2 to both sides, you get x is equal to 4. So you get x is equal to 4. So that's this guy right here. And then on this one, if you add 2 to both sides, you're going to get x is equal to 0. So x is equal to 0. Let me slide this down. So that's this guy right there. So basically, you can see that these two different x values, so 4 and then also 0, those are going to be associated with the same y value of 4. If I plug in a 4 here, 4 minus 2 is 2, 2 squared is 4. If I plug in a 0 here, 0 minus 2 is negative 2, negative 2 squared is also 4. So this would not be a one-to-one function. Let me get rid of this. Let me just write that this is not a one-to-one. All right, let's take a look at problem 5. So here we have f of x is equal to, we have our square root of x plus 1, then plus 3. Let me copy this down. So again, f of x is equal to the square root of x plus 1, and then plus 3. Okay, so let me paste this in here. So again, looking at this guy, you can see that no horizontal line would impact the graph in more than one location. So I'll just draw some horizontal lines in here. So this one would be y is equal to 3, And basically that would impact here where your x value is -1 and your y value is 3. So just one x value that's associated with that. Let me just mark to that. So this would be -1, 3. And then this one right here, this is the line y is equal to 5. And that just impacts the graph right there. So basically an x value of 3 is associated with a y value of 5. So this is 3, 5. So no horizontal line would impact the graph in more than one location. So we can say this is a 1-to-1 function. So this is 1, 2, 1. All right, let's take a look at the practice test. For the instructions, we're asked to determine if the function is 1-to-1. All right, let's take a look at the first problem. So here we have f of x is equal to the cube root of x plus 2 and then minus 1. So we want to know if this function is a 1-to-1 function, meaning for each x there's one y, and then also for each y there's one x. So usually we use the horizontal line test, so we would graph the function and see if any horizontal line impacts the graph in more than one location. If it does, that function is not a 1-to-1 function. But here we're going to use an algebraic approach. So how does this work? Well, essentially you start off with something like, let's say f of a, and then you do f of b. So you could also use, let me just put this over here, I'll erase it in a moment. Some books will do f of x sub 1 and then f of x sub 2. So if you see this in your book, it's basically the same thing. So I'm going to say f of a is what? This is me replacing x, my independent variable here in my function, with a. That's all I'm doing. So this is the cube root of, instead of x, it will be a, and then plus 2, and then we have minus 1. Then f of b, we would have the cube root of, again, instead of x, now I would have b, and then plus 2, and then minus 1. So this is the first thing you're going to do. You're going to set these up. And let me come down here and paste this in. Here's how the test goes. We would say that if f of a is set equal to f of b, let me stop here and think about this with you. So some of you might be confused by this notation. What is f of a? Well, that's a y value that's produced when I let x be equal to a. So this right here is a y value. Then what is f of b? Well, that's the y value that's produced when I let my x be equal to b. So if this y value equals this y value, that means I have the same y value or the same function value. You can think about it that way as well. But I think when you say y value here, it really clicks with the definition of a 1-to-1 function. This can only be true when you have a 1-to-1 function if you have the same x value. So I'm just going to write that this implies, so this implies that, and we'll say that a is equal to b. So in other words, this value that we plugged in for x is the same as this value that we plugged in for x here because we have the same y value. So what I'm going to do is set this right here equal to this right here, and then we'll try to see if we can get a equal to b. So on the left, I'll just say we have the cube root of a plus 2 and then minus 1. So that's my f of a. It's equal to this, so that's why I'm writing that there. And then we'll say this is equal to, your f of b is this guy right here. So we have the cube root, so the cube root of b plus 2 and then minus 1. And let's come down here and see if we can get a equals b. That's all we're looking for. So the first thing is you have -1 here and -1 here. So you can just add 1 to both sides of the equation. So that cancels and that cancels. And now I have the cube root of a plus 2 is equal to the cube root of b plus 2. Now, how can I get rid of this cube root? Well, on each side of the equation, I'm just going to cube. And let me just do that over here as well. And basically, let me come down here. In each case, the cubing is going to undo the cube root, so I'm left with the radicand. So here I would have a plus 2. So a plus 2, and this equals, so this would be b plus 2. So b plus 2. And as a final step, I'm just going to subtract 2 away from each side of the equation. So this cancels and this cancels. And what you get is that a is equal to b. So basically here, we've just shown that for a given y value, it's going to match up with or correspond to one unique x value. So basically, we can say this is a 1-to-1 function. So this is 1-to-1. All right, let's take a look at problem 2. So here we have f of x is equal to x squared minus 8. So most of you know this is going to be a parabola. And so basically, if you were to graph this, of course, it would not be a 1-to-1 function. But how do we show this algebraically? Again, we're going to set up our f of a and our f of b. So f of a is equal to what? All I'm going to do is replace x with a. So this would be a squared and then minus 8. Then f of b is what? I'm going to replace x with b. So this is b squared minus 8. Okay, let's grab this real quick and let's come down here. We're going to say that f of a equals f of b is going to imply, let me write this out. So implies that we'll say that a is equal to b. So f of a is equal to a squared minus 8. Let me write that out. So this is a squared minus 8. And then f of b is equal to b squared minus 8. So this equals b squared minus 8. This one, I'm just going to add 8 to both sides of the equation. Let me cancel this and cancel this. And now we're left with a squared equals b squared. So here's where you have to be really careful. I've had a lot of different tutoring sessions where I've covered this topic. And where people get confused is they take the square root of each side and then they say a equals b. Remember that when we do a lot of work in algebra, if I do something like the square root of a squared, if I say that a represents a positive real number, well, then I can say that this is equal to a. But we don't have that here. So really, this is equal to the absolute value of a. That's by definition, because a here would just be any real number. So it could be negative, it could be 0, it could be positive. So if you want to take the square root of each side, you can do that. So basically, let's say we have the square root of a squared is equal to the square root of b squared. But by definition, what we get is that this right here is the absolute value of a, and then this right here is the absolute value of b. So we know how to solve an absolute value equation. Two expressions would have the same absolute value if they're the same number or if they're negatives. In other words, let me give you a quick example in case you're a little bit lost. Let's say you had something like the absolute value of 3 is equal to the absolute value of 3. Well, of course, those have the same absolute value because it's the same number. This would give you 3 equals 3. But it would also be true if these guys are negatives. So the absolute value of 3 is equal to the absolute value of negative 3. So the absolute value of 3 is 3. The absolute value of negative 3 is also 3. So this is also a true statement. So what I would say here is that a could be equal to b, so they could be the same number. So in other words, 3 and 3. So I will say a is equal to b. But then you also have this situation where it's an or, right? Because you have to consider that they could be negatives. So a could be equal to the negative of b. Here you have 3 and then negative 3. The absolute values would still be equal. So you could say that a is equal to negative b. So this is proving that we don't have a one-to-one function. Now, let me show you a different way to do this in case you're lost. Let me come down here a little bit. You'll get the same thing. So if you have a squared is equal to b squared, you can subtract b squared away from each side of the equation. This would cancel and give you 0 over here. So that would lead to a squared minus b squared is equal to 0. So all I'm going to do is factor. So remember this right here, we can use our little special formula for. So this turns into a plus b, that quantity, times the quantity a minus b. And of course, this equals 0, right? So this is the difference of squares formula. So essentially, you can use your zero products property, and we'll just put this over here and say that, well, a plus b would be equal to 0. If I subtract b away from each side, so you get a is equal to negative b, then or for this one, you would have a minus b equals 0, add b to both sides, and you get a is equal to b. So it's the same thing. I think this is a little bit easier to understand. Some people struggle with this concept. So if you want to do it this way, that's fine. But you get a is equal to negative b or a is equal to b. The same thing we got over here. So either way, you don't just have a equals b, and so this function is not one-to-one. And we already know that that parabola shape would fail the horizontal line test. So let's go ahead and say that this is not 1, 2, 1. All right, let's take a look at problem 3. So here we have f of x is equal to the absolute value of x minus 1. So let me go f of a is equal to, this would be the absolute value of a minus 1. And then f of b, this would be the absolute value of b minus 1. Now remember, if you think about the graph of our absolute value function, it's a V shape. And so of course this is going to fail the horizontal line test, and it's not going to be one-to-one. But we want to prove that using an algebraic approach. Again, let me just write this out. If f of a is equal to f of b, this implies that we have a is equal to b. So this is for us to have a one-to-one function. Let's go ahead and say f of a is the absolute value of a minus 1, and we'll set that equal to f of b is the absolute value of b minus 1. So let's think about this for a moment. We have this absolute value equals this absolute value. Remember, just like in the last example, let me go back to the absolute value of 3 is equal to the absolute value of 3. So they can be the same, or you could have negatives. So the absolute value of 3 is equal to the absolute value of negative 3. It doesn't matter that you have an expression here. It's the same thing. So these guys could be equal. In other words, I could have a scenario where a minus 1 is equal to b minus 1. So you just drop the absolute value bars. And so here you could just add 1 to both sides, and you would get a equals b. So you would get a equals b. And of course, you could plug in for a or plug in for b and see that this works. If I plug in a b here, you'd have b minus 1 and you have b minus 1. And of course, the absolute value of b minus 1 is equal to the absolute value of b minus 1. So that's one of them. But then you have the or. You have to consider that they could be negatives. So just wrap one of them in parentheses. It doesn't matter which one. So let's go a minus 1. Let's put a negative out in front. And let's say this equals, over here, I'm just going to go b minus 1. So I'm just making these guys into negatives. And here you could distribute this negative to each. But if I'm going to solve for a, then it's probably better, let me just write this as negative 1, to divide both sides by negative 1. So let me do that like that. And I'm going to get rid of this. And basically, this would be a minus 1 is equal to, let's go negative b plus 1. So negative b plus 1. And let me add 1 to both sides. And so let me erase this. So you get a could also be equal to this negative b plus 2. So this negative b plus 2. So of course, this is not just giving us a equals b. So this is not going to be 1 to 1. Now, if you want to check this, you can plug this in here real quick. Let me do that. So let's say you had the absolute value of, instead of a, I'm going to plug in negative b plus 2, and then minus 1. Close that down and say this is equal to the absolute value of b minus 1. So this right here would be what? 2 minus 1 would be positive 1. And you might look at that and say, well, those two, I don't know if they're going to be equal in terms of absolute value. Let me show you a little algebraic manipulation here. I could pull out a negative 1 from this. So this is the absolute value of. Let's go negative 1 times the quantity. So I would have a positive b minus 1 like that. Close that down, and this equals the absolute value of b minus 1. And then from here, I can use my rule. Remember that the absolute value of a times the absolute value of b is equal to the absolute value of a, b. Well, I'm just going to do that in reverse. So the absolute value of negative 1 times the absolute value of b minus 1. So is this equal to the absolute value of b minus 1? Yeah, the absolute value of negative 1 is 1. So this becomes the absolute value of b minus 1 is equal to the absolute value of b minus 1. So we know that this part right here is a valid solution. So let me get rid of this. And basically, because we didn't get just the a equals b, we know that this is not 1 to 1. Of course, we know that from the graph already because it's a V shape, so it would not pass the horizontal line test. So this is not 1 to 1. All right, let's look at problem 4 now. So we have f of x is equal to 1 over x minus 8. So let's set this up. We're going to go f of a is equal to 1 over, again, for x, I'm going to plug in an a, so a minus 8. And then for f of b, we're going to have 1 over, again, for x, I'm going to plug in a b, so b minus 8. Okay, let's come down here. Again, let me write the rule, just so you can get used to it. So if f of a is equal to f of b, so for a one-to-one function, this implies that your a is equal to the b. All right, so let's set these guys equal. So we're going to say 1 over a minus 8, so that's your f of a. We're going to say that's equal to your f of b, which is 1 over b minus 8. All right, so for this type of problem, there's lots of ways to do it. I would just cross multiply. I think that's the quickest. So basically, you're going to go this way and say that you have b minus 8 is equal to a minus 8. And then at this point, you could just add 8 to both sides of the equation. So this cancels and this cancels. And what we're left with is b equals a, or you can turn that around and say a equals b. So of course, this function is 1 to 1. So this is 1 to 1. All right, let's take a look at problem 5. So here we have f of x equals the negative of the square root of 25 minus x squared. All right, so once again, let's go f of a is equal to the negative of the square root of 25 minus, for x, here I'm going to plug in an a, so this is a squared. And then for f of b, let's say this is the negative of the square root of 25 minus, for x, I'm going to plug in a b, so this is b squared. Okay, so let me just write the rule one more time. If we have a one-to-one function, then f of a being equal to f of b implies, so this implies that a is equal to b. So f of a is negative square root of 25 minus a squared. And this would be equal to f of b is negative square root of 25 minus b squared. All right, so what I'm going to do here is square both sides. So let's square both sides. So this negative is going to go away in each case. And basically, the square root is going to go away in each case. So I'm just going to have my radicand. I'm going to have 25 minus a squared is equal to 25 minus b squared. Now, let me just erase this. I'm going to put this in terms of what we had. And let me come down here a little bit. And basically, we see 25 and 25. You can subtract that away from each side of the equation. So this is going to cancel, and this is going to cancel. And so let's say we have negative a squared is equal to negative b squared. So you can multiply both sides by -1 or divide both sides by -1, whatever you want to do. But basically, this -1 is going to cancel away. And so you have a squared is equal to b squared, which of course we know is going to lead to something that is not just a equals b. We showed this the last time with factoring. We also showed it using the concept of the absolute value when you take the square root of each side. So basically the square root of a squared equals the square root of b squared. And this gives me the absolute value of a is equal to the absolute value of b. And so that's going to lead to us saying that a could be equal to b. So a could be equal to b, or a could be equal to the negative of b. Now I want to show you that this actually works using this original equation here. So basically the negative of the square root of 25 minus. So for a, obviously you could plug in a b and you would just have b squared, right? So this is b squared. And would this be equal to the negative of the square root of 25 minus b squared? Of course, that would work. And let me show you the other one. So a could also be negative b. Would that work? Well, this is the negative of the square root of 25 minus. For a here, you're plugging in a negative b, and that would be squared. Would this be equal to the negative of the square root of 25 minus b squared? So this right here, this negative is wrapped inside of these parentheses because I'm plugging in for a right there, and I'm plugging in a negative b. So don't get confused by that negative that's out in front. So this would be minus the negative of b being squared, and this is all wrapped. So because this is wrapped, we know that this is basically -1 squared, which is +1, and then b squared is just b squared. So I can legally replace this with b squared, and so this works as well. So because we know that both of those would work, basically we could say a is equal to b or a is equal to the negative of b. This is not a one-to-one function. So this is not 1 to 1. All right, let's take a look at the practice test. For the instructions, we're asked to find the inverse of each function. All right, for problem 1, we have f of x equals 2x plus 1. So in order for us to find the inverse of a function, remember that function has to be a one-to-one function. So I'm just going to tell you, you don't have to pull out a graph or anything today. All the functions I'm giving you are one-to-one functions and will have an inverse. So you can just concentrate on the procedure. Basically, what you're going to do is replace f of x with y. So that's the first thing. We're going to say y is equal to 2x plus 1. Now, the next thing you want to do is interchange x and y. So in other words, if you have a y, you're going to make it into an x. If you have an x, you're going to make it into a y. A lot of people will just say you're going to swap your x and y. So let's say this is x is equal to 2y plus 1. So at this point, all you really need to do is solve for y. And once you've done that, you'll have your inverse. Let me slide down here a little bit. If I want to solve for y, well, the first thing is I have this 1 that's being added to this term right here, this 2y. So I'm going to subtract 1 away from each side of the equation. So of course, this right here is going to cancel away. And what you're going to have on the left is x minus 1 is equal to, on the right, you're going to have 2y. Let me slide down here a little bit. Now, I like what I'm solving for to be on the left. This is just my personal preference. You don't have to do this, but I'm going to rewrite this as 2y is equal to x minus 1. Now, again, if I'm trying to solve for y, right now 2 is multiplying y. So I'm just going to divide both sides of the equation by 2, and this is going to cancel, and now I'll have my inverse. So basically, I have y is equal to, you have x minus 1 over 2. The last step is to put this in terms of the inverse notation. So instead of y, we're going to say this is f inverse of x. And so this equals x minus 1 over 2. So there's your inverse. All right, let's take a look at problem 2. So here we have f of x is equal to the cube root of x minus 2. So again, this is going to be a one-to-one function. And so I'm just going to start by replacing f of x with y. So y is equal to, we have our cube root of x and then minus 2. At this point, you want to interchange x and y. So again, that just means I'm swapping the x and the y. So I'm going to write this as x is equal to the cube root of y and then minus 2. So once you've done that, you basically want to solve for y. So I'm going to add 2 to both sides of the equation. So this is going to cancel. And so on the left, you're going to have x plus 2. So I'm going to write x plus 2, and this equals, I have the cube root of y. Now again, I like what I'm solving for to be on the left, so I'm going to put an extra step in here. I'm just going to say that I have the cube root of y is equal to x plus 2. And of course, if I want to get y by itself, I've got to undo this cube root here. And to do that, I'm just going to cube both sides of the equation. So basically, raise each side to the third power. Let me slide down here a little bit. So basically here, I'm just going to be left with y, my radicand there. So y is equal to, over here, I would not expand this. I would just leave it like this. So this is the quantity x plus 2 being cubed. So just leave it like that. And then essentially, you just replace your y with your inverse notation. So this is f inverse of x, and this equals your x plus 2, this quantity cubed. So that's going to be your inverse. All right, let's take a look at problem 3. So we have f of x equals 3/7 times x minus 6/7. So again, this is a one-to-one function. And so to find the inverse, let's replace f of x with y. So let's say y is equal to, we have 3/7 x minus 6/7. Now to make this problem a little bit easier, since we have some denominators involved, I would just clear them. So I would multiply both sides of the equation by 7. So basically you would have 7y is equal to, you'd have 7 times 3/7 x minus 6/7 times 7. Let me slide down here a little bit. And then basically, let's put 7y is equal to, these 7s would cancel. So you're going to have 3x. And then minus these 7s would cancel. So you have 6. So at this point, we're going to interchange x and y. And so that means these guys are going to swap. So let me say we're going to have 7x is equal to 3y minus 6. And just solve for y. So to do that, I'm going to add 6 to both sides of the equation. So this would cancel over here. So you're going to have 7x plus 6 is equal to 3y. Again, I like what I'm solving for to be on the left. So let's just write this as 3y is equal to 7x plus 6. If you want to solve for y, you're going to divide both sides of the equation by 3. And so that's going to cancel. And you're going to be left with your inverse. So y equals 7x plus 6 over 3. Again, we're going to replace that y with our inverse notation. So let's say f inverse of x is equal to this 7x plus 6 and then over 3. Okay, let's take a look at problem 4. So here we have f of x equals 1 over x minus 2 plus 2. So again, this is a one-to-one function. So let's go ahead and replace f of x with y. So y is equal to, let's go 1 over x minus 2 and then plus 2. Let me slide down here a little bit. And so basically what I would do here is, again, interchange x and y. So just swap your x and your y. Let's say this is x is equal to 1 over, we have y minus 2 and then plus 2. Now I'm trying to solve for y here. So what I would do is subtract 2 away from each side of the equation. So let me go minus 2 here. And so these are going to cancel. And let me go minus 2 here. Let me slide down a little bit. Let's write this as x minus 2 is equal to, we're going to go 1 over y minus 2. Now I'm trying to solve for y, and there's a lot of ways you could do this, but basically I think I'm going to write this as a fraction. So I think this would be the easiest way to understand. Let me write this over 1. And essentially I'm going to multiply by y minus 2 over x minus 2. And I'm going to do that to each side. So let me multiply over here by y minus 2 over x minus 2. So essentially over here, you're going to see that this is going to cancel with this, right? And you can wrap this if you want to do it that way. But essentially x minus 2 over x minus 2 would be 1. And then let me wrap this like this for clarity. So this would cancel with this. And so that would give you 1. So what you're left with on the left is y minus 2 over 1. Or you could just say it's y minus 2. And this equals, on the right, you're going to have 1 over x minus 2. Now, you don't have to do it this way, but I think this is the easiest way to understand. Feel free to do it in a different way, something that works for you. Let me slide down here a little bit. And essentially, if I want to solve for y, all I have to do is add 2 to both sides. And I'll say that y is equal to 1 over x minus 2 and then plus 2. Let me bring this down here. Here's where you'll get a little bit of confusion. So some books will actually leave it like this, but sometimes they'll get a common denominator. So your answer may be different and still be correct. So you can put it like this, or what you could do is get a common denominator. So I could multiply this by x minus 2, and this has to be wrapped, over x minus 2. So now you have a common denominator. So you could say that y is equal to 1 plus, this 2 needs to be distributed. So it's 2x minus 4. 2 times x is 2x. 2 times negative 2 is negative 4. And then basically you can do 1 minus 4, that's going to be negative 3. So let's put 2x minus 3 like that. And this is over the common denominator of x minus 2. So this is one way you can give your answer. The other way would have been y equals 1 over x minus 2 and then plus 2. If If you want to do it like that, it's fine. The only other thing you want to do is replace your y with your f inverse of x, so that notation. So whether you're using this form or this form, doesn't matter. We'll go ahead and say this equals 2x minus 3 over x minus 2. All right, for problem number 5, we have f of x equals the quantity x minus 1 cubed minus 2. All right, so again, I'm going to tell you this function is 1-to-1. And so I'm going to replace f of x with y. So y equals this quantity x minus 1 being cubed and then minus 2. All right, so we're going to interchange x and y. So basically, I'm going to have x is equal to this quantity. Now, instead of x, it will be y and then minus 1. And this is cubed and then minus 2. So how are we going to solve this for y? The first thing I would do is add 2 to both sides. So let me add 2 over here and just add 2 over here. So again, this is going to cancel. And on the left, you have x plus 2. This equals, on the right, it's y minus 1, and this quantity is cubed. Again, I like what I'm solving for to be on the left, so I'm just going to rewrite this. So y minus 1, quantity cubed, is equal to x plus 2. Okay, let me slide down here a little bit. Essentially, if you want to get y by itself, you're going to have to get rid of this operation right here where we're cubing. So basically, I'm going to take the cube root of each side. So I'm going to take the cube root of this quantity y minus 1 being cubed, and this would be equal to, you have the cube root of x plus 2. And make this 3 a little bit better here, and then also here. So on the left, you're just going to be left with this y minus 1. So y minus 1 would be equal to, on the right, you're going to have the cube root of x plus 2. All right, at this point, to solve for y, you would add 1 to both sides of the equation. So this cancels, and you get y is equal to, you're going to have the cube root of x plus 2. Let me make this 3 a little bit better. And then you're going to have plus 1. All right, let me come down to a new sheet so we have a little bit of room. So now I'm just going to change my notation. So instead of y, I'm going to put f inverse of x. And so this equals the cube root of x plus 2 and then plus 1. So that's your inverse. All right, for problem 6, we have f of x is equal to negative x cubed minus 1. So again, I'll just start by telling you this is a 1-to-1 function. So to find the inverse, we're just going to replace f of x with y. So this equals, we have negative x cubed and then minus 1. At this point, we're just going to interchange x and y. So we're going to say this is x is equal to negative, let's go negative 1 for clarity, times this will be y cubed and then minus 1. Essentially, I'm trying to solve for y. So what I'm going to do is add 1 to both sides of the equation. So that's going to cancel. And so you're going to have x plus 1. So x plus 1 is equal to, here, let's go negative 1 times y cubed. Now again, if I want y by itself, first I have to get rid of this negative 1 that's multiplying this y cubed. So let me slide down here a little bit. You can multiply both sides by negative 1, or you can divide both sides by negative 1. Whatever you want to do, let's just multiply both sides by negative 1. A lot of times you just put a negative out in front of parentheses. But for clarity, let me put negative 1 and then times this quantity x plus 1. Now we're going to distribute this in a moment. Let me just leave it like that for right now. Now this equals, over here, negative 1 times negative 1 is positive 1, and then times your y cubed. Let me slide down here a little bit. So this right here is y cubed. Let me put that on the left. So y cubed is equal to, I'm going to distribute the negative 1 to each guy inside the parentheses. So this would be negative x and then minus 1. So the last thing I want to do here is basically take the cube root of each side so I can get rid of this exponent of 3. So basically the cube root of y cubed is equal to, we'll have the cube root of negative x minus 1. On the left, we now have just y, and this equals, over here, is just going to be the cube root of negative x minus 1. Let me come down to a fresh sheet so we have a little room. So now I'm just going to put my inverse notation in. So instead of y, I'm going to say this is f inverse of x. And this equals, this will be the cube root of negative x minus 1. All right, for problem 7, we have f of x is equal to the fifth root of x plus 2. So again, this is a 1-to-1 function. So we're just going to change f of x into y. So y equals, we have our fifth root of x and then plus 2. Again, I'm going to interchange x and y. So basically these guys are going to swap. So x is equal to, you're going to have your fifth root of y and then plus 2. Let me slide down here a little bit. Again, if you're trying to solve for y, we're going to subtract 2 away from each side of the equation. So this is going to cancel, and you're going to have x minus 2 is equal to, you have your fifth root of y. Let me slide down here. Again, I like what I'm solving for to be on the left. So let me just write this real quick. we're going to have the fifth root of y is equal to x minus 2. All right, at this point, if I want y by itself, I'm going to have to get rid of this fifth root part here. And to do that, I'm just going to raise both sides of my equation to the fifth power. So basically just like this. And essentially on the left, I'm just going to have y, and this will be equal to, on the right, I have this quantity x minus 2 to the fifth power. Again, I wouldn't expand this, just leave it as it is. So let me slide down here. I'm just going to replace y with my notation for the inverse. So f inverse of x is equal to, again, this quantity x minus 2, and this is raised to the fifth power. All right, for problem 8, we have f of x equals, we have 2 over x minus 2. Again, this is going to be a one-to-one function. So I'm going to replace this f of x with y, and this equals, let's say we have 2 over my x minus 2. Again, at this point, I'm going to interchange x and y. So right now, I'll say that I have x is equal to 2 over y minus 2. So how am I going to solve for y? Again, there's lots of different techniques here. What I like to do is make myself a little fraction on the left. So I'll say I have x over 1 is equal to 2 over y minus 2. So I'm going to multiply this by, I'm going to go y minus 2, so right there, over x. And I'm going to do this to both sides. So over here, times we're going to have y minus 2 over x. So what is that going to do for me? So this is going to cancel with this, and then this is going to cancel with this. Let me slide down here a little bit. And essentially, you're going to have y minus 2 is equal to, this would be 2 over x. Okay, at this point, I would add 2 to both sides of the equation. This would cancel. You're going to have y is equal to 2 over x plus 2. So again, this is where your answer might be different. You could leave it like this and just say f inverse of x is equal to 2 over x plus 2. That's perfectly fine. Let me come to a new sheet. What a lot of people will do is get a common denominator. So you could multiply this right here, this 2. Let's say this is 2 over 1, so times x over x. So this would be y is equal to 2 times x is 2x, and then plus 2. Let me write this as 2x plus 2 like that, over the common denominator of x. So this is how I prefer to write it. If you want to write it the other way, that's fine. Perfectly acceptable for that answer. So let's go ahead and replace this with our inverse notation. So we'll say f inverse of x is equal to, we have 2x plus 2 over x. All right, let's take a look at problem 9. So here we have f of x is equal to x minus 2 over 3x minus 1. So the idea here again is that this function is going to be one-to-one. So basically, we're going to replace our f of x with y. So y will be equal to x minus 2 over, we have 3x minus 1. So at this point, I'm going to interchange x and y. Now you're going to notice that you actually have an x here and an x here. So in each case, that has to become a y, and this y needs to become an x. So we're going to say that we have x is equal to, this would be y minus 2 over 3y minus 1. All right, so at this point, we want to solve for y. So lots of different approaches you could take for this. What I'm going to choose to do is multiply both sides by this 3y minus 1. So let me do that over here, and then let me do that over here. I'm actually going to slide this down and put this like this. So this would be x times the quantity, 3y minus 1. So what's going to happen is we're going to say that this is going to cancel with this, so that would give me 1. And essentially, I would have x times this quantity. So you would distribute this x to each guy inside of the parentheses. So you would have 3xy, and then minus x is equal to, here I have y minus 2. So at this point, what you'd want to do is take all your terms with y involved and move them to one side. So in other words, this right here, I'm just going to subtract y away from each side of the equation. And then I'm going to get rid of this. So let me go ahead and add x to each side of the equation. So essentially, this right here is going to cancel away. And this right here is going to cancel away. So you're going to have 3xy minus y is equal to, let's write negative 2 plus x as x minus 2. Okay, let me pull this down here and get a fresh sheet going. So now we have a y here and a y here. So what we're going to do is we're going to factor that out. So we're going to put a y here outside of some parentheses, and inside you're going to have 3x and then minus 1. So this equals x minus 2. So if you're trying to solve for y, again, y is multiplied by this quantity. So I'm just going to divide both sides of the equation by that quantity, 3x minus 1. So this is going to cancel. and divide over here. So you don't need parentheses over here. It's really up to you. I'm just doing that for formatting here. So it's crystal clear that I'm canceling this quantity away. So let's go ahead and say that we have y is equal to x minus 2 over 3x minus 1. And again, to finish things up, I'll go ahead and replace this y with my inverse notation. So f inverse of x is equal to x minus 2 over 3x minus 1. And before we move on to the next problem, let me just address that this right here is different from what I gave in the practice test. So the computer-generated worksheet actually gives a different answer. You can answer like this or the way that it did, it doesn't matter. So f inverse of x is equal to, let's keep x minus 2 up here the same, and this is over. Down here, let me factor out a -1. So basically -1 times the quantity. This would be different in terms of the sign, and this would be different in terms of the sign. So -3x and then plus 1. Again, if I distribute the -1 to each guy inside the parentheses, I'm going to go back to 3x minus 1. Now, all you're going to do is just move this negative basically right there, and then you're just going to change this from -3x plus 1 to 1 minus 3x. All right, let's take a look at problem number 10. Let me slide down here. So we have f of x equals x minus 1 over 2x minus 4. So again, this is a one-to-one function. So I'm just going to start out by replacing f of x with y. So y equals, we've got our x minus 1 over the 2x minus 4. So again, at this point, I'm going to interchange x and y. You have to be careful because you have an x here and also here. So each one needs to become a y. So you're going to put this as an x. So x is equal to y minus 1 over 2y minus 4. So this becomes a y, and this becomes a y, and this becomes an x. At this point, I'm just going to multiply both sides by 2y minus 4. And let me do that over here as well. So let me put the x over here. So times the quantity 2y minus 4. Close that down. Maybe that could be a lot better. And essentially, this would cancel with this. And so I'm going to distribute that x to each guy inside the parentheses. You're going to have 2xy, and then minus 4x is equal to y minus 1. Again, what you're looking to do here is basically subtract y away from each side. Let me just write that like that. Or actually, let me move it over here like this and go plus. And then I'm going to add 4x to both sides. So like this. Let's say that this is going to cancel and this is going to cancel. And so we're going to have, let's go 2xy minus y is equal to, let's write this as 4x minus 1. Okay, let me come to a new sheet here. Again, if you have a y here and a y here, just factor it out. That's all you have to do. So we're going to pull this out in front of some parentheses. So you have y times the quantity, 2x minus 1. And this equals, you're going to have 4x minus 1. So I'm just going to divide both sides of the equation by this 2x minus 1, so this quantity. Again, you don't need parentheses here. Here, you're just showing it as a quantity so that you can cancel it. So this over this is going to be 1. Let me slide down here and just say that y is equal to 4x minus 1 over 2x minus 1. And I'm just going to change my notation to finish things up. So f inverse of x is equal to 4x minus 1 over 2x minus 1. And again, let me cover the different solution that's given on the practice tests. This is coming from a computer. Either way you want to answer is fine. They're both correct. So basically, the numerator is the same. So 4x minus 1 over, you're going to factor out a -1 from here. So let's say this is -1 times the quantity. This would be -2x and then plus 1. So just bring this up here. So I'm just going to say this is the negative of this. And then I'm just going to rearrange these terms to be 1 minus 2x. So 1 minus 2x. So if you want to give this as the answer or this, again, both are correct, whatever you want to do. All right, let's take a look at the practice test. For the instructions, we're asked to determine if the given functions f of x and g of x are inverses. All right, let's take a look at the first problem. So here we have f of x is equal to 3 over x minus 1, and then you have minus 1. Then we're given g of x. So this equals 3 over x plus 1, and then plus 1. So we're asked the question, are these two functions inverses? So how can we show that they're inverses or show that they're not inverses? What do we need to do? So recall in the lesson we said that if two functions are inverses, so let's say f of x and g of x, then it has to be true that f of g of x is equal to x, and also g of f of x would be equal to x. So to prove that these guys are inverses, we're going to use that technique of function composition. So I'm going to start off with f of g of x. Now this is a little bit hard to plug into on the screen and just to keep everything visible. So what I did was I already filled this out. So I'm just going to show you where this is coming from. Again, this is my f of x here. So this is the x involved there. So essentially all you're going to do is you're going to take g of x. So that's this guy right here. So this 3 over x plus 1 and then plus 1. And you're going to plug it in for x right there. So that's how you're going to get f of g of x. Then when you want g of f of x, well, now you're going to take, this is your x there, and you're going to take this f of x, and you're going to plug this guy in right there. So that's all you're doing. We've worked with function composition before, so hopefully you know how to do that. And I'm just going to slide down here. Again, this is already done. So I have f of g of x is equal to, you have your 3 over, again, this was x, but I'm replacing it with g of x. So g of x is 3 over x plus 1, and then plus 1. So I went ahead and wrapped this in parentheses. This is where x was, just to show that. You don't need the parentheses. We're going to drop them in a moment. Then you have this minus 1 here, and then outside of this fraction, you have minus 1 here. So let's go ahead and just put equals. For the first step, I'm just going to drop these parentheses. You don't need them. I just put them in there to show where x was. So I'm going to put 3 over, you're going to have 3 over x plus 1. And then outside of this, you'll have plus 1. And of course, then you have minus 1. Again, I'm just dropping the parentheses. And then you have this minus 1 out here. So what you would notice is that you have plus 1 minus 1. You can just cancel that away. That's going to end up being 0. So let me copy what we have now. So this is 3. And then I'm just going to write this actually as 3 over 1. You'll see why in a moment. And then this is over. You have your 3 over x plus 1. And then outside of this, so right here, you have this minus 1. Let me slide down here for a moment. So we know this is a complex fraction. And so this is the numerator and this is the denominator. And so what you could do to solve this is say that this is 3 over 1 times the reciprocal of this denominator here. So that's x plus 1 over 3. And then don't forget about this minus 1 here. So of course, this 3 would cancel with this 3. And so you have x plus 1 over 1, which is just x plus 1. So now we have x plus 1. And then you have this minus 1. And of course, we can see that again, plus 1 minus 1, that's 0. You can just cancel that away and say that this is x. So we've shown that f of g of x is equal to x. So that's the first part. The second part is that it also has to be true that g of f of x is equal to x. So you have to do this in both. So now we have 3 over, again, I put the parentheses here to show where x was. So this was x. Now I'm plugging in my f of x. So the 3 over x minus 1 and then minus 1. So that was my f of x. Then you have plus 1, and then outside of the fraction, you have plus 1. All right, so again, for the first step, I'm just going to drop the parentheses. I just put it there for formatting to show you where x was. So let's say that this equals 3 over, just drop this, so 3 over x minus 1. And then you're going to have minus 1 here, and then you're also going to have plus 1 here. So again, all I did was drop the parentheses. Then you have plus 1 outside of that. So we know that negative 1 plus 1, that's 0. You can just line that out. Let me put equals. And again, I'm just going to write this as 3 over 1, and then over 3 over x minus 1. And then we have plus 1 outside. Let's put this down here. And let's say that now the numerator will be multiplied by the reciprocal of the denominator in terms of the complex fraction. So let's say this is 3 over 1 times, again, the reciprocal of this would be x minus 1 over 3. And then you have this plus 1. So these 3's are going to cancel, and you're left with x minus 1 over 1, which is just x minus 1. And then you have plus 1. And again, minus 1 plus 1, that's 0. You can line that out and just say this equals x. So at this point, we know that f of g of x is equal to x, and g of f of x is equal to x. So we can conclude that these two functions, f of x and g of x, are going to be inverses. So I'm just going to put inverses, or maybe I could just put yes. It doesn't really matter, but I think on the practice test we put inverses, so that's what I'll put here. All right, let's look at problem number 2. So here we have f of x is equal to 4 over x minus 3, and then g of x is equal to 4 over x plus 3. So again, I'm going to do f of g of x, and then also I'm going to look at g of f of x. So here is f of g of x. So again, I've already done this for you. So this equals 4 over, I'll put the parentheses in here to show you where x was. And again, I'm plugging in for x, g of x. So g of x was 4 over x plus 3. So that's where that's coming from. And then outside of this, you have minus 3. So I'm just going to drop the parentheses to get things started. So I'm just going to put 4 over, let's go 4 over x plus 3, and then we have minus 3. And I would probably prefer, let me move this down here, just for clarity, to write this as 4 over 1, because again, we have a complex fraction here. So this is the numerator, this is the denominator. And so what I'm going to do is take this numerator, which is 4 over 1, and multiply by the reciprocal of this denominator. So this is times x plus 3 over 4. And then don't forget you have this minus 3 here. Let me slide down. All we're going to do is cancel this with this, and then you're going to notice that what you have is x plus 3 and then minus 3. Of course, the plus 3 minus 3, that's going to cancel away and give you 0. So this becomes x. So f of g of x is equal to x. So that's the first one. For the second one, now you have g of f of x, and this is equal to 4 over. Again, I'm wrapping where x was with parentheses. So this was an x. I'm plugging in f of x there. So the 4 over x minus 3. So that gets put in there. Then we have plus 3 here. So let's just say that this is equal to 4 over. Again, just drop the parentheses. So 4 over x and then minus 3 and then plus 3. Again, if you think about something like minus 3 plus 3, that's just going to cancel, right? That's just 0. Let's go 4 over 1, then over 4 over x. And all you're going to do is say this is equal to, we're going to have this 4 over 1, that's going to stay unchanged. And then we're going to multiply by the reciprocal of this denominator here. So times x over 4. And then, of course, we're going to see that the 4s are going to cancel. And what you're left with is just x. So again, we've seen that f of g of x is equal to x, and g of f of x is also equal to x, so we can conclude that these guys are inverses. So again, I'll just write that they're inverses like this. All right, let's take a look at problem 3. So here we have f of x is equal to 1 over x minus 1, and then g of x is equal to 4 over x minus 2, and then minus 1. So again, let's start with f of g of x. So here's f of g of x. Again, I've already set this up. So this equals 1 over, again, where x was, I just wrapped that with parentheses. We can just drop the parentheses. I'm just doing this for formatting to show you where x was. So inside of here, I'm going to plug in g of x. So that's 4 over x minus 2, then minus 1. And then we have this minus 1 here. So let me say this equals 1 over, again, I'm just going to drop the parentheses. So 4 over x minus 2, and then minus 1, and then minus 1. Now, you'll notice that with the previous two problems, we saw things that would just cancel. Here you have minus 1 and then minus 1. That's negative 2. So let's write this as 1 over. You have 4 over x minus 2 and then minus 2. Now, there's lots of different things you could do at this point. You could, and I think this is the fastest way to do it, multiply the numerator and denominator by x minus 2. Let's just go ahead and do it that way. This is going to get distributed to this, and then this, and then this. So x minus 2 times 1 is just going to be x minus 2. Then this is over. You would have x minus 2 times 4 over x minus 2. Let me show this real quick so nobody's lost. 4 over x minus 2 times x minus 2. We're going to cancel this with this. So that's just going to give you 4. So let's write this as 4. And then here's where you have to be careful. X minus 2 needs to get multiplied by negative 2. So let me go plus negative 2 times the quantity x minus 2. So it's real important if you're trying to simplify this to do that. So to finish things up, what I'm going to do is say this is x minus 2 over. You could factor out a 2 from here. You could also factor out a negative 2. I think that'll actually make it a little bit cleaner. Let me pull out a negative 2, and then you'd have a negative 2 there. And then if I'm pulling out a negative 2 from there, what you have is this x minus 2. You can just drop the parentheses. So let me go plus. You're going to have x and then minus 2. Let me move that down there and close this down. Now, negative 2 minus 2 is negative 4. So this becomes, let me write this down here, x minus 2 over. Let me move this negative up. So let me just put that negative there. And we'll say this is 2 times the quantity. This is x minus 4. So x minus 4. So this is one way you could write it if you were asked to find f of g of x. Of course, this is not equal to x. So these guys are not inverses. You could stop. You don't need to check the other one because both have to be true. So let me put that they are not inverses. Okay, let's look at problem 4. So here we have f of x is equal to the quantity x plus 1 cubed plus 1, and then g of x is equal to the cube root of x minus 1 and then minus 1. So this one's a little bit tricky to plug in for. Again, this is your x right here. Let me show you what we've done. You have your f of g of x. Again, you had the quantity x plus 1 cubed, and then you have plus 1. So this right here is where you're plugging in for your x. So again, I've wrapped that with some parentheses. Don't confuse it with these parentheses here. This is for the quantity being cubed. So where we're plugging in for g of x is right there in that blue color. Again, g of x is the cube root of x minus 1 and then minus 1. Okay, let's go through and just simplify. So the first thing is I'm going to drop these parentheses right here. I just put them in for clarity, again, or for formatting, however you want to think about that. So I'm going to say this is the quantity. Now you would have the cube root of x minus 1, and then you'd have minus 1. Let me make this a little bit shorter like this. And then you'd have plus 1, and this is cubed, and then you have plus 1. Okay, so again, if you have something like negative 1 plus 1, that's going to cancel and give you 0. So this turns into your cube root of x minus 1 being cubed, and then plus 1. Well, of course, the cubing will undo the cube root, and you're just going to be left with the radicand there. So what I would have is x minus 1, and then plus 1. And again, when you see something like minus 1 plus 1, those are going to cancel, and now we're going to have x. So f of g of x is equal to x. Now what about g of f of x? So here we have the cube root of, and this right here is where I'm plugging in for x. So this is x, and then minus 1, and then you have minus 1 here. So what am I plugging in for x? Again, f of x, that's the quantity x plus 1 cubed plus 1. So again, you can just drop these parentheses. So these right here, it's just there to show you where I'm plugging in for x. So I'm just going to say this equals the cube root of, you're going to have this quantity x plus 1 cubed, and then you're going to have, let me extend this a little bit. So you have plus 1 and then minus 1. So these are both going to be underneath that radical sign. And then outside of that, you have minus 1. Again, plus 1 minus 1, that's going to cancel. So this becomes the cube root of this quantity x plus 1 cubed and then minus 1. The cubing will be undone by the cube root, and you're going to have this x plus 1 here. So let's say we have x plus 1 and then minus 1. And so here, this plus 1 minus 1, you can just line that out and say that would be 0. And so we would just have x. So again, we see that f of g of x is equal to x, and g of f of x is also equal to x. So yeah, we can say that these functions are inverses. All right, let's take a look at problem 5. Here we're given f of x is equal to the cube root of x minus 2, then minus 2, and g of x is equal to negative x cubed plus 4. So for f of g of x, this equals the cube root of, again, I'm using parentheses to show you where x was, and we're plugging in negative x cubed plus 4. That's your g of x. Then you have minus 2, and then outside of the cube root, you have minus 2. So this would be equal to what? So let me put this up here. So the cube root of, you have negative x cubed plus 4. You could just drop those parentheses. Again, I'm just doing that to show you where x was. Then you have minus 2, but this minus 2 is underneath this radical sign. And then you have a minus 2 outside of that. Now, if you do 4 minus 2, that's 2. So let me just show this as the cube root of negative x cubed. And then you'd have plus 2. Again, that's coming from 4 minus 2. And then you have minus 2 outside here. Can you do anything to simplify this? Not really. Some computer programs, if you type this in, what they'll do is they'll say that, let me just show you this real quick in case you get a different result. You would get the cube root of, let's say I factor out a negative 1. So then times the quantity x cubed minus 2 like this. And then let's say minus 2. And so the cube root of negative 1 is negative 1. So you could pull that out as a negative. In other words, you could say that this is the cube root of negative 1 times the cube root of x cubed minus 2. So that's just using the product rule for radicals. And then minus 2 here. And of course, the cube root of negative 1 is negative 1. So you might see it written as the negative of the cube root of x cubed minus 2, and then minus 2. Now, if you list it this way or this way, it really does not matter because we're just trying to see if they're inverses or not. And of course, I don't get x from f of g of x, so that means immediately that they're not inverses. They're not going to undo each other. So let me come down here and just basically say that they're not. So not inverses. All right, let's take a look at problem 6. So here we have f of x is equal to 1 plus 1/2 x, and then g of x is equal to 2x minus 2. So again, if we take a look at f of g of x, this would be equal to 1 plus 1/2. Again, here's where x was in our f of x function. I'm plugging in g of x. That's why I put these parentheses here. So this is 2x minus 2. So what I'm going to do is just say this equals 1 plus. So this is just going to get distributed to each guy. The other way you could write it, if you didn't want to do that, you could just say it's 2x minus 2 over 2, but then you pretty much have to break it back up. So I'm just going to distribute it. I think that's a little bit faster. So 1/2 times 2x, let's just say that's 2x over 2, and then minus 1/2 times 2. We know that's 1, but let's just write it. So 1/2 times 2. Okay, so let's just keep the 1 right here, and then plus the 2's would cancel. So you have x, and then minus, again, the 2's would cancel, so you have 1. And again, you can rearrange this if you want. Of course, a lot of people will just cancel it and say it's x. But for completeness, let's just say that this is x plus 1 minus 1. And of course, at this point, your plus 1 minus 1, that's basically going to go away and be 0. So this is just x. Okay, for g of f of x, this equals 2 times, again, this quantity here, this is where x was. I'm plugging in my f of x, so my 1 plus 1/2 x. And then you have your minus 2. So I'm going to use my distributive property here and just say that this is 2 times 1, which is 2, and then plus 2 times 1/2 x. So 2 times 1/2 x, and then minus 2. So of course, this 2 would cancel with this 2, and this gives me, let me rearrange this and just say this is 2 minus 2 now, and then plus x. And of course, this is going to cancel. 2 minus 2 is just 0, so you're left with just x. So once again, we've seen that f of g of x is equal to x, and g of f of x is also equal to x. So we can conclude that these two functions are inverses. So these are inverses. All right, for problem 7, we have f of x is equal to the 5th root of x minus 1. And then for g of x, we have this being equal to x to the 5th power plus 1. So for f of g of x, this equals the 5th root of, you're going to, again, plug in right here. So this is where it was x minus 1, but I'm using the parentheses to show you where x was. So you're plugging in your g of x, so that's x to the 5th power plus 1. So if you just drop the parentheses here, you're going to have the 5th root of x to the 5th power plus 1, and then minus 1. And of course, when you see this plus 1 minus 1, that'll just cancel away and give you 0. So this becomes the 5th root of x to the 5th power, which is just x. Then for g of f of x, this equals, again, this was x to the 5th power plus 1, but we're plugging in for x. That's why I have these parentheses here. So you're plugging in the f of x, which is the 5th root of x minus 1. And so this would be equal to, the act of raising to the 5th power would undo this 5th root. So you would just have the radicand here of x minus 1. Let's say this is x minus 1 plus 1. So you have the minus 1 plus 1. So let's go ahead and cancel those away and say that would be 0. So this is just going to be x. So once again, we have f of g of x is equal to x. And it's also true that g of f of x is equal to x. So we can conclude that these guys are inverses. Okay, let's take a look at problem 8. So here we have f of x is equal to the negative of the cube root of 4x over 2. And then g of x is equal to the 5th root of x minus 2, and then plus 2. So this one is a little bit tricky to plug into. So f of g of x is equal to the negative of, again, you have your cube root of 4, and then this right here was where x was. That's why I have those parentheses there. And so basically inside you have the 5th root of x minus 2, and then plus 2. And then in the denominator down here, you have a 2. So this one is not going to work out. So what I'm going to do, let me just put the negative of the cube root of this guy right here. You could distribute the 4 to each guy. So this is 4 times the 5th root of x minus 2, and then plus 4 times 2 is 8. But again, there's not really a lot you can do here. This is not going to really simplify any further. Let me put this over 2. Let me move this down here and just put the negative out in front. And basically, you will not get this to simplify to x. So you can just stop and just say that these are not inverses. So not inverses. All right, for problem 9, this one's extremely easy. You can eyeball it and see it's going to work. You have f of x equals x plus 5, and then g of x equals x minus 5. So of course, for f of g of x, you have where x was here, plus 5. And again, what I'm plugging in for x, again, wrapped in parentheses, the g of x is x minus 5. So just drop the parentheses, you end up with x minus 5 plus 5. Again, this minus 5 plus 5, that's going to cancel, and you just get x. For g of f of x, this equals, you have this x plus 5 here. Again, inside the parentheses, that's where the x was, then minus 5. So just drop the parentheses, you get x plus 5 minus 5. And of course, this plus 5 minus 5, that's going to cancel and give you 0. So this just equals x. So again, we see that f of g of x is equal to x, and g of f of x is also equal to x, so we can conclude that these functions are inverses. All right, let's take a look at problem 10. So here we have f of x equals x minus 3 over x plus 7, and then g of x is equal to x minus 7 over x plus 3. So looking at f of g of x, this equals, again, where I have these parentheses, that's where you had an x, so I'm plugging in g of x for that. So you have this x minus 7 over x plus 3, that's your g of x, then minus 3 over your x minus 7 over your x plus 3. Again, that was your g of x, and then plus 7. Okay, so for this one, just drop the parentheses to start. So x minus 7 over x plus 3. And then this would be minus 3 over here. And then down here, you have x minus 7 over x plus 3. Let me make this 3 a little bit better here. And then you're going to have plus 7 here. Again, lots of ways to simplify something like this. When I see a complex fraction, I'm just thinking, what's the least common denominator? You have x plus 3 here, and you have x plus 3 here. So I think the quickest way to deal with this is to multiply the numerator and denominator of the complex fraction by x plus 3. So I'm just going to do that here. And again, if you want to do it a different way, if you want to simplify this part and then do a division, that's up to you. So this is going to get distributed to each guy. So we know that in the first case, the x plus 3 over the x plus 3 would cancel, and you're just going to have that numerator of x minus 7. Then you have this negative 3 that's multiplying this. You could write, for clarity, plus, let's go negative 3 times the quantity x plus 3 there. So that it's crystal clear that the negative 3 needs to multiply by each term. Then this is over. Again, I'm going to distribute this to this, and then also this. Let me make this multiplication sign more visible here. So this x plus 3 would cancel with this x plus 3. So again, you have x minus 7. And then this x plus 3 would multiply by 7. So let's do that with parentheses. So plus 7 times the quantity x plus 3. Okay, let me close that down. Now let me distribute this. We're going to say that this is x minus 7. And then you're going to have this negative 3 times x, so minus 3x. And then negative 3 times 3, that's minus 9. Let me move this down here like this for formatting. Let me put this over. So let's write x minus 7 here. You're going to distribute this 7 to each guy inside the parentheses. So plus 7x, and then plus 7 times 3 is 21. Okay, so let's think about what we're going to end up with. Obviously, it's not x. If you're on a timed exam, just stop and say these are not inverses. But for the sake of the tutorial, let's just continue. So here you have x minus 3x, that's negative 2x. And then negative 7 minus 9, that's negative 16. This would be over. You have x plus 7x, that's 8x. And you have negative 7 plus 21, that's going to be plus 14. Now, what you could do is cancel a common factor of 2. So let's factor out a 2 from the numerator, and that would give me negative x minus 8, and this would be over. If I factor out a 2 from the denominator, this would give me 4x plus 7. So if I cancel this 2 with this 2, I could say that this is negative x minus 8. Let me make that a little bit better, over 4x plus 7. Now, a lot of people would actually factor out a negative here as well. So in other words, you could put this as a negative and change this into a plus, because the negative of x is negative x, and then the negative of 8 is negative 8. So just distributing that negative will get you back to negative x minus 8. So then what you could do is write this as a negative out in front, and then put x plus 8 in the numerator over 4x plus 7 in the denominator. And I think that's pretty well simplified. Again, lots of different ways you could have written this. At the end of the day, our f of g of x is not equal to x, so we can just stop and say these are not inverses. So not inverses. All right, let's take a look at the practice test. For the instructions, we're asked to find the inverse of each. All right, let's take a look at the first problem. So here we have f of x equals the square root of x plus 5, and we're told that x is greater than or equal to negative 5. Although for this particular problem, this being listed here is actually unnecessary. We know if we see something like the square root of x plus 5, in the real number system, we can't take the square root of a negative. Of course, we can do it using the imaginary unit I, but we're not involving that here. So if you wanted to figure out where this is coming from, again, all you would do is take your radicand, so x plus 5, and say, where is that greater than or equal to 0? You would subtract 5 away from each side of the inequality. This would cancel, and you get x is greater than or equal to negative 5. So that's where this is coming from. So basically, your domain is going to be that x can be any value that's -5 or larger. Now, when I work these problems, I always like to look at a graph. It makes it a lot easier to find the domain and range without going through a lot of tedious algebra. So here, again, if you type this into Desmos, you have f of x equals the square root of x plus 5. You can see your domain is clearly where x is going to be -5 or larger. So let me just list that x is greater than or equal to -5. We're actually not going to need that here. We need the range. So this is going to come into play here. So the range is that y is greater than or equal to 0. So y is greater than or equal to 0. Again, you can see that from the graph. If you plug in a -5 there for x, -5 plus 5 is 0. Square root of 0 is 0. If you plugged in something larger than -5, well, then of course you're going to get something larger than 0. So y could be 0 or anything larger. Now, when we look at this function f of x equals the square root of x plus 5, it is a one-to-one function. It passes the horizontal line test, and so it will have an inverse. The issue is going to come up when we find the inverse. We're going to see that we actually have to restrict the domain because it won't be a one-to-one function. So just keep this in mind. So we're going to come down here to a fresh sheet and just get things started. So f of x is equal to, let's have the square root of x plus 5. So the normal procedure is we replace f of x with y. So we say y is equal to the square root of x plus 5. At this point, you want to interchange x and y, and that just means you're going to swap them. So this is a y right now, so it becomes an x, and this equals the square root of, this is an x, so it becomes a y, and then plus 5. So your goal now is to solve for y. So how do we do that? Well, I want to get rid of this square root guy, so I'm going to square both sides. So x squared is equal to the square root of y plus 5 being squared. And so what you're going to end up with is x squared is equal to, this guy would undo this guy, so you just have the y plus 5. And then I'm just going to subtract 5 away from each side of the equation. And so this, of course, is going to cancel. I'm going to write this because I like what I'm solving for on the left as y is equal to x squared minus 5. Now, there's a problem here. If you were to graph y equals x squared minus 5, that is a parabola. It's not going to pass the horizontal line test, so it's not one-to-one. So what you have to do, again, is go back to where you said that y is greater than or equal to 0. Remember that when you find the inverse of a function, the x's and the y's are swapping. So that means the domain becomes the range and the range becomes the domain. So the range here, where y is greater than or equal to 0, will become the domain. So we can say in the inverse, x will be greater than or equal to 0. So let's come back down here and say specifically that x is greater than or equal to 0. So by restricting the domain, we're creating a one-to-one function, something that's going to pass the horizontal line test and will have the same range. So now I'm just going to finish things up by replacing my notation here and saying that instead of y, I have f inverse of x, and this equals x squared minus 5, and specifically here, x is restricted to be greater than or equal to 0. So this right here is the inverse. If you leave off the restriction, remember this is not a one-to-one function, so you're not getting the right answer. Okay, there are different ways you can check this. The easiest way is using a graph, just going to Desmos and keying in your function and then the inverse. So a few things about using Desmos, they do not accept the f inverse notation. So you're going to need to use something like g of x. So you can key this in as g of x is equal to x squared minus 5. So what you want is to put in some curly braces there and say that x is greater than or equal to 0 like that. And that's going to produce this graph right here in yellow. So this guy, you can notice that if I didn't restrict the domain, it's going to give me a parabola. So this shape would continue this way. And again, that would fail the horizontal line test. So it's not one-to-one. So that's not what we want. You can clearly see that these guys are inverses. They are a reflection across the line y equals x. You can look at some points. So something like, let's say this point right here, which is -5, 0. And then in the inverse, you have this right here. So basically the x's and the y's are swapped. So this is 0, -5. A lot of books will show it like this. If you want to pick some points and do it. So maybe we'll do this one right here. And I'll just do this on the first one. On the next ones, I'll just fly through it and you can just do it on your own if you want. So just a few of those things so that we can see that, yes, this is a reflection across the line, y equals x. And so these guys are going to be inverses. All right, the other way to check, which is much more time consuming, especially for these problems, you can use function composition, just like we talked about in the last lesson. So in other words, we have f of x is equal to the square root of x plus 5. And then we have f inverse of x is equal to, we have x squared and then minus 5. And specifically here, x is greater than or equal to 0. You have to consider this right here when you do the function composition. Otherwise, you will not get the right answer. So let me show you what I mean. We would start off with f of f inverse of x. What does this mean? It means that I'm taking this right here, so this right here, and I'm plugging it in for x right there. That's all I'm doing. So let me set this up as the square root of, so this gets plugged in for this, so this is x squared minus 5, and then plus 5. Now keep in mind that what's getting plugged in here is that x is greater than or equal to 0. So I can't have negative values. That's going to come into play in a moment. So this right here would cancel. So this is equal to the square root of x squared. Now, we know from simplifying that if we say that x is 0 or some positive number, that basically this will undo this and I'll just have x. That's one way to think about it. The other way, if you want to use a more tedious definition, you can say that this is equal to the absolute value of x, which is true. So the square root of x squared is equal to the absolute value of x. But when you think about the definition of the absolute value of x, so the absolute value of x is equal to, let me set up some curly braces here. So it's equal to x when x is greater than or equal to 0, and it's equal to the negative of x when x is less than 0. So since we have x being greater than or equal to 0, we can say that this right here, this absolute value of x, is going to be x. So this one right here gives us x. Let me erase this and just put that this is x. So it also has to be true that f inverse of f of x is equal to x. So now what we're doing is we're taking this guy right here and we're plugging it in for x right there. So you're going to have, let me get rid of this. We're going to have this guy right here, square root of x plus 5. So that's getting plugged in right there. And then we've got to square this and then minus 5. So this one's pretty straightforward. The squaring will undo the square root operation. So let's just erase this. And then you have x plus 5 minus 5, which is just x. So that's another way to prove it. It's very, very tedious to do it this way. So just remember this rule when you're simplifying. And I'll let you do it this way on your own. I have a graph prepared for each one. So that's how I'm going to check it. All right, let's take a look at problem 2. So now we have f of x equals the square root of 2x minus 3. And we're told that x is greater than or equal to 3/2. Again, that's coming from taking 2x minus 3 and saying, where's that greater than or equal to 0? Add 3 to both sides of the inequality. This cancels, and you'll get 2x is greater than or equal to 3. And then you would just divide both sides of the inequality by 2. That cancels. And you end up with x being greater than or equal to 3/2. Again, you can't take the square root of a negative in the real number system. So we know the domain. So x is greater than or equal to 3/2. But what's the range? Again, for this guy right here, you can make it 0, but you can't make it negative. You can make it anything larger than 0. So basically, you would say that y is greater than or equal to 0. Again, you can see that from the graph. This point right here would be 3/2 comma 0. And again, you can always just think about it. If I plugged in a 3/2 for x, 2 times 3/2 is 3. 3 minus 3 is 0. And of course, if I plug in something that's larger than 3/2, I would get something that's greater than 0. So remember, we're going to need this. So let's write out the problem. So we have f of x is equal to the square root of 2x minus 3. I'm going to replace f of x with y. So y is equal to the square root of 2x minus 3. And then what I'm going to do at this point is interchange x and y, or you could say swap x and y. So x is equal to the square root of 2y minus 3. Again, if I want to get y by itself or solve for y, what I'm going to do is square both sides. So I'm going to say that x squared is equal to the square root of 2y minus 3. And this is going to be squared. Now I'm going to say that x squared is equal to, this squaring would undo the square root operation. So you have 2y minus 3. Let me add 3 to both sides of the equation here. So this would cancel. And you're going to end up with 2y is equal to x squared plus 3. Now, if I want y by itself, let's go ahead and divide both sides of the equation by 2. This would cancel. And I'm going to end up with y is equal to x squared plus 3 over 2. Now, again, this is not going to be a one-to-one function. And so that's why we come back up here and we say, well, the range here from this function that I'm working with is going to become the domain in the inverse. So in the inverse, it would be that x is greater than or equal to 0. So let's come back down and say that x is greater than or equal to 0. And so now I'm going to replace this y with my inverse notation. So we'll say f inverse of x is equal to x squared plus 3 over 2, where we'll say that x is greater than or equal to 0. Again, this is required here because if you don't list it, it won't be a one-to-one function. Okay, so once again, you could check this by function composition if you want. It's a little bit tedious. I think it's a lot quicker just to go to Desmos and type things in and just see if you have the function in the inverse as a reflection across the line y equals x, and you can see you have that. So the original function here, f of x equals the square root of 2x minus 3, And then the inverse, f inverse of x is going to be x squared plus 3 over 2. And specifically here, we're restricting the domain to where x is greater than or equal to 0. If you don't, you're going to see again that you get a parabola shape, which would not be 1-to-1. It would not pass the horizontal line test. So this is how you want to list your answer. All right, let's take a look at problem 3. So here we have f of x equals 1 over the square root of x plus 9, and we're told that x is strictly greater than negative 9. Now, where is this coming from? Why doesn't it say x is greater than or equal to negative 9? This square root operation is in the denominator. So we don't want this to be 0. We need this part right here, the radicand, to be greater than 0, because the square root of something that's greater than 0 will be greater than 0, and we'll be okay. 1 divided by some, let's just say positive number because it's not 0, you'll be okay. You're not going to violate anything. So you would have to say that x plus 9, the radicand there, is strictly greater than 0. Subtract 9 away from each side of the inequality, and you're going to get that x is greater than negative 9. So that's where this part right here is coming from. Now, if you want to go to the graph, again, let me write x is greater than negative 9. You can see the domain. So basically, x can be anything larger than negative 9. You can also see the range. So y here would be greater than 0. It's kind of hard to see from the graph here, but if you go to Desmos and key this in, I think it's a little bit easier to see. Now, you could also think your way through this. So if you have something like 1 over, again, this guy right here, we can't make it 0 and we can't make it negative. But we can make it something that's greater than 0. So think about something very, very close to 0. You'd have 1 divided by something that's very close to 0. That's going to approach infinity as this approaches 0, this denominator here. So that's why you see this guy right here blowing up. Now, in terms of this right here, this is going to approach 0 as x gets larger and larger. So the reason for that is, as you plug in bigger and bigger values for x, again, this part right here is going to get larger and larger, and 1 divided by something that's really, really big is going to approach 0. So that's where you're getting this y is greater than 0. Now let's come down and let's start off f of x is equal to 1 over the square root of x plus 9. Again, the normal procedure is just to say that we have y is equal to 1 over the square root of x plus 9. At this point, you're going to swap x and y. So let's say we have x is equal to 1 over the square root of y plus 9. Now you want to solve for y. This one's a little bit tricky, and there's different paths you can take depending on what you're comfortable with. So what you probably would want to do is raise both sides to the power of negative 2. So I would say this is x raised to the power of negative 2 is equal to, this right here is 1 over the square root of y plus 9, and this is raised to the power of negative 2. So this, x to the power of negative 2, we know that is 1 over x squared. And then this right here would be 1 raised to the power of negative 2, which of course is just 1, over, you have your square root of y plus 9 raised to the power of negative 2. You can actually erase this, and then you can drag this across the fraction bar and change this onto the exponent. So let me erase this and this and this, and get rid of this, and put these parentheses back in like this. And of course, when you square this, it's going to undo the square root guy. Let me move this over here like this, like what I'm solving for on the left. So y plus 9 is equal to this. At this point, you would just subtract 9 away from each side of the equation. So this is going to cancel, and you're going to have y is equal to 1 over x squared minus 9. Now, this is not 1-to-1. Again, when we come back up here, remember that y was greater than 0. So in the inverse, x will now be greater than 0 because the range becomes the domain in the inverse. So coming down here, we'll say that x is strictly greater than 0. So let's write this with our inverse notation. So f inverse of x is equal to 1 over x squared, then minus 9. And then specifically, I'm going to say that x is greater than 0. All right, so once again, I have a graph already set up for you. So we have our function f of x equals 1 over the square root of x plus 9. We have the line y equals x. And then we have our inverse. So f inverse of x equals 1 over x squared minus 9, where specifically x is greater than 0. Again, if you don't put this in right here, it's not going to be a 1-to-1 function. It will not pass the horizontal line test. So you need to make sure you put that in so that you get the right answer. But clearly you can see that these guys are going to be a reflection across the line, y equals x. So we found the correct inverse. All right, let's take a look at problem 4. So here we have f of x equals 1 over the square root of x minus 5. And here we're told that specifically x is greater than 5. So again, just like in the last problem, you have this guy in the denominator. So we know that it can't be 0. We also know it can't be negative. So we would say that x minus 5, where is that greater than 0? Add 5 to both sides of the inequality, and you're going to end up with that x is greater than 5 that you see. So that's where that's coming from. Again, if you want to look at the graph of this guy, we'll see that x is greater than 5. So in terms of the range, it's going to be that y is greater than 0 again, for the same reason that we talked about in the last problem. So 1 divided by, this can't be negative and it can't be 0. Something really close to 0, well, that's going to approach positive infinity as you get closer and closer to 0. And as you make x larger and larger, you're actually going to approach a y value of 0 because you have 1 divided by something that's really, really large. So that's going to approach 0. So here, y would be greater than 0. So let's write out that f of x is equal to, let me make that x a little bit better. So we have 1 over the square root of x minus 5. Again, I'm just going to write y is equal to 1 over the square root of x minus 5, and then I'm going to swap x and y. So I'm going to say that x is equal to 1 over the square root of y minus 5, and then I'm going to solve for y. So again, just like I did last time, I'm just going to raise both sides to the power of negative 2. So x raised to the power of negative 2 is equal to, this would be 1 over the square root of y minus 5 raised to the power of negative 2. So x to the power of negative 2 is 1 over x squared, and this equals, you would have 1 to the power of negative 2 over, you'd have your square root of y minus 5 raised to the power of negative 2. What I'm going to do is say that 1 raised to the power of negative 2 is still 1. In this, we're going to drag it across the fraction bar and change the sign of the exponent. So this like that. And when you square the square root, you're going to end up with that radicand of y minus 5. Let me move this up here like that. And I'm just going to erase this and add 5 to both sides like that. I'll show this as canceling. And we're going to get y is equal to 1 over x squared and then plus 5. But again, this is not going to be a one-to-one function. So coming back up, we see that y is greater than 0. So that means in the inverse, x will be greater than 0. So here, let's say that x is greater than 0. And let's come down here and say that f inverse of x is equal to, let me make this a little bit better, 1 over x squared plus 5. And specifically, again, we're going to say that x is greater than 0. So once again, I've already sketched our graphs here. So we have our f of x equals 1 over the square root of x minus 5. We have our y equals x, that line. And then we have our f inverse of x is equal to 1 over x squared plus 5. Again, where x is specifically greater than 0. Putting this in gives us a one-to-one function, so we'd pass the horizontal line test, we'll be good to go. You can see that these guys are going to be a reflection across the line y equals x, so we found the correct inverse. All right, let's take a look at problem 5. Here we have f of x equals x squared plus 3, and we're specifically saying that x is greater than or equal to 0. So with the first 4 problems, we were given one-to-one functions. We just listed the domain to make it easier to see, and basically you can come up with them by looking at the function. With this one, we know that f of x equals x squared plus 3. That's not a one-to-one function. This is a parabola, and it will not pass the horizontal line test. So we are actually required here to list this. Now we could do x is greater than or equal to 0, or we could do x is less than or equal to 0, whatever you want to do if you're told to find the inverse. But specifically, most books will just give you one of those, and then you'll have to find the inverse based on that. Now, if we look at the graph here, this is half of a parabola. So essentially, if you look at this point right here, this is the vertex if you had the parabola. So this is going to occur at 0, 3, but we don't have the whole thing. We've cut it in half. Basically, we're saying just take the right side of it, and we're going to find the inverse of that, because doing that gives me a one-to-one function. I can now pass the horizontal line test, and of course, I have the same range. So we're going to say that x, again, is greater than or equal to 0, and we're going to say that y is greater than or equal to 3. But the y values here are not going to come into play. We're going to need to use this right here. So let's come down and say we have f of x is equal to x squared plus 3. And we're going to list, again, that x is greater than or equal to 0. So this is actually required, again, when you're writing this problem, because this right here is not one-to-one. What I'm going to do is replace f of x with y. And we'll say this is x squared plus 3. And again, specifically, x is greater than or equal to 0. I'm going to swap x and y. So this is x is equal to y squared plus 3. And now, because I swapped my x's and my y's, my domain becomes my range. So I'm going to say that y is greater than or equal to 0. So what I'm going to do now is solve for y. So let me subtract 3 away from each side of the equation. That cancels. You're going to have y squared is equal to x minus 3. And let me write that y is greater than or equal to 0. So how do we solve for y? Well, basically, you just take the square root of each side, but you have to remember that because this is y squared here, you're going to end up with y is equal to plus or minus the square root of x minus 3. Now, you don't actually need the plus or minus, but again, if I was solving this and this wasn't involved, this is what you would do. But because this is involved, you have to think about this. We are saying specifically that y is greater than or equal to 0. Do I want this negative here. That would give me y values that are less than 0. So no, I don't want that. I'm going to get rid of this and say that because of that restriction, that y is specifically 0 or something larger. So I can make this guy 0, and I can make it something larger than 0. So basically what I would do is say that this is my inverse. So f inverse of x is equal to the square root of x minus 3. So you don't want the plus or minus, you just want the principal or the positive square root of x minus 3. So coming down here, again, I have everything sketched. So we have our f of x equals x squared plus 3, where x is greater than or equal to 0. So again, that's this right here. It's that half of a parabola. You have your line y equals x, and then you have your inverse. So f inverse of x is equal to, you have your principal square root of x minus 3. And again, you can see this is going to be a reflection across the line y equals x when you look at the function and the inverse. All right, let's take a look at problem 6. So I know this one's a little bit tricky. We have f of x equals x squared minus 4x minus 1, where x is less than or equal to 2. So this right here has to be written because, again, this is not going to be a one-to-one function. This is going to be a parabola if you sketch it, and it's not going to pass the horizontal line test. So you might want to sketch this on Desmos, but basically this is what your graph is going to look like. So f of x equals x squared minus 4x minus 1, where x is less than or equal to 2. So this right here, this point would be 2 comma negative 5. Again, if you had the full parabola, that would be your vertex. But essentially, you can see here we're just taking x values that are 2 or less. That's creating this right here. So if I think about my range, if you want that, so y is going to be greater than or equal to negative 5. Let me write the domain again. So x is less than or equal to 2. All right, let's come down here and let's copy our problem. So f of x is equal to, we have x squared minus 4x and then minus 1. We're told that x is less than or equal to 2. We are going to write y is equal to x squared minus 4x minus 1. Again, x is less than or equal to 2. And then we're going to swap x and y. So we're going to say x is equal to y squared minus 4y minus 1. And then we're going to say that y is now less than or equal to 2. All right, let me slide down here a little bit. This is where you really have to use a little bit of thinking. I gave you a hint that you could use the quadratic formula, but I know a lot of you are going to still be a little bit confused by that. So you want to solve for y. And right now you have y squared, you have y, you have an x over here. So what you can actually do is subtract x away from each side of the equation. And so this would cancel and give me 0 over here. And I'm just going to write this as y squared. And specifically, let me put 1y squared for clarity. And then I'm going to put plus, let's go negative 4y. And then basically you have negative 1 minus x. So let me write negative x minus 1. And then this would be equal to 0. Now, when you think about the quadratic formula, again, normally we're using x, but you can use y or whatever. You could say ax squared plus bx plus c equals 0. Well, you want to grab the coefficient of x squared, that's your a, the coefficient of x to the first power, that's your b, and then your constant is your c. So essentially what I'm going to do here is I'm going to grab this coefficient of y squared as a. I'm going to grab this coefficient of y to the first power as b, and then this whole thing right here is going to be my c, or my constant. So you're just going to plug into the quadratic formula. So we'll say y is equal to the negative of b plus or minus the square root of b squared minus 4ac all over 2a. So you're just going to plug in. So we know that b is negative 4. So this would be negative 4. And then b squared, so this would be negative 4 being squared. And then ac, so a we know is 1. You could put it in or leave it off, it doesn't matter. And c is negative x minus 1. Let me extend that and extend this. A is 1, so again, you can put that in. So let's see what we get here. Let me slide down. So y is equal to, the negative of negative 4 is 4. And then plus or minus the square root of negative 4 squared is 16. And then let me treat this as plus negative here. So you can get rid of this 1. It's going to make it a little bit easier. So negative 4 times negative x is plus 4x. And then negative 4 times negative 1 is plus 4. Now 16 plus 4 is 20. So let me write this radicand as 4x plus 20. Okay, then this is over 2. Now let me slide down here a little bit and let's think about what we can do. You'll notice that you have a 4 here and 20 is really 4 times 5. So you can factor that out. You can say y is equal to 4 plus or minus the square root of 4 times the quantity x plus 5. So just factoring out a 4, and then this is over 2. Maybe I can make that a little bit better there. Let me actually copy this because we are definitely going to run out of room. So at this point, remember, if you have the square root of ab, This is equal to the square root of a times the square root of b. So we're just going to use this here. We're going to break this up and say y equals 4 plus or minus. This would be the square root of 4 times the square root of x plus 5. And you don't need the parentheses. Let me get rid of that. And this is over 2. The square root of 4 is 2. Let me just erase that and put a 2 there. And of course, what you can do now is factor out a 2. So y is equal to 2 times the quantity, 2 plus or minus. You could put a 1 there or just leave it off. It doesn't matter. The square root of x plus 5. And then this is over 2. So of course, this is going to cancel. And let me slide down here a little bit more. And you're going to get y is equal to 2 plus or minus the square root of x plus 5. Now, let's think about this for a moment. We had a restriction that said that y is less than or equal to 2. Okay, let's observe this. We have a 2 right there, and then we have a plus or minus this guy right here. We know that the result of this right here, because it's a square root operation, is going to be non-negative. So it's going to be 0 if you plugged in a negative 5 for x, or if you plug in something larger than negative 5 for x, you're going to get some positive value. Now, if you have 2 plus some positive value, that of course is going to be greater than 2. So that's not going to work. If you go 2 minus some positive value, that's going to be less than 2. And of course, if you do 2 minus 0, that's going to be 2. So how can I get y is less than or equal to 2? What I want is this to be a negative. So here we're going to say specifically that y is equal to 2 minus the square root of x plus 5. Let me get rid of this. We don't need it anymore. We'll say f inverse of x is equal to, I would probably write this as the negative of the square root of x plus 5 and then plus 2. So that's going to be your inverse. So coming down here, again, I have everything sketched. So you have your line y equals x. You have this guy right here, your original function, f of x equals x squared minus 4x minus 1, where specifically x is less than or equal to 2. And then you have your inverse right here. So now we're saying the negative of the square root of x plus 5 and then plus 2. Again, for this one, you can look at it and see that these guys are reflections across the line y equals x. You can even look at a few points if you want to and just verify, but we can clearly see from the graph that these guys are going to be inverses. All right, for problem 7, we have f of x equals x to the 4th power plus 2, and we're told that x is less than or equal to 0. So again, this guy right here would not be a one-to-one function. So looking at the graph, again, we've restricted this guy to where x is less than or equal to 0. You can see that the range here, if you want to write it, so x is less than or equal to 0, the range here, y is going to be greater than or equal to 2. So this point right here, this is going to be at 0, 2. So 2 or anything larger, but you're not going to use the range here. You're just going to focus on the domain. That will become the range in the inverse. So let's say that we have, again, f of x is equal to x to the 4th power plus 2, where specifically x is less than or equal to 0. So again, all we're going to do is say that y is equal to x to the 4th power plus 2, and we'll say that x is less than or equal to 0. Then we're going to swap x and y. So we're going to say x is equal to y to the 4th power plus 2, but now we got to change this. So this becomes y is less than or equal to 0. So now if I'm trying to solve for y, let's subtract 2 away from each side of the equation. So we'd say x minus 2, let me make that a little bit cleaner there, is equal to y to the 4th power. Let me show that as canceling. Let me put over here that y is less than or equal to 0 so we don't forget. And we're just going to say that y to the 4th power is equal to x minus 2. And again, y is less than or equal to 0. Now to solve for y, you would take the 4th root of each side, but that's going to turn into y is equal to plus or minus the 4th root of x minus 2. So that's where this restriction, y is less than or equal to 0, is going to come into play. We know that y is not going to be positive. So if I just look at the principal 4th root of x minus 2, well, that's not going to work because I want y values that are either 0 or negative. So I want this right here. So basically the negative of the 4th root of x minus 2. I know that this right here will either be 0 or some positive value. So when I apply that negative to it, it's either going to be 0, the negative of 0 is still 0, or it's going to be some negative value because the negative of a positive number is going to be negative. So this right here would be your inverse. So you want to say that f inverse of x is equal to the negative of the 4th root of x minus 2. All right, so again, I have everything set up. If you want to go to Desmos and just type everything in, this is the function we were working with. So f of x equals x to the 4th power plus 2. And we said that x was less than or equal to 0. So that's this guy right here. And then the inverse, f inverse of x, is equal to the negative of the 4th root of x minus 2. So that's this guy right here. Again, you can see that these guys are going to be reflections across the line y equals x. I'll let you play around with it on Desmos on your own. But again, these are going to be inverses. All right, for problem 8, we're given f of x is equal to, we have the quantity x minus 1 to the fourth power minus 1, and we're told that x is greater than or equal to 1. So again, without this restriction, this would not be 1 to 1. So that's why we need this here. So we're saying the domain is x is greater than or equal to 1. And of course, you could write the range. You don't need it. But if you look at that right there, that point is going to be at 1, negative 1. So the range is y is greater than or equal to negative 1, in case you want it. And that's coming from plugging in a 1 here. 1 minus 1 would be 0. 0 to the fourth power is 0. So you get negative 1 there. So that's why you're getting negative 1 or anything larger. So let's keep this one in mind as we're solving. So we're going to say f of x is equal to, we have our quantity x minus 1 to the fourth power, and then minus 1, where x is greater than or equal to positive 1. All right, so I'm just going to say that we have y is equal to the quantity x minus 1 to the fourth power minus 1. And again, we'll say x is greater than or equal to 1. I'm going to swap x and y. So let's say that we have x is equal to the quantity y minus 1 to the fourth power minus 1. And here, we'll say y is greater than or equal to 1. Let's slide down a little bit. I'm going to add 1 to both sides of the equation, so that would cancel. You're going to get the quantity y minus 1 to the fourth power is equal to x plus 1. Let me copy this down so we don't forget. So y is greater than or equal to 1. Again, if I want to solve for y, I'm going to take the fourth root of each side. So I'm going to say that y minus 1 is equal to, again, over here, I'm going to go plus or minus the fourth root of x plus 1. Okay, so again, we got to think about what's going on here. Let me add 1 to both sides like this, and I'll just erase this. Do I need the plus or minus here? No, because y is greater than or equal to 1. Let's think about this for a moment. If this was positive, fourth root of x plus 1, again, I know that this part right here, forget about the plus or minus for right now, I know that this right here is going to be something that's either 0 or positive. So if it's 0 and I add 1, I get 1. If it's positive, I'm going to get something that's greater than 1. So here, y is greater than or equal to 1, so I want to get rid of the negative. I just want the principal fourth root of this x plus 1. So this right here. So this would be your inverse. So f inverse of x is equal to, again, the fourth root of x plus 1, and then plus 1. Okay, again, if you want to look at the graph, you can see you have f of x equals the quantity x minus 1 to the fourth power minus 1, where x is greater than or equal to 1. So this guy right here. Then you have your line y equals x, and then you have your f inverse of x. That's your fourth root of x plus 1, and then plus 1. So that's this guy right here. Again, just looking at points on those two graphs, you can see there are reflections across the line y equals x. So these are inverses. All right, let's take a look at problem 9. So here we have f of x is equal to x squared plus 3 over 3x squared, and we're told that x is greater than 0. So again, we need this here because this part right here is not a one-to-one function. So we have to restrict the domain to create a one-to-one function so that we can get our inverse. So once again, if you want to go to Desmos and sketch the graph and see what this would look like, of course, now we're going to pass the horizontal line test because we're just saying that we want the x values that are greater than 0. So we want this right here. Now, let me write out again that x is greater than 0. So that's what we actually need to derive the inverse because our y values in the inverse will be greater than 0. We'll need to know that. If you want to look at the range of this guy, it's not really needed. But in case you were curious, you're going to get y is greater than 1/3. Now, how do I know that without that being really labeled on a graph? If you look at this, you're like, well, where is 1/3 coming from? How do I get that? Well, essentially, earlier in the course, we talked about finding horizontal asymptotes. And essentially, if you have something like x squared plus 3 in the numerator and 3x squared in the denominator, notice that the degree of the numerator is 2, and the degree of the denominator is also 2. So that tells me that because I have the same degree, I'm going to have a horizontal asymptote. And you're going to take this coefficient here, which is a 1, and put it over this coefficient here, which is a 3. So the horizontal asymptote, let me put h period a period for that, is going to occur at y is equal to 1/3. So we talked about that earlier in the course. You can review that section if you need to. But basically, as x values get larger and larger, the y values are going to approach 1/3, but they'll never actually touch it. So for the range, you would say y is greater than 1/3. Okay, let's come down here and write our problem. So f of x is equal to x squared plus 3 over 3x squared. And we're going to say x is strictly greater than 0. So the first step here is to replace f of x with y. So now y is equal to x squared plus 3 over 3x squared, where x is greater than 0. So now we want to swap x and y. So this is what causes some confusion in this problem. You have an x here and an x here. You have to change both of those. So basically, you're going to say that you have x is equal to this will be y squared plus 3 over 3y squared. So make sure you change both of those. And now because we swapped the x's and the y's, the domain becomes the range. So we're going to say now that y is greater than 0. And if you wanted to, you could write that x will be greater than 1/3. That's coming from the range where we said y was greater than 1/3. So now here, when we get to the inverse, x will be greater than 1/3. But again, you don't need to list that. You'll see it on the graph. If you want to solve for y, and you have a y here and a y here, my strategy would be to move everything to one side, and then you're going to factor, and then you could solve it that way. So what we're going to do is multiply both sides by 3y squared. So let's do that over here as well. And of course, this is going to cancel with this. And so on the left, I'm going to have 3y squared x. Maybe that could be better. And this equals, now you have y squared plus 3. All right, so let me copy that we want y is greater than 0 so we don't forget. And then at this point, I want to get this over here. So I'm going to subtract y squared away from each side. So this would cancel. I'm going to have 3y squared and then x minus y squared is equal to 3. And let me just keep copying this. So y is greater than 0. Let me come down here. And at this point, notice that you have y squared and y squared. So you can factor that out. So I'm going to say that I have y squared times the quantity. If this gets pulled out, you have 3x. And then minus, if this gets pulled out, you have 1. So then this equals 3. And again, I'm just going to say that y is greater than 0, so we don't forget. Let's come down here. And now, if I want to solve for y, well, the first thing I'm going to do is solve for y squared. So let me divide both sides of the equation by this quantity 3x minus 1. So let me divide over here by this 3x minus 1. And of course, this is going to cancel with this. And what we have at this point is y squared is equal to 3 over this 3x minus 1. And again, I'm going to say that y is greater than 0. And let me paste this in here so I have some room. The idea now is that you want to solve for y. Again, because this is y squared here, if you did something like take the square root of each side so you can get y by itself, you would normally say that y is equal to plus or minus the square root of 3 over 3x minus 1. But we're specifically saying here that we want y to be greater than 0. When I think about this guy right here, it's actually not going to be 0 because of the way it's set up, your radicand there, but you can make it anything that's greater than 0. So it can't be 0 itself, but something greater than 0. So this is going to be positive. Now you have this plus or minus out in front. Do I need that? No, because y is greater than 0. So just get rid of this. You just want the principal square root here, and this would give you y values that are greater than 0. Notice that you can't actually get a y value of 0. If you think about this, for y to be 0, this radicand would have to be 0, and that's never going to happen. For a fraction to be equal to 0, the numerator needs to be 0, and the denominator needs to not be 0. The numerator is a 3. That's never going to be 0, so you can't get a 0 out of this guy. So basically, this would always be positive or greater than 0, so this is what we want. So let's go ahead and write this in a more clean way. Let me first use my inverse notation. So f inverse of x is equal to, first I'm going to split this up and say this is the square root of 3 over the square root of 3x minus 1. If you want to follow the rules of simplifying, again, you don't want a radical in the denominator. If you put your answer like this in your self-studying, I guess that's fine. It's not that big of a deal. But if you turn this answer in on a test, your teacher will probably remove points or at least leave some sort of remark like, hey, you should have rationalized the denominator. So let's go ahead and do that here. We're going to multiply by the square root of 3x minus 1 over the square root of 3x minus 1. And let me slide down here. So the easiest way to write this, I'm just going to say this is f inverse of x is equal to, let's write the square root of 3 times the quantity. That 3 could be a lot better there. And then this would be 3x minus 1. Let me fix both of these. So that's a 3 and that's a 3. And then this would be over square root of 3x minus 1 times the square root of 3x minus 1 would just give me that 3x minus 1. So this would be your inverse, again, after you clean it up. Okay, let's come down here and look at the graph. You can visually confirm that these two are reflections across the line y equals x. It's a little bit tricky to get points going, but you can get them. Again, if you go on Desmos and just mouse over things, you'll be able to see that a point that's on the original function is going to be reversed, meaning the x and the y values are swapped on the inverse. So I'll let you do that on your own. Here we have our f of x equals x squared plus 3 over 3x squared, again, where x is greater than 0. That's going to be this guy right here. So it's in this I guess you would say it's a sort of a red color. I don't know the actual color. I'm just going to say it's red. I know a lot of people say that's sort of pinkish or maybe maroon or something like that. But let's just say it's red to keep it simple. Then this guy in yellow, that's your inverse. So this is your f inverse of x is equal to the square root of 3 times the quantity 3x minus 1 over 3x minus 1. And again, there's different ways to write that, but that's how I'm going to choose to write it in a simplified form. So we can see these guys would be reflections across the line y equals x. So they are inverses. All right, let's take a look at problem 10. So here we have f of x equals 2x squared plus 1 over negative x squared, and we're told that x is less than 0. So again, we had to restrict this to make it 1 to 1, and so the domain will say that x is strictly less than 0. In case you're curious about the range, we're going to say y is less than negative 2. Again, you can look at the graph and see that. I guess it's a little bit tricky here to see because of the graph and the way it's drawn, but if you go to Desmos, you can zoom in and see that. Another way is you could think about what we learned earlier in the course when we talked about horizontal asymptotes. So you see that this numerator and this denominator, they have the same degree. So this is of degree 2, and so is this. So when that happens, basically you're going to look at this guy right here. So that 2 is the coefficient of this x squared. And here, this coefficient would be negative 1. So basically you have a horizontal asymptote at 2 over negative 1, which is negative 2, so y equals negative 2. So that's where that's coming from. So this would approach a y value of negative 2, but it would never ever touch it. So for the range, you could just say that y is less than negative 2. Okay, we're not going to use this one. We'll use the x is less than 0. So let's go down, and we're going to work with f of x is equal to, again, 2x squared plus 1 over negative x squared. And let's write specifically that x is less than 0. Okay, let's write y is equal to 2x squared plus 1 over negative x squared. And again, x is less than 0. So at this point, we're going to swap x and y. So we're going to say x is equal to 2y squared plus 1 over negative y squared. And then let's put the x's and the y's were swapped. So now this would be y is less than 0. Okay, so how are we going to solve for y? Again, one strategy would be to multiply both sides by, let's go negative y squared. So that would give me, let me actually slide this down so I can show this. I don't want anybody to be lost. Let me move this over here. So times negative y squared, and then times negative y squared. So of course, we'll say that this is going to cancel with this, and you have negative y squared x, and then this equals 2y squared plus 1. And let's just copy this. So comma, y is less than 0. And then at this point, let's subtract 2y squared away from each side of the equation. This cancels. We're going to have negative y squared x minus 2y squared, and this equals 1. Let me just copy this. So y is less than 0. I'm down here. And of course, now we're going to factor out the y squared. So y squared comes outside of the parentheses. Inside, you're going to have negative x and then minus 2. And then this equals 1. Let's divide both sides by this quantity negative x minus 2. Let's do that over here. I'm just going to slide that over here like that. So I'm dividing by negative x minus 2. And let me just copy that y is less than 0. So we have it. Let me bring this down here. Ran out of room. So this right here is going to cancel. And what we're going to have is y squared is equal to, you have 1 over negative x minus 2. Again, we want to keep in mind that y is less than 0. So again, normally, when you have something like y squared equals 1 over negative x minus 2, you're going to say that you take the square root of each side, and you go y is equal to plus or minus the square root of 1 over negative x minus 2. But again, because we're saying that y is less than 0, we want the negative of the square root here so that we get the y values that are less than 0. So what I would do at this point is just rationalize the denominator. Let me write this as f inverse of x is equal to the negative of, let's go the square root of 1 over the square root of negative x minus 2. So I'm going to multiply this by the square root of negative x minus 2 over the square root of negative x minus 2. So, of course, the square root of 1 is 1, and 1 times anything is itself. So let me slide down here and just say that our f inverse of x is equal to, this would be the negative of the square root of negative x minus 2 over this times this will give me negative x minus 2. So this is how I'm going to write it. This will be our inverse. So f inverse of x is equal to the negative of the square root of negative x minus 2 over negative x minus 2. Now, maybe it's a little bit better if you clean this up. So let me move this negative down here. I'm going to clean this up and write this as -1 and distribute this to each guy. So this would end up being a positive x and then plus 2 down here. So this is another way to write it. If you want to write it the other way, it's fine. So let me say the answer is going to be f inverse of x is equal to the square root of -x minus 2 over x plus 2. All right, again, I sketched the graph. This one's a little bit tricky because it's hard to see on the graph that I'm giving you. So you can just go to Desmos and make your own graphs. Not a big deal. So y equals x, again, we have that line. If you look at this guy down here, this is our original function we were working with. So f of x equals this 2x squared plus 1 over -x squared, where x is less than 0. So that's this guy right here. Again, I'm just going to call this red. I know it's more of like maybe a maroon or some other color that I don't know the name of, but I'm going to call it red. Then this guy in yellow, this is going to be your inverse. So f inverse of x is equal to the square root of -x minus 2 over x plus 2. Lots of different ways you could have written that, but that's going to be this guy right here. So again, you can see there reflections across the line y equals x, and they are going to be inverses. All right, let's take a look at the practice test. For the instructions, we're asked to find the transformation from f of x to g of x. All right, let's take a look at the first problem. Here we have f of x is equal to 2 to the power of x. Then we're given g of x is equal to -2 raised to the power of x, and then minus 5. So we want to describe the transformation from f of x to g of x. So a lot of times what I'll do is I'll write my g of x in terms of f of x, so it makes it crystal clear what's going on. The first thing you would notice is you have this negative here out in front of 2 to the power of x. So your f of x is 2 to the power of x. So if I put a negative out in front of that, I could really write that as the negative of f of x. In other words, I could say that g of x is equal to the negative of f of x. Let's talk about this right here. This is minus 5, so I'm just going to put this on the end, so minus 5. Okay, so looking at it in this form, remember, if you have the negative of f of x, that is creating a reflection across the x-axis. So for a given x value, so you plug something in, now the y value you get is going to be the opposite of what it would have been before because of that negative. So that's creating a reflection across the x-axis. Then you have this minus 5 here. That's going to create a vertical shift down by 5 units. Let me slide down here and let me just write this out. So this right here, let's say we get a reflection. And we'll go across the x-axis. Let me make that a little bit better there. And so let me circle this so that's crystal clear. And then this part right here, this minus 5, this is going to create a shift down by 5 units. So let me arrow to that down here. So this creates a shift down by 5 units. So if you wanted to answer this, you would say a reflection across the x-axis, and then you could do a shift down by 5 units. Now I went ahead and set up a graph for us to look at. It's hard to see all this stuff on such a small screen, especially if you're on a phone or something like that. So what I would recommend is doing this on Desmos with me, so it's easier to follow along. So the first thing is I've sketched the original function f of x equals 2 to the power of x. So this is going to be this guy, and let's just call it red. I know it's probably closer to maroon or something, but let's just call it red. So you have the points 0, 1, 1, 2, 2, 4, 3, 8. So we know those points already. Then what I did was I graphed the negative of f of x. So that would be negative of 2 to the power of x. That creates a reflection across the x-axis. So you can see that these points, again, have been reflected across the x-axis. So the x values are the same, but now the y values are their opposites or negatives. So instead of 0, 1, you have 0, -1. Instead of 1, 2, you have 1, -2. Instead of 2, 4, you have 2, -4. And then instead of 3, 8, you have 3, -8. So everything has been reflected across the x-axis. So the y values are changing it to their opposites. The x values are staying the same. After we've done that, we have this shift down by 5 units. So you can take these points here and then just subtract 5 away from the y values. So here you have 0, -1, you shift down by 5 units, you get 0, -6. Then you have 1, -2, you shift down by 5 units, you get 1, -7. You have 2, -4, you shift down by 5 units, you get 2, -9. And then you have 3, -8, you shift down by 5 units, and you get 3, -13. So again, I would just check this out on Desmos. It's definitely going to give you a visual representation of what's going on. All right, let's take a look at problem 2. So here we have f of x is equal to, we have 1/2 raised to the power of x. Now if we slide down a little bit, we have g of x is equal to 1/2, now raised to the power of -x, and then plus 2. So to make this crystal clear, again, what I'm going to do is write my g of x in terms of f of x. So let's say that g of x is equal to, well here, if I plugged in a negative x for x, well, I'd have this 1/2 to the power of negative x. So this is f of negative x, and then we just have our plus 2. Now let's think about what this does. It's pretty straightforward. When you look at this negative x right here, so basically that's creating a reflection across the y-axis now. So for a given y value, it's getting produced from the opposite x value, or you could say the negative of the x value versus the graph you were looking at before. So this right here, let me just put, is going to give you a reflection, and we'll say across the y-axis. Now the next thing here, we have this plus 2. So when we think about the plus 2, again, what is that doing? That's going to give me a shift up by 2 units. So let's just put that we're going to shift up by 2 units. Okay, so again, if you want to look at this graphically with me, you can go to Desmos. It'll be a little bit easier to see what's going on. But your original function, again, is going to be in this red color. So you have your f of x equals 1/2 to the power of x. I think we all know this function at this point. So you have a point like -3, 8. You have -2, 4. And then you have -1, 2. You have 0, 1. And then you have stuff down here, but it's a little bit tough to put that in because you have non-integer values. So you can mouse over those things on Desmos if you want. So you have your f of negative x equals 1/2 to the power of negative x. So in other words, just taking this right here and plugging in a negative x there, so that would give me a negative x there. So what that does is create a reflection across the y-axis. So this point right here, this -1, 2, well, the y value is the same. So it's still a 2, but the x value is coming from the opposite. So instead of it being -1, it's now +1. This is -2, 4, and this over here is 2, 4. This is -3, 8, and this is 3, 8. So that's my reflection across the y-axis. Now the graph we want to end up with, this guy's going to be in, I guess you call it green or teal or whatever it is. Let's say it's g of x equals 1/2 to the power of negative x. So that's this part right here, and then plus 2. So from this orange graph, we're just going to move everything up by 2 units. So this 0, 1, you just go up by 2 units. So the x value is still the same. It's 0, 3 now. And this 1, 2 becomes 1, 4. Again, just going up by 2 units. This 2, 4 becomes 2, 6. And this 3, 8 becomes 3, 10. All right, let's take a look at problem 3. So here we have f of x equals 3 to the power of x. And then we're going to have g of x equals -1/2 times 3 to the power of x, and then minus 2. So again, what I'm going to do is write my g of x in terms of f of x. It just makes it easier. So let me write g of x is equal to, well, you have this -1/2 that's multiplying 3 to the power of x. So 3 to the power of x, again, is f of x. So let's write -1/2 times your f of x. And then this part's very straightforward. You just go minus 2. Let me make that better there. All right, so looking at what we have now, if we think about this part right here, you have 2 things that are going on. You have the negative, and then you have the 1/2. So let's think about the 1/2 first. If I multiply 1/2 by my f of x, what's happening is I'm creating a vertical compression by a factor of 2. So the y values now that I would have gotten get divided by 2. So something like maybe a y value of 1 will become a y value of 0.5 or 1/2. So let's go ahead and write that for this part right here. Let me do this separately. For this part right here, we're going to have a vertical compression by a factor of 2. And that's coming from this 2 right here. Now, when we think about the negative, let me do that in a different color. I'll maybe use black for that. This guy right here, we know that if we have the negative of f of x, what does that do? It creates a reflection across the x-axis. So let's move this down here and just say that we're going to have a reflection across the x-axis. And then this one right here, let me change my color up again. This minus 2, that's just going to shift me down by 2 units. Let me put this over here and just say that finally we're going to shift down by 2 units. All right, so once again, you can look at this on Desmos. It makes it really easy to see what's going on. So I have this graph in, let's just call it red. Again, I know it's closer to maroon, but we have f of x equals 3 to the power of x. So we have some points that we should know at this point. We have 0, 1, 1, 3, and 2, 9. So I went ahead and broke this up into 2 steps. So the first thing I'm going to do, you have this guy in orange. It's going to be -1/2 times your f of x. So -1/2 times this. So you end up with -1/2 times 3 to the power of x. So what does that create? This graph right here. It's a little bit hard to follow because I have different points all over the place. So again, following me on Desmos will make this a little bit easier. But basically, when you multiply -1/2 by this f of x, what's happening is you're vertically compressing this by a factor of 2. So this x value would be the same. It would still be 0. The y value would get cut in half. So in other words, 1 divided by 2 would be 1/2 or 0.5. So let's just say that gives you a point right there. And let me just arrow to that real quick and just say that that would be 0, let's go 0.5. So then what happens is you have that negative that kicks in, and that reflects it across the x-axis. And so that basically brings this down here. So you get this point, which is 0, -0.5. So let me erase this. This is not anywhere on the graph that we drew. And so if you keep going through these points, you'll get the same thing. So this is 1, 3. Again, if you cut 3 in half, you get 1.5. And then if you reflect that across the x-axis, you're going to get this point right here, which is 1, -1.5. And then this 2, 9, if you cut 9 in half, you get 4.5. And then again, if you reflect that across the x-axis, you're going to end up with this point right here, which is going to be 2, -4.5. So that's your guy right there in orange. Now, the final step, once you've done that, we have this g of x here. This is going to be in teal. And we have this equal to -1/2 times 3 to the power of x. So that's this right here, and then -2. So based on this graph in orange, all we have to do is shift everything down by 2 units. So the x value is going to be the same. The y value is just going to decrease by 2 units. So this right here is going to be 0, -0.5. So I go down by 2 units. I get 0, -2.5. This right here is 1, -1.5. I go down by 2 units. I get 1, -3.5. And then this right here is 2, -4.5. I go down by 2 units. I get 2, -6.5. All right, so for problem 4, now we have f of x is equal to 4 to the power of x, and g of x is equal to 3 times 4 to the power of x minus 1, and then plus 2. Okay, so once again, let's write g of x in terms of f of x. So let's say that g of x is equal to, well, you have this 3 that's multiplying this guy right here. So let's start with that. So we have 3, and then times your f of, and I'm not going to put x in there yet, because you'll notice that you have this right here, this x minus 1. So basically, in the place of x, I want x minus 1. So I'm going to put x minus 1 in there. And then you have plus 2. Okay, so this right here, if you look at the 3, that's going to create a vertical stretch by a factor of 3. Let me go ahead and come down here and just write that. So this one right here, let me box this off so this is clear. This is a vertical stretch by a factor of 3. Then when you look at this right here, this minus 1, again, that's inside the function. So it's always the opposite of what you think. So this minus 1 here is actually going to give me a shift to the right by 1 unit. Let me change colors for this actually. And I'll just do the whole thing here. So this x minus 1, this is going to give me a shift right by 1 unit. And then this right here, this plus 2, actually, let me change colors again. So let me use this color now. So this plus 2 here is going to shift me up by 2 units. So let me bring this over here and just say this is going to be a shift up by 2 units. So again, let's look at the graph. This one's very crowded. So again, you can just go to Desmos. So the graph in red, that's my original function, f of x equals 4 to the power of x. You can see this one takes off pretty quickly. So I'm using some points here. I have 0, 1. I have 0.5 or 1/2, 2. I have 1, 4, and then I'm going to have 1.5, 8. Okay, so for the other ones, let's just say we go with this guy in orange. This is 3 times f of x. So this is your vertical stretch by a factor of 3. So looking at this point 0, 1, again, the x value stays the same, still going to be 0. You're just multiplying the y value by 3. So now you have 0, 3. And then you can take something like 0.5, 2. Again, we're just going to come up here and say this is 0.5, 6, just multiplying 2 by 3. And then something like, let's say 1, 4, again, coming up here. So now this would be 1, 12. The next thing is we have the g of x in green or teal. We'll say this is 3 times 4 to the power of x minus 1 and then plus 2. So we're going to do 2 things here. We're going to have a shift to the right by 1 unit, and then we're going to go and shift up by 2 units. So 1 unit to the right and 2 units up. So just starting from here. So if I go 1 unit to the right, that's going to be right here. And then 2 units up, that's going to put me right here. So in other words, that's the point there, 1, 5. So 0 plus 1 is 1. That's how I'm getting that. And 3 plus 2 is 5. So that's how I'm getting that. So 1 unit to the right, 2 units up. Then from this point right here, again, 1 unit to the right. So I'm going to go to 1.5. So that's going to be right there. And then 2 units up, that's going to be right there. So in other words, 0.5 plus 1 is 1.5, and 6 plus 2 is going to give me 8. Then from this point right here, I'm going to go 1 unit to the right. So right now it's at 1, so I'm going to go to 2. And then I'm going to go 2 units up, so that's going to be right there. So this is 2, 14. So 1 plus 1 is 2, and then 12 plus 2 is 14. All right, let's take a look at problem 5 now. So we have f of x is equal to 2 to the power of a negative x, and then minus 1. Okay, so for this one, realize that 2 to the power of negative x can be written as 1/2 to the power of x. So you could really write this as f of x is equal to 1/2 to the power of x and then minus 1. So if you know how to graph f of x equals 1/2 to the power of x, well then you could sketch that graph and just shift it down by 1 unit. So you could do it that way. What I'm going to do is actually just use the table approach. Let me copy this real quick. I'm going to go f of x is equal to 2 to the power of negative x. It's actually easier to get points like this, and then minus 1. So let me just grab this real quick and come down here. I've already pre-sketched this. And so I'm just going to take some points here. Again, just pick something for x and then y, make a few points and then sketch a smooth curve. Alternatively, again, you can do the graphing of, let's say f of x equals 1/2 to the power of x, and then just shift that down by 1 unit and you get the same graph. So to pick some points, let's just start with this -3 for x. So you'd have f of -3. This is equal to 2 to the power of, now you have a negative out in front, so be careful. The negative of -3, and let me make this 3 a little bit better here, and then we have minus 1. So this is equal to, the negative of -3 is positive 3, so this would be 2 cubed, and then minus 1. 2 cubed is 8. 8 minus 1 is 7, so this would be equal to 7. So let's put a 7 right there. So you can see we already have this. So 3 units to the left and 7 units up. That's going to be right there. Let me arrow to that and say that that point is -3, 7. Now the next one, we could do -2. So let's plug in -2 here, and we'll do f of -2. So this equals 2 to the power of, again, you have the negative of -2, and then minus 1. So the negative of -2 is 2. So this would be equal to 2 squared, which we know is 4, and then minus 1. So 4 minus 1 would be 3. So what we'll do here is go 2 units to the left and 3 units up. So that's this point right here. This would be -2, 3. So let me put that in there. And then let me get rid of this. And let's just get the next point. So let's go with -1 now. So f of -1 would be equal to 2 to the power of, again, the negative of -1, and then minus 1. So the negative of -1 is 1. So this is just 2. And then minus 1, which is 1. So that's going to be a 1 there. So that's going to be this point right here. Let me arrow to it like that. So that point is going to be -1 and then comma +1. So 1 unit to the left and 1 unit up. That's that point right there. Okay, so additional points. Let me get rid of this. Let's say we go with 0. Well, that one's really easy. So the negative of 0 is 0. 2 to the power of 0 is 1, and 1 minus 1 is 0. So this is 0. So that's this point right here, which is 0, 0. And then the last point we're going to do, let's say we go with +1. So we'll say f of 1 is equal to, we know 2 to the power of -1 would be 1/2, and then minus 1. So this would be equal to -1/2 or -0.5. Let's write -0.5. If you like -1/2, that's fine. It's the same thing. So right here, this point would be 1, -0.5. So once you have that, you have enough. Again, you know that this guy has been shifted down by 1 unit versus the graph of something like f of x is equal to, let's say, 1/2 to the power of x. We know that this right here has a horizontal asymptote at the x-axis. So as the x values approach positive infinity, the y values are going to approach 0. So we're going to approach the x-axis. This guy's been shifted down by 1 unit. So what you can see is that basically this guy is going to approach a y value of -1 because of the shift down by 1 unit, but it's never going to get there. So this is as x goes to positive infinity. So using all this information, you can sketch your graph just as a smooth curve through these points, and just keeping in mind your horizontal asymptote that's going to occur at y equals -1. All right, let's take a look at the practice test. For the instructions, we're asked to solve each equation. Now, before we get started on the problems, we're going to be solving exponential equations with like bases. So that means that we will not require logarithms to solve these equations. We're going to get to those problems later on. For right now, I want to remind you of the rule that we're going to use today. We talked about it in the lesson. So basically, for, let's say, a is greater than 0. So this just means that a is some positive real number. So it's something greater than 0, but we have an additional restriction. We're going to use the keyword and we're going to say that a is not equal to 1. So some positive real number, provided it's not 1. We're going to say if we get something like a to the power of x is equal to a to the power of y. So basically you have the same base here. Well, what we can say is that then this x here is equal to this y here. So essentially what we're going to do today is write everything with a common base. And then once we've done that, we're going to set the exponents equal to each other, and we're going to solve the resulting equation. All right, let's take a look at the first problem. So here we have 16 to the power of 2x plus 1 times 64 is equal to 64. Now there's different paths you can take to solve this problem. The easiest method that I can think of is to start by dividing both sides by 64. So I'm going to divide this side by 64 and divide this side by 64. So again, this is multiplication here. So I'm going to cancel a common factor of 64 between the numerator and denominator. So that's just a 1. And then 64 divided by 64 is 1. Let me slide down here. And now what we have is 16 to the power of 2x plus 1 is equal to 1. Now the idea here is that you have to have a common base. Now you could write 16 as 2 to the 4th power, but that's completely unnecessary. What you're going to do is use a trick from the rules of exponents. We know that if we had something like 16 to the power of 0, this is by definition equal to 1, right? Because this is 16 over 16, which is 1. So basically, I can rewrite 1 as 16 to the power of 0. So I'm going to say this is 16 to the power of 2x plus 1 is equal to 16 to the power of 0. So anytime you have 1 in an equation like this, just think about how you can use that rule there, where basically raising a non-zero number to the power of 0 gives you 1. Okay, so now we have the same base. We have 16 and we have 16. So all you have to do is take these exponents, so this guy right here and this guy right here, you're going to set them equal and you're going to solve the resulting equation. So you're going to say that 2x plus 1 is equal to 0. Subtract 1 away from each side of the equation. This cancels. Let me slide down. You get 2x is equal to negative 1. Divide both sides by 2. This cancels. And you get x equals negative 1/2. Now let me erase everything and let me write the solution here. So x equals negative 1/2. Remember, if you're unsure about if you got the right answer, you can always check. You're going to plug in for x right there and see what we get. So 16 raised to the power of 2 times negative 1/2 plus 1, and then times 64, is that equal to 64? We know that 2 times negative 1/2 is going to give me negative 1. You can think about it as these 2's canceling, and I'm left with negative 1. So negative 1 plus 1 would be 0. So this becomes 16 to the power of 0, and then times 64 is equal to 64. So essentially 16 to the power of 0 is 1. So we have 1 times 64 is equal to 64, which turns into 64 equals 64, which is a true statement. So our solution x equals negative 1/2 is correct. All right, let's take a look at problem number 2. So what we have here is 1 over 216. This is raised to the power of negative 2x. Then times 216 raised to the power of negative 3x. And this is equal to 36 raised to the power of x minus 1. So for this one, I'm looking at this 216 here in the denominator, this 216 here, and then this 36 here. And I'm thinking about how can I get a common base? So 216 is 6 cubed, and then 36 is 6 squared. So at the end of the day, if I want a to the power of x equals a to the power of y, so that I can set my exponents equal to each other, well, in this case, I'm going to be working with 6 as my a. So that's going to be my common base. So I'm just going to rewrite things. I'm going to start with this one. So let's go 1 over 6 cubed, and then I'm going to wrap this and say this is raised to the power of negative 2x. Then times, again, for 216, that's 6 cubed. I'm going to wrap this and say this is raised to the power of negative 3x. And this equals, for 36, that's 6 squared. Just going to wrap this and say it's raised to the power of x minus 1. Okay, sliding down now. There's lots of ways you can go about simplifying things here. What I'm going to choose to do is drag this across the fraction bar. Remember, that just means I'm going to change the sign of my exponent. Remember, we have a rule. If you have something like 1 over, let's just say a squared like this is equal to, you can drag this across the fraction bar. So I'm going to put a here, but I've got to change the sign of my exponent. So now this is to the power of negative 2. So I'm just going to use that rule here. I'm going to say that this is 6 to the power of negative 3. Let me make that 3 a little bit better. And then wrap that and say this is raised to the power of negative 2x. Again, all I'm doing is dragging this into the numerator and changing the sign of that exponent from positive 3 to negative 3, just following that rule. Then times, here we have our 6 cubed raised to the power of negative 3x. And this equals our 6 squared raised to the power of x minus 1. All right, at this point, we're going to use our power to power rule. So hopefully you remember how that works. If we have something like, let's say, x to the power of a, and this is raised to the power of b, again, x stays the same, and then we're going to multiply our exponent. So a times b is just ab. So here, if you look at what you have, the 6 to the power of negative 3 is then raised to the power of negative 2x. So 6 stays the same, and you're going to multiply exponents. So negative 3 times negative 2x, negative times negative is positive, 3 times 2x is 6x. So this is 6 to the power of 6x. Then times, here, 6 would stay the same, multiply the exponents. 3 times negative 3x is negative 9x. So 6 to the power of negative 9x, and this equals, here, 6 stays the same, multiply exponents. Now you have to be careful because 2 is multiplying by the quantity x minus 1. So 2 times the quantity x minus 1, use parentheses there, and then you've got to distribute that 2 to each guy inside the parentheses. So this would be 2x minus 2. Let me erase this and just put this is 6 to the power of 2x minus 2. Okay, at this point, to simplify this side on the left, you're going to use your product rule for exponents. So let me just show you that. So x to the power of a times x to the power of b. So we keep the base the same, and we add the exponents. So this is x to the power of a plus b. Let me get rid of this and just do this. So we would say 6 stays the same, and we're just going to add these exponents. So it's 6x plus negative 9x, or 6x minus 9x. And this equals, you'd have 6 to the power of 2x minus 2. So let me slide down here a little bit. Now I would simplify this. So 6x minus 9x is negative 3x. So we get 6 to the power of negative 3x is equal to 6 to the power of 2x minus 2. At this point, we can set our exponents equal to each other. We have 6 here and 6 here, so we have that common base. So to solve the equation, we're just going to say that negative 3x is equal to 2x minus 2. I'm going to subtract 2x away from each side of the equation. So this right here is going to cancel. Let me bring this to another page so we don't run out of room. Negative 3x minus 2x is going to be negative 5x, and this equals negative 2. To finish things up, I'm going to divide both sides of the equation by negative 5. And so let's say that this is going to cancel with this. So let's say x is equal to, negative over negative is positive, so this is 2/5. Now again, if you want to check this, I've already checked it, I know this is the correct solution. You can go back to the original equation and plug in a 2/5 for every occurrence of x, and you're just going to make sure the left and the right sides are equal. So I'm just going to omit the check here to save a little bit of time. All right, let's take a look at problem 3. So here we have 9 times 81 raised to the power of 1 minus 3x, and this equals 81 raised to the power of negative 2x. So with this one, we're dealing with 9, we're dealing with 81, and 81. Again, I want a to the power of x equals a to the power of y. So I need a common base. Now for 81, you're thinking about, okay, that's 9 times 9, and 9 is obviously 9. Now, you could also think about this in terms of 3. So 9 is 3 squared, and 81 is 3 to the 4th power. You could use 3 as the common base, or you could use 9. Whatever you want to do, you will get the same answer either way. I'm just going to use 9 because I think it's going to be a little bit easier. So let's just keep 9 the same there, and then times. For 81, again, that's 9 squared. So this is 9 squared, and then this guy would be raised to the power of 1 minus 3x, and this equals, for 81, again, that's 9 squared, and this is raised to the power of negative 2x. Okay, at this point, for this one, I would use my power to power rule. Let me copy this. So 9 times, 9 stays the same, multiply your exponents. So this would be 2 times the quantity, 1 minus 3x. So we got to distribute this here. So 2 times 1 is 2, and then 2 times negative 3x is negative 6x. So this is 9 to the power of 2 minus 6x. So let me write this 2 minus 6x here, and this equals, again, power to power rule, 9 stays the same. 2 is multiplied by negative 2x. That's negative 4x. On the left, we're going to use the product rule for exponents now. So 9 would stay the same. And then we're just going to add our exponents. Now this one, you have to realize that there's an implied exponent of 1 here. So I'm just going to write that in. So this becomes 9 to the power of 1 plus this guy right here. So 2 minus 6x. 1 plus 2 is 3. So let's just write this as 9 to the power of negative 6x and then plus 3. Okay, let me erase that and make that a little bit better. And this equals 9 to the power of negative 4x. Okay, at this point, we have a common base. So we have 9 here and 9 here. So I'm just going to say that I'm going to set my exponents equal to each other and just solve the resulting equation. So negative 6x plus 3 is equal to negative 4x. Let's add 4x to both sides of the equation. So that would cancel. And let me subtract 3 away from each side of the equation. So that would cancel. Negative 6x plus 4x is negative 2x. And this equals negative 3. To finish things up, let me divide both sides of the equation by negative 2. Let me tighten that down just a little bit, like that. And then let me show this is canceling with this. And so what we're going to have is that x is equal to negative over negative is positive. So this is going to be 3 halves. All right, let's move on and look at problem 4. Here we have 4 raised to the power of negative x minus 2 times 4 equals 8. So what I would do here is use a base of 2. Remember, 4 is 2 squared and 8 is 2 cubed. So for 4, I'm just going to write this as 2 squared. And then this is raised to the power of negative x minus 2. And then times, for 4, I'm going to write that as 2 squared. And this equals, for 8, I'm going to write that as 2 cubed. Now here I'm going to use my power to power rule. So 2 squared raised to the power of negative x minus 2. This is 2 raised to the power of, you'd multiply the exponents. So 2 times the quantity, negative x minus 2. You need to distribute this to each guy inside of the parentheses. So that would be 2 to the power of negative 2x minus 4. So this right here would be negative 2x minus 4. Then times, you have 2 squared, and this equals 2 cubed. At this point, you want to use your product rule for exponents. So 2 would stay the same, and then you would add your exponents. So negative 2x minus 4, then plus 2. So that becomes negative 2x minus 2. So this right here would be minus 2. That's coming from negative 4 plus 2. That's your negative 2. Then this equals, we have 2 cubed. So at this point, we're basically ready to go. We have a 2 here and a 2 here, so a common base. So you're just going to set your exponents equal. We're going to say this is negative 2x minus 2 is equal to 3. And then at this point, I'm going to add 2 to both sides of the equation. This cancels. And we're going to say that we have negative 2x is equal to 3 plus 2 is going to be 5. Divide both sides of the equation by negative 2. Let me move this in a little bit closer and say this is going to cancel with this. And so x is equal to, you're going to have 5 over negative 2. So that's negative 5 halves, or you could write negative 2.5 if you want to use a decimal answer. All right, for problem 5, we have 243 raised to the power of 2x times 81 raised to the power of x is equal to 243. Now, there's different strategies based on the problem you're given. What I think is the fastest method here is to divide both sides of the equation by 243 raised to the power of 2x. I'm going to divide over here as well. And so we know that this over this would be 1. So what I'm left with is 81 to the power of x on the left. This equals, on the right, you want to use your quotient rule for exponents. Let me put this as a 1 here. So you have that common base that's going to stay the same. So this is 243. And then you're going to subtract the exponent in the numerator. So that's 1 minus the exponent in the denominator. So that is 2x. At this point, you've got to think about a common base. So if we think about 81, this is 9 times 9, and then 9 is 3 times 3. So what we have here is 3 times 3 times 3 times 3, or 3 to the 4th power. 243 is nothing more than 81 times 3, or 3 to the 4th power times 3, which is 3 to the 5th power. So I'm going to write this 81 as 3 to the 4th power, and then this is raised to the power of x, and this equals, for 243, that's 3 to the 5th power, and then this is raised to the power of 1 minus 2x. At this point, I would just use my power to power rule. So here, we would keep 3 the same and multiply the exponents. So this is 3 to the power of 4 times x, or 4x, and this equals, here I'm going to keep 3 the same, and I'm going to multiply exponents. So this is 5 times the quantity, 1 minus 2x, which becomes 5 minus 10x. So this is 5 minus 10x for your exponent. Now we have 3 here and 3 here, so we can set our exponents equal to each other and solve. So we're going to have 4x is equal to 5 minus 10x. We will add 10x to both sides of the equation. This would cancel. 4x plus 10x is 14x, and this equals 5. At this point, we're going to divide both sides of the equation by 14. This cancels. So for the final answer, we're going to get x is equal to, this will be 5 over 14. All right, let's take a look at problem 6. So here we have 1 over 25. This is raised to the power of x minus 3. Then times, we have 1 over 125. This is raised to the power of 2x, and this equals 125. Before we do anything, let's think about 25, 125, and 125. If you factor 25, it's 5 times 5. And if you think about 125, well, that's 25 times 5, or basically 5 times 5, which is 25, times 5 again, which is 125, so it's 5 cubed. So I can write this as 1 over 5 squared, raised to the power of x minus 3. Let me move this over like this, times 1 over 5 cubed, and this is raised to the power of 2x, and then this is equal to, this would be 5 cubed. Now what I'm going to do is actually move this into the numerator and just change the sign of the exponent. Again, that's completely legal. So what I can do is say that 1 over 5 squared is the same thing as 5 to the power of negative 2. So I'm just going to wrap that and say this is to the power of x minus 3, and then times, over here I'm going to do the same thing. So basically 1 over 5 cubed is 5 to the power of negative 3, and this is raised to the power of 2x, and this equals 5 cubed. Okay, at this point I'm going to use my power to power rule. So 5 stays the same, and then you're going to multiply negative 2 times the quantity x minus 3. So negative 2 times the quantity x minus 3. This needs to be distributed. So let me write this here. So negative 2 times the quantity x minus 3 equals negative 2 times x is negative 2x, and then negative 2 times negative 3 is plus 6. Okay, let me erase this and put this as 5 to the power of negative 2x plus 6. Let me get rid of this, and let me multiply this by, now you have 5 that's going to stay the same, and you're going to multiply the exponents. Negative 3 times 2x is negative 6x, and this equals 5 cubed. All right, let's just use the product rule for exponents now. You have 5 and you have 5, so there's a common base with your multiplication. So just keep that, and you're going to add the exponents. So negative 2x plus, let's put negative 6x here, and then plus 6, and this equals 5 cubed. And of course, negative 2x plus negative 6x, that's negative 8x. So this becomes 5 raised to the power of negative 8x plus 6 is equal to 5 cubed. All right, so now we have what we want. We have 5 here and 5 here. So I can just set the exponents equal. I can say negative 8x plus 6 is equal to 3. Let me actually grab this real quick and come down to a fresh sheet so we have a lot of room. And I can make that a little bit better there. And so let's say that we subtract 6 away from each side. This cancels. You get negative 8x is equal to 3 minus 6 is negative 3. Let's divide both sides of the equation by negative 8. And so this would cancel with this, and you get x is equal to negative over negative is positive. So this is 3/8. All right, let's take a look at problem 7. So here we have 81 raised to the power of negative 2x minus 3 times 81 raised to the power of negative x, and this equals 1/3. Let me slide down here just a little bit. So again, if I think about 81, at this point we know that that is 3 to the 4th power. You could start again with 81 and factor that into 9 times 9, and 9 is 3 times 3. So this is 3 to the 4th power. So let's write this as 3 to the 4th power, raised to the power of negative 2x minus 3. Maybe make that a little bit better. Then times, this is 3 to the 4th power, raised to the power of negative x, and this equals, for 1/3, again, you can legally write that as 3 to the power of negative 1. This would be 1 over 3 to the 1st power. So this is how you would write this. Again, you're just dragging this up into the numerator. So this exponent, which is a 1 right now that's implied, becomes a -1. Okay, so at this point, what I would do is I would use my power to power rule to clean things up. Here, 3 would stay the same, and you would multiply exponents. So this is 4 times the quantity, -2x minus 3. And basically, this 4 is going to get distributed to each guy. So you're going to have 3 to the power of 4 times -2x is -8x, and 4 times -3 is -12. So this is 3 to the power of -8x minus 12. So 3 to the power of -8x minus 12. And then times, here you have 3 that stays the same. 4 times -x is -4x, and this equals 3 to the power of -1. So at this point, you can use your product rule for exponents. 3 would stay the same, and then you're going to add. So -8x minus 12 plus -4x. Let me show that. So -8x. Let's just go plus -4x here, and then minus 12. And again, this equals 3 to the power of -1. So -8x plus -4x, that's -12x. So this is 3 to the power of -12x, and then minus 12. And this equals 3 to the power of -1. And let's come down here where we have more room to work. And so at this point, again, we have what we want. So 3 here and 3 here. So we're just going to set the exponents equal and solve. We have -12x minus 12 is equal to -1. So let me add 12 to both sides of the equation. This cancels. You get -12x is equal to -1 plus 12 is going to be 11. Let's divide both sides of the equation by -12. This cancels. So positive over negative would be negative. So let's say x is equal to -11 over 12. Okay, let's look at problem number 8. So here we have 1/8 times 64 raised to the power of -x, and this equals 64. So lots of different strategies for this one. Let me first write 64 raised to the power of -x as 1 over 64 raised to the power of x. So you'll see why I'm choosing to do that in a moment. Again, there's different ways to solve this problem. I'm just going to multiply this by 1/8. So that's the left side just rewritten. Let me move this over here. And this equals 64. Now, what I'm going to do is actually multiply both sides of the equation by 64 raised to the power of x. Let me do that over here. So I'm going to multiply by 64 raised to the power of x, and then times 64 raised to the power of x. Let me slide down here a little bit. And so I'm going to show that this would cancel with this. And I have 1/8 is equal to. This right here, you're going to use your product rule for exponents. So this is an implied exponent of 1. So the base there, 64, stays the same. And I'm just going to say that I'm going to add the exponents. So it's 1 plus x, or you could write x plus 1. Now, thinking about what we have here, you want a common base. Now, with 8, that's 2 cubed. And with 64, that's 2 to the 6th power. But you really don't have to use 2. You can if you want. You could just use 8 because 64 is also 8 times 8. So I think it's a little bit easier, or I would say it would involve less work if you just use 8. But again, if you want to use 2, that's fine as well. So I'm just going to say that 1 over 8 is 8 to the power of -1. And this equals, for 64, I'm going to say that's 8 squared. And this is raised to the power of x plus 1. Now what you're going to do is use your power to power rule. So let's copy 8 to the power of -1. This equals 8 stays the same. You're going to multiply your exponents. So 2 times the quantity x plus 1. Then you've got to distribute. So 2 times x plus 2 times 1. 2 times x is 2x. And then plus 2 times 1 is 2. So 2x plus 2 is going to go right here. Okay, at this point, you're just going to set the exponents equal to each other because you have that common base of 8. So let's say that 2x plus 2, so this guy right here, is equal to this guy right here, which is -1. Let's subtract 2 away from each side of the equation. This cancels. You're going to say that 2x is equal to -1 minus 2 is -3. And then to finish things up, let's divide both sides of the equation by 2. This cancels. And as our final answer, we get x is equal to -3/2. All right, let's take a look at problem 9. Here we have 25 to the power of 3x times 125 raised to the power of -2x, and this equals 1. Again, for 25, that's 5 squared. For 125, that's 5 cubed. So let's go ahead and say that this would be 5 squared raised to the power of 3x times, this would be 5 cubed raised to the power of -2x, and this equals 1. At this point, what I would do is use my power to power rule here and here. So this would be 5 raised to the power of 2 times 3x, which is 6x, times, here you would have 5 raised to the power of 3 times negative 2x, which is negative 6x, and this equals 1. Now, here you're going to have something that's a little bit interesting. When you use your product rule for exponents, you're going to get 5 stays the same, and you're going to add 6x minus 6x. So let me show that. So 6x minus 6x. So this is going to be 0. So you end up with 5 to the power of 0 equals 1, which is always true. Any non-zero number raised to the power of 0 is 1. So this becomes 1 equals 1. So this, you could just say, is always true. So basically, it doesn't matter what you plug in for x, you're always going to end up with a true statement. So for this type of equation, let me just erase this. I'll just say that it's true for all real numbers. All right, let's take a look at problem 10. So here we have 1/2 raised to the power of negative 2x times 4 raised to the power of negative x, and this equals 64. So for this one, I'm going to write 1/2 as 2 to the power of negative 1, and then this is raised to the power of negative 2x, and then times, for 4, that's 2 squared, so this would be 2 squared, and then raised to the power of negative x, and this equals, for 64, let me say this is 2 to the 6th power. Looking at this, again, if you want to use your power to power rule now to clean up, 2 would stay the same, and you multiply exponents, so negative 1 times negative 2x is 2x, and then times, here, 2 would stay the same, multiply exponents, 2 times negative x is going to be negative 2x, and this equals 2 to the 6th power. Now you already see you're going to have a problem here, because basically you're going to use your product rule for exponents, so 2 would stay the same. You're going to add your exponents, 2x plus negative 2x or 2x minus 2x. Either way, that's 0. So you get 2 to the power of 0 equals 2 to the 6th power. So this right here is actually false, because you can say that this right here turns into 1 is equal to 2 to the 6th power. So that's like saying 1 is equal to 64. So this is a false statement. This right here is false. So when this happens, you basically say that you have no solution. So let me write that there is no solution. All right, let's take a look at the practice test. For the instructions, we're asked to solve each word problem. We want to round your answer to the nearest hundredth. All right, for the first problem, we are told that Larry invested $27,000 in a savings account that pays an annual interest rate of 1.8%. Let me highlight $27,000 and let me highlight 1.8%. because we're going to need those in a moment. The savings account is set to compound quarterly. So that's 4 times per year. So we're going to need that information as well. How much is in Larry's account after 5 years? So how do we solve this? Remember, we have a nice little formula that we can just plug into. So hopefully you watched the lesson and you know how to use this formula. It's very, very straightforward. All you have to do is know what each letter represents, and then you can just plug into your calculator and you'll have your answer. So A is the future value of your investment. In other words, it's the account balance after the given number of years. Here it's going to be 5 years, so A would represent the account balance after 5 years. Then P is going to be your principal or the amount invested. Some people call this the present value. Then R, that's going to be your interest rate as a decimal. N is going to be the number of compounding periods in a year, and T is going to be the number of years. So for the principal or the amount invested, it's $27,000. So this is the amount that is put into the savings account. Again, you can also think about that as the present value of the account when it starts. So this is $27,000. You can leave off the dollar symbol for now. For the interest rate, we are given 1.8%. So 1.8%. So as a decimal, this is equal to, you're going to delete the percentage symbol, and you're going to move this 2 places to the left. So in other words, this would be equal to 0.018. I think I can make that a little bit more clean. So 0.018. So as a decimal, so let me just grab this, and I'll get rid of this, and I'll come down here and paste this in, and I'll just arrow to this like that. And so the number of years is going to be 5. Right? Because we want to know how much is in Larry's account after 5 years. And the number of compounding periods, which we're going to need, In a year, that's going to be 4 times per year. Again, it's compounding quarterly. That's where we're getting that from. So t, again, is the number of years. So that is going to be 5. And n, which is going to be right here, and then also right here, that is going to be 4 because things are compounding quarterly. All right, so all you have to do at this point is basically plug into the formula, key that into your calculator, and round. That's all you have to do. It's very straightforward. So A, the future value of the account, or the account balance after 5 years, is going to be equal to, you're going to have your 27,000 times the quantity, 1 plus, this would be 0.018 divided by 4, and this is raised to the power of 5 times 4, so 5 times 4 is going to be 20. This is multiplication here. So let me slide down here a little bit, and actually this is a little bit jammed up, so let me slide this down, and then let me put this back up here. All right, so we're just going to key this into the calculator. So what I get is approximately 29,536.74175. Let me grab this real quick and copy it. So if you want to write a sentence, you can. I'm just going to put that it's approximately this and be done with it. Now, I do want to round to the nearest hundredth. So remember, this is your tenths. This is your hundredths. So basically, we're rounding, and we're thinking about the digit that follows that 4. So that 4 is in the hundredths place. So you're going to look at this digit right here, which is in the thousandths place. And this falls in the category of 4 or less. So that means we're going to leave this digit unchanged. So the 4 will remain as a 4. And then you're going to change everything that follows into a 0. But remember, when you're working with something that's after the decimal point, if I change these guys into zeros, they don't add any value, so you can just delete them. So this would be about $29,536.74. That's going to be how much is in Larry's account after 5 years. For problem 2, we have that Becky invested $19,800 in a CD, which is a certificate of deposit that pays an annual interest rate of 5.3%. The CD is set to compound daily. So we're going to say that's 365 times per year. I have a note down here that says ignore the extra day for leap years in case you're wondering about that. We are asked how much is in Becky's account after 9 years. So after 9 years. So again, I'm just going to go down to my formula. Let me just copy some things now and make it a little bit faster. P, the principal, or the amount invested, or again, you could say the present value of the investment when we're starting out. This is $19,800. Then the interest rate, we're going to call that R. That is 5.3%. So as a decimal, that is 0.053. Again, delete the percentage symbol and move the decimal point 2 places to the left. Then when we think about the N, again, it's going to be done daily. So we're just going to go with 365. And then in terms of the number of years, so that we represented with T, that is going to be 9. So let's grab this information and let's come down here and paste this in. And again, all I'm going to do now is just plug in. That's it. So the present value, or the amount invested, is this 19,800. So let me say A is equal to 19,800 times the quantity, 1 plus R, my interest rate as a decimal, is 0.053 over the number of compounding periods in a year is going to be 365. And then this is raised to the power of T times N. So T, the number of years, is 9, and N is 365. So let me put 9 times 365. Now, what I would do is just key this into the calculator, and you're going to get about, let's say, 31,901.31749. So I'm going to say approximately, let me put my dollar symbol in there. So we want to round, and again, we're rounding to the nearest hundredth. So if I look at the digit that follows, that's this 7 right here. So this falls in the category of 5 or greater. So what I want to do is add 1 to this digit in the hundredth place. And so this would be a 2. Again, you can put a 0, 0, 0, but that doesn't add any value, so you can just delete it. So we would say that the amount that's in Becky's account after 9 years is going to be about $31,901.32. All right, let's look at problem 3. So we're going to change things up just a little bit. So Jake invests in an annuity with an annual fixed interest rate of 6.2%. The annuity compounds monthly, so that means 12 times per year. If after 10 years, the account balance is $27,839.45, how much was the beginning investment? Here, what we actually have to do is solve for P. We're going to be given A, and we're solving for P. So let me write out some information. First off, we know that R, which is the interest rate, is 6.2%. Again, as a decimal, that would be 0.062. Just delete the percentage symbol and move the decimal point 2 places to the left. Then we know that your T, or the number of years, is 10. We know that N, the number of compounding periods, is 12. So this is in a year, right? 12 times per year. And then we also know that A, which is the future value. So how much is this account going to be worth, or what's the balance after 10 years? Well, that's told to us right here. So this is $27,839.45. We need to figure out P. How much was the beginning investment? So what was the initial principal? Or you can think about this as the present value. So let's go ahead and grab this real quick and bring this down here. Now, what you can do is solve the formula for P, or you can plug in first and then solve it for P. It really doesn't matter. Let me just come down here, and I'm going to say that your A is equal to P times the quantity, 1 plus R over N. This is raised to the power of Tn. If you want to solve this for P, you're going to divide both sides of the equation by this right here. That's what's multiplying P. So the quantity 1 plus R over N raised to the power of Tn. So let me move this down here so this fits. So this is divided by 1 plus R over N raised to the power of Tn. So what we're going to do is show this as canceling. So P will be equal to this. Let me actually just erase this. P is equal to this. So we know what A is. You're just going to plug in. This is 27,839.45. We know what R is, and this is probably not going to fit. So let me actually erase this and put, this is the quantity 1 plus your R is 0.062, and this is over your N, which is 12. Close that down. This is raised to the power of your T times N. So it's 10 times 12. You could write that as 120 now if you want. I think I'll just do that, make it a little bit simpler. And maybe what I'll do is erase this and make that as one continuous thing there so it's not different colors. Okay, at this point, you can just key it into your calculator. And what I get is about, let's go 15,000, and my calculator goes 0.00074. Of course, when you round that, it's just going to be $15,000. Let's come up here and let's paste this in and say, I'll put my dollar symbol in. Let me move this down. This is going to be approximately $15,000. Of course, if you're rounding to the nearest hundredth, this is a 0 and this is a 0, so you can just cut these off. This is basically just going to stay a 0, and everything after would become a 0, so you can just delete those digits. So we could say that in terms of Jake, he invested about $15,000 into this annuity. All right, let's look at one that requires a little bit of thought. So here we're told that Jennifer is saving up for a house and wants a 20% down payment. She will invest a lump sum into a savings account for 5 years that pays 4.3% annual interest and compounds monthly. So this is 12 times per year. After some calculations, she figures her ideal house will cost $140,000. So obviously she's not getting a house in California. How much should she put in the savings account? So this is the goal right here. How much should she put in the savings account? So you really have to think your way through this. Her goal is just to get 20% of the cost of the house. So let's start out with that. Let me come down to a fresh sheet. Her goal, let me write this out, is 20% of the house for her down payment. So 20% of $140,000. Now, most of you can do that without a calculator. You can basically put this into 0.1 times 140,000, and then you would just double that, right? So that's how I would do it if you wanted to do it quickly. If you multiply something by 0.1, you just move the decimal point one place to the left. So this would be 14,000, like that. So if you were multiplying this by 0.2, so let's say you did 0.2 times 140,000, Well, it would just be double this, so it would be 28,000. And of course, you could just use a calculator. So the goal, I'm just going to erase this, and I'm going to put, it's 28,000. So if we look at our formula, again, A equals P times the quantity 1 plus R over N raised to the power of T times N. What is my A? It's going to be $28,000. That's what her goal is, or the amount she wants in the account at the end of the 5 years. So let me plug in 28,000 right there. The principal is unknown. That's what we're going to solve for. We do know the interest rate. We do know how often things compound, and we do know the number of years that she wants to invest for. Let's go back up and let's grab those things. So again, we know that she's going to put this money in a savings account for 5 years. So the time is 5. And it pays 4.3% annual interest. So that's going to be 0.043 as a decimal. And the compounding periods in a year, it's going to be 12 because it compounds monthly. So let's go back down and let's just plug in. So we're going to put for R, this is 0.0, and I didn't leave myself enough room, so 4.3. Let me make this a little bit better. So N, the number of compounding periods in a year, that's going to be 12. This guy is compounding monthly. This is raised to the power of, again, it's T times N. Well, the number of years, which is T, is 5. And then the number of compounding periods in a year, again, that's N, that's going to be 12. So 5 times 12 would give me 60. So I'm just going to put that up there. And again, at this point, you're just solving for P. So let's divide both sides of the equation by this. So 1 plus this 0.043 over 12 raised to the power of 60. So this would cancel. And let me divide by that over here. Probably going to be hard to fit this. So let me move this over so that it fits. Let me move this over, and let me make this a little bit longer here. Or actually, let me redo that one more time. So this is divided by 1 plus 0.043 over 12, and then this is raised to the power of 60. So when I plug this into my calculator, I'm going to get that P is about, let's go 22,591 point, let's go 84049, and then my calculator cuts off. Let me copy this. So P, which is your principal, or really the amount she needs to put in the savings account, that's going to be about $22,591.84. Because if I round this to the nearest hundredth, here's your hundredths place. The digit that follows is a 0, so the 4 is going to stay unchanged. These would change into zeros, but again, they add no value, so you can just delete them. So again, the amount she should put in the savings account is about $22,591.84. If she does that, again, at the end of the 5-year period, she's going to have an account balance of about $28,000. It wouldn't be exactly because we're rounding here, but let's say about $28,000, and that's what she needs for her 20% down payment. Again, she doesn't need this. She just needs the down payment. The rest of it, she's just going to get a mortgage for or something like that. All right, let's take a look at problem number 5. Here we have that Melissa visits 2 competing banks. National Bank and Trust is offering a 5-year CD. Again, a CD is a certificate of deposit with an annual interest rate of 3.75%. This account will compound monthly, so that's 12 times per year. Now, the other bank, we have Jonestown Bank. They're offering a 5-year CD as well with an annual interest rate of 3%. This account will also compound monthly, so 12 times per year. The Jonestown Bank is offering a $300 bonus to all new customers. We're told that this bonus money will be deposited in Melissa's account on the first day of her account being opened. Now, here's the question. Assuming Melissa has $10,000 to invest, which bank should she choose? Then we're going to change things up. If her investment amount changed to $5,000, how would this impact her decision? So does she stay with the same bank as she used for the $10,000 investment, or she's going to change things up? So what I would do is set up a little table so you can organize the information. So most of this stuff is going to be the same. The difference is going to be the interest rate and the principal. But the T, the number of years, in each case, it's going to be a 5-year CD. So it's going to be 5 and 5. And the number of compounding periods in a year for each one, remember it's compounding monthly, so each of these guys is going to be 12. Now for this one, we're going to start with a $10,000 investment. So for the National Bank and Trust, that's NBT I'm abbreviating, this is $10,000 here. And then for the Jonestown Bank, again, JTB, I'm just abbreviating, she gets a $300 bonus deposited into the account on the first day. So let's say the principal or the amount invested here is $10,300. We just have a different interest rate here. If we go back up, for the National Bank and Trust, it's 3.75%. And then for the Jonestown Bank, it's only 3%. So let's put 0.0375, and then here 0.03. So again, 3.75% for the National Bank and Trust, and then only 3% for the Jonestown Bank. So all you have to do is use your formula for each bank and see what you would get. And obviously, you're going to choose the bank that gives you the highest return or the most money at the end of the investment period. So let's just write out our formula. Again, so we have A, the account balance at the end of the 5 years, or again, you could say the future value of the account, that's equal to your P times the quantity 1 plus your R over your N, and this is raised to the power of Tn. So let's just start with this one. We'll say that A is equal to, we'll have for P 10,000, so 10,000, times the quantity, 1 plus your R is 0.0375, over your N, that's going to be 12, and this is raised to the power of T times N. So T times N, 5 times 12 would be 60. So let's punch this into the calculator. Okay, so here what I get is about 12,000, let's say 58 point, I'm going to go 77648. So that's where my calculator stops. If we're going to round these to the nearest hundredth, you're going to look right there. That's the digit in the hundredths place. The digit that follows is a 6. So I want to add 1 to that 7. So that's going to become an 8. And then you can just delete everything else. So this would be about $12,058.78 that you would get from the National Bank and Trust. So maybe I can actually put this up here. Let me make another column, and I'll just put A, and then I'll put this in. So 12,058.78. A lot of this is going to be the same. So let me just change this to 10,300, and I'm going to change this to 0.03, or you could write 0.03 if you wanted to make that more clear. And now we'll just key this into the calculator, and I get about, let's say, 11,964, and then 0.65285. Again, if you're rounding to the nearest hundredth, you want to look at this 2 here that falls in the category of 4 or less. So just leave the 5, this digit here in the hundredths place alone, and you can delete all the digits that follow. So this, let's put 11,964.65. So obviously, she's going to get a better return going with National Bank and Trust. Even though they don't give her the bonus money, the fact that the interest rate is higher, it's going to make up for it over the 5-year period. So this is what she should choose in the first case. So let's go up here and just put for $10,000, she's going to choose the National Bank and Trust. Okay, we're going to come back down here. And now we're going to do the other scenario. So let me erase this. Again, a lot of this stuff is going to stay the same. We're just going to now invest only $5,000. And so her bonus here is still $300. It doesn't say that it's based on the amount of money you put in. It just says you get it if you're a new customer. So she's putting $5,000 in here and $5,300 in here. And so again, we're just going to plug into the formula. So we're going to say A is equal to the principal. Let's start with this one. So that's 5,000 times the quantity. We're going to have 1 plus. For the interest rate, again, it's 0.0375 over your N is going to be 12. And then this is raised to the power of 5 times 12, which is 60. So let's key this into the calculator and see what we get. So I get about 6,029.38, let's say 8239. That's where my calculator stops. So rounding this to the nearest hundredth, here's your digit in the hundredths place. The digit that follows is an 8. So I'm basically going to delete these. I'm going to add 1 to that 8 and put a 9 there. So let's say this is about $6,029.39 that you would get. Now let's look at the other scenario. We're going to put in 5,300 now. So that's going to change. And the interest rate is going to change. So she's only getting 3%. So 0.03 Everything else is the same. So let's key this into the calculator. And what I get is about, let's say 6,156. Let's go 0.568942. So if you want to round to the nearest hundredth, again, here's your digit in the hundredths place. The digit that follows is an 8. So let's just cut off these digits. We'll add 1 to that 6 and make it into a 7. So this right here would be about $6,156.57. So now what we see is that with an investment of $5,000, she's better off going with the Jonestown Bank because of this bonus $300 that they put in her account on the first day. After 5 years, she would have this $6,156.57 versus the only $6,029.39 that she would have with the National Bank and Trust. So let's go back up and say for $5,000, now we're going to change our decision and we're going to go with the Jones. So the Jonestown Bank. All right, let's take a look at the practice test. So for the instructions, we're asked to solve each word problem. We want to round your answer to the nearest hundredth. All right, before we jump in and look at any problems, again, let's think about the formula we're going to use, and I'll show you how to solve for different variables. This is going to be based on what you're asked for in the problem. So first and foremost, if we go back to the formula for compound interest that we talked about in the last lesson, so we have A is equal to P times the quantity 1 plus R over N raised to the power of Tn. A is the future value of this account. So it's the account balance after a given number of years. P is the principal. That means the initial amount invested. Some people call this the present value of the account. R is the interest rate as a decimal. N is the number of compounding periods in a year. And then T is the number of years. So I think that we all know for a given principal, interest rate, and number of years, as N increases, the amount of money we're going to earn is going to increase. Because with compound interest, you're earning interest on interest. So the more often that your bank or whatever financial institution it is that you're working with deposits your interest, the better off you're going to be. But what we talk about in this section is what happens when N gets really, really large and approaches infinity, and we have something called continuous compounding. So basically, we're not going to use this N anymore. We're going to change the formula up, and it's going to involve this special number E. So we have A is equal to PE raised to the power of RT. So you'll notice that you have this A here, this P here, this R here, and this T here. But again, the N, the number of compounding periods in a year, that's not involved in this formula because we're going to say that we have continuous compounding in the problem. Let me get rid of this. And this special number E is going to be available to you on your calculator. It's just something you're going to punch in. It's about 2.718 if you want to approximate it, but I would always use my calculator for it because it's going to give you many, many digits and give you a more accurate answer. So the first thing is you might have to solve this for P. In other words, you might have a problem where they say, well, what's the principal? So to solve this for P, let me drag this over here. Let me put a little border. So to solve for P, we start with A is equal to P E raised to the power of RT. This right here is multiplication. So to undo multiplication, we use division. I'm going to divide both sides of the equation by E raised to the power of RT. So do that over here as well. And we see that this would cancel with this. And so the formula, if you need to solve for P, is just going to be that P, which is the principal, is equal to A, which is the future value of the account, over your special number E raised to the power of R. Again, that's your interest rate as a decimal, times T, that's your time in years. Let me get rid of this, and I'll just write this up here so that we have it. Let me put that right there. Now, the more challenging things to solve for would be if you have to solve for R, the interest rate as a decimal, or T, the time. So both of those are going to come up. Let me put this like this. So as you're working problems, you have to solve for both of those. Now, when you want to solve for a variable and it's in the exponent, you're going to use logarithms. So let's talk about that. Most of you have taken Algebra 2 before, so you know how to do this. And if you don't, it's not that big of a deal. We're going to cover it in more detail coming up in the next few lessons where we're talking about logarithms. So let's start with A is equal to PE raised to the power of RT. If you want to solve for, let's say, R, first, you want to isolate this right here. So E raised to the power of RT. So to do that, I'm going to divide both sides of the equation by P. So this would cancel. And let's go ahead and say that this would be E raised to the power of RT is equal to, we would have A over P. Now here's where you have to know a few things. First off, when you do something like, let's say, log of x to the power of A, by rule, this is equal to, let me slide this down a little bit. And actually, this looks like a 9, so let me make this into a better looking A. This is by rule A times log of x. In other words, this can come down out in front and multiply by that logarithm. So that's all we're really going to do here, but we're going to use another property. If you do something like, let's say, log base e of e, this is equal to 1, because e to the power of 1 will give you e. And we'll talk about this when we get to logarithms. For right now, if you see log base e of e, that's equal to 1. But when we have log base e, we have a special name for that. That's the natural logarithm. So you're going to see that abbreviated with ln. So when you see something like this, ln of e, that equals 1. So we're going to use these properties. Let me get rid of this. And I'm going to take the natural log of each side. So I'm going to say this is ln of e raised to the power of rt is equal to the natural log, so again, ln of this a over p. You can delete this now, it's just in the way. And again, using our rule, this right here will come out in front. And so we're going to say we have rt multiplied by this natural log, or ln here, of e. And this equals, you have the natural log of this a over p. So what we see is that, again, the natural log of e, that's going to be 1. That is log base e of e. So that's 1. Get rid of this. And let's just say that this would be rt, again, times 1, you can just leave it off, is equal to the natural log of a over p. Now, if you want to solve for r, again, this is multiplication here. So go ahead and just divide both sides by t, and that's solving for r. So that's another formula for you. So let me bring this over here. And I'm going to just get rid of this and say r is equal to this. And again, you can put another formula up. We're not going to use this today, but if somebody asks you for the time, well, the r and the t are going to swap places because, again, we had rt is equal to the natural log of a over p. And so if you want to solve for t, you're going to divide both sides by r. So just erase it from here and divide by r here, and basically you've solved for t. So these are the different formulas you're going to use for these problems. Again, you could just copy it down for your notes, and as you see different problems, just think about what you're asked to solve for, and then you could just plug in. Again, we're going to talk about logarithms in more detail coming up. All right, let's take a look at the first problem. We are told that Steve invests $2,807 in a 401k account with a fixed annual interest rate that is compounded continuously. Again, when you see that, you know you're using the formula A equals PE raised to the power of RT. After 13 years, the account balance reaches $9,044.13. What is the interest rate of the account? So it's asking for the interest rate, or R. That means I want the formula that's solved for R. That's all I have to do. Let's come up here and let's grab this one. All right, so let's come down here and paste this in. So we need A, P, and T. So let's come down and say that A is equal to what? Well, this is the account balance after the given number of years. So after 13 years, that's this right here. So it's $9,044.13. The P is the principal. So that's the amount that was invested. So that's going to be $2,807. And then the T is the time in years. So that's going to be 13. So 13. So very straightforward. Just going to grab this, come down here and paste this in, put a little border, and we're just going to key this into the calculator. So it's nice and simple. So R, which is your interest rate as a decimal, is equal to the natural log, that's your ln there, of your A, let's write that in, so 9,044.13, over your P is 2,807, and then this is over your T, which is 13. So this is how you're going to key it into your calculator, and you're going to get about, so if I round to the nearest hundredth, I'm going to get about 0.09. So 9% if you convert it into a percentage. So let's come back up here. So let's say that it's approximately 9%. All right, let's take a look at problem 2. So here we have Adam invests $1,051 in a savings account with a fixed annual interest rate that is compounded continuously. After 8 years, the account balance reaches $1,698.49. What is the interest rate of the account? Again, we have another situation where we're trying to solve for R. So let me come back up here and grab this again. And let me just paste this in here and get rid of this right here and come up here and just write down what we need. So the A, again, the account balance after the 8 years, or the future value of the account, that is $1,698.49. Then your P, that's the principal, the amount that is initially invested, that's going to be $1,051. And then the t, the number of years, is going to be 8. So let's grab this, come down here and paste this in. Again, we're just going to key this into the calculator. So r, the interest rate as a decimal, is going to be the natural log. Again, that's the ln of your a is 1,698.49 over your p, that's 1,051. And then this is over your t, which is going to be 8. So again, if I key this into the calculator and I round to the nearest hundredth, I'm going to get about 0.06. So if you think about 0.06, again, as a percentage, that's 6%. So let's say it's about 6%. All right, for problem 3, we have that Daniel invests a lump sum of money in a savings account with a fixed annual interest rate of 5% that is compounded continuously. After 7 years, the account balance reaches $5,676.27. How much was initially invested? So in other words, what was the principal? So we've already figured out how we could solve for P. Let me go ahead and grab this real quick and come back down here and paste this formula in. This is what we're going to use. Let me put a little border and come back up here and fill some stuff out. So we need A. That's the account balance after 7 years. That's $5,676.27. We need R, which is the interest rate as a decimal. This is as a percentage is 5%. So as a decimal, that's 0.05. And then we need the number of years. That's T. So T is equal to 7. Let's come down here and paste this in. All right, I'm just going to tell you, you have to be really careful if you're keying this into a calculator based on the calculator you're using. If you're keying this into an online calculator, then you're probably okay. But if you're using a handheld calculator like a TI-83 or something like that, you have to be really, really careful with this problem. So let me plug in and I'll show you what I mean. So P is equal to, for A, you have 5,676.27 over E. Again, that's a special number. Your calculator will have that. Raised to the power of RT. So R is 0.05. And then times T is 7. Now, if you want to key it in like this, so 5,676.27 divided by E raised to the power of, you do this multiplication first. So 0.05 times 7 would be 0.35. If you want to key it in like that, you will get the right answer no matter what calculator you're using. You don't have to take any special steps. This is what I recommend just to guard against errors. If you don't want to do that, let me show you what could go wrong. So let's say you're keying this in to a TI-83 or something like that, and you just say, okay, I have 5,676.27, and you hit the divided by key, you have your special number E, and then you hit the to the key. So we're basically raising this to a power. But now you have, as the next guy, your 0.05 and then times 7. Looking at this, just in this form right here, what does the calculator want to do first? Remember the order of operations. We know that raising to a power is a higher priority than division or multiplication. So it's going to do e to the power of 0.05 first before it does anything else. And then it's going to be faced with division and multiplication, and the division occurs to the left, so it's then going to do that one, and then at the end it's going to multiply by 7. So you're going to get the wrong answer. So basically what you would want to do is wrap this with parentheses so that it does this first and has the highest priority, and then you would basically have this problem here. So this would then be equal to the 5,676.27 divided by your e raised to the power of 0.35, and that will give you the correct answer. So that would give you approximately 4,000 if you round to the nearest hundredth. So let me get rid of this, and we'll say that this is about, or approximately, 4,000, and so that would be $4,000 for the principal. So let's come back up and say that the principal was about $4,000. All right, let's take a look at problem 4. So we have that Harry invests a lump sum of money in a bond fund with a fixed annual interest rate of 7% that is compounded continuously. After 17 years, the balance reaches $10,775.05. How much was initially invested? So in other words, what was the principal? So again, coming back up here, this is the formula we want. So let me come down here and paste this in. And all we want to do is come up here and grab our information. So A, the account balance after 17 years, that's going to be $10,775.05. Then we have R, the interest rate as a decimal. It's 7%, so that's going to be 0.07 as a decimal. And then the T, the time in years, is going to be 17. Let me grab this real quick and come down here and paste this in. And let me do this like this. So you're just going to plug in. Again, if you're using a calculator like a TI-83, just be really careful. You can do the R times T first if you want, or you could wrap stuff with parentheses. Again, you just have to make sure that you're forcing your calculator to do things in the right order. So we're going to say that P is equal to your A, which is 10,775.05, divided by your E raised to the power of R times T. I'm just going to wrap this here for clarity. So 0.07. and then times 17. Again, if you keyed in like this, you won't have any issues. And so this would give me approximately, let's say $3,278 if you round to the nearest hundredth. Just come back up here and paste this in. So I'll say it's about, or approximately, $3,278. That was the amount that was initially invested. All right, let's take a look at problem 5. So here we're told that Jacob invests a lump sum of money in a certificate of deposit account with a fixed annual interest rate of 7% that is compounded continuously, and then after 20 years, the account balance reaches $7,863.03. How much was initially invested? Okay, so let's grab this once again, and let's come down here and paste this in. Let's put this like this. So again, we're told the account balance after 20 years is $7,863.03. We're told that the interest rate as a decimal, again, it's 7%, so as a decimal, that's 0.07. And then we're told that the time here, it's going to be 20, again, for 20 years. So let's grab this, come down here and paste this in, and let's just plug in. So P, your principal, is equal to, again, your A is going to be 7,863.03. This is over your E raised to the power of R is 0.07 times T, which is 20. Again, if you're going to key this into a TI-83 or something like that, just wrap this with parentheses. So I get about, let's say, $1,939. So $1,939 if I was to round to the nearest hundredth. So let's go back up and say that this is about $1,939, again, for the principal or the amount that was initially invested. All right, let's take a look at the practice test. For the instructions, we're asked to evaluate each. All right, let's take a look at the first problem. So here we have log base 343 of 1/7. So what is this equal to? In other words, this right here is the exponent that is required on this base of 343 to get an answer, or you could say a result of 1/7. I'm just going to set this equal to x since we don't know what it is. And then I'm going to write this in exponential form. So I'm going to say that this is my base, so 343. This would be raised to the power of x. So that's my exponent. And then this would be equal to this argument for the logarithm, which is 1/7. So we need to figure out what is the value for x that's going to make this true. Well, what you can do here, since you have a 343 here, and you notice you have a 7 here, well, 343 is really 7 cubed. It's 7 times 7, which is 49, then times 7 again, which is 343. So you could say that this is 7 cubed raised to the power of x, and this equals, for 1/7, you could write that as 7 to the power of -1. So here you could use your power to power rule. 7 stays the same, and then you're just going to multiply the exponents. So 3 times x is 3x, and this equals, here you'd have 7 to the power of -1. At this point, you have the same base on each side. So you have this 7 and this 7. And so we can use our rule that we talked about earlier on in the course, where basically we just set the exponents equal to each other and we solve the resulting equation. So 3x is equal to -1. And make this a little bit better there. We would divide both sides of the equation by 3. So we can isolate x. This cancels, and you get x is equal to -1/3. And let me get rid of this. So I'm going to, in the place of x, say this equals -1/3. Now, it's very easy to check this if you want. Again, just put it into exponential form. You would say 343. That's going to be your base. It's going to be raised to, this right here is your exponent. So -1/3. And this should be equal to, again, the argument for the logarithm. So this is 1/7. So how would we determine if these two sides are the same? Well, again, on the left here, all you'd really have to do is use your rules of exponents and say that this would be 1/343 raised to the 1/3 power. All you're doing is you're going to take this and drag it across the fraction bar and change the sign of the exponent. So that's where that's coming from. Does this equal 1/7? Yes, it does. This right here is the cube root of 343. So let me put this down here. This would be 1 over the cube root of 343 is equal to 1 over 7. And we should know that the cube root of 343 is 7. So let me come down here and say that this would be 1 over 7 is equal to 1 over 7. So yeah, our answer here, which is negative 1/3, is correct. Okay, let's take a look at problem 2. So here we have log base 3 of 1 over 81. Again, you could just say that this is equal to x. Would put this into exponential form. So the 3 is the base, and this would be raised to, your exponent is x, and this would be equal to the argument for the logarithm, which is 1 over 81. So for this one, what I would do is write 1 over 81 as 3 to the power of negative 4. In other words, this right here, let me do a new line so nobody's lost. I could write as 1 over 3 to the 4th power. And again, this 3 to the power of x would stay the same over here. Let me just drag this up here. Now I would say this is 3 to the power of x is equal to, you drag this across the fraction bar, you change the sign of the exponent. So this is 3 to the power of negative 4. And of course, at this point, because you have 3 here and 3 here, you could just set those exponents equal, and you would have x is equal to negative 4. So that just tells me that this right here is going to be negative 4. Let me erase all this so I can put this in frame. So let me say that this is equal to negative 4. And this one's really easy to check. You would have 3 to the power of negative 4 is equal to 1 over 81, which we know is true. This is, if you go through it, 1 over 3 to the 4th power is equal to 1 over 81. And of course, this would be 1 over 81 is equal to 1 over 81. So our answer here, negative 4, is correct. All right, let's take a look at problem 3. So here we have log base 5 of 1 over 125. So again, what am I going to do here? I'm just going to set this equal to x, since it's unknown at this point. Again, you could just put this into exponential form. So 5 to the power of x would be equal to this argument for the logarithm, 1 over 125. So 5 to the power of x is equal to 1 over 125. Now, most of you know that 125 is going to be 5 cubed. It's 5 times 5, which is 25, times 5 again, which is 125. So let me go ahead and write this as 5 to the power of x is equal to 1 over 5 cubed. And again, you can drag this across the fraction bar. You just have to change the sign of the exponent. So I'm just going to say that this is 5 to the power of x is equal to, we'll have 5 to the power of negative 3. So at this point, again, you have a 5 here and a 5 here. So that same base, you're just going to set those exponents equal to each other. So you're just going to say that x is equal to negative 3. So that's going to be the answer here, just negative 3. So let's say that log base 5 of 1 over 125 is going to be equal to negative 3. Now, again, in terms of checking it, you just go back into exponential form. You would say 5 raised to the power of negative 3. So this raised to this power is equal to 1 over 125. Is that true? Yes. This right here turns into 1 over 5 cubed is equal to 1 over 125. And of course, you get 1 over 125 is equal to 1 over 125. So the answer of negative 3 is correct. All right, let's take a look at problem 4. So here we have log base 4 of 64. And so again, I'm just going to set this equal to x. And then we're going to say 4 to the power of x. Again, just doing this. So this is my base. This is my exponent. That would be equal to 64. Now, most of you can eyeball that and see it's going to be 3 because 4 cubed would be 64. But again, you could just write 64 in terms of having a common base with 4. So you could say 4 to the power of x is equal to, we know this would be 4 cubed. And then because this right here, this base of 4 is the same as this base of 4, you can just simply say that now the exponents would be set equal to each other. So x is just equal to 3. So let me get rid of this and just say that this would be 3 here. And of course, this is really, really easy to check. You would just say that 4 cubed, so 4 cubed would be equal to 64. And of course it is. You would get 64 is equal to 64, which is a true statement. So this guy is going to be 3. All right, for the next few problems, we want to solve each equation. And these are going to be very simple equations, similar to what we set up for the first 4 problems. So for problem 5, we have log base x of 6 is equal to 1/3. Okay, so all we have to do again is just write this in exponential form. So x raised to the power of 1/3 would be equal to 6. X raised to the power of 1/3 is equal to 6. Okay, now I have this x here, and it's being raised to the 1/3 power, or we're taking the cube root of it. So basically, how do we undo that? Well, we're going to cube both sides. Let me slide down here a little bit, and I'm just going to cube this side and cube this side. So let me put an exponent of 3 and an exponent of 3. So basically, by the power to power rule, we know that x would stay the same. 1/3 times 3 is 1, so now I just have x by itself. And this equals 6 cubed is going to be 216. Again, if you want to check these, you can. You would be saying that log, let me put this off to the side, log base 216 of 6 is equal to 1/3. In other words, 216 raised to the power of 1/3, or the cube root of 216, would be equal to 6, and that's a true statement. This would give you 6 is equal to 6, so this is a valid solution. X is equal to 216. Okay, let's look at problem 6. Here we have log base 4 of x is equal to 2. So again, to put this into exponential form, you'd have 4 squared is equal to x. So we know that 4 squared is just 16, so we would say x is equal to 16. Now again, checking this is very, very straightforward. Let me move this over here like this. You would have log base 4 of, just plug in a 16 for x. Does this equal to, where you're saying 4 squared, does that equal 16? Yes, it does. So this x equals 16 is a valid solution. Okay, for problem 7, we have log base 3 of 243, and this is equal to x. So again, to put this into exponential form, 3 to the power of x is equal to 243. So 3 to the power of x is equal to 243. And again, for this one, 243, a lot of you will know that's 3 to the 5th power. 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. And then 81 times 3 is 243. So this you could just write as 3 to the 5th power. And then you could just set your exponents equal to each other. So x would just be equal to 5. So let me put that over here. I'll just put a little border and say x is equal to 5. And of course, if you want to check that, you would say log base 3 of 243 is equal to 5. So this is 3 to the 5th power. 3 to the 5th power is equal to 243, and that's a true statement. You would get 243 is equal to 243. So this x equals 5 is a valid solution. All right, for problem 8, we have log base 6 of negative 36 is equal to x. So this problem obviously has no solution, and that's because this right here is creating something that's undefined. When we work with a logarithm, we want to make sure that the argument is positive. So it can't be 0 and it can't be negative. If you try to set this up in exponential form, you have 6 raised to the power of x is equal to negative 36. Well, that has no solution, right? If you take this 6 right here and you raise it to some real number, let's say it's negative, 0, or positive, it doesn't matter. You're always going to get something that's positive. You can never get 0 and you can never get something that's negative. So let me just erase this and say that there's no solution. So there's no solution. All right, for problem 9, we have 5 minus 9 log base 5 of negative 4x minus 1, and this equals 14. Okay, so the idea here is we're just going to isolate this guy right here on one side and have a number on the other, and then we can just put it into exponential form. Now we're going to see more advanced logarithmic equations later on. For right now, these are pretty easy, and you just follow that format. So we're going to subtract 5 away from each side of the equation. This would cancel. We get negative 9. We have log base 5 of negative 4x minus 1, and this equals 14 minus 5 is going to be 9. Let me divide both sides of the equation by negative 9. And so what's going to happen is this would cancel with this, and we're going to have log base 5 of negative 4x minus 1, and this equals, so if we do 9 over negative 9, that's going to give me negative 1. So let's write negative 1 over here. Let me slide down a little bit. And now we can put this into exponential form. So this is your base, this is your exponent, and it's going to be equal to this right here, the argument for the logarithm. So 5 to the power of negative 1 is going to be equal to negative 4x minus 1. Now this right here is 1/5, so you could write it that way if you want. Let me write 1/5 here. And to clear that fraction, I'm just going to multiply both sides by 5. And so 5 times 1/5 is 1. You could show that as canceling if you want. So this equals, this needs to be distributed to each guy inside the parentheses. So 5 times negative 4x is negative 20x. And then 5 times negative 1 is negative 5. Okay, at this point, let me go ahead and add 5 to both sides of the equation. So this would cancel. 1 plus 5 is 6. So you're going to get negative 20x is equal to 6. Let me divide both sides of the equation by negative 20. So this would cancel. You get x is equal to positive over negative is negative. If I think about 6 and 20, let me rewrite 6 as 3 times 2. And let me rewrite 20 as 10 times 2. And of course, you can cancel a common factor of 2 between numerator and denominator. So this would be negative 3/10. All right, let's write out x equals negative 3/10. And let's just make sure we got the right answer. So that's going to get plugged in right there. So you have 5 minus 9 log base 5 of negative 4 times negative 3/10, and then minus 1, and this should be equal to 14. So let me write this out. 5 minus 9 log base 5 of. Here, negative times negative is positive, and basically, let me just cancel those away like that. If you think about 4 and 10, there's a common factor of 2. So 4 divided by 2 is 2. 10 divided by 2 is 5. So let's say this would be 2 times 3, which is 6 over 5. So this would be 6/5 minus 1. Let's write that as 5/5. And this should be equal to 14. Okay, let's come down here a little bit, and let's see what we have. So let me write 5 minus 9 log base 5 of. 6/5 minus 5/5 is 1/5. And then this equals 14. So what we see is log base 5 of 1/5. Now, we have not talked about the properties of logarithms yet. That's coming up in the next lesson. But there's a property that we can use here to make this very, very quick. If you have something like log base 5 of, let's say, 5 raised to the power of negative 1, then what happens is this exponent right here can come out in front as multiplication. In other words, something like, let's say, log base a of x to the power of r is equal to r times log base a of x. So this is called the power rule for logarithms, and we'll talk about this in the next lesson. So for right now, let's use this and say this would be equal to, you can bring the negative 1 out in front as multiplication, and then it's times log base 5 of 5. And so log base 5 of 5 is 1. So you would basically have, let me get rid of this. Let me move this over here like this. You would basically have negative 1 times 1, which is negative 1. So this right here can be replaced with negative 1. Let me get rid of this, and let me write that you would have 5, let me go plus negative 9, and then times negative 1, and this equals 14. Well, negative 9 times negative 1 is positive 9, so this is 5 plus 9 equals 14, and you get 14 equals 14. So that solution, which was x is equal to negative 3/10, is going to be correct. Okay, for problem 10, we have 4 log base 4 of negative 3x minus 6, then minus 3, and this equals 9. So again, I want to isolate this right here to get the problem started. So that will be equal to some number. Then you can put it into exponential form, and you can solve. So let me go ahead and add 3 to both sides of the equation. This cancels. We get 4 log base 4 of negative 3x minus 6, and this equals 9 plus 3 is 12. Okay, at this point, let me divide both sides of the equation by 4, and we'll say that this is going to cancel. And we'll say log base 4 of negative 3x minus 6 is equal to 12 over 4 is going to be 3. Okay, at this point, you can put it into exponential form. So we're going to say 4 to the power of 3, or 4 cubed, is equal to, we'll use the argument from the logarithm, so negative 3x minus 6. We know 4 cubed is 64, so let's go ahead and write negative 3x minus 6 is equal to 64. At this point, let's add 6 to both sides of the equation. Let's slide down here. This would cancel. You get negative 3x is equal to 64 plus 6 is going to be 70. So let's divide both sides of the equation by negative 3. This would cancel. You're going to get x is equal to negative 70 thirds. Now, 3 is a prime number, and 70 is going to be 7 times 5 times 2. So there's really not anything you can do to simplify there. So this is your answer. All right, so we found that x was equal to negative 70 thirds. Let's plug that in for x right there and make sure that we get a true statement. So we have 4 log base 4 of negative 3 times negative 70 over 3, and then minus 6, and this will be minus 3 out here. Let me make that better, and then we're going to say this equals 9. Okay, so starting on the inside, negative 3 times negative 70 over 3. We know that a negative times a negative is a positive, so let me just mark those out. And then 3 divided by 3 is going to be 1. So this becomes 70 minus 6, which is going to be 64. So you have 4 log base 4 of 64 minus 3 is equal to 9. Now again, you can go through and say, well, what is log base 4 of 64? A lot of you know that it's 3, but you can also use that trick that I just talked about in the last problem and just say that 64 is 4 cubed. And then log base 4 of 4 cubed, again, you can use that little shortcut. So log base 4 of 4 cubed. This, by definition, is going to be equal to 3. We'll see another special property where we can just do that. But the long way to do it is to say that the 3 comes out in front as multiplication, and then it's times log base 4 of 4, and log base 4 of 4 is 1, so this is equal to 3 times 1, which is 3. So lots of different ways that you can get that part of it. So this right here is 3. So you have 4 times 3 minus 3 is equal to 9. Well, 4 times 3 would be done first, so that's 12. And then minus 3 is equal to 9. And of course, 12 minus 3 is 9, so you get 9 equals 9. So our solution, which was x is equal to negative 70 over 3, is correct. All right, for the next few problems, we're going to change up the instructions. We want to sketch the graph of f of x and also g of x. We want to find the transformation from f of x to g of x. All right, for problem number 11, we have f of x is equal to log base 2 of x. And then we have our g of x. This is equal to the negative of log base 2 of x minus 2. So before we try to graph anything, let's think about the transformation that's going to occur from f of x to g of x. To do that, what I like to do is write things in terms of f of x. So I'm just going to write my g of x here is equal to, well, we see we have a negative out in front. So let me put the negative of, instead of log base 2 of x, I have log base 2 of x minus 2. So let me put f of x minus 2. Again, f of x minus 2 is just me plugging in x minus 2 for x right there. So g of x is equal to the negative of f of x minus 2. So that's how you could write it. Now, in terms of the transformation, you have this negative here, and then you have this minus 2 right here. So I'm going to think about those separately. First, if I think about the x minus 2 that's on the inside, remember this does the opposite of what you would expect. If you have x minus 2, that's going to shift me to the right by 2 units. So let me start by putting shifted. So shifted 2 units. And let me put right first before I put my comma. And then the next thing is I would think about this right here, the negative of, if you have the negative of f of x, that's creating a reflection across the x-axis. In other words, for the same x value, now you're getting the opposite y value. So let me put reflected across the x-axis. So those are the two things that are going to happen. So a point on this first function f would be shifted 2 units to the right and then reflected across the x-axis to get that point on g. So let's come down here. I already made some tables, and this is a good way to graph things. I'm going to start with my f of x equals log base 2 of x. So we talked a lot about how to evaluate things, so I'm not going to waste a lot of time here. I'm just going to tell you what it is. So if you plug in a 1/2 for x, you're going to get a -1 for y. So log base 2 of 1/2 would be -1. Then if you plug in a 1 for x, you get a 0 for y. You plug in a 2 for x, you get a 1 for y. You plug in a 4 for x, you get a 2 for y. You plug in an 8 for x, you get a 3 for y. You plug in a 16 for x, and you get a 4 for y. Now, if we look at the graph, and this is going to be in, let's just call it red, f of x equals log base 2 of x. So this guy right here, we have enough points to sketch this guy. You might want some additional points going this way, but the way I do that is I think about the fact that, okay, this right here, I know it can't be 0 and it can't be negative. So what happens is the y-axis for that is going to be a vertical asymptote. So basically, this is going to approach where the x value is going to be 0, but it's never going to quite get there. Okay, so once you have this basic graph sketched and you have those points there, again, you can just shift your points around to get this graph right here. And let me just talk about that with the table first. So we know that basically we're going to shift, or let me put shifted 2 units right. Or actually, instead of writing this out, let me do a shorthand. So let me go right 2 units. And then I'm going to go REF for reflected, and then I'm just going to put X for x-axis. So basically, that's just going to change the sign of Y. So if you look at the x value here and the x value here, in each case, it's just increased by 2. So 1/2, if I add 2, that's adding 4 over 2. Let me do that off to the side because I know people can't do fractions in their head. So basically, I'm writing 2 as 4 over 2, and that would give me 1 plus 4 is 5, and this is over the common denominator of 2, so that's 5/2. And then the other ones, if you go 1 plus 2, that's 3, 2 plus 2, that's 4, 4 plus 2, that's 6, 8 plus 2, that's 10, 16 plus 2, that's 18. So I'm just increasing my x value by 2. Now, the given y value here is actually going to be changed into its opposite. That's coming from the reflection across the x-axis. So instead of -1, I get +1. So I'm just basically multiplying this by -1. Now, because 0 multiplied by -1 is still going to be 0, this is not going to change. Then 1 becomes -1, 2 becomes -2, 3 becomes -3, 4 becomes -4, so on and so forth. So that's how you can get your points if you want to use the table method. Or again, you could just go to the graph and just shift them like that. I'll just go through that with you in case you want to see it. So this point right here, 0.5 comma -1. Well, if I go 2 units to the right, I'm going to go right here. That would be 1.5. Then right here, that would be 2.5 in terms of the x value. Let me just put a little dot there temporarily. So right now, you'd be at 2.5 comma -1. Well, I'm going to reflect across the x-axis. So that's going to change my y value from -1 to +1. So that's going to give me this point right here. Then if I look at this point right here, which is 1 comma 0, I'm going 2 units to the right. And then because the y value is 0, well, I'm not going to change the y value because multiplying it by -1, that's going to leave it unchanged. It'll still be 0. Then if I look at 2 comma 1, I go 2 units to the right. So go to 3, then 4. So it'd be right there. And then basically, you'd have 4 comma +1, you reflect across the x-axis, you change that y value to basically -1, so now you get 4 comma -1. Just changing this from +1 to -1 in terms of the y value. Okay, for this 4 comma 2, well, now I'm going 2 units to the right, so 1, 2, that would put me right there. So the x value is 6, the y value is 2. Reflect across the x-axis, that puts me down here. This is 6 comma -2. Then this 8 comma 3, if I go 2 units to the right, 1, 2, now I'm going to be at 10 comma 3. Well, now if I reflect across the x-axis, I'm coming down here to 10 comma -3. Then if I look at 16 comma 4, again, go 2 units to the right. That's going to be right there. So that would be 18 comma 4. Reflect across the x-axis. That puts me down here at 18 comma -4. So that's how you can get this sketch right here. Again, you can just look at the points and just do the transformation with each point, and that will give you enough to draw the graph here. You can also do it with the table like we did on the other page. All right, for problem 12, we have f of x equals log base 1/3 of x, and then g of x equals log base 1/3 of -x, and then +1. So in terms of the transformation from f of x to g of x, I'm going to write g of x as being equal to, well, this would be f of -x. If I plug in a -x for x there, I would get this right here. Then you just have the +1. So what does f of -x do? Remember, that's now a reflection across the y-axis. So in order to get the same y value, when you have f of -x, you need the opposite x value because you need to multiply by this negative here, or -1. So basically coming down here, let's go ahead and say that we are going to reflect, or I'll put reflected across the y-axis now. And this +1 on the outside, that's just going to shift me up by 1 unit. So let me put shifted up by 1 unit. Okay, so once again, I made some tables here. I put fewer points in. I think we kind of get the idea. If you need more points, you could just go through and get them. But if you have f of x equals log base 1/3 of x, again, if you plug in a 1/3 for x there, log base 1/3 of 1/3 would be 1. So you get 1 for the y value. Then if you plug in a 1 for x, you get 0 for y. If you plug in a 3 for x, you get -1 for y. If you plug in a 9 for x, you get -2 for y. Now again, if you look at the graph here, which is going to be this guy in red, so f of x equals log base 1/3 of x, again, x cannot be 0 and it can't be negative. So this guy is drawn to where it approaches an x value of 0, or again, the y-axis, that's going to be a vertical asymptote, but it's not going to actually touch it. Now notice that this guy, again, is going to be decreasing over the entire domain. If we go back to this graph right here, f of x equals log base 2 of x, this is increasing over the entire domain. So that's something we talked about in the lesson. When this base right here is greater than 0 and less than 1, we're going to be decreasing over the entire domain. If that base right there is greater than 1, we're increasing over the entire domain. So that's something to keep in mind. All right, so as we look at the points, we have 1/3 comma 1. So we're just going to say this is about 1/3 right there, and this is 1. And then this right here is 1 comma 0. This is your 3 comma -1, and this is your 9 comma -2. Okay, so that's our graph right there. In terms of getting this right here, let me come back to the table and do it this way first. Remember that we are reflecting, so let me put REF, across the y-axis, and then we are shifting up by 1 unit. Let me put U1 for that. So in terms of reflecting across the y-axis, your x value will now be its opposite. So 1/3 turns into -1/3. 1 turns into -1. 3 turns into -3. 9 turns into -9. And then you're shifting your y value up by 1 unit. So 1 turns into 2, 0 goes to 1, -1 goes to 0, and -2 goes to -1. So let's go back to the graph and we'll do these individually, just in case you want to see it that way. So basically, if I start with this one right here, 1/3, 1, well, if I reflect across the y-axis, now I'm going to be, let's just say right here, hard to line it up because we don't have a notch. So basically you'd have -1/3, 1, and then you're shifting up by 1 unit. So that's going to be right there. So this is -1/3, 2 now. Then if you take this point right here, 1, 0, reflect across the y-axis, that's going to put me right there. So -1, 0, then I shift up by 1 unit, and that gives me that point right there, which is -1, 1. If I take this point right here, 3, -1, again, reflect across the y-axis. So that's going to put me right here. So it would be at -3, -1, and then shift up by 1 unit. That gets me right there, which is -3, 0. And then lastly, let's do this one. So we have 9, -2. I'm going to reflect across the y-axis. So I'm going to come way over here. That's going to be right here. So now I would have -9, -2, and then I'm going to shift up by 1 unit. That gets me that right there. So that's going to be -9, -1. Again, you can get more points if you need them, but I think this is enough to sketch both graphs. Okay, let's take a look at problem 13. So here we have f of x is equal to log base 2 of x, and then g of x is equal to 2 log base 2 of x plus 1, and then minus 2. Okay, so when we think about what's going on from f of x to g of x in terms of the transformation, again, I like to write things in terms of f of x. So you have, let's just start with g of x is equal to, let's go with the inside part first. So log base 2 of x is what we have here. Here we have log base 2 of x plus 1. So that would be f of x plus 1. You have this 2 that's multiplying that. So let me put that out in front. And then you have this minus 2 right here. Okay, so there's a few things that are going on. First, I'm going to start with this inside part here, this x plus 1. That is a shift to the left by 1 unit. Remember, if it's on the inside, it's always the opposite of what you're thinking. So this would be shifted. So shifted left by 1 unit. This one right here, this 2, that is multiplying this guy, that is giving me a vertical stretch by a factor of 2. So in terms of your y values, now you're multiplying them by 2. So that's all you're doing. So let's go ahead and say that there is a vertical stretch by a factor of 2. Then the last thing here is we're going to shift down by 2 units. That's what this minus 2 is going to do. So I'm going to put shifted, let me make this better here, down by 2 units. So again, you can make yourself a little table for each one. So f of x equals log base 2 of x. We did that in the first problem where we started this, so problem number 11. So we already know these points here. So for the x value of 1, we get a y value of 0. For an x value of 2, we get a y value of 1. For an x value of 4, we get a y value of 2. And then for an x value of 8, we get a y value of 30. So we know these points already, and we already know what this graph looks like. So here's my f of x equals log base 2 of x. So this guy in red. So again, it's going to approach where the x value is 0 or the y-axis. That's going to be a vertical asymptote because x cannot be 0 and it can't be negative. Then you have this point right here, which is 1, 0. That's actually going to be on both of these. You have 2, 1, 4, 2, 8, 3. We know we have 16, 4, and again, we can make more points if we need them, but this is enough for right now. So coming back, let's again think about what's going on. So we have this shift to the left by 1 unit. So I'm going to put L1, and then we have a vertical stretch. Let me put VS for that, by a factor of 2. And then we're going to shift down by 2 units. So I'm going to put D2. So when we think about the shift to the left by 1 unit, that's straightforward. The x values will just decrease by 1. So you have 1 here, 0 here, 2 here, 1 here, 4 here, 3 here, 8 here, 7 here. Very straightforward. These 2 steps here, that's going to create a little bit of confusion. Basically, you're multiplying the y value by 2 first, and then after you've done that, you're going to subtract away 2. So if I multiply 0 by 2, I still have 0. If I subtract 2 away, now I have negative 2. If I multiply 1 by 2, I get 2. Subtract 2 away, now I have 0. 2 times 2 is 4. 4 minus 2 is 2. 3 times 2 is 6. 6 minus 2 is 4. So that's where this is coming from in terms of the y values. So these 2 steps done in that order. Now, if you want, again, we could just go to the graph and look at each point and say, well, if I start with this one right here, which is 1, 0, well, I know that I'm going to shift 1 unit to the left. So let's say that puts me right there temporarily. Now I'm going to multiply that y value, which in this case I'd be at the origin, right? I'd be at 0, 0. So I'd multiply that by 2. Well, 0 times 2 is still 0. Then I'm going to shift down by 2 units, so I'm going to subtract away 2 from the y value. So that puts me right there at 0, -2. So then if I look at this point 2, 1, again, I'm going to shift 1 unit to the left. So that's going to put me right there. And then I'm going to multiply that y value by 2. So basically 1 times 2 would be 2. So that's going to put me up here. Now at this point, I'm going to shift down by 2 units. So I'm going to go down right there, and this color is going to match, but I'm just going to go over it anyway. So it would put me at 1, 0. Okay, when I look at this point right here, 4, 2, again, I'm going to shift 1 unit to the left. So that's going to put me right there at 3, 2. I'm going to multiply that y coordinate of 2 by 2. So that would put me up here at 3, 4. Let me put this in here. This one's a little bit confusing. And then at this point, you're going to subtract 2 away from that 4 because you're shifting down by 2 units, and that's going to put me right there. Okay, let's move on to the next one. So now we have this 8, 3. Again, I'm going to shift 1 unit to the left. So that's going to put me right there. So now it would be at 7, 3. And then I'm going to multiply that y value of 3 by 2. So that's going to put me off my graph. Let's just say it's right there. Let's just say this right here. I'm just going to arrow to it. That would be 7, 6. We're just going to be there temporarily. Then we're going to shift down by 2 units. So we're going to take 6 and subtract away 2 from that. And that's going to put me at that point right there, which is 7, 4. Again, if you need more points to draw either one of these, feel free to add them in. But once you know the basic shape of your logarithmic graphs, you really don't need that many points to sketch something that's fairly accurate. All right, now let's change up the instructions again, and we're asked to find the domain. All right, for problem 14, we have f of x equals log base 5 of x squared plus x minus 20. So if you want to find the domain, remember that your argument for the logarithm needs to be positive. It cannot be 0, and it cannot be negative. So what we're going to do is say that x squared plus x minus 20 must be greater than 0. So you could go to Desmos and just make a sketch of y equals x squared plus x minus 20 and just look for where it's greater than 0. So in other words, for which x values am I getting y values that are greater than 0, or where am I above the x-axis in terms of the graph? But you can also solve it the old-fashioned way. So what we can do is just factor the left side here and say this is x and this is x. So this is a 1 here. So I need 2 integers that sum to 1 and give me a product of -20. That's really easy. It's going to be +5 and -4. So if you solve the related equation, so in other words, if you solve x plus 5, this quantity, times the quantity x minus 4, and you want to know where that's equal to 0, so you can get your critical values, where you do x plus 5 and set that equal to 0, you get x equals -5. So -5 is a critical value. And then you put x minus 4, you set that equal to 0, you get x is equal to 4, so that's another critical value. Let's put that like that. And basically you can just test. And you can do this really quickly. So things to the left of -5, is that going to work? Well, if I think about something like, let's just say -6, -6 plus 5, that's -1. So this is negative. And then -6 minus 4, that's -10. So this is negative. Negative times negative is a positive, so that's going to be greater than 0. So this would be a T for true. Then if I think about between -5 and 4, we could pick 0. 0 plus 5 is 5, so that's positive. And then 0 minus 4 is -4, so that's negative. Positive times negative is negative. A negative is not greater than 0, so this would be false. Will not work. Then anything to the right of 4, that's of course going to work. Let's say you choose 5. 5 plus 5 is 10, that's positive. And then 5 minus 4 would be 1, that's positive. Positive times positive is positive, so that's always going to be greater than 0, so this is true. Okay, let me get rid of this, and we can just write our solution here. So we know that x is strictly less than -5. Remember, this is a strict inequality, so you're not going to put less than or equal to there. You want strictly less than. Then you're going to say the keyword or. You would say that x is greater than 4. Again, strict inequality here. So let me grab this real quick, and let me come back up here and just paste this in. So just solving this part right here, saying this is greater than 0, you get this right here. So what I'm going to do is write this out as a domain statement. So let me write that the domain, you could write it like this if you wanted to. So another way you could list this, you could do it in interval notation. Some teachers like it that way. So we're going to go from -infinity going up to and excluding -5. So we're going to use a parenthesis with -5 because it's excluded. And then you want the union with, you want anything greater than 4. So 4 is not included. Make sure you use a parenthesis there. This is going out to positive infinity. Then you can use your set builder notation. So if you want to do it that way, let me change the color up. I'll use this color here. So you could do the set of all x such that, and you just put this in here. So I'm going to go x is less than -5, or x could be greater than 4. So these are 3 different ways that you could write this. Now you can also go to Desmos and just verify this graphically. So you can key in f of x equals log base 5 of x squared plus x minus 20 and just look at the domain. So here you can see that for x values that are strictly less than -5, you'd be okay. And then here you can see that also for any x value that's greater than 4, you'd be okay. So let me write out another way to do this graphically for your domain. Well, this piece right here is where x is anything less than -5. Can't be -5 itself. So it would be x is strictly less than -5. Then or this piece right here, this is where x is strictly greater than 4. Again, can't be 4 itself. So x is greater than 4. Okay, for problem 15, now we have f of x equals log base 2 of x cubed plus 3x squared minus x and then minus 3. Okay, so thinking about this guy again, you want your argument here, which is this guy right here, to be positive. So it can't be 0 and it can't be negative. So we'll set up x cubed and then plus 3x squared and then minus x and then minus 3. We want to know where is this greater than 0. Let me make this better here. And let me grab this real quick. And let me come down here and paste this in. Now, you don't have to do it this way. I'm going to do it the slow way. You could do this graphically. So you can go to Desmos and just type in y equals x cubed plus 3x squared minus x minus 3. And you're looking for where this guy is greater than 0. So give me all the x values for which the y values are greater than 0 or we are above the x-axis. So you want this piece of the graph right here. This piece of the graph right here. And then you want this piece of the graph right here. So basically from Desmos or any graphing software, you could say that x would be greater than -3 and less than -1. So that's this piece right here. Or you would say that x is greater than 1. So that's the quick way to do it if you want to use a graphing calculator. Alternatively, we can just do it the slow way, just in case you want to see that or your teacher makes you do it that way. Essentially, you would factor the left side. Now, in this particular case, you can actually factor this using grouping. So I'm going to pull out an x squared from the first guy. That would give me x plus 3. And the second group, I'm going to pull out a -1. That would give me x plus 3. And let me put for right now that this equals 0. We'll change it back in a moment. So if we factor out the common binomial factor, what you're going to end up with is this quantity x plus 3. And then times the quantity, you would have x squared and then minus 1. And of course, this can be further factored. X squared minus 1 is x plus 1 times x minus 1. So let me put this equals 0. And I'm going to slide down here and do this on a different step. So x plus 3 times the quantity x plus 1 times the quantity x minus 1. And this equals 0. Okay, let me copy this. So x plus 3 times x plus 1. And then you have x minus 1. So those 3 quantities. Where is this greater than 0? Well, basically, you're going to solve this equation to get the critical values. So you're going to set x plus 3 equal to 0. You solve that, you get x equals -3. That's this guy right here. You get x plus 1, you set that equal to 0. You solve that, you get x equals -1. That guy right there. Then you put x minus 1, set that equal to 0. You get x equals 1, so that guy right there. We already know, because we looked at the graph, that the solution is going to be this guy right here and then this guy right here. So in other words, let me do this in a different color. This right here would solve that inequality. That would be your solution. But let's see if we can find this algebraically. Let me back out of these. Now, if you pick something to the left of -3, so you could pick -4, for example, if you plug that in each case, you're going to get a negative. So you'd have a negative, and a negative. So negative times negative times negative. You have 3 negatives. That's going to give you a negative, so that's not going to be greater than 0. So this right here, I'm going to put an F for false. Then between -3 and -1, that's where it's going to work. So what's going to happen is, let's just say you pick -2. Well, -2 plus 3 is +1. So this is positive. And then these are both going to be negative. -2 plus 1 is going to be -1. So this is negative. And then -2 minus 1 is -3. So this is negative. Negative times negative is positive. Positive times positive is positive. So this is true, right? A positive is going to be greater than 0. Let me get rid of this. And now here, in this region, you could pick 0. So that's between -1 and +1. Well, this would be positive, this would be positive, and this would be negative, right? 0 minus 1 is negative 1. So positive times negative is negative. A negative is not greater than 0, so this is false. This is not going to work. Then if you pick something that's greater than 1, well, it's going to be positive everywhere. So in other words, if you pick something like 2, this would be positive, this would be positive, and then this would be positive. 2 minus 1 is 1. So positive times positive times positive is a positive, so this would work. So this would be T for true. So algebraically, we can find that x is strictly greater than negative 3 and less than negative 1, or x could be greater than 1. So this is what we want. Let me grab this real quick, come back up here. So this would be your domain. Again, if you want to write it like this is fine. So this is the domain, and then you can also do it in interval notation. So if you want to write it that way, we can say this right here, you'd have negative 3 to negative 1 with both being excluded, and then you have the union with anything that's larger than 1. Again, 1 would be excluded. If you want to write this in set builder notation, let's do that. So let's put the domain here like this. So we would have the set of all x such that you're just going to drop this in here. So x is greater than negative 3 and less than negative 1, or x could be anything that's greater than 1. So that's how you would write that in set builder notation. Okay, so it's a good idea to go to Desmos and just verify this graphically. So here's your f of x equals log base 2 of x cubed plus 3x squared minus x minus 3. And again, for the domain, if you look at the graph, let me write out domain here. You're going to have this part right here, which is between negative 3 and negative 1. Both would be excluded. So let's say that x is greater than negative 3 and less than negative 1. Again, that's this right here. And then you'd also have, let me write the keyword or here, anything that's greater than 1. So it can't be 1 itself, but anything greater than 1, that's this piece of the graph right here. So x is greater than 1. All right, let's take a look at the practice test. For the instructions, we're asked to expand each. Okay, so before we get started, I want to revisit the properties of logarithms that we talked about in the lesson. So I have some restrictions here. These are going to apply to these properties that we're going to talk about. So we're saying that x is greater than 0, y is greater than 0, a is greater than 0, and a is also not equal to 1. And then we're going to say that r is an element of the set of real numbers, just meaning that r is any real number. So let's start with our product property for logarithms. Some people call this the product rule for logarithms. And basically it goes like this. You have log base a of x, y is equal to, you're going to say this is log base a of x plus log base a of y. So you can go from this form to this form, or from this form to this form. So if you're expanding, you're going to go this way. If you're condensing, you're going to go this way. So just depending on what the problem says. Now, the next one is called the quotient property for logarithms, or you might hear it again called the quotient rule for logarithms. And that one goes like this. You have log base a of x over y. Let me make this a little bit better there. And this is equal to log base a of x. Then there's a minus. You're going to have log base a of y. So again, if you're asked to expand, you're going to go from this to this. If you're asked to condense, you're going to go from this to this. Now, the last property is called the power property or the power rule for logarithms. So you'll see something like this. Let's say you have log base a of x to the power of r. Well, this r can come out in front and multiply that logarithm. So in other words, you would say this is r times log base a of x. So if we're expanding, we're going this way, and if we're condensing, we're going this way. So you might want to write these properties down for your notes and try to solve these problems with me as you go, but these are the rules or the properties that I'm going to use. All right, let's take a look at the first problem. Again, we're asked to expand here. So we have log base 5 of, you have this x to the 4th power over y cubed. So the first thing I'm thinking about here is the quotient rule for logarithms. So let me put that this is equal to, and I'm just going to slide down a little bit, and I'm going to say that this is log base 5 of x to the 4th power, and then minus log base 5 of this y cubed. So that's just using our property that we just talked about. Now, there's more that you can actually do here. If you're asked to expand, notice that you have an exponent here and an exponent here. Again, with your power rule, you can bring that out in front. So what we'll do to finish things up is say this is equal to, let me slide down here just a little bit. I will say this is 4 times log base 5 of x. and then minus, again, this comes out in front. So this is 3 times your log base 5 of y. All right, for problem 2, we're given log base 2 of 12 cubed times 7 to the 4th power. Again, we're looking to expand here. So the first thing, because we see multiplication here, we're thinking about our product rule for logarithms. So I'm going to say I have the log base 2 of this first factor, so 12 cubed, and then plus, I'm going to go log base 2 of the second factor is 7 to the 4th power. Now we're not done because we can use our power rule for logarithms. You have an exponent of a 3 there and an exponent of a 4 there. So again, those can come out in front as multiplication. So let me put 3, and for emphasis, let me go times log base 2 of 12. Of course, you could just write this as 3 log base 2 of 12 if you want. But for right now, let me just put the multiplication symbol in there so it's crystal clear. And then we go plus. Again, this can come out in front as multiplication. So 4 times log base 2 of 7. Now, this right here is a perfectly acceptable answer. If you got this as a test question, you can stop here. If you were to plug this into an online calculator, you might get this as an answer, or you might get something different. So let me cover this in case you're curious, or also maybe your teacher will tell you that you have to go all the way down. So sometimes they'll tell you to do that. So you think about 12. 12 is not a prime number. It is 2 times 2 times 3. 7 is a prime number, so you really can't do anything with that. But this one right here is what we're going to focus on. So we could say, let me just rewrite this. So 3 log base 2 of, instead of 12, I'm going to write this as 2 squared times 3, and then plus 4 log base 2 of 7. So you see that you can actually use your product rule here to expand this further and say that this is 3, and here's where you have to use parentheses. So I'm going to put this here. So you have your log base 2 of, this would be 2 squared, and then plus log base 2 of 3. Let me close that down and close these down. Now, why did I say you have to use parentheses here? You have to realize that this 3 is multiplying this guy right here. So this log base 2 of 2 squared times 3. So when you expand this 3 needs to be distributed to each guy. So that's why I'm putting the parentheses there. That's the best way to ensure that the 3 is going to multiply each term. Then let's put plus 4 log base 2 of 7. Okay, let's put equals here. Again, I'm going to distribute this 3 to each guy inside the parentheses. So this is 3 log base 2 of 2 squared. And then plus, you're going to have 3 log base 2 of 3. And then plus 4 log base 2 of 7. Okay, let's keep going down here. Now, we can bring this out in front, again, as multiplication. So let's bring that out like that. And so this would be equal to 2 times, you have 3 log base 2 of 2, and then plus 3 log base 2 of 3, and then plus 4 log base 2 of 7. So first, 2 times 3 is 6, so let's just write that. And this right here is something we should know. Log base 2 of 2 is equal to 1. Why is it equal to 1? Because 2 to the first power gives me 2. So this, you could put times 1 if you want, but of course that's just 6, so you can leave it off. And then you have plus your 3 log base 2 of 3, and then plus 4 log base 2 of 7. So if you want to give this as an answer, that's acceptable, or the other answer we came up with, that's acceptable. Some teachers will actually make you go through all of this just to get this final form, but a lot of them will stop where we initially stopped. So really just get with your teacher if you're in a course, but if you're self-studying, you would just know that you can answer the first way or the second way. Either one is going to be perfectly acceptable. Okay, for problem 3, now we have log base 7 of, we have z squared times the square root of x. So what I'm going to do is first rewrite the square root of x as x to the 1/2 power. So let's say this is log base 7 of, let's go z squared times, I'm going to write this as x to the power of 1/2, like that, and then close this down, and we'll say this equals. At this point, again, I'm going to use my product rule for logarithms, and I'm going to say that this is log base 7 of, I'll take this first factor, so that's z squared, and then plus, I'm going to go log base 7 of this second factor, which is x to the power of 1/2. Okay, at this point, because I'm expanding, I have this exponent here and I have this exponent here. So let's pull those out in front as multiplication. So let's say this equals, I'm going to have 2 times log base 7 of z, and then plus, this is going to come out in front. So I'll write 1/2 times log base 7 of x. Now, some people will write this over 2 instead of multiplying by 1/2. So if you want to do this like this, that's perfectly fine. That's how I listed the answer on the practice test. So I'm just going to keep it this way. But if you want to put the 1/2 out in front, it's correct either way. Okay, let's take a look at problem 4. So this one might be a little bit tricky because of this exponent of 5 here. We have log base 5 of, you're going to have this x and then times y cubed. And then this is raised to the 5th power. So this whole thing right here is your argument. So the first thing I would do is move this 5 out in front, again as multiplication, using your power rule for logarithms. So I'm going to say this is 5 times. To not make a mistake, I'm actually going to wrap this in parentheses. So log base 5 of x, y cubed. The reason I'm wrapping this in parentheses is that this 5 is multiplied by this guy right here. At this point, you don't need it. But what's going to happen is when we expand this using the product rule for logarithms, the 5 needs to go to each part. So let me show you what I mean by that. I'm going to write that this equals, I'm going to put my 5, and I'm going to wrap this in parentheses. So I'm going to say this is log base 5 of x. So that's your first factor. And then plus, you have log base 5 of, the second factor is y cubed. So let's write that in there. And then let's close down these parentheses. So if I write it this way, it's completely clear that the 5 needs to multiply by this and also this. Again, you don't have to put these in at this step, but I like to do it with students because it's very easy to make a mistake and just say that, okay, well, I just have 5 times this first guy and then forgetting about the second guy. So you want to put parentheses there to remind yourself of that. So that's why I just go ahead and put them in there. It's just very helpful. So let me go ahead and put this down here. And let's say that this is going to be equal to. So again, this 5 would basically be distributed to each guy inside the parentheses. So this is 5 times your log base 5 of x. And then plus this 5 gets distributed here. So this is 5 times your log base 5 of y cubed. Now to finish things up, you have an exponent of a 3 here. So you can bring that out in front, again as multiplication. So let's say this equals 5 times log base 5 of x, and then plus, again, if this is coming down here as multiplication, you're going to have 3 times 5, and then times your log base 5 of, now you just have y. So to finish this up, let's just say this equals 5, and then times your log base 5 of x, and then plus 3 times 5 is 15. So let's write 15 and then times your log base 5 of y. All right, now the instructions are going to change. We're asked to condense each now. And what we're given for problem 5 is 12 log base 4 of a. So then we have plus 4 log base 4 of b, and then plus 4 log base 4 of c. So if we think about how we can condense this, so we'll put it into one single logarithm. You'll notice here in the first place that you have a base of 4, a base of 4, and a base of 4. You also have this multiplication. Let me do this in a different color. So here and here and here. Again, for emphasis, let me do this on the first one so nobody's lost. This is 12 times log base 4 of a, and then plus 4 times log base 4 of b, and then plus 4 times log base 4 of c. Of course, generally speaking, we don't put the multiplication symbols in there. I'm just doing that for emphasis. Some of you might be confused when you see that number next to that logarithm guy there. So I want to make this crystal clear what's going on. So we know at this point that these guys can go back up. So using the power rule in reverse, in other words, this guy can go back up there as an exponent, this guy can go back up there as an exponent, and this guy can go back up there as an exponent. So let's say this is equal to log base 4 of, this is a to the power of 12, and then plus, you have log base 4 of, this is going to be b to the power of 4, and then plus, you have log base 4 of, this would be c to the power of 4. So just using your power rule in reverse. That's all we're doing. Let me come down here, and let's think about what the next step is. You have addition and addition, And again, this base is 4, this base is 4, and this base is 4. So what we can do is legally say this is log base 4 of, you have a to the 12th power times, you have b to the 4th power times, you have c to the 4th power. And again, you don't have to put the multiplication symbols in there. I like to do it for emphasis when I'm first starting out with somebody. So you could write this as log base 4 of a to the 12th power, and then b to the 4th power, and then c to the 4th power. And that's pretty much it in terms of condensing it. Okay, let's take a look at problem 6. So here we have log base 5 of x plus log base 5 of y plus log base 5 of w plus 2 log base 5 of z. So the first thing I'm doing here if I'm trying to condense is I'm going to move this back up. So let's say this equals, I'm just going to copy all this. So log base 5 of x plus log base 5 of y plus log base 5 of w, and then plus, again, this is coming back up, just using the power rule in reverse. So this is log base 5 of z, and that would be squared. Okay, at this point, you're going to notice that all the bases are the same. So 5, 5, 5, and 5, and you have addition here, and here, and here. So I'm just going to write this by saying I have log base 5 of, these are all going to be multiplied together. So you're going to have x, y, w, and then z squared. Again, you could put multiplication symbols in there if you want, but typically we don't do that. So this is log base 5 of x, y, w, z squared, and that would be your answer. All right, for problem 7, we have log base 4 of 12 plus 3 log base 4 of 5 plus log base 4 of 7 over 2. So the first thing I'm going to do, notice that here you're dividing by 2. You can change that into multiplication by 1/2. So let's write this equals log base 4 of 12 plus 3 log base 4 of 5 plus, again, I'm going to write this as 1/2, and then times your log base 4 of 7. Let me come down here real quick and just put that this is going to be equal to. What I'm going to do at this point, again, is use my power rule in reverse. So this is going to come up here, and this is going to come up here. So we're going to have log base 4 of 12 plus, this would be log base 4 of, you'd have 5. Again, this is coming up here as an exponent, so then cubed, and then plus, this is coming up here as an exponent, so log base 4 of 7 to the 1/2 power. We know that's the square root of 7, but for right now, I'm just going to write it like that. Okay, let's say this is equal to, at this point, again, if you look at everything, you have 4, 4, and 4 for the base. And then you have addition and addition. So what I'm going to do is use my product rule for logarithms and just say that this would be log base 4 of, you're going to have 12 times 5 cubed, and then times 7 to the 1/2 power, or you could put the square root of 7. Now, could you simplify this further? Yes, but generally speaking, on this type of problem, you wouldn't do that. You would leave it like this. You might, at the preference of your teacher, put this as a square root of 7. So let me just put that answer there in case you want to use that. So log base 4 of, I'm going to go 12 times 5 cubed, and then times, let's go the square root of 7 like that. So this is acceptable and this is acceptable. Again, if you want to multiply things together and make it a little bit more simple, you can do that if you want. But generally speaking, this is the acceptable answer, either this one or this one. Okay, let's move on and look at problem 8. Here we have 6 log base 6 of u minus log base 6 of w minus 2 log base 6 of v. This one is a little bit tricky because you have subtraction here and you have subtraction here. So this is what I'm going to tell you. This is what I always use with my tutoring students. I would factor that out so it's crystal clear what's going on. It might take more steps to do this, but you'll always get the right answer. So let me put that this is equal to, I'm going to go 6 log base 6 of u. And then again, I'm going to factor out the negative there. So in other words, I'm going to write a minus in front of, this will be log base 6 of w. And then again, if this is getting pulled out now, this is a plus. You'll have 2 log base 6 of v. And you probably shouldn't use u, w, and v in a problem because those get easily confused. But this is what we have. And then let me close this down here. Now, when you set this up, you always want to check it. So this negative being applied to this would give me this, and this negative being applied to this would give me this. So I haven't done anything illegal. So at this point, let me put equals. I'm going to move this up here. So just using my power rule for logarithms, again, in reverse. So this would be log base 6 of u to the 6th power. And then minus, again, inside the parentheses, we're going to have log base 6 of w. And then plus, I'm going to bring this up here. So I'm going to say this is log base 6 of, this is v squared. Let me close that down and close this down. Okay, so I'm going to deal with what's in the parentheses here first. So let me just copy this. I'm not going to do anything with it. So let me put log base 6 of this u to the 6th power. And then minus. So inside of here, I want you to notice that you have addition. And you have the same base of 6 here and here. So I'm just going to write that this is log base 6 of, you're going to have w times v squared. So just wv squared. Now, you can keep the parentheses here, but really you don't need them. You can just erase them. And now I want you to look at this and see how easy it is to understand what's going on. You see that you have a base of 6 here and a base of 6 here, and then you have subtraction. So what do? We're going to say, using the quotient rule for logarithms, that this is equal to log base 6 of, this will be in the numerator. So let's put this as u to the 6th power over, this will be in the denominator. So this is wv squared. So you can see how much easier it is to do this once you've factored things. If you don't want to do that, it's fine. You can still get the right answer, but I think it's a little bit more complicated to think about it that way. So this is what I recommend, especially if you're having trouble with these problems. All right, let's take a look at problem 9. Here we have 5 log base 2 of x plus 5 log base 2 of z minus 20 log base 2 of y. So let's put equals here. I'm just going to send these back up. So again, using my power rule for logarithms in reverse in each case. So that will go up there. So we'll say this is log base 2 of x to the 5th power plus log base 2 of z to the 5th power, and then minus log base 2 of y to the 20th power. Okay, at this point, what I would do is just say that we have addition here. Let's just do that first. Again, you have the same base here and here. You have addition. So let's combine that and just say with our product rule for logarithms that we have log base 2 of, you'd have x to the 5th power. Let me write times z to the 5th power, just so that's crystal clear. You don't need the multiplication symbol, but let me just put it in for right now. And then minus, we have this log base 2 of y to the 20th power. Okay, so again, when I look at this problem, I have a base of 2 and a base of 2, and I have subtraction. So all I'm going to do is say that I have log base 2 of, this would be my numerator, so x to the 5th power, z to the 5th power, over, this would be my denominator, so this is y to the 20th power down here. Maybe this could be a little bit bigger like that. And that would be your answer. So log base 2 of x to the 5th power, z to the 5th power, over this y to the 20th power. All right, let's take a look at problem 10. So here we have 4 log base 4 of x plus 4 log base 4 of z minus 20 log base 4 of y. All right, so what I'm going to do again is start things off by just moving these back up using the power rule for logarithms. So let's say this is log base 4 of x to the 4th power plus log base 4 of z to the 4th power minus log base 4 of y to the 20th power. So real easy problem at this point. Essentially, you have the same base here and here. And again, you have addition. So all we're going to do is use our product rule for logarithms and say this is log base 4 of, again, this will be multiplied by this. You can put a multiplication symbol in there if you want. So x to the 4th power times z to the 4th power. Again, not needed, just something I'm doing for emphasis. Then I'm going to do minus, you have log base 4 of y to the 20th power. Okay, sliding down here, again, we have a base of 4 and a base of 4, and then subtraction there. So let's say that this is equal to log base 4 of, this would be the numerator, so x to the 4th power, z to the 4th power, over, this would be your denominator, so y to the 20th power. And let's just close that down. Maybe this could be a little bit bigger there. So your answer is just log base 4 of x to the 4th power, z to the 4th power, over y to the 20th power. All right, let's take a look at the practice test. For the instructions, we're asked to find the inverse. All right, let's take a look at problem 1. So here we have f of x equals log base 3 of x cubed plus 2 and then plus 7. So to find the inverse, you would first replace f of x with y. So let's say this is y is equal to log base 3 of our x cubed plus 2, and then we have plus 7. So the next step is to interchange x and y. That basically just means to swap x and y. So I'm going to put this as an x. So this equals log base 3 of, this is going to be put as a y. So y cubed plus 2 and then plus 7. Okay, at this point we want to solve for y. So how do we do that? Well, you would want to isolate this guy right here first. So let's go ahead and subtract 7 away from each side of the equation. And of course, this would cancel. So on the left, you now have x minus 7. This equals, on the right, you have log base 3 of y cubed plus 2. So the next thing I'm going to do is put this into exponential form. So this would be your base, and then this right here would be your exponent. Let me set this up. So this is 3 as the base. The exponent is x minus 7. And this would be equal to this guy right here, the argument of your logarithm. So this would be y cubed plus 2. At this point, again, we're trying to solve for y. So let's subtract 2 away from each side of the equation. And let's say that this is 3 to the power of x minus 7. Let me make this 3 a little bit better there. And then we're going to have minus 2, and this equals y cubed. Let me show this as canceling here. Okay, let me come to a fresh sheet so we don't run out of room. And I'm actually going to rearrange this because I like what I'm solving for to be on the left. So let me write y cubed is equal to 3 to the power of x minus 7 and then minus 2. Since I have this exponent of 3 on y and I'm trying to solve for y, let's take the cube root of each side. So that would give me y is equal to the cube root of 3 to the power of x minus 7 and then minus 2. And make this 3 a little bit better there. So at this point, we're done. We just want to use our inverse notation. So let me slide down a little bit, and I'll just write the answer here and say the inverse, f inverse of x, like this, is equal to, again, your cube root of 3 to the power of x minus 7 and then minus 2. So we've previously discussed how you can check to see if you got the right answer. You can use function composition. So you can go f of g of x and see if that equals x. And then it also has to be true that g of f of x is equal to x. But that's very time consuming for these problems. So what I would recommend is actually just going to Desmos and just keying everything in and just seeing if it's going to be a reflection across the line y equals x. So I have a little snapshot for you. I do recommend you do this on your own, but I have y equals x here. That's going to be this line in, let's call it orange. I have the original function f of x equals log base 3 of x cubed plus 2 and then plus 7. That's going to be this guy in, let's just call it red. And then this guy right here in, let's call that green. This is your inverse, so f inverse of x is equal to the cube root of 3 to the power of x minus 7 and then minus 2. Again, you can clearly see that these guys are reflections across the line y equals x. So when you go to Desmos, that's what you're looking for to see if you got the right answer. Okay, for problem 2, we have f of x equals 7 log base 2 of x minus 3, and then we have minus 3. So the first thing I'm going to do is replace f of x with y. So y is equal to 7 log base 2 of x minus 3, and then minus 3. At this point, I'm going to interchange x and y, or again, swap x and y. So this is x is equal to 7 log base 2 of, now this would be y minus 3, and then minus 3. At this point, I want to solve for y. So how do I do that? Well, the first thing is to isolate this guy right here. So I would add 3 to both sides of the equation first. So let's go ahead and cancel that away. And on the left, you're going to have x plus 3, and this would be equal to your 7. For emphasis, let me put times log base 2 of this y minus 3. So see how you have 7 that's multiplying this guy? So you want to isolate this. So just divide both sides of the equation by 7. Let me get rid of this, and I'll divide over here by 7. And of course, this is going to cancel with this. And now what you're going to have is x plus 3 over 7 is equal to log base 2 of, you're going to have this y minus 3. Again, at this point, I'm going to put this in exponential form. So this right here would be your base. This right here would be your exponent. So 2 to the power of x plus 3 over 7. And this would be equal to this right here, your argument for that logarithm. So this is y minus 3. Okay, at this point, solving for y is extremely easy. Let me go ahead and come down here a little bit. And actually, I'm going to reorder this. Let me put y minus 3 on the left. And this equals 2 to the power of x plus 3 over 7. Let me actually slide this out of the way a little bit. Come down here. And at this point, all you need to do is add 3 to both sides of the equation. So that cancels. That 3 could be a lot better. And let's go ahead and say that y is equal to 2 to the power of x plus 3 over 7, and then plus 3. The last step is to use our inverse notation. So let's go ahead and say this is f inverse of x is equal to, again, 2 to the power of x plus 3 over 7, and then plus 3. So once again, I already have a little sketch for you. You can follow this on Desmos if you want. So this guy, and again, I'm just going to call this red. This is your original function. So f of x equals 7 log base 2 of x minus 3, and then minus 3. Then your guy in orange here, that's y equals x. And then your inverse is f inverse of x is equal to 2 to the power of x plus 3 over 7, and then plus 3. You can clearly see these guys are reflections across the line y equals x. So you can conclude that these guys are inverses. All right, let's take a look at problem 3. So here we have f of x is equal to log base 3 of negative 3x minus 6, and then minus 4. Okay, so let's start out by saying this is y is equal to our log base 3 of, you have negative 3x minus 6, and then you have minus 4. Now, to make this problem a little bit easier, what you could do to start things off, I want you to notice that you have a 3 here, and then 6 is really 3 times 2. So you could rewrite this and say this is y is equal to log base 3 of, let's pull out the 3, and then inside you'd have negative x and then minus 2. So let's close that down and then close this down and say this is minus 4. We know about the product rule for logarithms. So legally, we can say this is y is equal to log base 3 of, this factor here is 3, and then plus, this would be log base 3 of, this factor right here is negative x minus 2. Let's close that down and then say minus 4. We know at this point, or at least we should know, that log base 3 of 3 is equal to 1, because this is 3 to what power gives me 3, and the answer is 1. So that's why log base 3 of 3 is 1, but pretty much all of you will know that at this point. So let's say this is y is equal to, let's go 1 plus log base 3 of negative x minus 2, and then minus 4. And of course, if you do 1 minus 4, that's negative 3. So let's go ahead and say that this is y is equal to log base 3 of negative x minus 2, and then minus 3. Okay, at this point, we're going to swap x and y. So let's say that x is equal to log base 3 of, this would be negative y minus 2, and then minus 3. And let's think about what we can do to solve for y. Again, this is the goal right here. So the first thing is I would want to isolate this right here. And to do that, let's add 3 to both sides of the equation. And let's say that we have x plus 3. Let me cancel this away. So this would be equal to log base 3 of negative y minus 2. And now I'm going to put this in exponential form. So this would be your base, and then this would be your exponent. So 3 to the power of x plus 3. This would be equal to this argument here for this logarithm, so negative y minus 2. Let me write this as negative y minus 2. Again, I like what I'm solving for to be on the left. So this equals 3 to the power of x plus 3. I'm going to add 2 to both sides of the equation. So this is going to cancel. You'll have negative y is equal to 3 to the power of x plus 3, and then plus 2. And then the last thing here, you have this negative y, and you want y. So you can just multiply both sides by negative 1. So let me just put that y would be equal to, this would be the negative of 3 to the power of x plus 3, and then minus 2. So basically, that's all there is to it. You're just going to use your inverse notation at this point. So let's say this is f inverse of x is equal to, again, the negative of 3 raised to the power of x plus 3, and then minus 2. All right, so looking at the graph, again, we can clearly see these guys are reflections across the line y equals x. So you can do this on Desmos. Again, the guy in red here, that's your original function. So that's this guy right here. So f of x equals your log base 3 of negative 3x minus 6 and then minus 4. Again, if you want to rewrite it like we did earlier, you can type it in that way. You'll get the same thing. And then this guy in green, this is your inverse. So f inverse of x is equal to the negative of 3 to the power of x plus 3 and then minus 2. So again, you can play around with this on Desmos. You'll see that there are reflections across the line, y equals x, and so they are inverses. Okay, let's take a look at problem 4. So here we have f of x is equal to, we have 4 to the power of x plus 4 over 4, and this is raised to the 1/4 power, or you could really say that you're taking the 4th root of that. So let's come down here, and again, start with our regular procedure. So let's say that y is equal to, you can go 4 to the power of x plus 4 over 4, and this is raised to the 1/4 power. At this point, you want to swap x and y. So let's go ahead and say that this y would be x, and this equals, you're going to have 4 to the power of y plus 4 over 4 raised to the 1/4 power. Now, if I want to get y by itself or solve for y, you've got to get rid of this exponent of 1/4. So to do that, I'm going to raise both sides to the 4th power. So let's say that this is x to the 4th power is equal to, again, if I raise this, let me actually show this fully. If I raise this 4 to the power of y plus 4 over 4, and this is to the 1/4 power, and again, I'm raising this to the 4th power here. Well, from the power to power rule, you're going to multiply these exponents, and 1/4 times 4 is going to be 1. Basically, you can just show this as x to the 4th power is equal to, you would just take what's inside the parentheses here, so 4 to the power of y plus 4 over 4. So you can multiply both sides by 4. So let me show that as multiplying by 4 over here and also over here. So this cancels. You're going to get 4x to the 4th power is equal to 4 to the power of y and then plus 4. At this point, I'm going to subtract 4 away from each side of the equation. That cancels. Let me slide down here a little bit. You're going to end up with 4x to the 4th power minus 4 is equal to 4 to the power of y. Let me put this on this side. So let me put it like this, just because I like what I'm solving for to be on the left. And what I would do here is take log base 4 of each side. So the reason I'm choosing that is because you have a base here of 4. And so log base 4 of 4 would be 1. And so you'll just be left with y there. So let's go log base 4 of 4 to the power of y is equal to log base 4 of 4x to the 4th power minus 4. We know from the power rule for logarithms, this can come out in front. So you would have y times log base 4 of 4, which of course this is 1. I'll just cancel this out right now and just say this is 1. And this equals log base 4 of 4x to the 4th power minus 4. Let me slide down here a little bit. And let me put that we have y is equal to log base 4 of 4x to the 4th power minus 4. Is this the inverse? No. And the reason it's not is because you're looking at this to the 4th power here. That's going to create something that's not 1-to-1. If you were to go to Desmos and sketch this graph, I just do it with g of x. So g of x equals log base 4 of 4x to the 4th power minus 4. This does not pass the horizontal line test. What you actually want is this piece of the graph right here. So the guy on the right, you're going to want to say where x is greater than 1. Now, how do I know that x is greater than 1? Where does that come from? So let's come back to the original function and went ahead and sketched a graph for this. Again, you could do this on Desmos. So f of x equals, you have this 4 to the power of x plus 4 over 4, and this is raised to the 1/4 power. Or again, you could take the 4th root of this guy inside the parentheses. It's going to give you the same graph. Okay, so looking at this, you should be able to see that y is greater than 1. Now, if you're on Desmos and you mouse over this, because of the way they approximate things, you might actually get a y value of 1, but that's not actually true. This guy can never actually be 1 in terms of the y values. To think about y, let's just start with the domain. What can I plug in there for x? I just have 4 to the power of x. Can I plug in a negative? Yes. Can I plug in 0? Yes. Can I plug in a positive? Yes. But the result of this, when I think about 4 to the power of x, remember that's always going to be positive. It can't be 0 and it can't be negative. So when you think about making these x values very, very large, what's happening is this 4 to the power of x is getting very large, and then you're adding 4 and dividing by 4 and then taking the 4th root of that. So you can make y as large as you want. This is going to go out to positive infinity. But when you think about x going the other way, So let's say we're approaching negative infinity. Let's think about what's going on there. So as x approaches negative infinity, this 4 to the power of x is basically going to approach 0. You can't actually get to 0, but you can get as close as you would like. So let's just pretend that that was 0 for a moment. What would you have? You would have 0 plus 4, which is 4, over 4, which is 1, and the fourth root of 1 would be 1. But we can't actually get to 1 because, again, this can't actually be 0. But I can get it as close to 0 as I would like without touching it, which means that I can get this guy right here, this function, f of x, as close to 1 as I would like without touching it. So that gives me a range here where y is going to be greater than 1. So when we go to the inverse, again, the domain becomes the range, and the range here, y is greater than 1, becomes the domain. So you'll see that x is greater than 1 in the inverse. So when we come back, we just put a little comma, and we say specifically that x is greater than 1. We don't want that left piece, we want the piece on the right. So let's go ahead and say that it's f inverse of x is equal to log base 4 of 4x to the fourth power minus 4, and this is for x is greater than 1. You absolutely need this to get the correct answer, otherwise you're putting something in that is not a one-to-one function. You have to restrict the domain here to match the range of which we're finding the inverse of. All right, so again, we can always check this on Desmos. My guy in red is the original function. So f of x equals, again, 4 to the power of x plus 4 over 4. This is raised to the 1/4 power, or you could say it's the fourth root of this. Then my guy in orange is y equals x. And my inverse is f inverse of x is equal to log base 4 of 4x to the fourth power minus 4. But again, you've got to put this x is greater than 1 in there. Otherwise, this is not going to work out. You only want this piece of the graph. You do not want that piece over there. If you put that piece over there in, it's not going to be the correct answer. And if you're trying to type this into Desmos and you're having a hard time, it doesn't take commas at this present time, which you have to do if you want to put in a restriction for the domain. You put in some curly braces and you put x is greater than 1 after your function. It also doesn't take f inverse of x notation. I probably should have mentioned that earlier. You can put in g of x if you want. That's what I usually do. So I'll put g of x equals log base 4 of 4x to the fourth power minus 4. And then you open up these curly braces and you can throw in x is greater than 1. And that's going to give you this part right here. And again, you can see these guys are reflections across the line, y equals x. If you don't put this in here, you're going to see that other part, and that's not going to match up with what we know about inverses. So this is what you want right here. All right, let's take a look at problem 5. So here we have f of x is equal to 4 to the power of x minus 2 over negative 4, and this is raised to the 1/4 power. So let's say we have y is equal to 4 to the power of x minus 2 over negative 4, and this is raised to the power of 1/4. Again, if you want to take the fourth root of that, that's fine as well. Let me slide down here, and now we're going to swap x and y. So let's say that we have x is equal to, we have 4 to the power of y minus 2 over negative 4. And again, this is raised to the 1/4 power. So I'm trying to solve for y. So I really want to undo this exponent of 1/4. So what I'm going to do is raise both sides to the fourth power. Let's go ahead and say we have x to the fourth power is equal to, again, let me copy this, 4 to the power of y minus 2 over negative 4. And this is raised to the 1/4 power. And then what we're going to do is raise this whole thing. Let me make that a little bit better there. So to the fourth power here. So by the power to power rule, you do 1/4 times 4, which is 1. So you're just going to be left with what's inside the parentheses there. Let me slide down and just say that we're going to have x to the fourth power is equal to, this would be 4 to the power of y minus 2 over negative 4. We want to solve for y. So let's go ahead and multiply both sides by negative 4. And I'm going to show that this right here would cancel with this right here. I'm going to flip things around because I want what I'm solving for on the left. So let me write 4 to the power of y minus 2 is equal to negative 4 x to the fourth power. At this point, I'm just going to add 2 to both sides of the equation. And so this is going to cancel. And what you're going to have is 4 to the power of y is equal to negative 4 x to the fourth power plus 2. So to solve for y here, let's take log base 4 of 4 to the power of y and say this is equal to log base 4 of negative 4x to the fourth power plus 2. Now, why did I choose log base 4? Well, that's because log base 4 of 4 is 1. So what we'll do is first use the power rule for logarithms. This comes out in front as multiplication. So we're going to say y times log base 4 of 4 and log base 4 of 4, again, is going to be 1. So this equals log base 4 of negative 4x to the 4th power plus 2. So let's say we have y is equal to log base 4 of negative 4x to the 4th power plus 2. Is this your inverse? No. This x to the 4th power is going to create a problem for you. It's not going to give you something that's 1-to-1. If you were to key this into Desmos as, let's say, g of x equals log base 4 of negative 4x to the 4th power plus 2, I want you to notice that you get something that's not 1-to-1. What you actually want is this piece of the graph right here. So this rightmost piece right here. And if we want to think about the domain of this guy, well, it's probably best to come back up here to the original function we were working with. Remember, when you find the inverse, the domain becomes the range and the range becomes the domain. So here we're really concerned with the range because that's going to become our domain. So let's think about this point right here and where that's coming from. This is actually going to be the point 1/2, 0. If I plug in a 1/2 there for x, 4 to the power of 1/2, that's the square root of 4, so that's 2. 2 minus 2 would be 0. 0 over negative 4 is 0, and then the 4th root of 0, or you could say 0 to the 1/4 power, same thing either way, is 0. So that's where this point is coming from. Now, why don't we see any x values to the right of 1/2? Well, that's because you would end up with something in the numerator that's positive, and the denominator is negative, so positive over negative is negative, and this right here is the 4th root. So the 4th root of 4 to the power of x minus 2 over negative 4. So you can't take the 4th root of a negative in the real number system. So that's why you don't see any x values that are to the right of 1/2. So they can be 1/2 or anything less. Now, when we think about what happens as x gets closer and closer to negative infinity. So as x approaches negative infinity, what's happening here? Well, 4 to the power of x is actually going to get very, very close to 0. So as we get closer and closer to 0, what's happening is the inside of this is just going to be closer and closer to negative 2 over negative 4, which is 1/2. So just think about it like this. As x approaches negative infinity, so as we go this way, basically this guy is going to approach the 4th root of 1/2, which would be equal to the 4th root of 1 over the 4th root of 2. And of course, this would just be 1 over the 4th root of 2. Let me make this a little bit better. So 1 over the 4th root of 2. Now, typically, you will rationalize the denominator there. So what you would do is multiply by the 4th root of 8 over the 4th root of 8. Now, why am I multiplying by the 4th root of 8 and not the 4th root of 2? Remember that if you did it like this, so let's say this is a common mistake. Let's say you did this and you did this. Well, this would give you the 4th root of 4, and that's not really going to do anything. That's not going to rationalize the denominator. You need something that's a perfect 4th. So that's why I'm picking 8 there as the radicand, because 2 times 8 is going to be 16, and the 4th root of 16 is 2. So this would be equal to the 4th root of 8 over, this would be, again, the 4th root of 16, which is 2. So what we can say is that as the x values approach negative infinity, the y values are going to approach, but never touch, the 4th root of 8 over 2. Now, I have that written out for you already. This is in the practice test if you're taking it that way. So the range is the set of all y, such that y is greater than or equal to 0, so it can be 0, and less than, strictly less than, the 4th root of 8 over 2. It can never actually be the 4th root of 8 over 2 because that 4 to the power of x part can never be 0. It's always going to be something that's positive. Even though it can be something that's very, very close to 0, it can never actually be 0. Now, another way you can look at this, again, if you come back here, knowing your domain that you're going to work with, so x is greater than or equal to 0 and less than your 4th root of 8 over 2. Again, all you'd have to do is plug in the 4th root of 8 over 2 for x right there, and you see that this guy would be 0. So that's not allowed. So basically it would have to be something in this interval right here. It's got to be greater than or equal to 0 and less than the 4th root of 8 over 2. If you put something in here that's greater than the 4th root of 8 over 2, you're going to get something here that's negative. And again, you can't have 0 or a negative for the argument for your logarithm. It's got to be something that's positive. So let's go ahead and grab this. This is going to be the domain. Again, that's coming from the range from the original function. So I'm just going to put a comma, and let me move this down here so I can fit this all the way in there and paste that in. So that's going to be your restriction there. So let's say f inverse of x is equal to, let's say log base 4 of negative 4x to the 4th power plus 2. And this would be true for x is greater than or equal to 0 and less than the 4th root of 8 over 2. All right, so once again, you can go to Desmos and just key this stuff in and really look at it. So we have our line y equals x in orange. The original function, so that's going to be this guy right here. This is your f of x equals 4 to the power of x minus 2 over negative 4. This is raised to the 1/4 power. And this guy in green, this is your inverse. So f inverse of x is equal to log base 4 of negative 4x to the 4th power plus 2. And again, we only want this piece right here. We do not want the piece over here that is not involved in the inverse. So for that piece, we're saying that x is greater than or equal to 0 and less than the 4th root of 8 over 2. All right, let's take a look at problem 6 now. So we have f of x is equal to negative 1 over, you have 2 to the power of x plus 2. Now for this one, I've had quite a few people ask where the solution came from in terms of the practice tests. So I'm going to show you 2 different ways to do this one. I just want you to remember in this section, you can get something that looks different and it will still be correct. There's different ways to write your logarithm. So let's go ahead and say that we're going to start with y is equal to negative 1 over 2 to the power of x plus 2. And then we're going to swap our x and y. So let's say x is equal to negative 1 over, you have 2 to the power of y plus 2. Okay, so what I'm going to do is multiply both sides by negative 1, and that would just make this over here negative x, and this equals, over here, this would just be positive 1 over 2 to the power of y plus 2. Now, here's where we're going to stop, and we're going to think about our rules for exponents. We know that something like 1 raised to some real number, let's just call it a for right now. So a is just some real number. This is always going to be equal to 1. So 1 raised to a positive number is 1, 1 raised to 0 is 1, 1 raised to a negative number is 1. So as long as a is some real number, we're going to say 1 raised to the power of a is 1. So what we're going to do here is use that rule, and let's just go ahead and say that 1 would be the same as 1 raised to the power of y plus 2. So what I can do at this point is just say that it's negative x is equal to, using the rules of exponents, you write this as 1/2 for the base, and this would be raised to the power of y plus 2. Because again, this would be 1 raised to the power of y plus 2 over 2 raised to the power of y plus 2. And again, 1 raised to the power of y plus 2 is just 1. So I haven't done anything illegal. We're just rewriting things. I am going to rearrange this first. Let me put this 1/2 here. This is raised to the power of y plus 2. And this is equal to negative x. So what I'm going to do, since I want to solve for y, I'm going to take log base 1/2 of each side. Again, log base 1/2 of 1/2 is 1. So let's say that this is log base 1/2 of, you're going to have this 1/2 raised to the power of y plus 2. And this would be equal to log base 1/2 of our negative x. Now, from the power rule for logarithms, this can again come out in front as multiplication. I'm going to write this as the quantity y plus 2, and that is multiplying this log base 1/2 of 1/2, and this equals log base 1/2 of negative x. We know that this right here would cancel and give me 1, so really I can just drop the parentheses here and say this is y plus 2 is equal to your log base 1/2 of negative x. Now at this point, I'm going to subtract 2 away from each side of the equation. This cancels, and you get y is equal to log base 1/2 of negative x. And then instead of minus 2, I'm just going to write plus negative 2. You're going to see why in a moment. You'll notice that the answer I gave on the practice test was f inverse of x is equal to log base 1/2 of negative 4x. Now, how do you get this from this? Let me erase this real quick. We'll get back to it in a moment. Essentially, you're going to think about how I could write negative 2 using a logarithm with a base of 1/2. And then once you've accomplished that, then because this is a plus right here, you're going to use your product rule for logarithms. So let me go real slow on this. The first thing is you can just write out a simple little equation. Let me put a border so nobody's lost. We're just going to do something separate. We're going to say log base 1/2 of something that's unknown. So we don't know this right now. Let's just call it z, since we don't want to get confused with x or y here. So let's just call it z. And this is going to be equal to this negative 2. In other words, if I can figure out what z is, I can legally take this right here and I can plug it in for negative 2 right there because these guys are equal. Okay, so how can we figure this out? You could put it into exponential form. In other words, you could say that 1/2 raised to the power of negative 2 is equal to z. We put a little border here. So we'll say that 1/2 raised to the power of -2 is equal to z. I think we all know that's going to end up being 2 squared or 4. But in case you don't, again, we can do this the slow way. This would be 1 to the power of -2, which is 1, over 2 to the power of -2. You can drag this across the fraction bar, change the sign of the exponent. So z is equal to 4. So that means I can plug in a 4 right there. And again, because these two sides are equal, I can legally replace -2 with log base 1/2 of 4. So that's all I'm going to do. I'll keep this in the frame so nobody is lost. Let's write y is equal to log base 1/2 of -x. And then again, instead of plus -2, I'm going to go plus log base 1/2 of 4. Okay, to finish things up, we're going to use the product rule for logarithms. You have the same base here and here, and you have addition here. So all you have to do is say that this is y equals log base 1/2 of, you're going to multiply these guys together, so this would be -4x. So that's how I got the answer. Just replace this with your inverse notation. So f inverse of x is equal to log base 1/2 of -4x. So again, you can go to Desmos and just check this. You have your guy in orange, which is y equals x. Your guy in red, which is your original function, f of x equals -1 over 2 to the power of x plus 2. And then your guy in green, this is your f inverse of x is equal to log base 1/2 of -4x. You can see that these guys are inverses because they're reflections across the line y equals x. You're probably going to ask, what happens if I got something different? Again, as I talked about before, you can have a different form for this inverse and it could still be correct. So you could type it in on Desmos and see if it matches the graph here, and that's one way you can prove that you got the right answer. Let me just paste this in here. This is what we started with. And I'm just going to go through the process again, and I'll give you another form, and yours might be different from this. So let me just give you an alternative answer just so you can see that it's okay to get something different. So here, again, swap x and y. X equals -1 over, let's say, 2 to the power of y plus 2. And then what I would do here is, again, multiply both sides by -1. So let's say -x is equal to 1 over 2 to the power of y plus 2. And at this point, I would raise each side to the power of -1. Or another way you can think about this is you're just going to take the reciprocal of each side. So this would be -1 over x is equal to, this would come up here, so 2 to the power of y plus 2. And so at this point, what I would do is take log base 2 of each side. So let's do that. We'll say this is log base 2 of -1 over x. And this equals log base 2 of 2, and this is to the power of y plus 2. Okay, so we know this is going to come out in front. So let me write this on the left. That's how I like to put it. Let's put y plus 2. Again, this is a quantity that's multiplying this. That's why I'm using parentheses. This is times your log base 2 of 2. And you can cancel this right now and say this is equal to 1. So that's coming over here. Then I'll say this is equal to your log base 2 of -1 over x. And now you can just drop the parentheses because this is being multiplied by 1. So let's just put y plus 2 is equal to log base 2 of -1 over x. And to finish things up, we can just subtract 2 away from each side of the equation. Let me do that over here. And you could write your answer as, let's say, y, or let's just skip that and put f inverse of x. We'll just shortcut this a little bit. We'll say this is equal to, let me show that as canceling, log base 2 of -1 over x, and then -2. So this is a perfectly acceptable answer. So if you got this one and you weren't able to get the one that I put on the practice test, that's perfectly fine. There's different forms for your answers when you get to this section. Okay, let's take a look at problem 7. So here we have f of x is equal to 4 to the power of x plus 4. So this one's real easy. So let's replace f of x with y. So this equals 4 to the power of x plus 4. Let's swap x and y. X is equal to 4 to the power of y plus 4. Let's subtract 4 away from each side of the equation. So you're going to get x minus 4 is equal to 4 to the power of y. Let me go ahead and take log base 4 of each side. So let's say that we have log base 4 of 4 to the power of y. Again, I'm doing that because log base 4 of 4 is 1. And this equals log base 4 of x minus 4. Okay, so again, this can come out in front as multiplication. So you get y times log base 4 of 4. And of course, this is going to be 1. And this equals log base 4 of x minus 4. Let's just say we have f inverse of x is equal to log base 4 of x minus 4. So again, looking at the graph, here's your guy in red. That's your original function. F of x equals 4 to the power of x plus 4. Your guy in orange, y equals x. And then your guy in green, that's your inverse. So f inverse of x is equal to log base 4 of x minus 4. Again, you can clearly see these are reflections across the line y equals x. Okay, for problem 8, we have f of x equals 6 to the power of x over 2. So another easy one, let's put y is equal to 6 to the power of x over 2. Let's swap x and y. Let's say this is x is equal to 6 to the power of y over 2. And then to solve for y, let's multiply both sides by 2. Let me slide down here a little bit. And let's say we have, I'm going to go 6 to the power of y. Let me cancel that. Is equal to 2x. And then what I'll do is take log base 6 of each side because this base right here is 6. So let's go log base 6 of 6 to the power of y is equal to log base 6 of 2x. So we know this can come out in front as multiplication. This is y times log base 6 of 6 here. And again, we know that this is going to be 1. Let's just cancel that now. And this equals log base 6 of 2x. And we're basically done. Let's go ahead and say that we have f inverse of x is equal to log base 6 of 2x. Okay, so again, going to Desmos, you have your function in red here. F of x equals 6 to the power of x over 2. Your line y equals x in orange. And then in green, we have the inverse. So f inverse of x is equal to log base 6 of 2x. So once again, you can see these guys are reflections across the line, y equals x. So they are going to be inverses. All right, for problem 9, we have f of x is equal to 1 over the 4th root of 3 to the power of x. Let me slide down here. Let's replace f of x with y. So y equals 1 over, instead of the 4th root, let me raise 3 to the power of x to the 1/4 power. If you want to use this, that's fine as well. It's the same thing. So let me come down here and let me swap x and y. So let's say that x is equal to 1 over 3 to the power of y, and then this is raised to the power of 1/4. Now, before I go any further, you know that legally you can raise 1 to the power of 1/4, and that's still 1. So let me come down here, and I'm just going to write this as x is equal to 1 over 3 to the power of y, and this would all be raised to the power of 1/4. Now, what I want to do is I want to get rid of this exponent of 1/4 here because I'm trying to solve for y. So I'm just going to raise both sides to the 4th power. Let's say we have x to the 4th power is equal to, let me write all this, so 1 over 3 to the power of y, raised to the power of 1/4, and I'm going to raise this all to the power of 4. So I would say this is x to the 4th power is equal to, power to power rule, you multiply exponents, so 1/4 times 4 is 1. So I just have what's in the parentheses there, so 1 over 3 to the power of y. Now at this point, you might be a little bit stuck in terms of how I got the solution on the practice test. Again, I'm just using the rules of exponents, and so I'm going to say that 1 could be written as 1 to the power of y, because 1 to the power of y is always going to be 1 for any real number y. So you can just say that x to the 4th power is equal to 1 over 3 raised to the power of y. That's all I'm doing there is a little trick. So now what I can do is take log base 1/3 of each side, and log base 1/3 of 1/3 is 1, so you're just going to have y by itself. So let's say that we would have log base 1/3 of this 1/3 raised to the power of y is equal to log base 1/3 of x to the 4th power. So we know that this would come out in front as multiplication. We have y times log base 1/3 of 1/3, and this equals, you have log base 1/3 of x to the 4th power. This right here is going to be 1, so we end up with y is equal to log base 1/3 of x to the 4th power. Now, is this the inverse? No. If you see something like x to the 4th power, again, you should immediately be suspicious. You know that that's not going to be 1-to-1. So if you go to Desmos and you type in g of x equals log base 1/3 of x to the 4th power, you get this graph right here. So what do we want? We want this piece of the graph right here on the right. So we're going to want to say that x is greater than 0. Now, where does that come from? Well, if we go back to the original function, again, the domain becomes the range and the range becomes the domain. So what's the range going to be here? This one's pretty easy to think about. So you have 1 over the 4th root of 3 to the power of x. We'll just focus on 3 to the power of x. Can that ever be negative? No. Can it be 0? No. It has to be something that's positive. So the 4th root of something that's positive is going to give me something that's positive. So something that's greater than 0. I can get very, very close to 0, but I can't touch it. And you can see that as this guy right here, so as x approaches negative infinity, this whole thing, or the y value or the function value, is going to approach positive infinity. But as you plug in bigger and bigger values for x, so as you're going this way, what's happening is the denominator is getting bigger and bigger, and you have 1 divided by something that's really, really big, and so that's going to be really, really close to 0, but you can't ever get there. So this is going to approach 0, but never touch it. And again, this guy going this way is going to approach positive infinity. So we can say that basically the range here is that y would be greater than 0. So anything greater than 0, you're okay. So coming back, let's just put that for the inverse. We want to say that x is greater than 0. So we'll say f inverse of x is equal to log base 1/3 of x to the 4th power, again, where x is greater than 0. So this is coming from the range of the original function. That becomes the domain in the inverse. So once again, we can check this on Desmos. Here's your line y equals x in orange, your original function that we already looked at in red. So f of x equals 1 over the 4th root of 3 to the power of x. So that guy right there. Again, you can see that the y values would be anything greater than 0. Then here's the inverse. F inverse of x is equal to log base 1/3 of x to the 4th power. And we only want where x is greater than 0 because here we have that y is greater than 0. So the range here becomes the domain here. Okay, so that's really important. But once again, you can see these guys are inverses. There are reflections across the line. Y equals x. All right, let's look at problem 10. So here we have f of x is equal to, we have 4 times 3 to the power of x plus 1 over 3 to the power of x. So let's replace this f of x with y. So y equals 4 times 3 to the power of x plus 1 over 3 to the power of x. So at this point, we're going to swap x and y. So let's say we have x is equal to 4 times 3 to the power of y plus 1 over 3 to the power of y. Let's make that 3 better there. Okay, if I want to solve for y, what I would do is get everything with a y over to one side and then everything else to the other. So let's multiply both sides by 3 to the power of y. Let's do that over here as well. Slide down a little bit, and I'm just going to show that this would cancel with this. And so we're going to say that we have 3 to the power of y times x is equal to, we'll have 4 times 3 to the power of y plus 1. So what we'll do is subtract 4 times 3 to the power of y away from each side of the equation. So let's say that this is going to cancel here. And so what we'll have is 3 to the power of y times your x minus 4 times 3 to the power of y. And this would be equal to 1. Okay, at this point, I'm going to factor this out. So let's say that we're going to have 3 to the power of y times the quantity. You'd have x minus 4 inside, and this equals 1. Now let's divide both sides by 3 to the power of y. So this right here is going to cancel. And what you're going to have, let me write this on the left. So 1 over 3 to the power of y is equal to x minus 4. Again, I'm going to use my trick. So I can say this is really 1 to the power of y here. That's still 1. And so legally, you can write this as 1/3 to the power of y. Let me make this a little bit better there. And so once you've set this up, again, you could just go log base 1/3 of each side. So let me say that this is log base 1/3 of, you have this 1/3 raised to the power of y, and this equals log base 1/3 of this x minus 4. Now, this can come out as multiplication. So let's say this is y times log base 1/3 of 1/3, and this equals, we have log base 1/3 of x minus 4. We know that log base 1/3 of 1/3 is 1. Just cancel that. So let's say that this is y is equal to log base 1/3 of this x minus 4. And let's just replace this y with our inverse notation. So f inverse of x is equal to log base 1/3 of x minus 4. Okay, so looking at this, we have our line y equals x. Again, that's in orange. We have our guy in red. So this is our original function. F of x equals 4 times 3 to the power of x plus 1 over 3 to the power of x. And then the inverse is in green. So f inverse of x is equal to log base 1/3 of x minus 4. Again, this is one where you could have gotten something different. Depending on the path that you go down, you can just key what you got into Desmos and see if it matches. And basically, you're just looking to see that there are reflections across the line y equals x. And you can see here that's what we have. So these guys are going to be inverses. All right, let's take a look at the practice test. For the instructions, we're asked to approximate each. We want to round to the nearest thousandth. Okay, before we look at any problems, let's go through our change of base rule. So we have here that x, a, and b are positive real numbers. So we're just going to say they're greater than 0. And we say that a is not equal to 1 and b is not equal to 1. So as long as these conditions hold, we're going to say that log base a of x is equal to log base b of x over log base b of a. Now, why do we need this change of base rule? Remember, if you're trying to get an estimate for your logarithm and you're using a calculator, many calculators only have a log key, which is a base 10 logarithm, or an ln key, which is a base e logarithm, otherwise known as a natural logarithm. And so you can't directly calculate something like, let's say, log base 2 of 31. But a lot of online calculators will let you do that without using the change of base rule. But just in case you're stuck with a regular calculator, you can change this over and say that it's log, which is log base 10, of this 31, so of this argument here, over log of this base of 2, like this. So if you key this into your calculator, you would get about, let's say, 4.954 if we're rounding to the nearest thousandth. So that's one way you could calculate a problem like that. You could also use the natural log. So if you keyed it in like this, you would get the exact same answer. So this is basically what we're going to do today. It's going to be pretty easy. All right, let's take a look at the first problem. So here we have log base 7 of -6. And when you look at this problem, you should know immediately that this is going to be undefined. So let me write that there, and then we'll explain. So this is undefined. If you've watched the lessons in order, you know why. But just in case you don't understand the concept here, let's think about something like log base 7 of -6, and let's say we set this equal to x. Well, in exponential form, this becomes 7 to the power of x is equal to -6. So 7 to the power of x is equal to -6. Does this equation have a solution? No. Because if you think about something like 7, if I raise it to a positive number, let's say we do 7 squared. Well, this is 49, so obviously this is positive. Let's say I raise it to the power of 0. We know that any non-zero number raised to the power of 0 is 1. Then let's say I raise it to something like -2. So 7 to the power of -2, well, this is 1 over 7 squared, which is 1 over 49. That's still a positive number. So there's no value of x here that would satisfy the equation, because 7 raised to some real number is going to give me a positive result, so I can never get -6 out of this guy. So that's why we would just stop and say that this guy is undefined for log base 7 of -6. All right, for problem 2, we have log base 2 of 6. So let me say this is equal to, I'm just going to use my change of base rule. So I'm going to use log, which again is a base 10 log. So you don't have to put the base down there, it's implied. And then we're going to say of, you're going to use this argument here. So this is 6 over, you're going to have your log of, you're going to use this base here, which is 2. After you do this a few times, it's just something you memorize. And so you key this into the calculator. It'll be approximately, again, we're rounding to the nearest thousandth. So let's go 2 point, I've got 5, 8, and then I get, let me write this out. So 4 and then 9. Now, if you're rounding to the nearest thousandth, that's going to be there. This is the tenths, hundredths, thousandths. So the digit that follows is a 9. So that means I'm going to add 1 to that 4 and make that into a 5 there. And then everything that follows you can just delete. So this would be about 2.585 for our answer. All right, for problem 3, we have log base 6 of 65. So once again, I'm just going to go log of this argument here, so of 65, over, I'm going to go log of, let's go with this base here, which is 6. Key this into the calculator, and I get about 2 point, let's go 32, and then let's go 97. Again, I'm rounding to the nearest thousandth. So that's going to be right there. Now the digit that follows is a 7. So that means I want to add 1 to the 9, but 9 plus 1 is 10. So really what you want to do here is add 1 there, and then basically everything after that, you're just going to cut it off. So this would be about 2.33. All right, for problem 4, we have log base 7 of 47. So again, let's go log of 47. So we're going to use that argument there. And then over, you have log of that base there, which is 7. Key that into the calculator, and I get about 1.9785. I'm just going to stop there. Again, we're rounding to the nearest thousandth, so that's right there. The digit that follows is a 5, so I'm going to add 1 to that 8. That's going to give me 9. So this is about 1.979. All right, for problem 5, we have log base 2 of 49. So let's say this is equal to, we're going to go log of this argument here, which is 49, over log of this base here, which is 2. So this is going to be about, let's say 5.6147. So this guy right here, this is your thousandths place. The digit that follows is a 7. So I'm going to add 1 to that 4. That's going to give me a 5. And again, just delete everything that follows. So this would be about 5.615. All right, for the next one, you can use the change of base rule, but you really don't need it. If you put this in exponential form, let's say you write this as being equal to x, and you said something like this to this power gives me this. So 3 to the power of x is equal to 1. Remember that any non-zero number, if you raise that to the power of 0, you get 1. So x here would be 0. So I think a lot of you can just realize that right away and put the answer as 0. But in case you don't, you can still use this in your calculator and say that, let's just use the natural log from here on out just to get a little change. You can put the ln there of, again, you're going to use this argument of 1 over, put your ln there, again, for the natural log, use your base of 3. And if you key this into the calculator, you're going to get exactly 0. Okay, for problem 7, we have log base 3 of 2.2. So let's say that this is, I'm just going to use the natural log, so ln of this argument here, so 2.2, and then over my ln, so the natural log of this base here, which is 3. Let's key this into the calculator, and I get about 0.7176. Again, this is your thousandths place. The digit that follows is a 6, so I'm going to add 1 to that 7, and that's going to give me 8. So this would be about 0.718. All right, for problem 8, we have log base 3 of 16. So again, I'm just going to use the natural log. You can use that or the log key if you want. It doesn't matter. You get the same answer. So ln for natural log of this argument here of 16 over ln of this base here, which is 3. Let's key this into the calculator, and I get about 2.5237. Again, this is where I'm rounding to the thousandths place. The digit that follows is a 7. So I want to add 1 to that 3. That would give me a 4. And again, you could just delete everything that follows. So this is about 2.524. All right, so let's look at problem 9. So we have log base 5 of negative 25. Again, this argument here is negative, so we're immediately going to stop and say that this is undefined. So undefined. If you wanted to go further, just like we did earlier, if you set this equal to x, you can quickly see that there's no solution for your equation you set up. In other words, you're saying 5 to the power of x is equal to negative 25. Well, there's no value for x that you can plug in there and get a true statement. If you did something like, let's say 5 squared, that's 25. If you did 5 to the power of 0, that's 1. If you did 5 to the power of negative 2, that's 1 over 5 squared, which is 1 over 25. So there's no value for x there that's going to result in me getting a negative 25 over here. So let's just go ahead and say that this is undefined. And again, you don't have to go through this each time. Whenever you see a negative argument for your logarithm, just stop and put undefined. All right, for problem 10, we have log base 2 of 25. So let me again use the natural log, the ln of this argument here, which is 25, over. I'm going to use the ln, or the natural log of this base here, 2, and just key this into the calculator. And I get about 4.64, and then I'm going to go 38. So this is your thousandths place. The digit that follows is an 8. So let's add 1 to that 3. That's going to give me a 4. And then again, you can just delete everything that follows. So this is about 4.644. All right, let's take a look at the practice test. For the instructions, we're asked to solve each equation. All right, let's take a look at the first problem. So we have 18 to the power of 6x plus 6 is equal to 60. We're trying to solve for x here. And again, that's in the exponent. So what I'm going to do is turn to logarithms, and specifically the power rule, or you could say the power property of logarithms. Remember, if you have something like, let's say, log of, let's say, x to the power of r, well, this is equal to, that r comes out in front as multiplication, so r times log of x. So we're just going to use that property here. And so I'm going to first isolate this guy right here, this 18 to the power of 6x. To do that, I'm just going to subtract 6 away from each side of the equation. So that cancels. Let's write that we have 18 to the power of 6x is equal to 60 minus 6 is 54. Now, here's where you have different choices. You can use a base 10 logarithm. So we know that this log of x is the same as log base 10 of x. This is the common logarithm, so we don't write that base of 10, it's implied. You will have this on your calculator as the log key, or at least most calculators will have it. Then you can also use the natural logarithm here. So that's the ln key. So the ln of x is equal to, this is a base e logarithm. So log base e of x. Now you can use that one as well. You'll have an ln key in most cases. Or if you're trying to get an exact solution, so you're not trying to approximate it, remember that if you do something like log base 18 of 18, this is by definition 1, because 18 raised to the power of 1 gives me 18. So if I was trying to give an exact answer, I would use that property there. If I was trying to key this in on a calculator and I had limited functions, so I just had a log key and an ln key, then I would probably use either the common log or the natural log. So really there's a lot of choices here. Let me just start by going log base 18 of 18 to the power of 6x, and this equals log base 18 of 54. Okay, so for this one, we already know that this is going to be equal to 6x, because again, by rule, this can come out in front as multiplication. So this is 6x times log base 18 of 18 is equal to log base 18 of 54. So again, this is going to be 1, and so you get 6x is equal to log base 18 of 54. And then let's divide both sides of the equation by 6. This cancels. And so if you want an exact answer, you could say that x is equal to log base 18 of 54 over 6. Now, if you're trying to key this into your calculator, again, this is probably not going to be that helpful, especially if you're using an older calculator or something like that. If you have an online calculator, then you can just key this in and it'll spit out an answer. But in case you want to change it over, again, you have your change of base formula. So essentially, all you'd have to do here is say that this can be converted. Let me first write this as x is equal to, I'm going to go 1 over 6 times log base 18 of 54. So then this would be equal to, let's go 1 over 6 times, this would be, let's use the common logarithm. So the base 10 log, we're going to go log of, you're going to take this argument here of 54 over your log of this base here, which is 18. And so this would be equal to your log of 54 over 6 log of 18. So you could have also gotten this same thing by, instead of taking the base 18 logarithm of each side, just taking the base 10 logarithm of each side, and you would have gotten the same answer. So let me erase this, just bring this down here like this. So this is another form that you can answer with. Let me put that like that, and maybe drag this down here. Now, this was the one that you can key into the calculator easiest. So I'm just going to do that real quick. And what I get is about 0.23. Let's go 0, 0, 1, 5, and I can stop there. In general, they'll usually ask you to go to the nearest 10,000th. So here's the tenths, hundredths, thousandths, 10,000ths. So the digit that follows is a 1. So you can basically leave that 0 unchanged. Remember, these two zeros do not add any value to the number. So let's say it's about 0.23. And another thing is that I want to bring up before we conclude this problem, if you're keying this into a basic calculator, remember you have to think about the order of operations. So something like the log of 54 is divided by, now you have this 6 times the log of 18. So hopefully you know that when you work with fractions, the numerator and denominator are done separately. So in other words, to get the right answer here, you have to wrap this with parentheses so the calculator knows to do 6 times the log of 18 first and then do the division. Otherwise, because of the order of operations, remember the M and the D step in PEMDAS, the multiplication and the division, they have the same priority level. So we multiply or divide working from left to right. So here the division occurs to the left of the multiplication, so the calculator is going to divide first and then multiply. So if you do it like that, you're going to get the wrong answer. So this is how you would want to key it in if you want that answer that I got. So this is going to be about 0.23. All right, for problem 2, we have negative 10 times 15 raised to the power of 4x plus 10, and then minus 4, and this equals 25. So we're going to use the same strategy that we did in the last problem. So we're going to isolate this guy right here. So this whole thing. So 15 raised to the power of 4x plus 10. And then we're going to use the power rule for logarithms to bring this out in front and solve. So let's add 4 to both sides of the equation. So let's say this is going to cancel. So we would have negative 10 times 15 raised to the power of 4x plus 10. And this equals 25 plus 4 is going to be 29. Now at this point, again, if I'm trying to isolate this whole thing right here, well, what I would do is divide both sides of the equation by negative 10. So this is going to cancel with this. And let's say that we have 15 to the power of 4x plus 10. And this equals negative 29 over 10. So at this point, you should be a little bit suspicious. Remember, when we think about raising something like 15 to a negative power, let's just say this 4x plus 10 turns out to be negative, well, we know that's still going to be something that's positive. If we have something like 15 raised to the power of 0, well, that's 1. That's still positive. If we have 15 raised to something that's positive, well, that's going to be positive. So we would say that there's no solution for x here. There's nothing I can plug in that would give me a true statement. So let's just stop and say that there's no solution. All right, let's take a look at problem 3. Here we have 2 times 20 raised to the power of negative 6x minus 9, and then minus 7, and this equals 19. All right, so first I'm going to isolate this right here. So let's add 7 to both sides of the equation. This cancels. You get 2 times 20 raised to the power of negative 6x minus 9, and this equals 19 plus 7 is going to be 26. At this point, I'm going to divide both sides of the equation by 2, and so this would cancel. You get 20 raised to the power of negative 6x minus 9, and this equals 26 divided by 2 is going to be 13. So at this point, again, you have different choices in terms of what base logarithm you want to use. I'm just going to use the common logarithm, but if you want to use a log with a base of 20, that's up to you. So I'm just going to say that we want the log of 20 raised to the power of negative 6x minus 9, and this equals the log of 13. Okay, so we know that this exponent now can come out in front as multiplication. So let's say that, and this is going to be a quantity, so negative 6x minus 9, make sure you wrap this with parentheses, and then times your log of 20, and this equals, we're going to have the log of 13. Okay, so what you're going to do is actually distribute this. So in other words, you could write this on the other side if you want. That makes it easier for you. Let me just move this over here. Just rearrange it like that and put this like this. I think it's a little bit easier to think about like that. So this gets distributed to each guy. Remember, the log of 20 is a number. So this is going to be distributed to each guy. So let's say that this is negative 6, and then let's go times log of 20, and then times x, and then minus 9 log of 20, and this equals your log of 13. Let's add 9 log of 20 to both sides. So this is going to cancel. We have negative 6 and then log of 20. And then let me put times x here for emphasis. And this equals, so let's say this is log of 13 and then plus 9 log of 20. Since we have this negative 6 log of 20 that's multiplying x, we're going to divide both sides of the equation by negative 6 log of 20. Now be careful here because you have this sum. So what I would do is divide it by each guy. So divided by negative 6 log of 20. And let's go divided by negative 6 log of 20. So this is going to cancel with this. So let's write that we have x is equal to, over here, let's put the negative of log of 13 over 6, and then we have log of 20. Let me make this 3 a little bit better here. And then positive over negative is negative, and then 9 over 6, 9 divided by 3 is 3, and 6 divided by 3 is 2, and then you would have log of 20 over log of 20, that's going to cancel. So in other words, this would cancel. So you could write it like this, or you could put the negative 3 halves out in front. It's really up to you. The main thing is you have a form that you can key into your calculator. So do so carefully, and you will get negative 1.642700. Let's just stop there. So we want to go to the nearest 10,000th. So tenths, hundredths, thousandths. Here's the 10,000ths. So the digit that follows is a 0, so we just cut these off and say it's about negative 1.6427. All right, for problem 4, we have 4 to the power of x plus 4 to the power of 2 minus x is equal to 10. All right, this one is pretty easy once you understand the tricks involved. So this is something you'll probably get as a challenge question on a test or something like that. And really, you start with this part right here, and you use the rules of exponents to change the form. If you have something like, let's say, 4 squared over 4 to the power of x, well, the base here, 4, stays the same, and you subtract your exponent in the numerator, which is 2, minus your exponent in the denominator, which is x. So all I'm going to do is go from this form back to this form. So let me erase this, and then just say that you have 4 to the power of x plus 4 squared, which you could write as 16, and then over 4 to the power of x, and this equals 10. Let me just subtract 10 away from each side and say this equals 0. Okay, at this point, the way I'm going to solve it, and you don't have to do it this way, but the way I like to do it is use a substitution. So I'm going to let u be equal to 4 to the power of x. I think it just makes it easier. So let me move this over here and just say that, okay, well, this would be u, and then plus 16 over u, and then minus 10, and this equals 0. So here I would multiply both sides of the equation by u, so I can clear that denominator. Let me just do this in line. So I'm going to do that right there, and then right there. And then let me scooch this down a little bit more. So times u there, and then times u there. So u times u is u squared. And then plus, the u's would cancel here, so you have 16. And then minus, you would have 10u. And of course, 0 times anything is 0. So this guy is going to be a quadratic that we can solve. Let me reorder this. So u squared minus 10u, and then plus 16 like this. And of course, you can factor the left side. Pretty easy to factor that. So this is u, and this is u. And basically, two integers that sum to negative 10 and have a product of positive 16, that's going to be negative 8 and negative 2. From the zero product property, you would say u minus 8 is equal to 0, then or you would have u minus 2 is equal to 0. Let's add 8 to both sides of the equation. This cancels. You get u is equal to 8. Here, let's add 2 to both sides of the equation. This cancels. You're going to get u is equal to 2. And let's come back to this point right here. Let me put a little border. Now, since u is equal to 4 to the power of x, I can legally replace this u right here with 4 to the power of x. So that equals 8. Or, again, for u, 4 to the power of x is equal to 2. So for these two equations, it's probably easier to write each side as having a common base. But because we're working with logarithms for this section, let's just do it that way. So the first one, let's just go log base 4 of 4 to the power of x is equal to log base 4 of 8. So log base 4 of 4 to the power of x, we know that's going to be x, and this equals. This one is a little bit tricky. It's going to end up with 3 halves for the value here. You can punch that into a calculator, or you can do an analysis there and think about the fact that, okay, well, 2 cubed is going to be 8. So you could start with that like that. And basically, you want this 4 right here, the base, to match this base right here so that those will cancel and you're just left with the exponent. So what I could do there is say that this is 4 raised to the 3 halves power. Now, how did I get that? Well, the square root of 4 is 2, and then 2 cubed gets me back to 8. So let me write this as 4 raised to the 3 halves power. Again, if you need to write that off to the side, you can. You're basically saying that this would be the square root of 4, and then this guy right here would be cubed. So the square root of 4 is 2, so this is 2 cubed, which is 8. So nothing illegal there. I'm just writing it to where the answer is obvious. Log base 4 of 4 raised to the power of 3 halves is 3 halves. Okay, so that's the first one. For the second one, you can go log base 4 of 4 to the power of x is equal to log base 4 of, again, if I want this to be a 4 right here, well, 2, you can think about that as being the square root of 4. In other words, this is 4 to the power of 1/2 there. And so log base 4 of 4 to the power of x is x. I'm just going to put a comma here because I already have an x right there. And then over here, log base 4 of 4 to the power of 1/2 is just 1/2. So although it's not required here, I would just check this one because it's kind of a tricky problem just to make sure we did everything right. So let's go 4 to the power of 3 halves first, and then plus 4 to the power of 2 minus 3 halves. Get a common denominator there. So 2 times 2 over 2 would be 4 over 2. So 4 over 2. And so 4 minus 3 is 1. So 1 over the common denominator of 2. So this is 4 to the power of 1/2. Does this equal 10? Well, we know that 4 raised to the 3 halves power, that's 8, right? Because this is the square root of 4, which is 2, being cubed. So that's 8. So this is 8 plus 4 raised to the 1/2 power, that's the square root of 4, that's 2. Is that equal to 10? Yeah, you get 10 equals 10. That is a true statement. So this one works. In terms of the other one, let's see what we get. So we have 4 to the 1/2 power, and then plus 4 raised to the power of 2 minus 1/2. Does this equal 10? So let's write this 2 as 4 over 2. So 4 over 2 minus 1 over 2, that's going to be 3 over 2. And so we have the same thing that we had before, it's just reversed. So before, we ended up with 4 to the power of 3 halves plus 4 to the power of 1/2. And of course, we got 10. Now it's just 4 to the power of 1/2 plus 4 to the power of 3 halves. So it's still going to give me 10. This right here is 2, and this right here is 8. And of course, 2 plus 8 is going to be 10. So you get 10 equals 10. So both solutions are valid. So x can be 3 halves or 1/2. All right, for problem 5, we have 9 to the power of x minus 1 is equal to 3 to the power of x plus 4. Now for this problem, of course, you could write 9 as 3 squared. So you could say this is 3 squared, and then this would be raised to the power of x minus 1, and this equals 3 to the power of x plus 4. And then this would get distributed. So in other words, you would have 3 to the power of 2x minus 2. You're just using the power to power rule. So 2 gets multiplied by x, and then 2 gets multiplied by -1. And this equals 3 to the power of x plus 4. And now you could set the exponents equal to each other. So you could say that 2x minus 2 is equal to x plus 4. Add 2 to both sides of the equation. And so I would also subtract x away from each side of the equation. This cancels. And so let's say that 2x minus x is going to be x, and this equals 4 plus 2 is going to be 6. So x equals 6 there. That's the, I think, quicker way to do it. But because we're in a section where we're using logarithms, I'm just going to do this using logarithms, so you see that as well. So since you have this 9 raised to the power of x minus 1 and this 3 raised to the power of x plus 4, what I'm going to do is just use a base 9 logarithm on each side. So let's go log base 9 of, you have 9 to the power of x minus 1, and this equals log base 9 of 3 to the power of x plus 4. Okay, so we know that basically this would be x minus 1 on the left, because log base 9 of 9 is 1, and of course this can come out in front as multiplication. So this is just x minus 1 here, and this equals, this would come out in front, so this is the quantity x plus 4, and then times log base 9 of, you would have your 3 there. Now, what you could do is write 3 as 9 to the power of 1/2, because the square root of 9, or 9 to the 1/2 power, is 3. So you're just changing the form so that you can say log base 9 of 9 raised to the power of 1/2. Well, that's just going to be 1/2. So let's say that now this is x minus 1 is equal to, let's go 1/2 times the quantity x plus 4. And let's just distribute that now, so that would be x over 2, or you could do 1/2 x if you want. So 1/2 x, and then plus 4 over 2, which is 2. Let's just do that like that. And let's just solve this equation real quick. So I'm going to multiply everything by 2. So this is 2x minus 2 is equal to x plus 4. And you'll notice you're right back to where we were when we wrote things with like bases and set the exponents equal. So we know we're going to get the same answer. So let's add 2 to both sides. This cancels. Let's subtract x away from each side. This cancels. Let me make that x look a little bit better. And so we would have 2x minus x, that's x, and this equals 4 plus 2 is going to be 6. So either way you want to do this problem, you're going to get that x is equal to 6. All right, let's take a look at problem 6. So here we have 3 to the power of x plus 9 to the power of x is equal to 90. So the first thing is you would notice that 9 is basically 3 squared. So let's replace that first and see what happens. Let's go 3 to the power of x plus, I'm going to go 3 squared. This is raised to the power of x. We know from the power to power rule, this would be 3 to the power of 2x. What we're going to end up doing is actually breaking this back up in a moment, but I'll explain why. For right now, let's just write 3 to the power of 2x. And then you have equals 90. Let me subtract 90 away from each side and say this is equal to 0. So this guy is actually going to be quadratic in form. And so when you see that, generally speaking, you'll use a substitution strategy. You don't have to, but that's what I like to do. So I'm going to let u be equal to, let's go 3 to the power of x. So that's what I was talking about breaking this back up. So legally, I can say, since this is multiplication here, that this is 3 to the power of x and then squared. At the end of the day, it's still 3 to the power of 2x. So now I'm just going to replace all my 3 to the power of x's here, so this one and this one, with u. And let me write this one out in front. So this would be u squared plus you would have u, and then minus 90 equals 0. Can we solve this with factoring? Yes. If you think about 90 for a moment, forget about the fact that it's negative, you have 9 and 10. So those guys differ by 1. And so this is really easy. I'm just going to put a u here and a u here, and I want a positive 10 here and a negative 9 here. So basically your outer is negative 9u, your inner is plus 10u. And so 10u minus 9u, that's going to give you 1u or just u. And then 10 times negative 9 is negative 90. So this is the correct factorization. So we would want to say that u plus 10 is equal to 0, or u minus 9 is equal to 0, just using the zero product property. And so here you would subtract 10 away from each side of the equation. This cancels. You get u is equal to negative 10. Then here let's add 9 to both sides of the equation. This cancels, and we're going to get that u is equal to 9. So since u is equal to 3 to the power of x, I'm going to replace this with 3 to the power of x, and I'm going to replace this with 3 to the power of x. Now, can 3 raised to the power of x ever be equal to negative 10? No, it's going to be positive. It can't be 0, and it can't be negative. So this has no solution. This has no solution. What about 3 to the power of x equals 9? Well, yeah, that one's really easy. You can eyeball that and say, well, it's going to be 2, because 3 squared is obviously 9. But how could we solve that more efficiently? Of course, you could change 9 into 3 squared. But since we're using logarithms here, let's just keep with that. So let's go log base 3 of 3 to the power of x is equal to log base 3 of, instead of 9, let's write 3 squared. Let me slide down here and make that a little bit better there. So log base 3 of 3 to the power of x, that's going to be x. And this equals log base 3 of 3 squared, that's going to be 2. So of course, x is just equal to 2. Okay, let's check x equals 2 in this equation here. So this would be 3 squared, that's 9, plus 9 squared, that's 81. Does this equal 90? Yes. You would get 90 equals 90, which is a true statement. So x equals 2 is a valid solution. All right, for problem 7, we have e to the power of 5x minus 1 times e to the power of 2x, and this equals 7e. So let's think about the first step here. I would combine this guy right here using the rules of exponents. So you have the same base here. So you're going to go e to the power of, you would add your exponents. So you're going to have 5x minus 1 plus 2x. Now 5x plus 2x is 7x. So let's just do that now and say that this would be e to the power of 7x minus 1. And this equals, this would be 7e. Now if you have e involved, remember you have your ln, or your natural logarithm, which is a logarithm with a base of e. So by rule, when you see your ln of e, this is equal to log base e of e, which is equal to 1. So what I'm going to do here is take the natural log of each side. So you'll go ln of e raised to the power of 7x minus 1 is equal to ln of 7e. So let's think about what we have. This right here would end up just being 7x minus 1. And then this right here, you would expand that using your product rule for logarithms. So this is the natural log of 7 plus the natural log of e. Now again, the natural log of e, that's going to be 1. What we have at this point is 7x minus 1 is equal to ln, or the natural log of 7, plus this right here is 1. So what I'm going to do is add 1 to both sides of the equation. This cancels, and we're going to have 7x is equal to ln of 7 plus 1 plus 1 is 2. Now, as a last step, let's go ahead and divide both sides of the equation by 7, and let's cancel this with this, and let's say that we have x is equal to ln, or the natural log of 7, plus 2 over 7. If you want to approximate this, you can just key it into the calculator. So I get about 0.56, let's say 37014. Let's just stop there. I'm going to round to the nearest 10,000th, so it's going to be right there. So the digit that follows is a 0. So basically, you can just stop it there and say this is about 0.5637. All right, for problem 8, we have something that is a common bonus question on a test, something you just need to think about a little bit. So we have the quantity 4x plus 3 raised to the power of x squared minus 16, and this equals 1. Okay, so how do we solve something like this? We're not going to think about any of the methods we've used so far. We're just going to go back to something very basic. We're going to let something like a be equal to this base here. So this is 4x plus 3. And then we're going to say that b is equal to this exponent here. So this is x squared minus 16. Okay, I'm just going to put a little border here. And we're going to consider that a and b are real numbers. So we're not going to think about non-real complex solutions here at all. And we're going to say that if a to the power of b is equal to 1, what could a be and what could b be? Well, you have 3 different scenarios. So the first one is that a is equal to 1. So if a is equal to 1, then b can be any real number, because 1 raised to any real number would be 1. So the way you would translate that over is you would take this 4x plus 3. So this, let me put for number 1, you would take 4x plus 3, and you would set that equal to 1. And let me just paste this in here. We'll come back and solve that in a moment. Let me put a little border. And let's come back and think about number 2 here. So what else could be true? Well, we know that any non-zero number raised to the power of 0 is going to be 1. So that means that a is not going to be 0. So a is not 0, and b is equal to 0. If those were true, well, then I would get 1 here. So you would write out, and forget about the a doesn't equal 0, you can just check that. You can just set x squared minus 16 equal to 0. So that's your b. And then once you have those solutions, you can plug it in for x here, and you can see, does it make it 0? If it does, it would be rejected. If it doesn't, then you're okay, because any non-zero number raised to the power of 0 is going to be 1. And let's paste this in here, and I'm going to put 2, and then I'm going to put a little note here that we need to check in 4x plus 3. Okay, just so we remember. We put another little border. Now, the last one is a little bit hard to think about, so let's put a number 3 here. And this is where a is equal to -1. So this one's a little bit tricky, because if a is -1, and you can think about the easiest case to think about, well, if b is something that's, let's say, an even natural number, so 2, 4, 6, 8, something like that, well, -1 raised to one of those powers would be 1. Something like -1 squared is 1, or -1 to the 4th power is 1. But it's also true that you could have, let's say, -1 raised to the power of something like, let's say, 2/3. Well, what is this? This is the cube root of -1 squared, by definition, which could also be written as the cube root of -1, and then that being squared. So either way, -1 being squared is 1, the cube root of that is 1. Here, the cube root of -1 is going to be -1, and then -1 squared is going to be 1. So there's different scenarios that can occur when a is equal to -1. So for this one, I'm just going to write a equals -1, and then I'm going to put, to make it simple, check. Just check, see if it works. So we're going to check. So that would be 4x plus 3 equals -1. Okay, let's grab that real quick. And let's put 3 here. And let me paste that in. So for scenario 1, it's pretty simple. We're just going to subtract 3 away from each side. That cancels. We get 4x is equal to 1 minus 3 is -2. Divide both sides by 4. This cancels. You get x is equal to -2 over 4 is -1/2. So of course, this makes the a part in the a to the power of b 1. And so 1 raised to any real number would be 1. So we know this is going to work. We don't have to check anything. Then for this one, we have x squared minus 16 equals 0. So we would say that x squared is equal to 16 just by adding 16 to both sides of the equation. And so then you would use your square root property and say x is equal to plus or minus 4. Now it also has to be true that this 4x plus 3, if I plug in a 4 for x, that can't be 0. Okay, well, I have this 4 times, plug in a 4, plus your 3. What does that equal? If it's 0, then again, we've got to reject. 4 times 4 is 16, plus 3 is 19, so that's not 0, so it's okay. Then the other one is negative 4, so let's plug that in. Let's get rid of this. 4 times negative 4 is negative 16, plus 3 is negative 13, so again, not 0, so these are going to work. So x could be plus or minus 4. The last one, this is the one that's a little bit more complicated to think about, so you're just going to solve this real quick and check. So subtract 3 away from each side. This cancels. You get 4x is equal to negative 1 minus 3 is negative 4. Let's divide both sides by 4. And you get x is equal to negative 4 over 4 is negative 1. Okay, so for this one, I would just check it. So again, the original problem is 4x plus 3. This is raised to the power of x squared minus 16. And you're trying to see, is this going to be equal to 1? So in other words, I already know that plugging in a negative 1 here is going to give me a negative 1 for the base. Because 4 times negative 1 is negative 4. Negative 4 plus 3 is negative 1. So this would be negative 1 raised to the power of, this would be negative 1 squared, which would be positive 1, and then minus 16, that's not going to work. Because this is going to be to the power of negative 15. That's not going to equal 1. This is going to be false. If you were to keep going with this, you would say that this is 1 over negative 1 to the power 15, and negative 1 to the power 15 is just negative 1. So this is 1 over negative 1, which equals negative 1. So this would not give me a result of 1. So again, that's why we just check it, and we say that's false. So that one is going to get rejected. So let me go ahead and mark this one out. That's a reject. Okay, so the solutions we're going to come up with, we get x is equal to negative 1/2, and then we get plus or minus 4. Let me grab this real quick, and let me paste this in. So this one, because it's a little bit complicated, I'm just going to go ahead and check just to make sure we got the right answer. So let's start with this one. So you have 4 times negative 1/2 plus 3. So this right here would end up being negative 2, and negative 2 plus 3 is 1. And so you would have 1 raised to the power of, this right here would be negative 1/2 squared, and then minus 16. You don't really need to go through this. I mean, this would end up being 1/4 like this, but this is kind of a waste of time because at the end of the day, 1 raised to any real number is always going to be equal to 1. So this would be a true statement. Okay, so we have verified this one right here. Then the plus or minus 4. So again, we know that 4 times 4 plus 3, because we already did it, this is going to be 19. So this right here would be 19. And then raised to the power of, well, this is going to be 0. 4 squared is 16. 16 minus 16 is 0. So this does equal 1. The other way, if you do it, if you go 4 times negative 4, that's negative 16, plus 3, that's negative 13. And this is raised to the power of negative 4 being squared is 16. 16 minus 16 is 0. So this would be 1 as well. So these all work. Right, so you can just plug those in and check. So the only one that didn't end up producing something for us is this number 3, where a is set equal to negative 1. Again, when you check that, it doesn't work. And if you didn't check it there, you would just check it here and see that, hey, that doesn't work. So you need to reject that solution and just go with negative 1/2 and then plus or minus 4 for x. All right, for the next 2 problems, we're going to change up the instructions. We're going to have a basic word problem. So for the instructions, it just says solve each word problem. And what we have for problem 9, if money is invested in a CD, that's a certificate of deposit, that is compounded continuously. So remember, we have a formula for that. It's on the next page. At 1.9%, let me highlight that. So 1.9%, let me highlight compounded continuously. Annual interest, how long will it take for the investment to double in value? Okay, this is a very common question, and it's very easy to solve. So this is for continuous compounding. Remember, we have that other formula if it's just compound interest, but it's not continuous. So here, what you're going to think about is you want your principal to double. So if the initial principal is P, that means double that is 2P. So that's your A there. That's the amount at the end. So you want that to be 2P. So that's all you're going to do. So 2P is equal to P, then times E raised to the power of R. Now R, the rate as a decimal that's given to us, again, it's 1.9%. So that's going to be 0.019. So 0.019, again, just converting that over into a decimal, and then times your t. Now, it wants to know how long. So that means you're going to solve for t, or the time. So the first thing I would do here is divide both sides by p. Let's go ahead and take care of that. So this is going to cancel. Let me slide down here. And so the p's would cancel. You have 2 is equal to e raised to the power of 0.019 times t. Now, I need to get this t down. So we already know what we're going to do. We're going to take the natural log of each side. So we're going to say ln, that's the natural log of 2, is equal to ln, that's your natural log of e, raised to the power of 0.019t. Let me close that down. So we know that these would cancel, right? This comes down and then the natural log of e is 1. So let me actually write this on the other side. I'm going to put 0.019t is equal to the natural log, or ln, of 2. Since I'm trying to solve for t, I'm just going to divide both sides by 0.019. Let me do that over here as well. So this would cancel. You're going to get t, or the time for that investment to double, is equal to the natural log of 2 over 0.019. Let's key that into the calculator. And I get about, let's say 36 let's go 48. I'll just round to the nearest hundredth. And let's go back up and I'll just say about, so about 36.48, and we'll go years. Okay, for problem 10, we have if money is invested in a CD, again, that's a certificate of deposit, that is compounded continuously at 3.5% annual interest, how long will it take for the investment to triple in value? So again, we're going to use the formula for continuous compounding, and that's A equals PE raised to the power of RT. So we want to know how long before it triples. So your A, that's the amount you're getting at the end, that's going to be 3P. So you're starting with P and you're ending with 3P, 3 times the principal. So that equals PE to the RT. Now we know that the rate, again, is 3.5%. So as a decimal, that's going to be 0.035. Let me put my T back in here with a different color. And of course, I'm going to divide both sides by P just to get rid of that. So this would cancel with this, and this would cancel with this. Let me slide down here. And let's say that now we have 3 is equal to, we have e to the power of 0.035t. Okay, let me actually slide this down a little bit so I can just do this here. And we don't have to use another line. We'll just take the natural log of each side. And of course, this part right here is going to cancel with this because this comes down. So you're going to have this 0.035t is equal to ln, or the natural log of 3. Let's divide both sides of the equation by 0.035. And let's cancel this with this. And let's say that t, or the time for the investment to triple, is going to be equal to ln, or the natural log of 3, over 0.035. Okay, let's key this into the calculator. And if I round to the nearest hundredth, I get about 31.39. Let's come up and say about, let's go 31.39 years. All right, let's take a look at the practice test. For the instructions, we're asked to solve each equation. All right, for the first problem, we have -6 log base 9 of -9x minus 6, then minus 9, and this equals -15. So the strategy for this problem is to first isolate this guy right here. So log base 9 of -9x minus 6. Once you've done that, then you can basically put it into exponential form, and from there you can just solve the resulting equation. So the first thing I would do is just add 9 to both sides of the equation. Let me go ahead and say that this is going to cancel. So you have a -6 and then log base 9 of -9x minus 6, and this equals -15 plus 9, that's going to be -6. All right, at this point, because you have -6 that's multiplying log base 9 of -9x minus 6, let's divide both sides of the equation by -6. So just like that. And so this would cancel with this. And -6 over -6, let's just line that out and say that's 1. Let's come down here and now say that we have log base 9 of -9x minus 6, and this equals 1. And so what you're going to do at this point is just put it into exponential form. So you're going to say that 9 is your base, raised to the power of 1, which is just 9. But let's just write 9 to the first power like this. And this equals this guy right here, the argument for the logarithm. So negative 9x minus 6. And you can delete this if you want, or you can leave it there. It's up to you. So let's come down here and just solve this. So I'm just going to add 6 to both sides of the equation. And so this would cancel. 9 plus 6 is 15. Let me write this on the left. That's how I like it. So let me put negative 9x is equal to 15. To finish things up, let's divide both sides of the equation by negative 9. And so this will cancel with this. And you get x is equal to, you get negative, and then you have 15 over 9. So let's write 15 as 5 times 3. And let's write 9 as 3 times 3. And so we can cancel a common factor of 3 between numerator and denominator. So this ends up giving me negative 5 thirds. So that's going to be your answer. Okay, let me come back up here and paste this in. So hopefully you're aware that in some cases, when you solve a logarithmic equation, you can get extraneous solutions. Now, this particular one, that's not going to happen. I'll show you why this happens later on in the practice test when we get one with an extraneous solution. It has to do with your product or quotient rule for logarithms, and when you condense, you'll have something that would not work in the original equation, but it works in the one that's modified. Let's just check this one, just for the sake of completeness. If you want to skip this, it's fine. So we'll go negative 6 log base 9 of, you have a negative 9 times negative 5 thirds, and then minus 6, and then minus 9 here, and this should be equal to negative 15. Okay, so here, negative 9 times negative 5 thirds, let's go ahead and say that negative times negative would be positive, 9 divided by 3 would be 3, so you basically have 3 times 5, which is 15. I'm just going to erase this as I go and say that this is 15. We know that 15 minus 6 is going to be 9, and so this right here would be log base 9 of 9, which is 1. Let me get rid of that and say that this is 1. Negative 6 times 1 is negative 6. So you get negative 6 minus 9, which is negative 15. So you get negative 15 equals negative 15. So this answer is going to work. X equals negative 5 thirds. That's a valid solution. Okay, let's take a look at problem 2. So we have 2 log base 3 of negative 6x minus 5, and then minus 9, and this equals negative 13. So again, we're going to use the same strategy here. So we just have one logarithm involved. So this guy right here, so log base 3 of negative 6x minus 5, you want to isolate that and then put things in exponential form and just solve. Okay, so the first thing I'm going to do is just add 9 to both sides of the equation. This would cancel. So negative 13 plus 9 is negative 4. So let me write 2 log base 3 of negative 6x minus 5. And this equals, again, this would be negative 4 over here. So at this point, I would divide both sides of the equation by 2. So this would cancel, and you get log base 3 of negative 6x minus 5, and this equals negative 4 over 2 is negative 2. Okay, at this point, you're going to put it into exponential form. So this is your base, so you have 3, and then it's going to be raised to the power of negative 2. So let's put negative 2 there, and this equals, you're going to use the argument from the logarithm, so negative 6x minus 5. So we know that 3 to the power of negative 2 is the same thing as 1 over 3 squared. So this would be 1 over 9. And this equals negative 6x minus 5. I would multiply both sides by 9 to clear that denominator. Let me slide down here a little bit. And let me break this up so I can show this. I'm going to go plus negative 5 like that. And let me move this down. So I'm going to multiply this by 9, multiply this by 9. Let me put my x back in, and then multiply this by 9. So all I did was I multiplied this by 9, this by 9, and this by 9, just multiplying both sides of the equation by 9, so I can clear this denominator. So this would cancel, and I have 1. And this equals negative 6 times 9, that's negative 54. So you're going to have negative 54x, and then negative 5 times 9, that's negative 45. So you could just put minus 45 here. Okay, at this point, if you want to solve for x, let's add 45 to both sides of the equation. So that would cancel, and you'll have negative 54x is equal to 1 plus 45 is going to be 46. Okay, to finish things up, let's divide both sides of the equation by negative 54. And so this is going to cancel. You'll have x is equal to positive over negative is negative, and then you have your 46 over 54. Okay, well, I know 46 is 23 times 2, and 23 is a prime number. And then for 54, that's 27 times 2. So let's write 27 times 2. So we can cancel the common factor of 2 between numerator and denominator. And we'll say this is negative 23 over 27. All right, so I'll just paste this in here, and we're just going to do a check for the sake of completeness. Just like in the last problem, this one's not going to be a problem that's going to have extraneous solutions, but if you're not sure about which ones do and which ones don't, then just check everything. So let's go to log base 3 of -6 times, you have negative 23 over 27, and then -5, and then you have -9, and this should be equal to -13. Okay, so with negative times negative, that's positive. Let me just mark those out. 6 and 27 have a common factor of 3. 6 divided by 3 is 2. 27 divided by 3 is 9. So this would be 2 times 23, which is 46 over 9. So this is 46 over 9. Now, if I want to get a common denominator here, with 5, you could multiply that by 9 over 9. So let me put minus. You'll go 5 over 1 times 9 over 9. So this is 45 over 9. So 45 over 9. So 46 minus 45 is 1 over the common denominator of 9. So this right here would be 1/9. Now, if you look at the base here, which is 3, what you could do is rewrite this. Remember earlier we saw 3 to the power of -2 to represent 1/9. So we're going to do that again. So this is 3 to the power of -2. And then by the properties of logarithms, log base 3 of 3 raised to the power of -2, that's just -2. So you can erase this and just say that this is times -2. So 2 times -2 is -4. So now you have -4 minus 9. And of course, that is -13. So the left and the right sides are equal here. So we can say that this is a valid solution. So x equals -23 over 27. All right, for problem 3, we have 9 log base 7 of -6x minus 5, and then -10, and this equals -19. So again, same strategy. We're going to isolate this logarithm right here, and then we're going to put it into exponential form. So let's add 10 to both sides of the equation. This cancels. You're going to have 9 log base 7 of -6x minus 5, and this equals -19 plus 10, that's -9. All right, at this point, I'm going to divide both sides of the equation by 9. And so let's say that this is going to cancel with this, and we have log base 7 of -6x minus 5, and this equals -9 over 9. That's going to be -1. Okay, at this point, we're going to put it into exponential form. So this right here is your base. So you have 7. This right here, we're going to raise it to the power of -1. So we know that's really 1 over 7, but we'll write that in a moment. And this equals, this is going to be this guy right here, the argument from the logarithm. So -6x minus 5. Okay, so I'm just going to rewrite this as 1 over 7 is equal to, you have -6x minus 5. If you want to clear that denominator, you can multiply both sides by 7. So let me erase this and go plus -5 like that. Let me move this down here like that. So I'm going to multiply by 7, and then multiply by 7. Okay, so we see that this would cancel. And so on the left, you have 1. And this equals -6 times 7 is -42, and then times x, and then plus -5 times 7 is -35. So to solve this, let's add 35 to both sides of the equation. And so this right here is going to cancel. So on the left, you have 1 plus 35, which is 36. Let's write -42x is equal to 36. And then let's divide both sides of the equation by -42. And so this right here is going to cancel with this right here. And let's slide down and say that x is equal to positive over negative is negative. For 36 and 42, there's a common factor of 6. 36 is 6 times 6, and 42 is 6 times 7. So let's cancel a common factor of 6 between numerator and denominator. So the answer here is going to be that x is equal to -6/7. So just coming back to this one, again, for this type of problem, the check is going to be optional. You're not going to end up with an extraneous solution here. So let's go ahead and plug in for x there. So we have 9 log base 7 of -6 times, you have -6/7, and then -5, and then close that down, and then we have -10. Let me slide this down here, and we'll say this equals -19. Okay, so we know that negative times negative is positive, and so what I'm going to do is actually just get rid of these instead of just canceling them. And 6 times 6/7 is 36/7. So this right here is 36 over 7. Now for this, for 5, let's multiply that by 7 over 7. So this would be 35 over 7. So you get 36 minus 35, that's 1 over 7. So this is 1 over 7. And we saw earlier that we wrote that as 7 to the power of negative 1. So let's write 7 to the power of negative 1. So log base 7 of 7 to the power of negative 1 is negative 1. So this right here becomes 9 times negative 1, which is negative 9. So you get negative 9 minus 10 equals negative 19. So yeah, that's a true statement. So you get negative 19 equals negative 19. So x equals negative 6/7 is a valid solution. All right, for problem 4, we have log base 6 of negative 13x minus 3 is equal to log base 6 of x squared plus 27. Now for this problem, since your bases here are the same, you're going to set the arguments equal to each other. So you're just going to say negative 13x minus 3 is equal to x squared plus 27. Let me make this a little bit better there. So the first thing is, let's subtract x squared away from each side of the equation. So this would cancel. And let me subtract 27 away from each side of the equation. So that's going to cancel. We'll have 0 on the right. And basically, you're going to have negative x squared. And then you're going to have minus 13x. And then negative 3 minus 27. That would be minus 30. And this equals 0. For this right here, we would multiply both sides by negative 1. So that would change the sign of everything on the left. And of course, 0 times negative 1 is still 0. So this would be positive x squared plus 13x plus 30 is equal to 0. So just multiplying both sides by negative 1. Okay, so this is something you're going to be able to solve with factoring. So let's go ahead and set this up. We'll have an x here and an x here. Give me two integers whose sum is 13 and whose product is 30. That's going to be 10 and 3. So plus 10 and then plus 3. And I think you know that the solutions will be x equals negative 10 and then x equals negative 3. But for the sake of completeness, let's write this out. So x plus 10 is equal to 0, or x plus 3 is equal to 0, just using the zero product property. So subtract 10 away from each side of the equation. This cancels. You get x is equal to negative 10. And then or subtract 3 away from each side of the equation. This cancels. You get x is equal to negative 3. Let me come back up here and write x is equal to negative 10 or negative 3. And we're going to check these. Again, for this problem, you're not going to get extraneous solutions. You're just going to get those when you have some condensing that you're doing. And we're going to see that as we move forward. All right, so I'm just going to plug in a negative 10 to start for each x. So you have log base 6 of negative 13 times negative 10 and then minus 3. So negative 13 times negative 10, that's positive 130. And positive 130 minus 3 would be 127. Okay, let me close that down there. And this equals, you have log base 6 of negative 10 is plugged in for x. You got to be careful because the negative 10, that needs to be wrapped and you're squaring that. So if you're keying this into a calculator, make sure you wrap this with parentheses. So this becomes positive 100 and then plus 27. So that's 127. And at this point, we know that these two sides are equal. So log base 6 of 127 is equal to log base 6 of 127. That is the same number. So we can just put a check there. Okay, for the other one, you have log base 6 of negative 13 times negative 3. Well, negative 13 times negative 3 would be positive 39. And then positive 39 minus 3 would be 36. Now this one you could write as 6 squared, like that. And of course, this would give me 2. Log base 6 of 6 squared would be 2. So you can replace this with 2 if you want. Not necessary. Over here, again, if you're plugging in on negative 3, make sure you wrap that if you're doing this with a calculator. So log base 6 of, you're going to have negative 3 squared, and then plus 27. So this would be 9. And then 9 plus 27, we know that's 36. And again, you can write 36 as 6 squared. Log base 6 of 6 squared, that's going to be 2. So you get 2 equals 2. So again, this is a valid solution. All right, let's take a look at problem 5. So here we have log base 7 of 8x plus 1 is equal to log base 7 of x squared plus 1. Again, this base is the same as this base. So I could just set these arguments equal to each other. This is all I have to do. So I'm going to solve 8x plus 1 is equal to x squared plus 1. Let me grab this real quick. And let me just come down here to this fresh piece of paper. And basically, you have 1 on this side and 1 on this side. So you could just cancel it away. For the tutorial, let me actually show this. So I'm subtracting 1 away from each side. So that cancels and that cancels. So you have 8x is equal to x squared. Well, I think you can eyeball that and tell that the solutions would be 0 and then also 8. But for the sake of completeness, let me do this with factoring. Let me subtract 8x away from each side of the equation. So this would cancel and give me 0 on the left. I'm just going to flip this around and say we have x squared minus 8x is equal to 0. So at this point, we're going to factor out an x. So you have x times the quantity, x minus 8, and this equals 0. So by the zero product property, we can say that x is equal to 0. So that's one solution. Or x minus 8 equals 0. So the other solution would be x equals 8, right? So let's add 8 to both sides for completeness. This cancels, and of course you get x equals 8. Let me just write that in there. Okay, let's come back up here and say x equals 0 or 8. Again, for this type of problem, generally speaking, you're not going to get extraneous solutions. So you just plug in and check. This is going to be really, really easy. So you have log base 7 of 8 times 0 would be 0. So this is just 1. And this equals, you have log base 7 of, if you plug in a 0 for x, again, 0 squared would be 0. So you just have 1. So at this point, you can see that you have the same number on each side. This would evaluate to be 0. So 7 to the power of 0 would be 1. So you could replace this and say that this ends up with 0 is equal to 0. That's up to you if you want to do that. Once you get to the other point, you could just stop and say this is valid. Okay, if you plug in an 8, you would have 8 times 8, which is 64. And then 64 plus 1 is 65. So you'd have log base 7 of 65 is equal to, let me make this 5 a little bit better. You'd have log base 7 of 8 squared is 64. 64 plus 1 is again 65. So you have the same number on each side. So 8 is a valid solution as well. All right, for problem 6, we're given log of 3 minus 4x minus log of 7 is equal to 1. Now, hopefully you know this at this point. If you just see log and there's no base down here, the base is implied to be 10. This is the common logarithm. So when we look at this problem and we think about, well, how are we going to get a solution? We're not going to be able to set these two logarithms equal to each other because you have this loose number over here. If this wasn't over here, if this was 0, well, then I could just add log of 7 to both sides, and then I could set the arguments equal, and I'd be done. I could just solve that equation. But you can't really do that here. So basically, you're going to use your properties of logarithms, and specifically, you're going to use your quotient rule for logarithms. So let's remind ourselves of that. If you have something like, let's say, log base a of, let's go with x over y, this is equal to log base a of x minus log base a of y. So we're just going to use this in reverse. We're going this way. That's the condensing. So all we'll do here is say that we have log, again, this is with a base of 10, so I'm not going to write it. So let's go of, you're going to take this guy right here. That's going to be your numerator. So 3 minus 4x over. You're going to take this guy right here, this argument. That's going to be your denominator. So 7. Say this is equal to 1 now. When you do this condensing here, this is what ends up causing these extraneous solutions. In this case, because this is a 7 right here, it's not really going to give me an extraneous solution. But if you have an expression here, some algebraic expression with a variable, and you have an algebraic expression here with a variable, that's where you have to be very, very careful. Again, I'll show you why this is happening when we get to an example with extraneous solutions. Let me slide down here. Now let's just put this into exponential form. It might be helpful to put the base of 10 in here so it reminds you that this would be 10 to the power of 1. So 10 to the power of 1 or just 10. And that equals your argument for the logarithm. So 3 minus 4x over 7. Okay, pretty easy equation to solve. Let me get rid of this exponent of 1 here. We don't need it. I would multiply both sides by 7 just to get things started. So this would cancel. You're going to have, let's go negative 4x plus 3 is equal to 7 times 10 is 70. Let's subtract 3 away from each side of the equation. That's going to cancel. You get negative 4x is equal to 70 minus 3 is going to be 67. And to finish things up, let's just divide both sides by negative 4. That's going to cancel. And you're going to get x is equal to positive over negative is negative and just 67 over 4. 67 is a prime number and 4 is 2 times 2. So you really can't do any better than that. So let's grab this real quick. Okay, let's come back here and paste this in. And we're just going to check. Maybe it's better to just put this out of the way like that. So I'm just going to plug in for x there. So log of 3 minus, you have 4 times negative 67 over 4. Let me go plus negative here. Negative times negative is positive. Let me just cross those out. 4 over 4 would be 1. So basically you're left with 3 plus 67, which is 70. So this is the log of 70. And then you have minus the log of 7, does that equal 1? Okay, you could punch this into a calculator if you want to and verify that it's 1, or an alternative approach is to break this up into 7 times 10. So like that. Let me slide down a little bit, and this answer is going to go off the screen, and I want to be able to check mark it. So let me put this down here, and then we can slide down a little bit. And basically, using the product rule for logarithms, you can now legally break this up and say this is the log of 7, and then plus the log of 10, and then minus the log of 7, and this equals 1. Okay, so we know that log of 7 minus log of 7, well, those are going to cancel. That's going to be 0. So now I have log of 10 is equal to 1, and that is a true statement. Again, remember that the base here is implied to be 10. So essentially, this is log base 10 of 10, and of course that equals 1. 10 to the power of 1 gives me 10, so this is 1 equals 1, so this is a valid solution. X equals negative 67 over 4. All right, let's take a look at problem 7 now. So we have log base 3 of 3 minus 5x, then plus log base 3 of 7, and this equals log base 3 of 24. Okay, so what I'm going to do is condense on the left side here because you have this base of 3 and this base of 3. And again, if this is addition right here, you can use your rule. So again, log, let's say base a of x, and then plus log base a of y. You can condense this and say this is equal to log base a of x times y. So that's all we're going to do. Let me get rid of this. And we're going to say that this is log base 3 of. You're going to multiply these guys together. You can have 7 times the quantity, 3 minus 5x. So you have to make sure to use parentheses here because this 7 needs to multiply by the 3 and also the negative 5x. And this equals log base 3 of 24. Let me make the 3 better there. So let me say this is log base 3 of 7 times 3 is 21, and then minus 7 times 5 is 35, and then of course times x, and let's close that down, and this equals log base 3 of 24. Okay, at this point, you have the same base on each side. So you could just set the arguments equal to each other. So let's go ahead and say that 21 minus 35x is equal to 24. And what I'll do is subtract 21 away from each side of the equation. So this cancels. We'll slide down. We'll have negative 35x is equal to 24 minus 21 is going to be 3. Let's go ahead and divide both sides of the equation by negative 35. This will cancel. We're going to end up with x is equal to positive over negative is negative. So this is 3 over 35. All right, so let's come back up here. So once again, this is an example where you're not going to end up with an extraneous solution, and that's because this is a 7, so that's always going to be a 7. It's never going to be something that could be negative. If you had an algebraic expression like this here and also here, well, that's where you're potentially going to get extraneous solutions. Okay, so let's just plug in. We have log base 3 of, we have 3. You're going to have, let's go plus negative 5 times for x, this negative 3 over 35. Okay, so let's go ahead and say that negative times negative is positive, and then 35 divided by 5 is 7. So basically, this is going to be 3/7 here. So let me put 3 plus 3/7. Now you can multiply 3 by 7 over 7, and that would give you 21 over 7. And so 21 plus 3 is 24. So this would be 24 over 7. So let's write 24 over 7. And then let's go plus log base 3 of 7. So is this equal to log base 3 of 24? Again, you could do this with a calculator, but you could also just, again, use your quotient rule for logarithms, and you can break this up and say this is log base 3 of 24. And then you would go minus log base 3 of 7. And then you have plus log base 3 of 7. Does this equal log base 3 of 24? Yes. So you can see that negative log base 3 of 7 plus log base 3 of 7, that's going to cancel. That's 0. So you're left with log base 3 of 24 is equal to log base 3 of 24. So this is a valid solution. X equals negative 3 over 35. All right, for problem 8, we have log base 5 of 4x squared plus 7 minus log base 5 of 9, and this is equal to 1. So again, we're going to use the fact that this base is a 5 and this base is a 5, and you have subtraction to condense, right? So we're going to use our quotient rule for logarithms. Let me write that one more time. So if you have log, let's say base a of x, and then minus log base a of y. This is equal to log base a of x over y, like that. So we'll use this to condense. Let me get rid of this. And we'll say that this is log base 5 of, this will be your numerator, so 4x squared plus 7 over, this will be your denominator, so 9, and this equals 1. So for this one, you're just going to put it into exponential form. So 5 to the power of 1, or just 5, is equal to your argument here. So this is 4x squared plus 7 over 9. The first thing I would do is just multiply both sides by 9. That way you can clear this denominator. So this would be 4x squared plus 7 is equal to 45. So subtract 7 away from each side. Let's cancel this. And let's say we have 4x squared is equal to 45 minus 7. Well, that's going to be 38. Let me slide down. Let's divide both sides by 4. This cancels. And you get x squared is equal to 38 is 19 times 2. So this is 19 times 2. And obviously 4 is 2 times 2. So let's cancel a common factor of 2 between numerator and denominator. So you get x squared is equal to 19 over 2. Okay, by the square root property, we can say x is equal to plus or minus the square root of 19 over 2. And let's simplify this. Let's break this up into the square root of 19 over the square root of 2. All right, so for this, I would rationalize the denominator. So I'd multiply by the square root of 2 over the square root of 2. So that gives me that x is equal to plus or minus square root of 19 times square root of 2. That's just going to be the square root of 38. And this is over square root of 2 times square root of 2 is 2. Okay, let's come back here and paste this in. So checking this one is very easy. Again, because this right here is a 9, you're not going to have an issue. So let's go log base 5 of 4 times, for x squared, you have the square root of 38 over 2. You could put the plus or minus in there, but because you're squaring this, you can really leave this off, because whether this is a positive or a negative, when you square it, you're going to get a positive. So you can just leave that out. And then let's go plus 7. And let's just stop there for a moment. So if I square the square root of 38, that's 38. If I square 2, I get 4. So this would be 38 over 4. So 38 over 4. And of course, the 4s would cancel. So now you have 38. So 38 plus 7. And that's going to be 45. So this is 45. And then you have minus log base 5 of 9. And this equals 1. Again, if you want, you can just use a calculator, or you can use some properties from logarithms. So write 45 is 5 times 9. And so you can say this is log base 5 of 5, which of course is 1. And then you'd have plus log base 5 of 9. And then you'd have minus log base 5 of 9. And this equals 1. Well, we know that this part right here is going to cancel. So log base 5 of 9 minus log base 5 of 9, that's going to be 0. So you're left with log base 5 of 5 equals 1. And of course, log base 5 of 5 is 1. So you get 1 equals 1. So this guy right here is going to be a valid solution. X equals plus or minus, both would work because we're squaring there, the square root of 38 over 2. All right, let's look at problem 9. So this is one where you have to be really, really careful about extraneous solutions. So we have ln, which is the natural log. Remember, this is the same thing as log base e of x minus 13 there. So these mean the same thing. So we have ln of this x minus 13 plus ln of x minus 3. This equals ln of 75. All right, so the first thing I'm going to do here is condense. So I'm going to write ln, or the natural log of, these guys are going to get multiplied together. Let me actually use a bracket here, and I'm going to show this like this. So this is x minus 13, this quantity times the quantity x minus 3. So I'll show you why this is going to give us extraneous solutions at the end. For right now, let me just write this here. And then let me go, this equals ln, or the natural log of 75. Okay, let me copy this. I'm going to leave this here for later on. I'm just going to come to a fresh sheet and we'll work here. We know that this ln, or natural log, is a log with a base of e. So you have that here and you have that here. So what you can do is just set these arguments equal to each other and just solve that equation. So this would be x squared. And then your outer would be minus 3x. Your inner would be minus 13x. Your last would be plus 39. So negative 3x minus 13x, that would be negative 16x. Let me put that like that. So x squared minus 16x plus 39 would be equal to, over here, this is 75. So because this is a quadratic, I would subtract 75 away from each side of the equation. This cancels and gives me 0. Let's say now that we have x squared minus 16x, and then 39 minus 75, that's going to be negative 36. And of course, this equals 0. All right, so we're going to try to solve this with factoring. So when you think about 36, the first thing that comes up is 6 and 6, but that's not going to work. You're trying to get a sum of negative 16 and a product of negative 36. So when you think about 36, first you do 1 and 36, so that's not going to work. But then the next one would be 2 and 18. So I can make that work. So if I go x here, and then I go positive 2 and negative 18, well, positive 2 minus 18, or positive 2 plus negative 18, if you want to say it that way, that would give you negative 16. And then positive 2 times negative 18, that would give you negative 36. So this is what you want. Let's go ahead and say that x plus 2 is equal to 0, or x minus 18 is equal to 0. So we would subtract 2 away from each side of the equation. This cancels. You get x is equal to negative 2. Then or, we'll add 18 to both sides of the equation. This cancels. You get x is equal to 18. So now let me explain why one of these solutions is not going to work, why it would be extraneous. If you go to the original equation and you plug in a negative 2, you will notice that, let me slide this out of the way real quick. So if you have the natural log of negative 2 minus 13, you can immediately stop, right? You don't even have to go further. This is going to end up giving you negative 15. We know that this is going to be undefined, right? So you can't have a negative argument here. And then plus, if you keep going, so the natural log of negative 2 minus 3, that's negative 5. And this equals the natural log of 75. So this right here, as soon as you plug it in, you see, oh, there's a problem. So this one's going to be extraneous. You can mark it out. Now, why does it end up working in that equation that we set up? It's because these two guys here got multiplied together. So negative times negative gives me a positive. So here, the negative 2 would actually be defined. So in other words, if you go and plug this in, so you have the natural log of, let's say you have that negative 2 minus 13, that's negative 15. So negative 15 times negative 2 minus 3, that's negative 5. So that would be positive 75, right? So this ends up giving me the natural log of 75 is equal to the natural log of 75. So that gives me a valid solution. But that does not work in this original equation. When we condensed this equation, we created a new equation with solutions that don't work in the original. So you have to be very, very careful and always check things in the original. If you checked it in the modified form, okay, it's going to work, but it doesn't work in the original, so you have to reject it. So now the next one, that's going to work whether you plug it in here or here. I'm just going to get rid of this. We don't need this anymore. So if you plug in at 18 there, 18 minus 13 is 5. So this would be the natural log of 5. And then plus, you have the natural log of 18 minus 3 is 15. Does this equal the natural log of 75? Again, you can just say that this is the natural log of 5 times 15, which is 75. And this equals the natural log of 75. So this one would work, right? So it works in the original. That's what you're looking for. So x equals 18 is your only valid solution. All right, let's take a look at problem 10. So here we have the natural log of x plus 3 minus the natural log of x minus 1. This equals the natural log of 4. So be very, very careful. Notice that you have this algebraic expression here and an algebraic expression here. So here's where we really have to check for extraneous solutions. So we're going to use, again, the quotient rule for logarithms. One more time. Log base a of x minus log base a of y is equal to log base a of x over y. That's what we're using here to condense. Let me get rid of this. And let's say this is ln, or the natural log of, you're going to have x plus 3 over, you're going to have x minus 1. And this would be equal to the natural log of 4. We're just going to set these two arguments equal to each other. So let's go x plus 3 over x minus 1 is equal to 4. Okay, so what I would do is multiply both sides by x minus 1. So let's say times x minus 1, and then times, this would be a quantity x minus 1. So this would cancel. And let's say we have 4 times the quantity x minus 1 is equal to x plus 3. So this right here is going to be distributed to each guy. So you're going to have 4x minus 4 is equal to x plus 3. Let's subtract x away from each side. This cancels. 4x minus x is 3x. Let's add 4 to both sides. So this would be equal to 7. Divide both sides by 3 to finish things up. And we're going to say that x is equal to 7 thirds. Okay, coming back up, let's put x is equal to 7 thirds. You're not going to have an extraneous solution in this case. Let me move this down here. But you do need to be aware of it. Again, if you're dividing things here, if you're dividing or you're multiplying, well, then you could have a negative divided by a negative giving you a positive. And so something that's going to work out in your transformed equation is not going to work in the original because you would have had something that's undefined. So you have to be very careful when you get this situation. Okay, with that being said, let's just plug in. You can get rid of this. You don't really need it anymore. Let's say that this is the natural log of 7/3 plus 3. So let's write 7/3 plus, let's go 9/3. So we can have a common denominator. So 9 plus 7 is 16. So this would be 16/3. And then minus, you'd have the natural log of, this is 7/3 minus 1. You could write that as 3/3. So 7 minus 3 is 4. So this is 4/3. So 4/3. And this equals the natural log of 4. Okay, so for this one, if you don't want to use a calculator, you could just say that this is the natural log of, you're going to go 16 over 3, and you're going to divide by 4/3. So you can do that by multiplying by the reciprocal. So times 3/4. So the 3's would cancel, and 16 divided by 4 is 4. So this is going to give me ln, or the natural log of 4, is equal to your natural log of 4. So we have the same number on the left as we do on the right. So x equals 7/3 is a valid solution. In this lesson, we want to talk about solving exponential and logarithmic inequalities. All right, before we get started with any problems, I'm going to give you a few rules that you can use to quickly solve any exponential inequality. And then as we get into logarithms, I'll give you some rules for those. If you don't want to memorize these rules or they're a little bit difficult for you, you can always just turn to the test point approach. Okay, so for the first thing, we have that a is greater than 1 and x is greater than y. So what is a? That's the base in this exponential inequality. What is x? That's your exponent over here. What is y? That's your exponent over here. So if this part is true, we can conclude that a to the power of x is greater than a to the power of y. So for example, let's say you had something like a 2 here and a 2 here. So this is a base that's greater than 1. Well, if I want to put a greater than symbol here, then it must be true that the exponent here is larger than the exponent here. There's no other way to make that a true statement. So let's say I choose something like a 3 here and a 2 here. Well, this would be a greater than. This would be 8, and then this would be 4. 8 is obviously greater than 4. If you wanted to use a less than there, well, then you'd have to make this exponent here smaller than this exponent over here. So let's say you picked a 5 here and a 7 here. Well, because this exponent is smaller than this exponent, and this is a 2 and this is a 2 for the base, well, we can conclude that this is a less than here. 2 to the 5th power is 32. That's going to be less than 2 to the 7th power, which is 128. If you want to think about this with a graph, a lot of books will show it this way. You can pick something where the base is greater than 1. So let's just say we pick 2 to keep it easy. So y equals 2 to the power of x. Over the entire domain of this function, as the x values increase, the y values are also going to increase. So as a simple example, let's just say we pick an x value of 2. So you plug that in, 2 squared is 4. So the y value is 4. So obviously that leads to the point, which is going to be right here. So this is going to be 2, 4. Now let's say you pick an x value to the right of 2. So let's say we pick an x value of 3, just to keep it simple. We would expect that the y value is going to increase, and of course it will. So now we get a y value of 8. So this right here would be the point 3, 8. But the main thing is to see that as the x value increases here, so we go from 2 to 3, the y value increases, we go from 4 to 8. And the way you would relate that is you say, okay, well, if I had 2 here and 2 here, again, the base is 2 for this. So if I plug in a 2 here, and then if I plug in a 3 here, well, then I know because this guy right here is increasing over the entire domain, while this x value right here is going to produce a smaller value than if I plugged in this x value right here, because this is smaller than this. So it must be true that this is a less than here. So this would be 4 is less than 8. Again, this is the y value of 4. This is the y value of 8. So that's another way to think about it. All right, so this next rule is really going to give a lot of students trouble. So you have that a is greater than 0 and less than 1. So basically a is between 0 and 1 with both being excluded, and x is greater than y. What happens is you have to flip the direction of the inequality symbol. So you might be given this way. So a is greater than 0 and less than 1. And you might see and, let's go with a to the power of x is less than a to the power of y. Well, you can conclude that x has to be greater than y. So whether you see it this way or this way, it's telling you the same thing. In other words, let's say we took something like 1/2. So something like 1/2, that is obviously going to fit in here. So 1/2 is greater than 0 and it's also less than 1. And let's put 1/2 right here. Now let's say that I took an exponent here that is larger than the exponent here. Let's just say we put a 3 here and a 2 here. Well, 1/2 cubed, that's going to give me 1/8. 1/2 squared, that's going to give me 1/4. So this exponent is larger than this exponent, but at the end of the day, I need a less than here and a less than here for this to be a true statement. 1/8 is less than 1/4. Again, you can always go to the graph of something like y equals 1/2 to the power of x if you want a visual representation of what's going on. For this one, as the x values are increasing, the y values are decreasing, and this is over the entire domain. So let's say we pick something like an x value of -2. Let me actually plug that in so nobody's lost. So y equals, let's say 1/2 raised to the power of -2. This would be equal to 1 raised to the power of -2 over 2 raised to the power of -2. So this is equal to 1 raised to the power of -2 is just 1. You can drag this across the fraction bar and change the sign of the exponent. So this would be 2 squared, which is 4. So the y value here would be 4. Let me get rid of this, and we'll just put this point here. So let's say that this is going to be right here, and that point is going to be -2, 4. Now to pick something easy, because it's hard to get stuff down here because you don't really have integer values to match up with it, let's say we pick an x value of 0. That's going to be right here. So that's your x value of 0. Well, what's the y value going to be? 1/2 raised to the power of 0 is going to be 1. So that's going to be your point right there. And notice that if we look at it, you get 0, 1. So the x value increased. It went from -2 to 0, and the y value decreased. It went from 4 to 1. So in other words, let me write this out. So you have 1/2 here raised to the power of -2, and then you have 1/2 here raised to the power of 0. So because this guy right here is less than this guy right here, we need to use a greater than here. So the sign flips when you compare it to the exponents. -2 is obviously less than 0, but when you set this up, you've got to flip the direction of the inequality symbol. This is the one that gives students a lot of trouble. This ends up giving you 4 is greater than, this ends up giving you 1. So this would be a true statement when you put the greater than symbol in. Okay, let's go ahead and look at the first example. So I'm going to do this twice. I'm going to do it the first way using our little rule, and then I'll do it again using the test point approach if you want to do it that way. So first and foremost, I would write this as having a common base of 2. You have 2 here, you have 4, which is 2 squared, you have 64, which is 2 to the 6th power, and you have 8, which is 2 cubed. So I'm just going to say that this is 2 raised to the power of 3x plus 2, and then times, I'm going to write this as 2 squared raised to the power of -x, and this is greater than or equal to. For 64, this is 2 to the 6th power, and this is over. For 8, that is 2 cubed, and then raised to the power of x. Let me slide down here a little bit. And at this point, what I'm going to do is just use my power to power rule to simplify. So 2 to the power of 3x plus 2, and then times, for the power to power rule, 2 stays the same. You're going to multiply 2 times -x. That's -2x. This is greater than or equal to. So here you're going to go 2 to the 6th power over. This would be 2 stays the same. Multiply exponents. 3 times x is 3x. Okay, so a lot more that we can do here. We're going to use the product rule for exponents over here, and we're going to use the quotient rule for exponents over here. So 2 would stay the same, and you're going to add your exponents. So you'd have 3x plus 2, and then plus this -2x. This is greater than or equal to. Over here, you'd keep 2 the same, and you'd subtract 6 minus 3x. So again, this is the quotient rule for exponents. 2 stays the same. You subtract the exponent in the numerator, which is 6, minus the exponent in the denominator, which is 3x. At this point, you could do 3x minus 2x. That's going to be x. So let me write this as 2 to the power of x plus 2. And we're going to put is greater than or equal to 2 to the power of 6 minus 3x. I'm going to copy this real quick, and I'm going to come down here and paste this in and leave this. I'm going to come back in a little while to this point and do the test point approach with you. For right now, let me come to another sheet, and we'll just continue with the rule. So when we think about how to solve this, you have a base of 2 and a base of 2, and you have a greater than or equal to here. So the only way that this would be true is if this exponent right here, this x plus 2, is greater than or equal to this exponent right here, which is 6 minus 3x. And that is true because we have this base of 2 and this base of 2, which is greater than 1. So that's why we're keeping the sign the same. This is very easy to solve. We're just going to subtract 2 away from each side of the inequality. So this is going to cancel. Let's add 3x to both sides of the inequality. And so this would cancel. And so on the left, x plus 3x is 4x. This is greater than or equal to. We have 6 minus 2, that's going to be 4. Divide both sides of the inequality by 4. Let's say that this would cancel. You're going to get x is greater than or equal to 4 over 4 is 1. So that's your solution. X is greater than or equal to 1. Let me come down here and write this. So X is greater than or equal to 1. A lot of people, when they solve inequalities, they want to do interval notation. So basically, you put a bracket next to 1 because that's included, and then you're going to put infinity here. So we're going to go out to positive infinity. Okay, so here we go to positive 1, and we're going to put a bracket. So that means it's included. Again, a lot of books will use a filled-in circle. If you're more comfortable with that, you can use it. It's the same thing. Then we're going to shade everything to the right here. So that's graphing on the number line. All right, let me show you a little way that you can check this. So I'm starting with 2 to the power of x plus 2 is greater than or equal to 2 to the power of 6 minus 3x. I'm going to subtract this away from each side. So let me write this as 2 to the power of x plus 2, and then minus 2 to the power of 6 minus 3x. Let's put that is greater than or equal to 0. You can delete this form now. And basically, look at what we've graphed here. So you can do this on Desmos. You have y equals 2 to the power of x plus 2 minus 2 to the power of 6 minus 3x. So this right here is equal to y. So I have the same thing over here. I want to know where the y values are greater than or equal to 0. So that means I'm either going to be on the x-axis, so that's my x-intercept right there. So this point, if you arrow to it, this is 1, 0, or anything where the y values are above that. So another way to say that is, for which x values am I going to get y values that are greater than or equal to 0? Well, you would see that it's at 1 or anything to the right of 1. So we could say that x is greater than or equal to 1. So that's how you could show that graphically. You want this right here, again, where the y values are either 0 or greater than 0. Okay, in case you're struggling with the rules, you can always use the test point approach. So essentially for this problem, you know that you're going to have a common base of 2 on each side. So there's no need to use logarithms or anything like that. So just get it to this point, and then you're going to replace this with equals. So now I have an equation. I have 2 to the power of x plus 2 is equal to 2 to the power of 6 minus 3x. Why are we doing that? We're getting the critical value here, which is going to be at 1. And that's going to separate the solution region from the non-solution region. So basically, if you solve this, you can just set this exponent right here equal to this exponent right here. So we're going to say x plus 2 is equal to 6 minus 3x. Let's add 3x to both sides of the equation, and then let's subtract 2 away from each side of the equation. So let's go ahead and say that this is going to cancel, and this would cancel. So x plus 3x is 4x, and this equals 6 minus 2 is 4. Divide both sides of the equation by 4. This cancels, and you're going to get that x is equal to 1. So let me erase this and just put that x equals 1. That right there is your critical value. Okay, so that's what you need to know. A lot of people call this a boundary. So let me grab this real quick. So we'll come to the number line. The way I do this is I would subtract this away from each side. That way I can just key it in and see if it's positive or negative, and then I can make a decision. So at 1, we know it would work. We're going to forget about that for right now. So again, let me put a little border here. So let's call anything to the left of 1 region A, and then anything to the right of 1, let's call that region B. And you just want to pick a number and test. I just want to know if it's greater than 0 or less than 0. I know it's 0 at 1, so I don't need to worry about that. I'm just checking something on each side. So for region A, I'm just going to pick 0. You plug that in. Let me put this off to the side. You would get 2 to the power of 0 plus 2 is 2. So this would be 2 squared minus 2 to the power of, if this was 0 right here, 3 times 0 is 0, so you'd have 2 to the power of 6. So 2 squared minus 2 to the 6th power, this would be 4 minus 64, so that would give you negative 60. So you get negative 60 is greater than or equal to 0, which is a false statement. So this is false. So you can reject anything in region A to the left of 1. And we already know from solving this problem that things to the left of 1 don't work. So you can put an F here for false. Okay, let's check something on the right side of 1. So you can pick 2. So you'd have 2 to the power of 2 plus 2, which is 4. And then minus 2 to the power of 6 minus. You're going to have 3 times 2 there. 3 times 2 is 6. So this right here would be 6 minus 6, which is 0. 2 to the power of 0 is 1. So this would be 2 to the 4th power minus 1. So that would be 16 minus 1, which is 15. So you get 15 is greater than or equal to 0. So that is true. So I'm going to put a T here for true, so that would work. So once you find the region that works, that's how you set up your solution. You would say that things in region B are going to work. So that's where we're greater than 1. And because it's a non-strict inequality, 1 would work. So you just set up your solution and say that x is greater than or equal to 1. So that's the test point approach. If you want to do it that way, it's a lot longer, but it's going to stop you from making simple mistakes. If you're good on the rules that I talked about, then you could just use that strategy. All right, let's look at another problem. So for this one, I'm going to use a base that's between 0 and 1, with both being excluded, so I can show you how you need to flip. So here we have 1/8 raised to the power of 3 minus 3x times 1/4 raised to the power of 2x. This is less than 16. So I'm going to choose to use a base of 1/2. So let me go ahead and do that. So 1/2. And then how would I get to 1/8 from 1/2? Well, I would need to cube this because 1 cubed is going to be 1. And then basically 2 cubed is going to be 8. Let me go ahead and put some brackets in here. And now I'm going to use this exponent right here. So 3 minus 3x. So just writing this with a base of 1/2 here. Then times. I'm going to do the same process here. So 1/4 is really 1/2 being squared. Let me put some brackets in like that. This is raised to the power of 2x. And this is less than. For 16, how can I write that with a base of 1/2? So let's go 1/2 like this. You would need to raise this to the power of -4. You can use the power to power rule to simplify this and this. Don't need to do anything over here. So keep 1/2 the same and just multiply the exponents. So you have to multiply 3 by the quantity, 3 minus 3x. So that would be 3 times 3, which is 9, minus 3 times 3x, which is 9x. So that's going to be 9 minus 9x. Then we have times. Over here, you have your base of 1/2, and this is raised to the power of 2 times 2x, which is 4x. And this is less than. You have your 1/2 raised to the power of -4. Okay, at this point, what we're going to do is use our product rule for exponents to simplify over here. You have a base of 1/2 and a base of 1/2 in multiplication. So keep 1/2 the same, and you're going to add the exponents. So if you do -9x plus 4x, that's -5x. And then you have plus 9, and this would be less than here. You have your 1/2 raised to the power of -4. So here's where you need to turn to your rule. This base is 1/2 and this base is 1/2. If that base is between 0 and 1, with both being excluded, the direction of this has to be flipped. I'm going to put flip when you set up your inequality. So in other words, you're going to go -5x plus 9, not is less than, you want to be greater than -4. If you forget to do this, you will get the wrong answer. So this is where if you're making mistakes, you might want to turn to the test point approach like we did in the last problem. Okay, at this point, you're just going to solve a very simple inequality. Let me grab this real quick. We're actually going to go back to that point in a minute, and I'm going to show you how to solve it in a different way. So let's subtract 9 away from each side of the inequality. This cancels. You get -5x is greater than -4 minus 9. That's going to be -13. Let's divide both sides of the inequality by -5. Now remember, if you're working with an inequality and you divide both sides by a negative, again, you have to flip the direction of the inequality symbol. So let's say that we have x. This greater than here becomes a less than. Let me cancel this with this. And negative over negative is positive. You get 13/5. So x is strictly less than 13/5. So as a decimal, 13/5 is 2.6. So let's just put a notch maybe about right there. I'll just arrow to that and say it's 2.6, or you could also say it's 13/5 if you want to write it that way. And x is strictly less than 13/5, so in interval notation from -infinity going up to and excluding 13/5. So you want to use a parenthesis next to 13/5 to show it's not included. And again, for the graphical representation of this on the number line, you can use an open circle to show that it's not included, or you can use a parenthesis facing to the left, which is what I always do. And then you're just going to shade everything here to the left. So just like that. Okay, I'm going to come back to this point and show you an alternative way to do this. So let me actually erase this and erase this flipping here. I'm just going to start from this point, but you could do this at any point. You could have done this at the beginning of the problem. Let's say that I'm a little bit confused or a little bit shaky about the rule, and I don't want to go through the trouble of using the test point approach. What you could do is actually write 1/2 as 2 to the power of -1. And then this would be raised to the power of -5x plus 9. This is a less than. Let's write this as 2 to the power of -1. And this is raised to the power of -4. I think you see where I'm going with this. So basically power to power rule, this -1 is going to multiply by each guy here. Let me show this so nobody's lost. So 2 to the power of, you'd have -1 times the quantity -5x plus 9. So it's just going to change the sign of each. So you'd have positive 5x minus 9. So this right here is 5x minus 9. Then we have is less than. This would be 2 stays the same. -1 times -4, that's positive 4. Now we have a base that is greater than 1. We have a 2 here and a 2 here. So all we have to do in that case is just keep the sign the same. So this stays the same. So let me put stays the same. So that's crystal clear. So this would be a less than. You take this exponent here, so 5x minus 9, and you say it's less than 4. So let me come to a new sheet. We're going to get the same answer. Let me just add 9 to both sides of the inequality. This cancels. You get 5x is less than 13. 4 plus 9 is 13. divide both sides of the inequality by 5. This cancels. And what do we get? We get that same solution of x is less than 13/5, or you could say x is less than 2.6. All right, so a good way to check this is, again, to go to Desmos and look at this graphically. So what you can do here is start with 1/2 raised to the power of negative 5x plus 9 is less than 1/2 raised to the power of negative 4. This is, of course, positive 16. So I would just replace that and then just subtract it away from each side of the inequality. So you have 1/2 raised to the power of negative 5x plus 9 minus 16. You want to know where that's less than 0. So going to Desmos, you're just going to say y equals this right here. So 1/2 raised to the power of negative 5x plus 9, then minus 16. So I want to know for which x values am I going to get y values that are less than 0, or where am I going to be below the x-axis? This point right here, if you look at it, this would be 13/5, or you can say 2.6, comma 0. So this would not work because it's a strict inequality. But anything to the left of that in terms of the x value, that's going to produce a y value that is less than 0, or where you'll be below the x-axis. So again, the solution just from Desmos, you can say x is strictly less than 13/5, or you could also write x is less than 2.6. All right, before we get to the next problem, I want to cover some rules for logarithms. So we have here that a is greater than 1. So that's the base for the logarithm here and here, and x is greater than y. So x is the argument here, and y is the argument here. Well, basically, you can conclude that log base a of x is greater than log base a of y. In other words, let's say let's use a base 10 log. I'm going to show the base here for clarity. So we have base 10 log and base 10 log. So we know that the base here is 10 and the base here is 10, and that's greater than 1. So let's say we have an argument here and an argument here, and I want to use a greater than. What must be true? Well, this must be greater than this. So in other words, something like, let's say 100 and let's say 10. That would be true. But let's say I did something like this. So log base 10 of something here, and let's go log base 10 of something here, and I want to use a less than. Well, now let's maybe use 100 and let's use 1000. This right here has to be less than this right here. And you can go through these really quickly. So log base 10 of 100, we know basically that 100, you could write this as 10 squared to make this super easy. This is 2 is greater than log base 10 of 10, that's 1. So that's a true statement. Then for this one, log base 10 of 100, we know that's 2, that's less than. Log base 10 of 1000, again, you could write this as 10 cubed. So 10 cubed, so that's going to be 3. 2 is obviously less than 3. So if you want to see this graphically, again, you can look at something like y equals the log of x. We know the base here would be 10. And you can just do this on Desmos. We can see that this is defined for x values that are greater than 0 because the argument needs to be positive. As we increase the x values, the y values are increasing over the entire domain. So something like, let's say, the log of 1, well, that's going to be equal to 0. We can see that right there. And then something like, let's say, the log of 10, well, that's going to be equal to 1, and that's kind of where the arrowhead is, but let me just put that right there. So this right here is 1, 0, and then this right here is 10, 1. So looking at this argument here is smaller than this argument here. And the base here is 10, and the base here is 10, so you can conclude that this would be a less than here. All right, for the next one, we have that a is greater than 0 and less than 1. Again, a is the base for the logarithm, and then we have that x is greater than y, x is your argument here, y is your argument here. So just like we saw with the rule for exponential inequalities, you have to flip the direction of the inequality symbol. So this is a greater than, this is going to be a less than. So something like, let's say log base 1/10 of, let's just go ahead and say 10, and let's go log base 1/10 of, let's say, 100. Without evaluating this, let's think about this rule. So this base right here is between 0 and 1, both being excluded. This right here is a 10, and this right here is 100. We know that 10 is less than 100. But based on this rule, because of where the base is, we need to flip the sign here. So instead of this being a less than, it needs to be a greater than for this to be true. And let's check that real quick and make sure that our rule is working. If we think about 10, you could write that, let me write log base 1/10. You could write that as 1/10 raised to the power of -1. So this right here would be log base 1/10 of 1/10 raised to the power of -1. That would be -1. And then this over here, let me write is greater than. We have log base 1/10 of, I'm going to write 100 as 1/10 raised to the power of -2. So this would be greater than this would end up being log base 1/10 of 1/10 raised to the power of -2, and that's -2. So is this true? Is -1 greater than -2? Yes. -1 is to the right of -2 on the number line, so this is a true statement. So I went ahead and just made a graph of y equals log base 1/10 of x. Again, you can do this with any base that's between 0 and 1 that you want, and you'll see as the x values are increasing, the y values are decreasing. Again, if you want to pick this point right here, this is going to be 1, 0, and then let's say you want to pick this point right here. So let's say right there, again, it's on the arrowhead, but that'll work for us. Let's say this is 10, -1. When you set this up, if you go log base 1/10 of 1, and then you have log base 1/10 of 10, well, since 1 is less than 10, you have to flip this to a greater than. So log base 1/10 of 1, we know that's 0. Log base 1/10 of 10, we know that's -1, and we know that 0 would be greater than -1. So again, this rule is a little bit tricky, so if you're having trouble with it, you can always just use the test point approach. All right, let's take a look at the next problem. So here we have 9 times 10 raised to the power of 4x plus 6, then minus 9. This is greater than or equal to 33. So what we're going to do is isolate this part right here first. To do that, I'm going to add 9 to both sides of the inequality. This cancels. You get 9 times 10 raised to the power of 4x plus 6 is greater than or equal to 33 plus 9. That's going to be 42. Now I'm going to divide both sides of the inequality by 9. And so this would cancel. You're going to get 10 raised to the power of 4x plus 6 is greater than or equal to, for 42, let's go ahead and write that as 14 times 3. So 14 times 3, and then for 9, that is 3 times 3, and then you can cancel a common factor of 3 between numerator and denominator. So this is 14/3 over here. All right, at this point, I'm just going to take the log of each side. So remember, that's a logarithm with a base of 10. So we're going to go log of, we have 10 raised to the power of 4x plus 6 is greater than or equal to, we have the log of 14/3. Again, I can put a base of 10 here and a base of 10 here if that makes it easier. Now you're going to simplify here. Log base 10 of 10 raised to the power of 4x plus 6, that's just going to be 4x plus 6. And then let me make this symbol a little bit better here. This would stay the same. So log base 10, or you could just write log of 14/3. Hopefully you know at this point the base is 10. And at this point, you're just going to solve for x. That's all you have to do. Let me subtract 6 away from each side of the inequality. This cancels. And then we have 4x is greater than or equal to, we have the log of 14/3 minus 6. And then basically you're going to divide both sides of the inequality by 4. Let's say that this would cancel. Let me slide down and say that x is greater than or equal to, we have this log of 14/3 minus 6 over 4. Now there's different ways you can write that. I'm going to keep it this way. Let me come down here to the number line. And basically, if you want to put this in interval notation, let me put a little border. So you have a greater than or equal to. So let me put a bracket here and just put this in. So log of 14/3 minus 6 over 4. And then I'm going to put a comma. And then you're going to put your positive infinity there. Let me slide this over so it all fits. Don't want it to go off the screen. And then you want a parenthesis next to that. Okay, so you would approximate this if you want to do this graphically. So I get about negative, let's go 1.33, just to keep it simple. So let's say it's about right there. I'm just going to arrow to that and say this is approximately negative 1. Let's go again 33, just rounding with my calculator. And basically you want to say that x is greater than or equal to this. So let me put a bracket here. And that's to show that it's included. Again, if you want to use a filled in circle, that works too. And we're just going to shade everything to the right. Okay, so once again, if you want to go to Desmos and look at this graphically, so we had 10 to the power of 4x plus 6 is greater than or equal to 14/3. So this is once we simplified. Let me just subtract this away from each side. And basically you see I've graphed y equals 10 to the power of 4x plus 6 minus 14/3. Y equals this, and this matches over here. So we want to know for which x values am I getting y values that are greater than or equal to 0. You see an arrow to this? So this is your log of 14/3 minus 6 over 4, about negative 1.33 if you punch that into the calculator. So it would work there. That's where we're on the x-axis, so that's the x-intercept. And then anything that is greater than that. So as we move to the right in terms of the x values, so you could say anything that's either about negative 1.33 or larger. All right, now let's talk about solving logarithmic inequalities. So these are definitely going to be way more tedious than solving exponential inequalities. And so when something's more tedious, there's more of an opportunity to make a mistake. So what I recommend and what I'm going to do in the practice test and the quiz, I solve these with the test point approach. With that being said, I'm going to show you the shortcut or using the rules that we developed for the lesson in case you want to use them. It's not that bad. You just really have to pay attention to what you're doing. So the first thing is when you work this problem, you have to remember that the argument for each logarithm, so you have one here and here, it has to be positive. So you want to say that negative 4x minus 7 is greater than 0 and, so you're using the keyword and, negative 2x minus 1 is greater than 0. That is the first step when you solve a logarithmic inequality. Don't do anything until you've done that. So when I look at this, I'm going to add 7 to both sides. This cancels. You get negative 4x is greater than 7. Divide both sides by negative 4. Let me make this better here. And so here we're dividing both sides of an inequality by a negative, so we need to flip. So this cancels. You get x is, this is a greater than, it will turn into a less than, and this is a 7, kind of hard to see. So this is a 7 over a negative 4, so that's negative 7/4. Let me erase this and just replace it with x is less than negative 7/4. Okay, over here, let's add 1 to both sides. And so this is gone, and basically you get negative 2x is going to be greater than 1. Divide both sides by negative 2. Again, this has to be flipped. So this has to be flipped. So this would now be a less than. This cancels. You get x is less than 1 over negative 2 is negative 1/2. Okay, let me get rid of this. If I have that x is less than negative 7/4 and x is less than negative 1/2. Again, it's got to work in both. Well, when you consider this, they're both less thans. So you want the one that is more restrictive. In other words, you want the one that includes fewer numbers because it's going to have to work in both. So this negative 1/2 is to the right of this negative 7/4. So you want to choose this one. If you go with x is less than negative 7/4, that's going to work in both. You can get rid of this now. You can just use this. And I'm just going to put this off to the side. We need to keep this in mind as we're solving. So basically here, you have your 1/9 and you have your 1/9. So what does that tell you? It tells you that you want to flip the direction of this inequality symbol when you set things up, because this base is between 0 and 1 with both being excluded. So it's got to be true that negative 4x minus 7, this right here needs to be flipped. So you're going to flip because of the base. So it's a greater than this right here. So negative 2x minus 1. If you don't flip this, you're going to get the wrong answer. So what we want to do is add 7 to both sides of the inequality, and we can add 2x to both sides of the inequality. And let's say that this would cancel, and then this would cancel. So over here, negative 4x plus 2x, that's negative 2x. This is greater than negative 1 plus 7, that's going to be 6. We're going to divide both sides by negative 2. So again, because we're dividing both sides by negative, we have to flip again. So this is going to flip. So this cancels, and you get x is, now this would be a less than, 6 over negative 2 is negative 3. So x is strictly less than negative 3. So let me get rid of this. And here's where you need to combine things. So when you do this with what you found earlier, you want to use the keyword and. So I'm going to say that this is and. Now looking at this, if we have x is less than negative 7/4 and x is less than negative 3, again, these are both going to be less thans. You want to take the one that is more restrictive. So it includes fewer values. This negative 7/4 is to the right of negative 3. So I want to just get rid of that and say the solution is x is less than negative 3, because that would work in both. So this is what you want right here. Okay, so let me write x is less than negative 3. So in interval notation, so from negative infinity going up to and excluding negative 3. Again, make sure you use a parenthesis there. Here's negative 3. So I'm going to use a parenthesis facing to the left. You can again use an open circle. We're going to shade everything to the left like that. Okay, so if you want to look at the graph, again, we started with log base 1/9 of negative 4x minus 7. We said that is less than this log base 1/9 of negative 2x minus 1. Well, if you subtract this away from each side, let me just go ahead and say this is going to be a minus here. Let me slide this down so it fits. I'll just put this over here out of the way. So this would be less than 0. So I have graphed y equals log base 1/9 of negative 4x minus 7 minus log base 1/9 of negative 2x minus 1. That matches this right here. We want to know for which x values are the y values going to be less than 0. You can see at negative 3, well, that's where it's going to be 0. That's your x-intercept. But that's not included because it's a strict inequality. You want less than negative 3. So you want this right here for your solution. That's where the y values are going to be less than 0. So you can say from the graph that this is x is strictly less than negative 3. Okay, let me show you another example that's highly similar. So you're going to see the arguments are the same. And basically the base here is now a 9 and the base here is a 9. So we know that 9 is greater than 1. So now we can just keep this sign the same. So when we look at this, again, the first thing you would do is say negative 4x minus 7 is greater than 0, and negative 2x minus 1 is greater than 0. We already solved this. We know that this leads to x is strictly less than negative 7/4. So you can go back earlier in the video if you missed that part. But basically, this is what we need for these both to be defined. Okay, let me get rid of this. And now, what you can do, again, because this base is 9 and this base is 9, you can just keep this sign the same. Let me actually show that. So, same. This would be a less than. So you just take your arguments. Negative 4x minus 7 is less than negative 2x minus 1. Okay, let me move this down. So what we'll do is add 2x to both sides. This will cancel. And let me add 7 to both sides. So this will cancel. Negative 4x plus 2x, that's going to be negative 2x. This is less than negative 1 plus 7. That is going to be positive 6. Divide both sides by negative 2. Again, we're dividing both sides of an inequality by a negative, so you have to flip this. This is x, let me show this is canceling, is greater than 6 over negative 2 is negative 3. So again, when you look at this, x needs to be less than negative 7/4, and x needs to be greater than negative 3. So both have to be true. So you could write this as a 3-part inequality and say x is going to be greater than negative 3 and less than negative 7/4. So that's what you want. So let me grab this, come down to the number line, and we can set up our solution here. So let's go negative 3 here and then negative 7/4 here. Both would have a parenthesis next to them because they're not included. And so negative 3 is right here. You put a parenthesis there. Negative 7/4 is negative 1.75. Let's just say that's about right there. Let's say that's negative 7/4. So I'm going to put a parenthesis there and then just shade everything in between. Okay, so again, if you want to look at the graph, this right here, we started with log base 9 of negative 4x minus 7. We had a less than log base 9 of negative 2x minus 1. Go ahead and subtract this away from each side. So you're going to have a minus here. Again, let me move this down so it fits. This would be a less than 0 here. We have that over here. Y equals log base 9 of negative 4x minus 7 minus log base 9 of negative 2x minus 1. Now, that matches this right here. So for which x values am I getting a y value that is strictly less than 0? We know the y value is 0 at negative 3. Again, that's your x-intercept, but we want less than 0. Because we can only plug in values for x that are less than negative 7/4, we're looking at this piece of the graph right here. So this piece of the graph right here. So what you would say is that x is strictly greater than negative 3. So that's coming this way like that. And then less than your negative 7/4, because it can't be negative 7/4 or something greater because you're going to end up with something that's undefined. All right, let's take a look at the next problem. So we have 1 minus 4 log base 6 of 7 minus 2x is greater than or equal to negative 3. Again, when you work on a problem like this, you want to make sure before you do anything else that you take that argument for your logarithm, so 7 minus 2x, and you want to see where it's greater than 0. Remember, the argument of your logarithm needs to be positive. Whether you're using the rules that we talked about today or you're using the test point approach, always do this first. So go ahead and subtract 7 away from each side of the inequality. This would cancel. You get negative 2x is greater than negative 7. Let's divide both sides by negative 2. Remember that if you're dividing both sides of an inequality by a negative, you have to flip the direction of the inequality symbol. This would cancel. You get x is less than negative over negative is positive. So this is 7/2 or 3.5. Okay, let's get rid of this and move this up here. Now what I'm going to do is just solve this using the rules that we talked about. Now you can do the test point approach if you want. You'll get the same answer. That's going to be up to you. So I'm going to say 1 minus 4 log base 6 of 7 minus 2x is greater than or equal to negative 3. What you want to do is isolate this part first. So just like if you were solving an equation like this, so if you had equals like that, you would isolate that first. So let's go ahead and put this back to an inequality. And so I'm going to subtract 1 away from each side. So this cancels. Negative 4 log base 6 of 7 minus 2x is greater than or equal to negative 3 minus 1 is negative 4. So at this point, we're going to divide both sides by negative 4. You have to be very, very careful here because what did we do? We divided both sides of an inequality by a negative. So that means that this guy has to be flipped. Flip. So this is going to be a less than or equal to. This cancels. You get log base 6 of 7 minus 2x is less than or equal to negative 4 over negative 4 is positive 1. Let me actually erase everything that I've done to this point, and I want a lot of room to show you what I'm going to do next. So here's where people make a mistake with these problems. It's very, very common, so you really have to pay attention if you're not going to use the test point approach. We know that if we had something like log base 6 of 7 minus 2x is equal to 1, you can write that in exponential form. So you can say 6 to the power of 1, so 6 to the power of 1 is equal to this 7 minus 2x. But here, you can do it that way, but this has to stay on this side. So we can write it like this with an equation, or you could flip it around and say 7 minus 2x is equal to 6. This doesn't matter. It's going to give you the same solution either way. But when you work with an inequality, where you are in terms of things does matter, because the direction of this is always going to be important. So in other words, what I want to do is say 6 to the power of 1, that's going to stay over here. So that's just 6. This less than or equal to would stay, and this right here needs to be on the left. So 7 minus 2x. Now, if what I did was super confusing, there's another way you can do this, and it's very easy to understand what's going on. You're going to exponentiate each side. So since the base here is 6, what you're going to do is choose a base of 6 here and a base of 6 here, and this is going to be your exponent, and this is going to be your exponent. So that's all you're going to do. So this is log base 6 of 7 minus 2x. And then let me put the less than or equal to, this is 6 to the first power. So now if you just go through and simplify things, 6 raised to the power of log base 6 of 7 minus 2x, we know that this is just 7 minus 2x. So now let's say this is less than or equal to 6 to the power of 1, which is 6. Okay, at this point, let me subtract 7 away from each side of the inequality, and let me cancel this away. And let's say that negative 2x is less than or equal to, this 6 minus 7 is negative 1. Let's divide both sides by negative 2. Once again, if you divide both sides by a negative and you're working with an inequality, you have to flip the direction of the inequality symbol. So this becomes x is greater than or equal to negative 1 over negative 2 is positive 1/2. And come back up here and paste in this right here. I'm going to write the keyword and. So you could write this as a 3-part inequality. So x is greater than or equal to 1/2 and strictly less than 7/2. So it can't be 7/2 and it can't be anything greater because this guy right here is going to be undefined. Let's come down here and paste this in. So if we look at 1/2, let's just say that that's right there. So this is 1/2. And if we look at 7/2, that's 3.5. Let's say that's right there. So that's 7/2. And let's go ahead and put a bracket here at 1/2. And let's put a parenthesis here at 7/2 and just shade everything in between. So that's your graphical solution. Again, an interval notation. So let's put 1/2 next to the bracket because it's included. And then we'll put 7/2 here next to a parenthesis because it is excluded. All right, so let's come to the graph here. You can do this on Desmos. So you can type it in using the original form or this one right here. Remember, the reason this is a less than or equal to, and in the original problem we had a greater than or equal to, we ended up dividing both sides by a negative. So that's why this guy got flipped when we're doing our simplifying, trying to get this isolated. So you can graph y equals log base 6 of 7 minus 2x, and then minus 1. Again, all you have to do is subtract 1 away from each side and keep this as a less than or equal to here. And so you'd have 0 over here. And basically, you're looking for where the y values are either 0, so you're on the x-axis, so that's right there at 0.5 or 1/2. And then you want something that's also going to be less than 0. So remember that this guy right here, we said was defined where x was less than 7/2, or you could say 3.5. So this is the part that you're looking for in the graph. So anything from 1/2 going up to and excluding 7/2, which would be 3.5. So 3.5 is not included here, but 0.5 is included. So it would say x is greater than or equal to, you could use 0.5 or you can do 1/2. Let's just stay with that. And strictly less than, again, this 3.5 or 7/2, that's not included because that would make this guy undefined. So let's put 7/2 here. All right, let's look at one more problem here. So I'm going to do this one using 2 different techniques. Again, I'll show you the rule-based strategy, and then also we'll use the test point approach. So first and foremost, let's just think about where this guy, x minus 6, so this argument, where is that greater than 0? And then x minus 10, where is that greater than 0? Again, when you start these problems, always think about that before you do anything else. If you forget to do that, in a lot of cases, you're going to get the wrong answer because you'll be missing part of it. So we're going to add 6 to both sides here. This will cancel. You get x is greater than 6. And then I'm going to add 10 to both sides here. So this will cancel. We get and x is greater than 10. So if you get x is greater than 6 and x is greater than 10, well, then it's going to be x is greater than 10. And let me write here that x is greater than 10. And let me also copy this problem. So log base 5 of x minus 6, and then plus log base 5 of x minus 10 is less than or equal to 1. Okay, how do we solve this? Well, we know that we can use our properties of logarithms to condense this here. But when you condense things, again, if you're solving an equation, in some cases you get extraneous solutions. And here you would. But it's not really going to impact us here. And I'll show you why. And it's because we have this guy right here to protect. All right, so what we're going to do is say that we have log base 5 of. You're going to multiply these two together. So x times x is x squared. And then you're going to have a negative 6x minus 10x, so that's negative 16x. And then negative 6 times negative 10, that's plus 60. And then let's close that down. And we're going to say, where is this less than or equal to 1? So again, you can exponentiate each side if you want to do it that way, or you can just go 5 to the power of 1, that stays over here, and then this is over here. So whatever you want to do, let's just put a 5 here and a 5 here as the base. So this is crystal clear. So this is going to give me x squared minus 16x plus 60 is less than or equal to. This is, it looks kind of goofy. So maybe I'll do this in a different line because maybe somebody got lost by that. Let me move this down here. But let me put the 1 back in here. And let me put that this would be 5 to the first power here. So let me write this more cleanly. This is 5 raised to the power of log base 5 of x squared minus 16x plus 60. Close that down. And this would be less than or equal to 5 to the power of 1. So just exponentiating each side. So that's what we did. All right, so coming down here now, 5 to the power of 1 is just 5. Go ahead and subtract that away from each side. So this would be 55 over here. And then this would be 0 over here. We know how to solve a quadratic inequality. It's pretty easy. So I would just factor this over here and basically put an x here and an x here. Two integers that sum to negative 16 and have a product of 55. That's going to be negative 5 and negative 11. Okay, so if you solve the related equation, you would get x is equal to 5, and that's positive 5. And then x is equal to positive 11. So you're setting x minus 5 equal to 0. That's where you get x equals positive 5. And then x minus 11 equals 0. That's where you get x equals positive 11. Let me change this back to less than or equal to. Okay, at this point, you can just test and get your solution. Let me grab this real quick. Let me come down here. And let's say that this is positive 5 and this is 11. So let's call this A, let's call this B, and let's call this C. So to the left of 5, just pick something. You can pick 0. So 0 minus 5 is negative 5. That's negative. 0 minus 11 is negative 11. That's negative. Negative times negative is positive, so that's not less than 0. So this is a big fat F for false. Won't work. So in region B, just pick something like maybe 6. So 6 minus 5 is 1. That's positive. 6 minus 11 is negative 5. That's negative. Positive times negative is negative. So this would work. So this is a true. And so in region C, let's pick 12. 12 minus 5 is 7, positive, and then 12 minus 11 is 1, positive. Positive times positive is positive, so this is not going to work. This is false. Okay, so we know that the solution now, keep in mind this is a non-strict inequality, is that your x is greater than or equal to 5 and less than or equal to 11. Okay, let's grab this real quick. So let's come back here and we're going to put in the keyword and. So x is greater than 10 and x is greater than or equal to 5 and less than or equal to 11. Well, this turns into x is strictly greater than 10 and less than or equal to 11 when you put these two together. So this would actually be your solution. Let me go ahead and grab this real quick. Okay, let's come down here and just paste this in. So let me put a 10 here and an 11 here because we'll graph this. But first, let's go ahead and write it in interval notation. So I want a parenthesis next to 10 because it's not included. And then I want a bracket next to 11 because it is included. We're going to use this same strategy here. Let me use this guy right here. So at 10, I want a parenthesis. Or again, if you want to use an open circle, that's fine. And then over here at 11, I want to use a bracket, again, to show that's included. If you want to use a filled in circle, again, that would be fine. So let's just shade everything in between. So that would be your solution graphically. And then this is your x is greater than 10 and less than or equal to 11. And then this is your interval notation. So just coming to the graph, we had log base 5 of x minus 6 plus log base 5 of x minus 10. And what we had was, where is this less than or equal to 1? So subtract 1 away from each side. You go minus 1 is less than or equal to 0. So y is equal to this log base 5 of x minus 6 plus log base 5 of x minus 10 minus 1. So that's right here. So basically I'm asking, for which x values am I getting y values that are less than or equal to 0? Well, looking at the graph, here it's going to be 0. In terms of the y value, that's your x-intercept. That's where you're on the x-axis. And then for less than 0, you've got this piece of the graph right there. And so basically, x would be strictly greater than 10. It can't be 10, and it can't be anything that's less than 10, because basically you would have something that's undefined in here. And you would say, and it's less than or equal to, so the or equal to 11. It can be 11 because at 11, basically you have a y value of 0. So this would be your solution graphically. Okay, I'm going to restart the problem, and I'm going to show you the test point approach. So this is what I personally prefer when I work these problems. It's just really easy to make a mistake on logarithmic inequalities, and this will guard against mistakes. So if you want to see this, you can stick around for this example. So we're going to say that first and foremost, x minus 6, again, is greater than 0, and x minus 10 is greater than 0. So we've already solved this. We know x will be greater than 10, but let's just do it again. So we're going to add 6 to both sides. We get x is greater than 6, and add 10 to both sides. We get x is greater than 10. So of course that becomes x is greater than 10. So let me get rid of this, and let's put x is greater than 10. All right, so for the test point approach, you're going to replace this with equals. So you're going to say, and this is probably not going to fit over there. Let me just write it like this. So log base 5 of x minus 6 plus log base 5 of x minus 10. You're going to say, again, where does that equal 1? So what I'm going to do here again is just condense. We're going to say log base 5 of, you're going to multiply these two together. So you get x squared, and then basically minus 16x, and then plus 60. And you want to know where this is equal to 1. So at this point, again, you could put it into exponential form. So 5 to the power of 1, or just 5, would be equal to x squared minus 16x plus 60. So let's go. X squared minus 16x plus 60 is equal to 5. Subtract 5 away from each side, and so this would be 55, and this would be 0. Now, when you solve this, let me slide down here a little bit, you're going to end up with something that's extraneous. It won't work in this original equation. So let's go ahead and factor this. And we're going to say we have an x here and an x here. And then let's go ahead and say that we have minus 5 and then minus 11. Those are two integers that sum to negative 16 and have a product of 55. So when you solve this guy, x minus 5, if you set that equal to 0, you get x is equal to 5. And then if you do x minus 11 is equal to 0, you get x is equal to 11. So this solution of 5 here is going to be extraneous. We know that x needs to be greater than 10. And let me write, for the critical values, you're going to have 10 and then 11. And let me move this over here like this, so we know that. Okay, let me copy this real quick. We have log base 5 of x minus 6 plus log base 5 of x minus 10. We want to know where that's less than or equal to 1. So again, you can subtract 1 away from each side and say, where is this less than or equal to 0? Okay, let's grab this real quick and come down here. And basically, you're just going to set up, you could use a table or a number line. You just want something to organize your information. Let's say this is 10 and this is 11. So we know that things to the left of 10 and even 10 itself will not work. So you can, let me do this in a different color. You could just mark this out and put an F for false. Will not work. You don't need to check it. Between 10 and 11 is where I want to check, and then anything greater than 11, I want to check. Now, it's a non-strict inequality, so I know that 11 will work, but we'll deal with that in the end. Let me get rid of this. I think we've already basically taken care of that. Let me move this up here and just pick something between 10 and 11. You could just pick 10.5. So let me plug that in. We're going to go log base 5 of, let's go 10.5 minus 6 plus log base 5 of, let's go 10.5 minus 10, and then minus 1. So if you punch this into your calculator, let's say that this is about negative 0.496. Now, it doesn't matter where you round to. You just want to know, is this positive or negative? And it's negative. So a negative is always less than 0. So this would be a T for true. All right, let's look at something that's greater than 11. So I'm just going to use 12. So get rid of this, get rid of this. So this would be 12, and this would be 12. So let's just key that into the calculator. And I get about 0.544. Again, it doesn't matter where you're going to round to. It's just a matter of this guy's positive and we want less than or equal to 0. So of course this is not going to work. So this is an F for false. So this is using the test point approach. You can go through and say, okay, well, 10 is not going to work and anything less than 10 doesn't work. But numbers that are greater than 10 work up to and including this positive 11. So we would say X is greater than 10 and less than or equal to, because this is non-strict, this 11. All right, let's take a look at the practice test where the instructions were asked to solve each inequality. All right, so before we jump in and look at any examples, I want to review something that we talked about in the lesson. So if you have an easier scenario, so you're solving an exponential inequality with a common base, you can use this formula. So let's say that a is greater than 1 and x is greater than y. Well, then it's going to be true that a to the power of x is greater than a to the power of y. Now you can also write this in a different way. So if a is greater than 1 and a to the power of x is greater than a to the power of y, well, then it must be true that x is greater than y. So let me give you a quick example, and I think this will make sense right away. So let's say we put a little border here, and we use 2 as the common base. So let's put a 2 here and a 2 here. Let's say I want to use a greater than here. Well, it must be true that the exponent here is going to be greater than the exponent here. So let's say I use a 5 here, and let's say I use a 3 here. So obviously this would be a true statement. 2 to the 5th power is 32, and 2 cubed is 8. So this becomes 32 is greater than 8. So this is always going to produce a true statement as long as this exponent right here is greater than this exponent right here. Now, what happens if I put an exponent over here that is smaller than the exponent over here? Let's say I do something like 2, let's go to the 4th power, and here let's go 2 to the 7th power. Well, now I need a less than for this to be a true statement. 2 to the 4th power is 16, 2 to the 7th power is 128, so obviously 16 is less than 128. So this right here, this example, leads to another rule. We're basically just going to piggyback on this one, so let me put a little border here. And we're going to say if a is greater than 1, and we're going to say x is less than y, well then it must be true that a to the power of x is less than a to the power of y. And again, you could also write this as a is greater than 1 and a to the power of x is less than a to the power of y. Well, then it must be true that x is less than y. All right, let's look at the first example. And on this one, I'm going to do the problem twice. So first, I'm going to use that formula that I gave you, and then I'm going to use the test point approach in case you want to solve it that way. And basically what we're going to do is first write each side with a common base. So you have 4 to the power of 2x times 64 raised to the power of x plus 1. This is greater than 1 over 16 raised to the power of x plus 2. So you could use different things for your common base. A lot of people will choose 4 here because you have a 4, 64 is 4 cubed, and then 1 over 16, you could write that as 4 to the power of, let's say, negative 2. So you could use 4, but I think I'm going to use 2. So let's go ahead and do that. Again, if you want to use 4, that's up to you. So let's go ahead and say this is 2 squared. That's just for 4 there. And then this is raised to the power of 2x, and then times 64 is 2 to the 6th power. This is raised to the power of x plus 1, and then this is greater than 1 over 16. Let's first write that as 1 over 2 to the 4th power. You can drag this across the fraction bar and change the sign of the exponent. So this would be 2 to the power of negative 4, and then this would be raised to the power of x plus 2. At this point, we're going to use the power to power rule. So something like 2 squared raised to the power of 2x, you keep the base 2 the same, and you multiply the exponents. So 2 times 2x is 4x, then times. Here, 2 to the 6th power raised to the power of x plus 1, you're going to keep 2 the same, and then you're going to multiply the exponents. You have to be careful here because 6 is multiplying this quantity, so this is 6 times the quantity x plus 1. And when you distribute this, you get 6 times x, which is 6x, plus 6 times 1, which is 6. So this is 2 to the power of 6x plus 6. So 6x plus 6, and then let's say this is greater than 2 to the power of negative 4 raised to the power of x plus 2. So 2 stays the same. You're going to multiply negative 4 times the quantity x plus 2. Again, this needs to be distributed, so this would be negative 4x minus 8. So let me write negative 4x minus 8. Okay, we're going to keep simplifying on the left. So you have 2 to the power of 4x times 2 to the power of 6x plus 6. You have multiplication here and a common base. So you're going to use the product rule for exponents. 2 stays the same, and you're going to add the exponents. So 4x plus 6x plus 6, well, 4x plus 6x is 10x, and then you have plus 6, and this is greater than 2 to the power of negative 4x minus 8. So now I'm going to use my rule. I have this common base, which is 2 here and 2 here, and that is greater than 1. So basically when that happens, you would say for this to be a greater than here, this exponent has to be greater than this exponent. So in other words, 10x plus 6 must be greater than negative 4x minus 8 for this to be true. So let's go ahead and add 4x to both sides of the inequality here. This will cancel. Let's subtract 6 away from each side of the inequality. This will cancel. Let me slide down here. And let's say that 10x plus 4x is 14x. And this is greater than Negative 8 minus 6, that's going to be negative 14. Let's divide both sides of the inequality by 14. And so this is going to cancel. We'll say x is greater than negative 14 over 14. That's going to be negative 1. So this is your solution. X is greater than negative 1. Let me come down here and just say that x is greater than negative 1. You can also show this in interval notation if you want. So you're going to write that like this. So make sure you use a parenthesis next to negative 1 because this is a strict inequality and negative 1 is not included. Maybe that infinity symbol could be better there. And then if you want to show this graphically, so using the number line, what you can do is put a parenthesis at negative 1. Again, some books will use an open circle. So if you want to use an open circle there to show that negative 1 is not included, that's fine. Then we're just going to shade everything to the right, including this right here. And so let's go ahead and say that this would be the solution graphically. This would be your x is greater than negative 1 form. And then this is your interval notation. All right, for anybody that wants to see it, let's use the test point approach. So this is something that always works with any inequality that you want to solve. It's a great way to make sure that you got the right solution. The trade-off is it takes way longer. So you have more work that's involved. So to use the test point approach, essentially the first thing is you want to find the critical values. Here you're just going to have 1. It's going to happen at x equals negative 1. The way you find your critical value is you replace your inequality symbol with equals. So you would solve this equation 2 to the power of 10x plus 6 is equal to 2 to the power of negative 4x minus 8. So we should know already that x equals negative 1. But again, in case you don't, you're just setting these exponents equal to each other because you have a common base. So you're saying that 10x plus 6 is equal to negative 4x minus 8. And then all we have to do is add 4x to both sides of the equation. And so this would cancel. And let's subtract 6 away from each side of the equation. This would cancel. So you have 10x plus 4x, that's 14x, is equal to negative 8 minus 6, that's negative 14. Let me just write that 14x is equal to negative 14. You can divide both sides by 14 now. And basically this would cancel. And you're going to get x is equal to negative 14 over 14, that's negative 1. So x equals negative 1. Let me write that there. So what is negative 1? This right here is a critical value. So it separates the solution region from the non-solution region. The reason you want that is you basically need a boundary or something to say I'm going to test on this side and then I'm going to test on this side. So I'm going to write this inequality in a different way. I'm going to say this is 2 to the power of 10x plus 6. I'm going to subtract this away from each side. So minus 2 to the power of negative 4x minus 8. And this would be greater than 0. So we come down to this little table. And basically, you're going to pick something on the left side of negative 1, and you're going to pick something on the right side of negative 1, and you're just going to test. And so let's say I pick x equals negative 2. That's something that's to the left of negative 1. You plug in, and you're just trying to see, is it greater than 0 or is it less than 0? Here, it's approximately negative 1. I don't care about the value. I just care that it's negative, and a negative is never going to be greater than 0. So I would reject anything that's to the left of negative 1. That will not be in my solution. Then you can pick x equals 0. That's something to the right of negative 1. You plug that in, you get about 64. So the only thing I care about, again, is that this is positive. So this would work. It would be greater than 0. So anything that's greater than negative 1 would work. So you can also look at this graphically by just sketching y equals 2 to the power of 10x plus 6 minus 2 to the power of negative 4x minus 8. Again, all we're doing is saying, for this, let's write 2 to the power of 10x plus 6 minus 2 to the power of negative 4x minus 8. We're just saying, where is this greater than 0? So in other words, what are the x values for which the y values are greater than 0, or we are above the x-axis? We can see clearly that the x-intercept, or where the y value is 0, is going to occur at negative 1. We found that already. You can see also that anything that is to the right of negative 1 produces a y value that is greater than 0. So that's how you can find your solution graphically, in case you're curious. So we can say here that x is strictly greater than negative 1. Again, it's not equal to negative 1 because that's where it's 0. We want to know where this guy is greater than 0. So that's for x values that are greater than or to the right of negative 1. All right, for problem 2, we have 1/9 raised to the power of 2x times 81 raised to the power of negative 4x. This is less than or equal to 1/3 raised to the power of negative 4. All right, looking at this, again, I would write each side with a common base. You have different choices that you can use. I would go ahead and use 3. So what I'll do is say 1/9. Let's write that as 3 to the power of negative 2. And this would be raised to the power of 2x. And then times, for 81, that is 3 to the 4th power, and this is raised to the power of negative 4x. This is less than or equal to, for 1/3, let's write that as 3 to the power of negative 1, and this is raised to the power of negative 4. Okay, let me slide down here a little bit, and we're just going to use our power to power rule. So 3 here is going to stay the same. You're going to multiply your exponents. So negative 2 times 2x, that's negative 4x, then times. 3 here stays the same. You're going to multiply your exponents. So 4 times negative 4x, that's going to be negative 16x. And then this is less than or equal to, 3 stays the same. You're going to multiply exponents. Negative 1 times negative 4 is 4. Okay, let me slide down here a little bit. And all you really have to do is use your product rule for exponents now. So 3 would stay the same. You're going to add the exponents. So negative 4x plus negative 16x, that's negative 20x. And this is less than or equal to, you have 3 to the 4th power. Okay, let me slide down here a little bit. And let's say that you have a common base here. So 3 and 3. And that is greater than 1. So it must be true if this is a less than or equal to here, that this right here is less than or equal to this right here. In other words, negative 20x is less than or equal to 4, just by our rule. So we would divide both sides by negative 20. Now notice that we divided both sides by a negative. So when we divide both sides by a negative, and we're working with an inequality, we have to flip the direction of the inequality symbol. So let me write here that we're going to flip, just so we don't forget. So this is a less than or equal to, it's going to become a greater than or equal to. And so this would cancel, and you're going to get that x is greater than or equal to 4 over negative 20. That's going to be negative 1/5. And that's coming from positive over negative is negative. 4 divided by 4 is 1. 20 divided by 4 is 5. Okay, let me come down here and say x is greater than or equal to negative 1/5. If you want to write this in interval notation, you could just do it like this. So you want a bracket here because negative 1/5 is going to be included. And this is going out to positive infinity. And then for negative 1/5, we don't have a notch for that, but let's just put one in. Let me move this down here. And let's just say that maybe it could be about right there. Wouldn't be perfect, but let's just pretend it is. So let's say that's negative 1/5, which you could also write as negative 0.2. So let's put a little bracket there to show that that's included. A lot of books will put a filled in circle, so you can do that as well. And we're just going to shade everything here to the right. So there's your solution graphically. Again, this right here would be at negative 1/5. Here's your solution in interval notation. And then here's just x is greater than or equal to negative 1/5. Okay, let me paste this in here. If you go to Desmos, it's a little bit hard with this one because of the way it looks. So I had to change the scale quite a bit. But if you start with 3 to the power of negative 20x is less than or equal to 3 to the power of 4, well, you could rewrite this and say this is 3 to the power of negative 20x and then minus 3 to the 4th power. Where is that less than or equal to 0? So essentially, if you're graphing this right here, this y equals 3 to the power of negative 20x minus 3 to the 4th power, well, again, this right here is your y value. These are the same. So this is giving you a y value. And you want to know where that y value is going to be less than or equal to 0. So you want to know where you're going to be below the x-axis or on the x-axis because you have a non-strict inequality. You have the or equal to part there. Well, this right here, although there's not really a notch for it, this right here is going to be, you could say negative 0.2, or you could say that it's negative 1/5, however you want to write that. And essentially that would be included, and then anything that is to the right of that. So that's why we're saying that x is negative 1/5, or anything to the right, or anything greater. So your solution there graphically, if you look at it, again, where are the y values that are less than or equal to 0? Well, the x values that are going to produce that, you're going to have x is greater than or equal to negative 1/5, or again, you could write x is greater than or equal to negative 0.2. All right, for the first two problems, we had a base that was greater than 1, but now we're going to look at the case where a is between 0 and 1, with both being excluded. So if a is greater than 0 and less than 1, and x is greater than y, you're going to conclude that a to the power of x is less than a to the power of y. Again, you could also write this as a is greater than 0 and less than 1, and a to the power of x is less than a to the power of y. Then you can conclude that x is greater than y. So why do we flip the sign here? What's going on? Well, let's say that we started with something, just using this as the example, where you had, let's say, x being greater than y. So let's use something like a half because it's easy to work with, and let's use 1/2 here. And let's say that I put a larger exponent here than I do here. So let's just say this is to the 4th power, and let's say this is squared. Would we say that this is greater than this? No, you have to flip the sign. So in other words, you have to put this as a less than here to make that true. This exponent is greater than this exponent, and this base here is between 0 and 1 with both being excluded, so now you have to use a less than. This right here would be 1 over 2 to the 4th power is 16, and then this right here would be 1 over 2 squared is 4, so this is 1/4. So of course we know that 1 over 16 is a smaller number than 1/4. So 1/16 is less than 1/4. That's how you have to set that up. If you look at the other scenario, and it's just basically the same logic, let me put a little border here. If I say that a is greater than 0 and less than 1, and I'll go and, so now we'll go x is less than y, well then it's going to be true that a to the power of x is greater than, you've got to flip the sign, a to the power of y. Again, as a simple example, let's say you use something like 1/3. So let's say I go 1/3 and I go 1/3. Okay, so now I'm going to use an exponent here that's less than the exponent here. So let's say that I use something like squared, and let's say I use something like to the 4th power. So would I put a less than there? No, I want to put a greater than. Again, I've got to flip the sign because this base here is between 0 and 1 with both being excluded. This right here would be 1/9. And then this right here would be 1 over 81. And of course, 1/9 is greater than 1 over 81. So just keep this rule in mind as we solve the next problem. All right, for problem 3, we have 1/4 raised to the power of x times 1/4 raised to the power of 2x plus 3. And this is going to be less than 64. And what I would do first is just write everything with a common base. You could use 4 if you wanted to. So you could use negative exponents to do that. I've already solved 2 problems using that strategy. So what I'm going to do is keep the base as 1/4. So that's something you can do. So I'm just going to write 1/4 like this, raised to the power of x times 1/4. And this is raised to the power of 2x plus 3. And then this would be less than, for 64, you could write that as 4 cubed. And then what you could do is you could drag it across the fraction bar. So you could say that this is 1 over 4, but you've got to change the sign of the exponent. So that's the power of -3. And of course, you could raise 1 to the power of -3. That would still be 1. And so you could write this outside as 1/4 raised to the power of -3 like that. That would give you 64. Okay, so writing things with a common base of 1/4, just so we can use that rule that we just talked about. And what I'm going to do now is use my product rule for exponents here, keep the base of 1/4 the same, and this would be adding exponents. So x plus 2x is 3x, and then just plus 3. And this would be less than, you have 1/4 raised to the power of -3. Okay, so here's where you really have to pay attention if you're using this base of 1/4. This right here is between 0 and 1 with both being excluded. So because this is a less than here, you want to flip the sign. Let me write that. We're going to flip. So you're going to say that 3x plus 3 is greater than -3. At this point, what you're going to do is just solve this simple inequality. We're going to subtract 3 away from each side. That cancels. You get 3x is greater than -3 minus 3, that's -6. Let me slide down a little bit. And we're going to divide both sides of the inequality by 3. That cancels, and you get x is greater than -6 over 3, that's -2. So it's very important to flip the sign. That way you get the correct answer of x is greater than -2. And let me restart the problem. I'm going to do it in a different way. So instead of using a base of 1/4, you can use a base of 4, just by saying that this right here is 4 to the power of -1. And then this would be raised to the power of x. And then times this would be 4 to the power of -1. This would be raised to the power of 2x plus 3. This would be less than 64 is 4 cubed. Okay, so over here, again, power to power rule would be done first. So this is 4 to the power of -1 times x, that's -x. And then times 4 raised to the power of -1 times 2x plus 3. So that -1 has to be distributed. So it's basically the negative of 2x plus 3, that quantity. So you're just changing the sign of everything. So that's -2x minus 3. So -2x minus 3, that's less than 4 cubed. And then here, again, you're just going to add your exponents and keep that base 4 the same. That's just using the product rule for exponents. So -x plus -2x, that's -3x, and then minus 3. And this is less than 4 cubed. Okay, so you're going to see that you still get your x is greater than -2. So we're going to have that -3x minus 3. Now, because this is a 4 and this is a 4, again, the base is greater than 1. So you're just going to keep this sign. You don't have to flip it here. You're going to say this is less than 3. Now, what you're going to see is that you end up flipping the sign because you're going to divide both sides of an inequality by a negative. So it's going to give you the same answer either way. So let's add 3 to both sides of the inequality. This cancels. You get -3x is less than. 3 plus 3 is 6. Let's divide both sides of the inequality by -3. And again, when you do this, let me move this off to the side, you have to flip the direction of the inequality symbol because you divided both sides by a negative. Let me write flip. So this right here is going to cancel with this right here, and you're going to get that x is greater than, again, this is a less than, I flip because I'm dividing by a negative, and I get 6 divided by -3 is -2. So either way you solve this, you get x is greater than -2. It's just really important to understand that sometimes your teacher will give you a problem where you have a base that's between 0 and 1, with both being excluded, and you have to remember to flip the direction of the inequality symbol when you set things up. If you want to write it like I did there, so where you have a base that's greater than 1, that's fine. You could just go back to the original rule. So whatever you want to do. All right, let me write here that x is greater than -2. In interval notation, you have -2 next to a parenthesis and then out to positive infinity. Here is -2 here. Let me use my red color. Again, you can use an open circle if you prefer that, and that'll just shade everything to the right to show my solution graphically. Again, you have x is greater than -2 and then your interval notation. Okay, so again, you can always check this on Desmos if you want. So we got to the point where we had 1/4 raised to the power of 3x plus 3, and we said that that was going to be less than, you had your 1/4 raised to the power of -3. So we know 1/4 raised to the power of -3 is going to be 64. So you can just write 64 there if you want, or you can keep it that way. It doesn't really matter. You would subtract 64 away from each side of the inequality, and so you would get -64. You want to know where this guy right here, again, if I sketch y equals 1/4 raised to the power of 3x plus 3 minus 64, again, this right here is producing a y value. I plug in something for x, I get something out for y. So this right here, this whole thing is producing a y value. And I want to know for which x values am I going to get a y value that is less than 0. So where am I going to be below the x-axis? Again, at -2, that's where you'd be equal to 0. That would be your critical value or your boundary. But anything, let me use a different color here, anything that is to the right of -2 or greater than -2, that's going to produce a y value that is less than 0. And so that's where you're going to satisfy the inequality. Again, you can just say that x, and I kind of covered this up. So let me start maybe like right there, or actually, let me go over this again like this. And I'll just arrow to this and say this is -2 there. So basically you can see that for any x value that is greater than -2, this inequality would be satisfied. All right, so before we start working with any problems that involve logarithms, let me cover those rules again with you. So suppose you have something where a is greater than 1, so a is the base for the logarithm here, and x is greater than y, so x is your argument here, y is your argument here. Well, then it's going to be true that log base a of x is greater than log base a of y. You could also write it as if a is greater than 1 and log base a of x is greater than log base a of y, well then x is greater than y. Now keep in mind that you have to think about your restrictions when you work with logarithms. These arguments here have to be positive real numbers. They can't be 0 and they can't be negative. Now you could also write, if you wanted to, that if a is greater than 1, and you can go and, let's say x is less than y, well then it's going to be true that log base a of x is less than log base a of y. When you have a, your base for the logarithm, that is between 0 and 1, with both being excluded, you have to flip the direction of the inequality symbol. So just like we saw earlier. So if a is greater than 0 and less than 1, and x is greater than y, then log base a of x is less than log base a of y. And then you could also say, if a is greater than 0 and less than 1, and let's just go x is less than y, then log base a of x, you're going to flip the sign, so it would be greater than log base a of y. All right, for problem 4, we have -2e raised to the power of 5x plus 5 plus 3 is greater than -47. Let me slide down here a little bit. Our goal is going to be to first isolate this guy right here on one side and then have a number on the other. So how do we do that? We're going to subtract 3 away from each side of the inequality. This cancels. You're going to have -2e raised to the power of 5x plus 5. This is greater than -47 minus 3, and that is -50. When you divide both sides by -2, remember you're working with an inequality. So if you divide both sides of an inequality by a negative, you must flip the direction of the inequality symbol. Let me just write flip here. It's a greater than, so let me put that this will now be a less than. So this will cancel, and now you're going to get that you have e to the power of 5x plus 5 is less than, negative over negative is positive, and then 50 over 2 is 25. So this is what we have at this point. So here's where we're going to use logarithms. So we know that log base e is the same as the natural log, or ln. So in other words, log base e of, let's say, x is equal to ln of x. And we know that ln of e is equal to 1 because it's log base e of e. So what we're going to do here is just take the natural log of each side. So let's say this is ln, that's for the natural log, of e raised to the power of 5x plus 5. And this is less than ln of 25. We know at this point that this would come out in front as multiplication, and then ln of e would be 1. So basically what you would have is 5x plus 5. And now this is less than your ln, or natural log, let's make that better there, of 25. At this point, you just need to solve for x. That's all you have to do. So we're going to subtract 5 away from each side. This cancels. You get 5x is less than ln of 25 and then minus 5. To finish things up, let's divide both sides of the inequality by 5, and we'll have our solution. We'll just say that x is less than the natural log of 25, then minus 5 over 5. Okay, let me come down here and paste this in. And I'm going to put here as a side note, so the natural log of 25 minus 5 over 5. This is approximately, I'm just going to key this into the calculator real quick. So I get about negative 0.36, like that. If you're keying this into a TI-83 or something, make sure you're wrapping things correctly. You want to make sure you do the numerator divided by the denominator. If you're using an online calculator, then it doesn't matter. It'll do it for you. So this is about negative 0.36. So let's go ahead and set this up with interval notation. Let me put a little border here and put my interval notation. So I'll put negative infinity here and going up to and excluding. Let's write the full thing. So the natural log of 25 minus 5. And this is over 5 here. And then for a graphical solution, let's just say that that's going to be about, I don't know, right there. So I'll just arrow to that and say it's approximately this negative 0.36. And we want something that's less than that. So basically, you're going to put a parenthesis facing to the left. You could also put an open circle if you want to show it's not included. And you're just going to shade everything to the left like that. All right, if you want to look at the graph just to verify your solution, you can also use the test point method. That's up to you. Essentially, what you're going to do is start with this right here and then subtract 25 away from each side. So let's go minus 25 is less than 0. So you're sketching the graph of y equals e to the power of 5x plus 5, then minus 25. Again, this right here produces a y value. Y is equal to that or the same as that. So when I key things in for x, I'm producing a y value there, and I'm just asking for which x values am I getting a y value that is less than 0. So you look at where we have the x-intercept. So this value right here, this would be the natural log of 25, then minus 5, and the whole thing would be over 5. Or if you want to use an approximation, you could say this is about negative 0.36. So at that guy right there, you're on the x-axis, that's your x-intercept, so the y value is 0. We want less than 0. So we want something that's to the left of that guy right there. That would satisfy the inequality. So this right here, this is where we want to be in terms of solving that inequality. So it would be for x values that are strictly less than this natural log of 25 minus 5, and the whole thing is over 5. Okay, let's take a look at problem 5. So for this one, we have 1/5 to the power of x plus 25 raised to the power of negative x, and this is greater than or equal to 30. So you might have gotten stuck on this one, and all you're going to do to start is think about the fact that you have 1/5 here, and then you have 25 here. So could I write 25 using a base of 1/5? Sure. Let me slide down a little bit more here. Let me copy this 1/5 raised to the power of x, and then plus, for 25, I'm going to write that as 1 over 5 raised to the power of negative 2. Is that legal? Sure. If I bring this up across the fraction bar, the 5 stays the same, and you change the sign of the exponent, so this would be 5 squared, which is 25. Then we're going to raise this to the power of negative x, and we'll say this is greater than or equal to 30. Let me slide down here a little bit. Let me make this 3 a little bit better. So we have this 1/5 raised to the power of x, and then plus, What I'm going to do here is use a little rule that 1 raised to any real number is still going to be 1. So you could say this is 1 raised to the power of negative 2 over 5 raised to the power of negative 2. And then basically you can pull this out. So you can say that this is 1/5. So 1/5 raised to the power of negative 2. And then you can do this like this. You can say that this would be raised to the power of negative x like that. Now we're going to combine this using the power to power rule. So basically you would keep 1/5 the same and you would multiply the exponents. So negative 2 times negative x, that's going to be 2x. Let me get rid of this and just put this as 2x now. And then you could subtract 30 away from each side of the inequality. So minus 30, and this is greater than or equal to 0. Okay, so hopefully at this point you see what I'm going to do. I'm going to make a little substitution. And actually, let me write this as 2x, and let me write this as x. I'm just switching this so this is more clear. You can really say that you could let something like u be equal to your 1/5 raised to the power of x. So what you would have here is u, and here this would be u squared. Again, if that's not clear, again, you can always write this as 1/5 to the power of x. You can use some brackets or additional parentheses and put your 2 here. So this would be u squared. So you could say u squared and then plus u, and then minus 30 is greater than or equal to 0. Let me solve this real quick. Let me paste this in. This is really easy to solve. So again, for this one, you replace the inequality symbol with equals. You say, where is u squared plus u minus 30 equal to 0? Again, this is the test point approach. So you're just going to factor this. This is u and this is u. Give me 2 integers whose sum is 1 and whose product is negative 30. Well, that's going to be positive 6 and negative 5. So here by the zero product property, you're going to say u plus 6 is equal to 0, or u minus 5 is equal to 0. Subtract 6 away from each side here. And so this is going to cancel. You get u is equal to negative 6. Then or add 5 to both sides. This would cancel. You get u is equal to 5. Okay, so u equals negative 6 or u equals 5. So those are the critical values. Let me come down here. We're going to do some testing. So basically at negative 6, we're going to put a little boundary there. Let's just say anything to the left of that would be a. And then at 5, we're going to put a little boundary there. So let's say this is b. So that's between negative 6 and 5. And then anything greater than 5, let's call that c. Okay, let me put a little border here. I'll put a, b, and c. So first you would pick something that's to the left of negative 6. We already know that negative 6 would work because it's a non-strict inequality. But again, we're not including that in testing. You could just pick negative 7. Again, all you need to know is it positive or is it negative? So you could say negative 7 plus 6, and then you have negative 7 minus 5. Well, I know that this is negative and this is negative. Negative times negative is positive. So I know that this would end up giving me something that is greater than 0. So that is going to work here. I'm going to say in region A, this would be true. Now in B, you could pick something like 0. So this would be, let's say 0 plus 6, and then 0 minus 5. So this is positive and this is negative. Positive times negative is negative. A negative is never greater than 0. So this is false. Not going to work. Okay, let's get rid of this. And maybe that could be written more cleanly. So let me try that once more. Okay, for region C, let's pick 6. So you'd have 6 plus 6, and then you'd have 6 minus 5. So this is positive and this is positive. So positive is always greater than 0. So this would be true. So the solution for this inequality, you would have negative 6 or anything less. So you'd write u is less than or equal to negative 6. So that's coming from region A. And then also the fact that we have a non-strict inequality here. So negative 6 is included. Then we're going to put or. We have u is, it can be 5 or anything larger. That's coming from C. And again, the fact that we have a non-strict inequality. So let's go greater than or equal to 5. Let me paste this in right here and put a little border. So we know that u is equal to 1/5 to the power of x. So let's put in the place of u that we have 1/5 to the power of x. Again, I'm just making a replacement. U is equal to this, so I can legally replace u with 1/5 raised to the power of x. I'm going to say this is less than or equal to negative 6. And then I'm going to go or in the place of u, I'm going to go 1/5. Let me slide down a little bit so I can get some room. So this is raised to the power of x. Let me move this down here like that. So this fits. Well, now it would be greater than or equal to 5. Okay, we're not going to fit this on the sheet, so let me grab this. Okay, let me come down here and just paste this in. So for the first one, I think it's pretty obvious that there's no solution. You have 1/5 raised to the power of x is less than or equal to negative 6. Well, something like 1/5 being raised to the power of x it doesn't matter if x is negative, 0, or positive, the result of this is always going to be greater than 0. So it won't be 0 and it won't be negative. So there's no way that 1/5 raised to the power of x is going to be less than or equal to negative 6. This right here has no solution. So now we're going to move on to this one. 1/5 raised to the power of x is greater than or equal to 5. So there's lots of ways you could solve this. The first way I'm going to do it, that's why I came to this page with this rule. We're going to use a logarithm with a base that's between 0 and 1, with both being excluded, just so we can get a little practice. So remember, we have here that if a is greater than 0 and less than 1, and you have x being greater than y. So here we have a greater than or equal to. What's going to happen is if you set this up with a logarithm that has a base, again, between 0 and 1, with both being excluded, you have to flip the direction of the inequality symbol. Let me put a little border here, and I'm just going to write that we have log with a base of 1/5, and I'm doing that because the base here is 1/5, so those are going to cancel. Log base 1/5 of 1/5 is 1. Let me put some brackets here, and inside I'm going to put this 1/5 raised to the power of x. So of course this is just going to give me x at the end of the day. On the other side here, I have 5. Now what I'm going to do is actually write that as 1/5 raised to the power of -1. So let me write log base 1/5. And let me put in here that I'm going to have 1/5 raised to the power of -1. Of course, that's going to give me positive 5. Let me close that down. And let me slide this over just a little bit. Again, at this point, you have a greater than or equal to. Following this rule, because this base right here is 1/5, what we have to do is flip the direction of the inequality symbol. So we don't want a greater than or equal to. We want a less than or equal to. So that's really important. Let's put a less than or equal to in there. Let me slide down here, and I'll solve this in a different way, just so you can see that this is valid. So what we'll do first is say log base 1/5 of 1/5 raised to the power of x. Well, of course, the long way is to bring the x out in front as multiplication, and then say log base 1/5 of 1/5 is 1. So this is just x. And then we have is less than or equal to. Here you have your log base 1/5 of 1/5 raised to the power of -1. So this would be -1. Okay, so we get x is less than or equal to -1. Let me put this off in the corner here. And let me show you a different way if that's too confusing, or maybe you don't want to deal with memorizing all these different rules. Well, you could do this a different way. You could write 1/5 as 5 to the power of -1, and then this is raised to the power of x. So using the power to power rule, you could really say this is 5 raised to the power of -x. So this is 5 raised to the power of -x. Then over here, we have a greater than or equal to. And then for 5, let's write that as 5 to the power of 1. Okay, going back to the first rule that we wrote. Remember, we said if this base right here is common, so you have a 5 and a 5, and it's greater than 1, which 5 is, then really you could just say that -x is greater than or equal to 1. So -x is greater than or equal to 1. Okay, if we, let's say, write that as -1 to make this crystal clear, and we divide both sides by -1, what happens when we divide both sides of an inequality by a negative? Well, we flip the direction of the inequality symbol. So this would cancel. This is going to flip. Let me write that it's going to flip. So we're going to have that x is less than or equal to 1 divided by -1 is -1. So whether you do it the first way or this way, you get x is less than or equal to -1. So again, if you're a little bit confused by what I did with the logarithms and having that base between 0 and 1 with both being excluded, you could just do it this way. This rule is a lot easier to remember and to work with. So let's grab this. So let me come down here and just paste this in. I'm going to put my interval notation in. So from -infinity going up to and including -1. All right, so at -1, I'm going to put a little bracket facing to the left. Again, if you want to use a filled in circle, if your book does that, that's fine. And we're going to shade everything to the left like that. So this is a graphical solution. This is an interval notation, and this is just x is less than or equal to -1. Okay, once again, if you want to look at this on Desmos, it's a good way to check your answer. Let me paste the original problem in. All you're going to do is subtract 30 away from each side of the inequality. So essentially, you're going to key in y equals 1/5 raised to the power of x plus 25 raised to the power of -x minus 30. So remember that this right here is the same as y. It's equal to y. So this produces a y value when you punch something in for x. So you have the same thing over here. So you're saying, for which x values am I going to get a y value? So this guy right here, that is greater than or equal to 0. So it can be 0. So you'll notice that's going to be right there at -1. Let me arrow to that and say that's -1. So it could be on the x-axis or above that. So that's going to be this part of the graph right here. Let me just sketch that like that. So essentially you see that it's at -1 or anything to the left in terms of the x values for where the y values are greater than or equal to 0. So let's put x is going to be less than or equal to -1. So that's how you could look at it graphically. All right, for problem 6, we have the quantity 5x plus 2 raised to the power of x squared minus x minus 2 is less than or equal to 1, and 5x plus 2 is greater than 0. Okay, so the first thing is you have the keyword and. So we're looking for the intersection of the two solution sets. Now, the reason this part right here is important for this problem, remember, if you look at f of x equals a to the power of x in your book, you're going to see where they say that a is greater than 0, and then also we're going to say that a is not equal to 1. So the reason this comes up, again, if you had something like, let's say f of x is equal to, let's go with -2. So now this is a value that's negative. Let's say I raise that to the power of 1/2. Well, that's the square root of -2, which is not a real number, right? So to avoid dealing with things like that, that's why we have this in here. So that's the purpose of this. We're going to have this 5x plus 2 being greater than 0. That's going to help us to simplify the problem. So 5x plus 2 is greater than 0. Subtract 2 away from each side of the inequality. That cancels. You get 5x is greater than -2. Divide both sides by 5. Let me just erase this. And basically this cancels. And you're going to get that x is greater than -2/5. So that's going to make sure that the base is always positive. Okay. Then we're going to write and. I'm just going to copy that. So 5x plus 2, that quantity, let's say that is raised to the power of x squared minus x minus 2. And this is less than or equal to 1. All right, let me grab this real quick. Let me come down here to this fresh piece of paper. Now, there are different ways that you can solve this. A lot of people, what they're going to do, they're going to see 1 right here, and they're going to say, hey, I can write that as the quantity 5x plus 2 raised to the power of 0. So I could do that if I wanted to. That's one strategy, but you will run into some issues on that. So to avoid getting into that, what I'm going to do is actually just use the test point approach. Again, the test point approach, if you're confused by something, is always going to work. It takes longer, but you're not ever going to get the wrong answer unless you make a mistake while you're doing some calculations. But this is the way you want to go, in my opinion. So what you would do, let me put a little border, is to say that 5x plus 2 raised to the power of x squared minus x minus 2, where is that equal to 1? So that's going to give me the critical values. And again, once I have the critical values, I can set up intervals on the number line and I can just test. Let's think about what we have here. First and foremost, we know for something like a to the power of b is equal to 1, where a here is the base, that's 5x plus 2, and b here is the exponent, that's x squared minus x minus 2. Well, this is going to be true if a is 1 and b is a real number. So let's write that out. So a is 1, so 5x plus 2 is equal to 1. And b can be any real number, so we don't need to write anything there. Then it would also be true if b is 0, so this part right here. So let me put a little border. So x squared minus x minus 2, if that equals 0, and then a doesn't equal 0. Now we know a won't be 0 because this x value here is greater than -2/5. So this right here will always be positive. It won't be 0 and it won't be negative, so you don't need to put anything else in there. And then the last scenario is that a is -1, and basically b is something to where you raise it to that power and you get a positive one. So it could be something like, let's say 2 or 4 or 6 or 8. You have other scenarios that would come up. So let's say something like 2/3, for example. So let's just write that 5x plus 2 is equal to -1, and then we'll just say check. So we're just going to check. We come to another fresh piece of paper, and we're just going to solve these. They're pretty easy to solve. So this one, subtract 2 away from each side. This cancels. You get 5x is equal to 1 minus 2 is -1. Divide both sides by 5. Cancel this. You get x is equal to -1/5. Okay, so that is going to work. Let me get rid of this. And we have this right here. For this one, x squared minus x minus 2 is equal to 0. You're going to factor the left side. And you're going to say x here and x here. And basically, you want to think about two integers that have a sum of -1 and a product of -2. Well, that's going to be -2 and +1. So if we solve this using the zero product property, you get x minus 2 is equal to 0, or x plus 1 is equal to 0. Let's add 2 to both sides of the equation. This cancels. You get x is equal to 2. So x is equal to 2. This one is going to cause a problem. Subtract 1 away from each side. You get x equals negative 1. So this is not going to be included here because we're only looking at x values that are greater than negative 2/5. So I'm not going to include that here. I'm just going to erase this, and I'm only going to use x equals 2. So let's put that here. X is equal to 2. Let me get rid of this, and then let's put this one. So 5x plus 2 is equal to negative 1. Subtract 2 away from each side. This cancels. You get 5x is equal to negative 3. Divide both sides by 5. This cancels. And you get x is equal to negative 3/5. Now, normally, again, if you're solving that problem, you would check this. It actually does produce something that gives you positive 1. You can check it on your own if you want. We don't need to use this because this is to the left of negative 2/5. So we don't even need it. We only need these two values here to test. So let me put a little comma here like this. Let me move this over here, and let me grab this real quick, and let me paste this in right here. So these are the only critical values you're going to need to work with. Again, because we have this x is greater than negative 2/5. That's why I threw out the negative 1, because that's to the left of negative 2/5, and also the negative 3/5, because that's to the left of negative 2/5. So you don't have to worry about those. These are the only two things we're going to focus on. Let's go down to a little table that I've already set up to make this a little bit quicker. So we have the quantity 5x plus 2 raised to the power of x squared minus x minus 2. All I did was subtract 1 away from each side of the inequality. We're saying, where is this less than or equal to 0? If you look at this first column here, this is where the x values are less than negative 2/5. So where they're less than negative 2/5, we're not even going to worry about that. We're not going to test because we know in that other inequality, x had to be greater than negative 2/5. So here we're going to go between negative 2/5 and negative 1/5. So basically looking there, I could pick an x value like negative 3/10. And if I plug that in, I get about 2.05. Again, I don't care what the value is. I just want to know if it's less than 0, and it's not. Right now, I don't care about where it's equal to 0. We know that that's going to be at negative 1/5 and 2. We'll put that in the end. So I'm basically excluding everything to make it simple. So this will not work. You can mark this out, will not work. And let me just mark this out as not working. Okay, here, between negative 1/5 and 2, well, if you choose something like x equals 0, and you plug that in, you get exactly negative 0.75. Again, this would be negative, so this would work. Then if you go in the interval that's greater than 2, well, you have x equals 3 you could pick. You plug that in, you get a really large number, 83,520. Again, I don't care what the value is. I just want to know if it's less than 0, and it's not. This is positive, so you can mark that out. So at this point, you're basically done. You can write your solution is between negative 1/5 and 2, and those would both be included because this is a non-strict inequality. All right, let's come down here to a fresh sheet, and let's just formally write our answer. So we have that x is greater than or equal to negative 1/5 and less than or equal to 2. In interval notation, let's put a bracket next to negative 1/5, and let's put a bracket next to 2. Both will be included. And if you want to show this on the number line, let's just say we don't have a notch for negative 1/5. Let's just put that about right there. Again, in decimal form, that's going to be negative 0.2. Let's just say this is negative 1/5 like that. And again, because this would be included, I'm going to use a bracket here, and then I'm going to use a bracket here at 2, and just shade everything in between. So there's the solution graphically. So between negative 1/5 and 2, with both being included, here's your solution listed as x is greater than or equal to negative 1/5 and less than or equal to 2. And then here's your interval notation if you want to list it that way. Okay, now let's look at the graph of this guy. So you can go to Desmos and key this in. So remember that we had the inequality. We had the quantity 5x plus 2, and this was raised to the power of x squared minus x minus 2. And we said, where is that less than or equal to 1? And of course, you can subtract 1 away from each side of the inequality. Let me move this down here so it fits. So you could say minus 1, where is that less than or equal to 0? So we're graphing this part right here as y equals the quantity 5x plus 2 raised to the power of x squared minus x minus 2, and then minus 1. Remember, we also had the keyword and. Let me write that over here. So we had and. We also said that this guy right here needed to be positive to avoid issues where you would have non-real complex numbers coming up. So we also said that 5x plus 2 is greater than 0. And of course, that became x is greater than negative 2/5. So let me just write that. So x is greater than negative 2/5. Now, without keying this part in right here to Desmos, it's automatically going to do that because when you work with Desmos, it's going to treat an exponential function. Again, if it gets something like f of x equals a to the power of x, if you try to plug in something here that's a negative base, it's not going to actually graph that because of the issues with non-real complex numbers. This right here represents the real numbers, so it's not going to do that. So automatically, without keying this in, if you just put this in right here, you're going to get this graph right here where x is greater than negative 2/5. Okay, let me get rid of this, and let's think about our solution. We want to know for which x values are the y values going to be less than or equal to 0. We can see immediately that it's going to be 0 here, and then also here. So that one's obvious, it's 2. This one right here, you'd have to mouse over on Desmos, and you're going to see that that is negative 1/5, or you can also write it as negative 0.2 if you want. And essentially it's going to be from here to here, with both being included, in terms of where the y values are going to be less than or equal to 0. So that's going to be your solution for this problem. It's not too bad once you really break things down into a step-by-step process and just go through it. The graph is the best way to check it. So let's just go ahead and write the solution one more time. And we'll just say that, again, x is going to be greater than or equal to this negative 1/5 and less than or equal to 2. All right, for those of you that are interested, I'm going to show you an alternative way to solve this problem. So I think a lot of people would prefer to write this side and this side with a common base. And the way you would do that is you would say that really you can write any non-zero number raised to the power of 0 as 1. So in other words, you can say that 5x plus 2 raised to the power of x squared minus x minus 2 is less than or equal to this right here. Instead of writing 1, let's have a common base. So let's go 5x plus 2, and we're going to raise this to the power of 0. Now, this right here is going to stop us from having issues with this. Remember that 0 raised to the power of 0 is undefined, but because when we solve this right here and we have the keyword and, this right here becomes x is greater than negative 2/5. So if x was negative 2/5, 5 times negative 2/5 is going to be negative 2, and then negative 2 plus 2 is 0. 0 raised to the power of 0 is undefined, but this can never be negative 2/5 because x is strictly greater than negative 2/5, so we're okay there. Let me go ahead and grab this real quick, and let me come down here to a little rule that we need to work with in order to get the correct solution here. So at the very beginning of this practice test, I told you that if a was greater than 1, so here a is going to be your base, so 5x plus 2, and a to the power of x, so this is your a to the power of x, is less than a to the power of y, so that's this a to the power of y here, then it's going to be true that x is less than y. Okay, well, to follow this, in other words, to say that x squared minus x minus 2, just keeping this, so not flipping anything, is less than or equal to 0, you would want to put in the keyword and here, and you would want to say, well, this base here, which is our a, so 5x plus 2, well, that's going to have to be greater than 1. Now, in this case, we can adjust things. And that's because we do have a non-strict inequality here. So if 5x plus 2 was equal to 1, well, then you would have 1 raised to any real number, that's going to be 1. And this would be 1 raised to the power of 0, that's going to be 1. So you'd have 1 is less than or equal to 1, so that would be a true statement. So let's put greater than or equal to here. And then let's just grab this now, and let's come to the number line and see if we can get the same solution as before. Okay, so we already know how to solve x squared minus x minus 2 is less than or equal to 0, but let's just go through it again. Let's say x squared minus x minus 2 is equal to 0. We can solve this with factoring. Let me move this up here. I'm going to say that this is x and this is x. Again, two integers that sum to negative 1 and have a product of negative 2. That's negative 2 and positive 1. So if you were to solve this with the zero product property, you would say x minus 2 is equal to 0. Add 2 to both sides, you get x is equal to 2. And then you would have x plus 1 is equal to 0. Subtract 1 away from each side, you get x is equal to negative 1. So we have x equals 2 and negative 1. So those are the critical values. So over here at negative 1, let me put a little border like this. And then over here at 2, let me put a little border like this. And let me write this as less than or equal to 0. And we can get rid of this right here. And actually, let me just drag this up here in line. Okay, so now we're going to be ready to go. If you look at values to the left of negative 1, you're going to see that they don't work. So if I plugged in something like, let's say negative 2. Well, negative 2 minus 2 is negative 4, so that's negative. And then negative 2 plus 1, that's negative 1, so that's negative. Negative times negative is positive, and that's not less than 0. So this right here, let me just put an F for false. It doesn't work. We know that between negative 1 and 2, things would work. Let's say you pick 0. 0 minus 2 is negative 2, so that's negative. 0 plus 1 is 1, so that's positive. A negative times a positive is a negative, and a negative is always less than 0, so this would work. Let me put T for true. Then when we get to things that are greater than 2, it's not going to work again. So let's say you pick 3. 3 minus 2 is 1, that's positive. And then 3 plus 1 is 4, that's positive. Positive times positive is going to be a positive, and that's not less than 0. So let's go ahead and say here, it's going to be an F for false. Okay, so what you're going to do is replace this right here with the solution. So we know that both negative 1 and 2 would work because that's a non-strict inequality. So let's say that x is greater than or equal to negative 1 and less than or equal to 2. But now you've got to combine it with this right here. So this keyword and this 5x plus 2 is greater than or equal to 1. So let me come over here and subtract 2 away from each side of the inequality. This cancels. You get 5x is greater than or equal to 1 minus 2 is negative 1. Let me get rid of this and move this up here like that. And let's divide both sides of the inequality by 5. That cancels. So we see that x is greater than or equal to negative 1/5. Okay, so now we're back to that solution we had. Let me get rid of this. Because of the keyword and, again, it has to work in both. So if I graph this right here, let me put this right here as your negative 1/5. So x is greater than or equal to negative 1/5. That looks like this. You have a bracket at negative 1/5, and you're shading everything to the right. If you graph this one right here, so let me do this in a different color, maybe like a light blue. So here's negative 1. Let me put a bracket there. And then here's 2 right here. Put a bracket there. And then shade everything in between. You're looking for the overlap between the two solution sets because you have the keyword and. And basically, let me do this in this color here. That's going to be from right here, which is at negative 1/5, so that would be included, going up to and including 2. So that's going to work in both. So that's what you want for your solution. So let me put my notch back in here, or negative 1/5. And then let me put a bracket here. And then let me put a bracket at 2. And we'll shade everything in between. So the solution, when you combine these together, you're going to say that x is greater than or equal to this negative 1/5 and less than or equal to 2. This is the solution we found with the test point approach. Of course, this is faster, but there's more things to consider, and I would say that there's more of an opportunity to make a mistake. So if you get a problem like that and you're just solving it on your own, of course you can use this strategy, but if you're on a test or something like that, I would always stick with the test point method. It takes a little bit longer, but as long as you don't make a mistake in your calculations, you're going to get the correct solution. All right, for problem 7, we have 9 log base 6 of 5x minus 9, and this is greater than or equal to 27. So when I have a logarithmic inequality, I always use the test point approach. You can do this in a different way, and it's probably going to be quicker, but I like the test point approach because when you think about the logarithmic inequality, remember for a logarithm, the argument needs to be positive. So it can't be negative, it can't be 0. And so it's just a little bit easier to organize the information with a table or a number line or something like that, and then just check things. It's very easy to make a mistake on these problems. So what I'm going to do first is just say, where is 5x minus 9 greater than 0? And then once I do that, I'm going to solve the related equation. So I'm just going to replace this with equals, solve that, and so I'm going to have my critical values at that point. And then I can just set up intervals on the number line and just test. That's all I have to do. So let me solve this first. Let me add 9 to both sides of the inequality. You get 5x is greater than 9. Divide both sides of the inequality by 5. You get x is greater than 9/5. So when we think about things, we're going to say that we want x to be greater than 9/5 before we do anything else. Let's write out 9 log base 6 of 5x minus 9. We want to know, where is this greater than or equal to 27? Okay, let me grab both of these, come down here and paste this in. And I'm just going to replace this with equals for right now, just to find that boundary. And so let's go ahead and divide both sides of the equation by 9. And so this would cancel. You have log base 6 of 5x minus 9. And this equals 27 divided by 9 is 3. Okay, at this point, I would put it into exponential form. So you have 6 cubed, that's 216, would be equal to the argument of the logarithm, which is 5x minus 9. If I add 9 to both sides of the equation, this is going to cancel. 216 plus 9, that's going to be 225. So you're going to get 5x is equal to 225. Let's divide both sides of the equation by 5. Let me get rid of this. and this would cancel. And you get x is equal to, for 225 divided by 5, that's going to be 45. We can set up some intervals on the number line, and we could just test. Let me come back and grab this. I'm going to write it in this form. So log base 6 of 5x minus 9. Where is that greater than or equal to 3? Let me cut this away and come back down here and paste this in. Also, to make it a little bit easier, you could subtract 3 away from each side. Let's go minus 3 is greater than or equal to 0. So we're going to test, and I've already set this up for us. So in the first interval, anything less than 9/5, I'm not including anything here, so that's important to remember. This here on the left, nothing's going to work because basically if it's 9/5 or less than 9/5, this guy right here is going to be undefined. This guy has to be positive. So he needs to be greater than 9/5, so that's why we're just marking this out. So between 9/5 and 45, we would just pick a value and test. Does it work? Does it not work? So if you pick 2 for x and you plug that in, you're going to get exactly -3. And you can do that on your own if you want. The main thing is that we're looking for something that's greater than or equal to 0. And so this is negative, so this is not going to work. When we think about something that's greater than 45, you can just pick 46, plug that in, and you get about 0.013. Again, it doesn't matter what the value is. You're looking to see is it greater than 0, and yes, it is. So this is a check. Now, I never include anything when I set up these intervals. A lot of people complain about it. I just think about the critical values separately. We know that 45, if I plug that in for x, that solves the related equation. So that's where this left side right here would be equal to 0. So if I plugged in a 45 for x, 5 times 45 is 225. 225 minus 9 is 216, and log base 6 of 216 is 6 cubed. So log base 6 of 6 cubed is 3. 3 minus 3 is 0. So you would have 0 is greater than or equal to 0, which is a true statement. So you could say x is greater than or equal to 45. So let's come to a fresh sheet and just put x is greater than or equal to 45. For your interval notation, let's put a bracket next to 45 because that's included. We're going to go out to positive infinity. We'll make a little number line here because the normal one we use does not have 45 on it. Let's just say 45 is right there. And let's just say this is 46. And maybe this right here is 44. Again, it doesn't have to be perfect. We're just making a basic sketch to say, graphically, I would put a bracket at 45. And then I would just shade everything to the right to show my solution. Graphically, this is interval notation. And of course, this is just x is greater than or equal to 45. Okay, so if you want to key this into Desmos, you have y equals log base 6 of 5x minus 9, and then minus 3. A moment ago, we looked at log base 6 of 5x minus 9, minus 3, and we said, where is that greater than or equal to 0? Again, y equals this. So this right here, this whole thing, is a y value. I plug in something for x, and I get a y value. Y equals this. So this right here, I'm looking for where the y values are going to be greater than or equal to 0. So for which x values is that going to occur? So if you look at an x value of 45, that's your x-intercept, right? That's where the y value is going to be 0. You're on the x-axis. And then anything to the right of that in terms of the x values, where your y value is going to be greater than 0. So let me shade that like that. So here you're above the x-axis, so the y values are greater than 0. So again, the solution, if you want to do it from Desmos, is just that x is greater than or equal to 45. All right, for problem 8, we have log base 5 of x minus 3 plus log base 5 of x plus 1, and this is less than or equal to 1. So again, I'm going to use the test point approach here. The first thing you would do is you would look at this argument here and this argument here, and you're going to say that both of those guys have to be positive. So it must be true that x minus 3 is greater than 0, and you want to use the keyword and here, x plus 1 is going to be greater than 0. So what I'm going to do on this one is just add 3 to both sides of the inequality. This would cancel. You get x is greater than 3. And then on the other one, you're going to subtract 1 away from each side of the inequality. This cancels. So you're going to get that x is greater than -1. Okay, if I'm solving x is greater than 3 and x is greater than -1, you want to take the one that is more restrictive. So in other words, the one that includes fewer values where it would work in both. So you want x is greater than 3. So in other words, if I pick something like, let's say 4, that's going to work here and also here. But let's say I pick something that was like 0. So 0 would work here. 0 plus 1 is 1. That's fine. But if you plug in a 0 here, 0 minus 3 is -3. That doesn't work. So you want to go with this one right here. X is greater than 3. The next thing is you would want to solve the related equation. So if I got log base 5 of this x minus 3, and then plus log base 5 of x plus 1, we would say, where is that equal to 1? Forget about the less than or equal to for right now. We're just solving the related equation. Let me grab this real quick. And let me come down here. And I'm just going to put this off to the side for right now. Okay. For this equation right here, what you would do is condense. You've got to be careful because this is a perfect scenario to get extraneous solutions. So you're going to get log base 5 of, you're going to multiply these two arguments together. So you can have x minus 3 times x plus 1. You can put this here like that if you want. I know a lot of people don't care, so I'm just going to leave it off. And then this would be equal to 1. So for this one, you could write this as log base 5 of, this would be x squared, and then you would have plus x and then minus 3x. So x minus 3x would be negative 2x, and then negative 3 times 1 is negative 3, and this equals 1. Let me slide down here a little bit. And basically what you would do at this point is put it into exponential form. So 5 to the first power would be equal to this argument here. You can wrap this if you want. So you could say 5, that's 5 to the first power, is equal to x squared minus 2x, then minus 3. Let me write this like this. And let me subtract 5 away from each side. So this would be minus 8 over here if I'm subtracting 5 away. And this would be 0. All right, let me slide this over here. And I think you know that you can solve this with factoring. Let me set this up like this. So x here and x here. So give me two integers whose sum is negative 2 and whose product is negative 8. Well, that's going to be negative 4 and positive 2. And actually, let me get rid of this. I want to keep this on the screen because we are going to have an extraneous solution here, and I want you to see where it's coming from. Okay, so if you solve this, again, you can go x minus 4 is equal to 0. Add 4 to both sides, and you get x is equal to 4. The other one, you have x plus 2 is equal to 0. Subtract 2 away from each side. This would be x is equal to negative 2. Do these each work? No, one of them is not going to work. So this one right here, this x equals negative 2, that's not going to work. We said earlier, and this is off the screen now, so let me come back here to where this is there, that x needed to be greater than 3. Well, this is x equals negative 2. So of course this isn't going to work. If you look here, when you multiply these guys together, when you do the condensing, you have a negative 2 there minus 3, which gives you negative 5. And then you have a negative 2 plus 1, which gives you negative 1. Well, when you multiply these guys together, you get positive 5, and log base 5 of 5 is 1. So it works in this condensed form, or the transform version of the equation, but it's not going to work in the original, so you have to reject it. Okay, so you have to reject it. So this one's not going to work. Again, if you plug that in, either here or here, you're going to get something that's undefined, so it doesn't work. So you're just going to get x equals 4. That's a valid solution. Okay, so now let's go back to this being less than or equal to 1, and you can subtract 1 away from each side. So minus 1 is less than or equal to 0. So again, I already have this set up for us. So log base 5 of x minus 3 plus log base 5 of x plus 1 minus 1 is less than or equal to 0. So anything that's less than 3, automatically reject it. You could just put x's there, don't worry about it. Between 3 and 4, you could pick 3.5. You plug that in, and you're going to get about negative 0.496. I don't care what the value is. It's less than 0, so this works. Then anything greater than 4, you could plug in, let's say 5. You get something that's about 0.544. Again, it's positive, so this is out. Now, here's where people get mad at me because I don't include things when I set up my intervals. I always exclude everything. So you have to think about these critical values separately. Does 3 work? No, because we said specifically that x needed to be greater than 3. If you plug in a 3 right there, 3 minus 3 is 0, and log base 5 of 0 is undefined. So 3 is not going to work. Does 4 work? Yes. 4 solves the related equation. If you plug in a 4 for x, you're going to get 0 is less than or equal to 0, so that's a true statement. So what you would say is that x here is strictly greater than 3, and then less than or equal to 4. Let me write that right here. So x is strictly greater than 3. Again, it can't be 3 because that would give you something that's undefined, and less than or equal to 4. So in interval notation, 3 would be excluded, so you want a parenthesis there, and then 4 would be included, so you want a bracket there. Let's go to the number line. Let's put a parenthesis at 3, and then a bracket at 4, and then you could just shade everything in between. So this would be your graphical solution, and maybe that could be a little bit better there in terms of how it's on 4. So this is your graphical solution, and then this is your solution, x is greater than 3 and less than or equal to 4, and this is your interval notation. So again, you can always check this on Desmos. So we have log base 5 of x minus 3 plus log base 5 of x plus 1. I'm not going to fit this the way I'm writing it. And then we have minus 1. Where is this less than or equal to 0? When you graph it this way, this right here is equal to y, right? So that's a y value. When you plug in an x and you go through and do all the calculations, you're getting a y value. So for which x values am I going to get a y value that is less than or equal to 0? Well, you can see right here at 4, I'm going to get a y value of 0. That's where I'm on the x-axis. That's my x-intercept. And then basically any x value that is to the left of 4 but greater than 3, this is also going to work. You can't actually plug in 3 because, again, 3 minus 3 is 0, and log base 5 of 0 is undefined. So let's say, let me erase this, add 4, and basically anything that's less than that going to the point where we're anything greater than 3. So the way you would say that is x is strictly greater than 3, can't be 3, and it's less than or equal to, it can be 4, so it's less than or equal to 4, because at 4, this left side would be 0, and 0 is less than or equal to 0. That's a true statement. So this is your solution. All right, let's take a look at problem 9. So here we have log squared of x plus log of x is less than 2. So what does this notation mean? So some of you have taken trigonometry before and others haven't. It's very common if you have something like, let's say the sine of x, let's say this is squared like this, to write this as sine squared x. And you could wrap this stuff or not. It kind of doesn't matter. But basically, when you see something like log squared of x like that, that's just the same principle. So it's just a notational thing. I know it trips up a lot of people. So on the practice test, I put a note that log squared of x is the same or is equal to your log of x like this, and this would be squared. So now that we have that out of the way and we understand the notation, how are we going to solve this? Well, again, I'm going to use the test point approach. And the first thing I'm going to do is say, well, this is x and this is x, so that needs to be greater than 0. So I know that x is greater than 0. Okay, so that's out of the way. Now I want to solve the related equation. So I have log of x, I'm just going to write it like this, and I'm just going to say this is squared, plus log of x, subtract 2 away from each side, so minus 2. Where does that equal 0? So this is what I care about. Let me grab this real quick, and I'll come back in a moment. Put that right there. Let me move this over here. Well, the first thing is I would make a substitution. So I would say that we're going to let u be equal to the log of x, and then I'm just solving u squared plus u minus 2 equals 0. Super easy to solve that. So I'm just going to say that we have u here and u here. Let me make this better here. So this is a 1 and this is a negative 2. So give me two integers that sum to 1 and have a product of negative 2. So that's going to be positive 2 and negative 1. Okay, so we would say that u plus 2 is equal to 0, or u minus 1 is equal to 0. Let's subtract 2 away from each side of the equation here. We get u is equal to negative 2. Then or, let's add 1 to both sides of the equation here. We'll have u is equal to 1. I just want to replace each u with log of x. So I'm going to say log of x is equal to negative 2. Let me make this a little bit better. Then or log of x is equal to 1. So log of x is equal to 1. Where did I get that from? Again, u is equal to log of x. So if I have a u, I can just plug in a log of x. So now, once I've done that, you can get rid of this. You don't need it anymore. You can solve this by saying, okay, the base here is 10, and the base here is 10. So this is 10 to the power of negative 2, which is 1 over 10 squared, or 1 over 100, is equal to x. Then or, this one would be 10 to the first power, or 10, is equal to x. Okay, so that tells me that if I'm looking at this on the number line, that basically I'm going to have an interval where I'm greater than 0, that way this guy can be defined, and I'm less than 1 over 100. Then I'm going to have between 1 over 100 and 10, and then I'm going to have anything that's greater than 10. Again, I'm not including any of these critical values. So coming back up, this is a less than. So let me write this as strictly less than 0. Okay, I've already set this up with the table. So log squared of x, or again, log of x being squared, if you want to say it that way, that's fine. Then plus log of x minus 2, where is that less than 0? So we know that if x is not greater than 0, this guy's undefined. So basically this interval right here, just mark everything out. This one, you're greater than 0 and you're less than 1 over 100. You could just pick something and plug it in. So here, x is equal to 0.001. This would be 1 over 1,000 if you key that into your calculator. So what you would get on the left side is 4. So again, we don't care about the value. We just care about if it's positive or negative, and this is positive, so this doesn't work. If you look between 1 over 100 and 10, you could pick something like 1. And if you plug that in, you're going to get negative 2. So is negative 2 less than 0? Yes, because this is negative. So you can check this one off. And then if you pick something that's greater than 10, so let's say 11, and you plug that in, you get about 0.126. So again, this is positive, so this is not going to work. So basically, because this is a strict inequality, I don't have to think about the 1 over 100 or 10. I know those are not going to work because they're going to make the left side 0. Right? Those were coming from solving the related equation. So basically, you would have 0 is less than 0, which is false. So let's write this as a 3-part inequality. We'll say x is greater than 1 over 100 and less than 10. So I don't have a notch for either of these. Let's put a notch right there and just say that this would be 10. And then for 1 over 100, that's really small. That's really, really close to 0. Let's put that right there. I'll just arrow to that and say that's 1 over 100. Neither one's going to be included. So I'm going to use a parenthesis here. And I'm going to use a parenthesis here. Again, if you want to use an open circle, that's fine. Let's go ahead and shade everything in between there to show the solution graphically. And then in interval notation, you want a parenthesis next to 1 over 100. And then again, another parenthesis next to 10 because neither one is going to be included. So the graph for this one is a bit strange looking. But again, if you write out that log squared of x, let's write that as log of x being squared. So you have this one, and then plus you have log of x. And then we would say minus 2. We want to know where is that strictly less than 0. So again, this right here, if you plug in something for x, that's going to produce a y value. Y equals this. So we want to know for which x values am I going to get y values that are strictly less than 0. So I want to be below the x-axis. Right here, and this is really close to 0, so that's where that point right there is. This is actually not 0, it's 1 over 100. Comma 0. And this point right here, this is 10, comma 0. Again, if you solve the related equation, if you say, hey, where is y 0, or where are the x-intercepts, you're going to get 1 over 100 and 10. So we know that between those values, the x values would produce y values that are less than 0. So let me trace this out in a different color. So you'll see just like that. So basically all your y values there are going to be less than 0. Again, once you hit 10, you're at 0, and then anything to the right of 10, well, then you're above 0 in terms of your y values. So the solution here, if you want to write it out, again, if you were going to Desmos, you would just say x is strictly greater than 1 over 100 and less than 10. Okay, let's look at problem 10. So I know some people probably struggled with this one, but it's actually one of the easier ones. You have log base 3 of x minus 2 log base 1/3 of x is greater than 6. Now again, you have x here and x here, so you would just say that x is greater than 0. So x is greater than 0. And basically for this, the way you're going to do it, let me write log base 3 of x, and then minus, you have 2, and then let me put times log base 1/3 of x like this. Let me put that this is equal to 6. I'm just going to solve the related equation. Let's just leave that there for right now. We'll come back and get it in a moment. Okay, so what you would do is actually move this back up. You're going to try to condense. So you're going to say that this is log base 3 of x, and then minus log base 1/3 of x squared, and then this equals 6. Some of you know that you could rewrite this as plus log base 3 of x squared. Now, where is that coming from? Well, basically what you would do is you would say, by the change of base rule, that you could write log base 3 of x minus, you want to change this to something where you have a log with a base of 3. So you would go log base 3 of your argument, which is x squared, over log base 3 of your base here, which is 1/3. Let me close that down and say this is equal to 6. Okay, now when you think about log base 3 of 1/3, that is negative 1. 3 to the power of negative 1 is going to give you 1/3. Again, if you don't see that right away, you could write this as 3 to the power of negative 1, and then log base 3 of 3 to the power of negative 1 is negative 1. So basically, you could erase this and replace it with negative 1. Well, that's just going to change the sign of this. So essentially, you could just put this as a plus now, and that's the hardest part of this, is just realizing the simplification. Once you've done that, well then, all you have to do is say you have log base 3 of, you can multiply these arguments together. So x times x squared would be x cubed, and then this would be equal to 6. So let me slide down here, and let's say that we would put this in exponential form. So 3 to the power of 6 would be equal to x cubed. 3 to the 6th power would be 729. So let's write x cubed is equal to 729. Now, depending on how you solve this, whether you want to do factoring and go for the full solutions, so the non-real complex solutions, you can get those by saying that you have x cubed minus 729 is equal to 0. You can set this up by factoring, and you can solve and get all the solutions. We don't really need that here, so we're just going to say that we want the real solutions. So specifically, the real solutions here. For those, you just take the cube root of each side. So you'd have x is equal to the cube root of 729, and that is going to give you 9. So x here is 9. So that is basically a boundary for you. Let's come back up here. Again, solving the related equation, you're going to get x is equal to 9. So what I would do is write this as log base 3 of x, then plus you have log base 3 of x squared. Again, that came from simplifying. We saw that already. And let's go minus 6, and this is greater than 0. Okay, let's look at this with our little table. It's already set up. So we know that one critical value, again, x needs to be greater than 0. So you have anything here that's less than 0, it's not going to work. So we just mark it out. Then we have between 0 and 9. Again, I'm not including anything. So between 0 and 9, you could pick an x value of 1, plug it in, you get exactly negative 6. Again, this is negative, and I'm looking for greater than 0, so this doesn't work. Then anything that's greater than 9, again, you could pick something like 10, plug it in, you're going to get about 0.288. Doesn't matter what it is, it's going to be positive, so this works. Again, at the end, I like to consider my critical values. So does 9 work? No, because if you plug that in, this is going to be 0. 0 is not greater than 0, so the solution here is x is greater than 9. So let me put x is greater than 9, and I'll put 9 here and positive infinity there. Make sure you use a parenthesis here with 9 because it's not included. Okay, here, let me put a little parenthesis there at 9 and just shade everything here to the right. So that's graphically, here we have x is greater than 9, and here we have our interval notation. Okay, let's look at the graph. So log base 3 of x plus log base 3 of x squared, and then minus 6, we want to know, where is this greater than 0? Well, we can see at an x value of 9, the y value is 0. Right, we're going to be on the x-axis. Where are we above the x-axis? So where are the y values that are greater than 0? So it's anywhere where x is going to be greater than 9. Strictly greater than, because x can't be 9 because that makes y 0. So you could say from the graph that here, x is going to be strictly greater than 9.